Welcome, everyone. This is Mike Gibbs and the team at Go Cloud Careers, and we are here for a completely free AWS Solutions Architect Associate Bootcamp. This is our summer AWS Solution Architect 2024 free bootcamp, and this bootcamp is going to focus on getting you guys and gals out there through the AWS Solutions Architect certification. We are going to have all kinds of fun over the next 2 weeks. And we're really going to make sure that you get through this AWS full course tutorial and that you get this free AWS certification training that we told you about. So, here's the key. We're going to make this a course where we really want you to learn. I've been in technology now for over 25 years as an architect. I've been a cloud architect, a network architect, an enterprise architect, a business architect. And not only have I worked for about 25 years as an architect, people I've trained or coached over the last 20 some years are now working at Apple and Amazon, at Cisco, at Microsoft, Google, Accenture, Deloitte, KPMG, Capgemini, PricewaterhouseCoopers, JP Morgan Chase Bank, Barclays Bank, Zscaler, Palo Alto Networks, and every other prestigious organization you can think of. So I want to really help you, and I want to make this a really good boot camp for you. So in this free AWS course, I'm going to let you know the flow. We have approximately 3 hours per day of this AWS Solutions Architect training. And we're going to do this from 2 to 5 p.m. for 2 weeks straight. Additionally, after this is over, we're going to do some hands-on tutorials for you and live tutoring. We want to make sure you get some feel for the systems that we're talking about. And our team has about 40 to 50 labs for you. And these are good labs for you to get some hands-on experience. I want you to go through these labs. I want you to work these labs, and I want you to get hands-on. But we're going to focus this time on teaching you the technology. What is the technology? How does that technology work? And why you should use it. So not only can you easily pass this SAA-CO3 exam, but at least you are able to work as well. Because when I interview people or any technology professional interviews you, they ask you about the tech it is. And if you can't explain what it is, how it works, and why you would use it, no matter how good your skills are at clicking a bunch of boxes on a management console, they can't hire you. So let's get good training time. Let's get some good education, because I want you to all love this. I love working on the cloud. I've been working on the cloud since 1993 with the ISDN cloud, 1996 on the Frame Relay cloud, 1999, 2000 on the BGP cloud, and then the VPLS cloud, and every other cloud there's been. So I've consulted the cloud providers on how to design their clouds for decades as well. So I want to make sure this is free AWS course is great for you. And this is, again, a full AWS course tutorial. So let's get on with our free AWS course training. So before we begin, I want to know where you're at. So tell me where you're at. I'm over here in South Florida today. And I also want to tell you about a guide that we've written for you. We have a certification guide that you can use to maximize your career opportunities. Certifications are a very powerful way to build your brand, to get employers to want to talk to you. And if you build your brand the right way as a strong, focused brand, you will have more opportunities than you can think of. Sadly, most people do crazy things with their certifications, and meanwhile, they work so hard. I mean, truly so hard to get to their goals. And in the end, they spread themselves too thin learning other people's careers. So we've got a certification guide that's going to help you say if you want to be a cloud architect, and it's going to be focused on everything you should do. I love this. I see South Florida. I see Mississippi. I see California, Houston. I see UAE. I used to work in the UAE. I kind of loved it over there. Philippines, which is great. I see Kenya. I see Nigeria. I see Toronto. I see India. This is great. New Jersey. I lived there for many, many years. And I see all kinds of great places as well. So wonderful. Love it. I also want to know that you are awake and you're ready to get started. So please give me a hashtag AWS Solutions Architect Associate. There's about 230 of you, and I see a bunch of that. We will begin and we will have some fun. We are not only going to just talk about the materials in the Solutions Architect Associate course, but we're going to talk about the technology. When we talk about virtual machines, we'll bring you back to our data center and show you what it looks like in the original way. When we talk about databases, we're not just going to talk about the stuff AWS supports this and this, this and this. We're going to talk about those individual databases and their strengths and weaknesses and what they're used for, so you know how to design your systems like a cloud architect or a solution architect will. And we're going to get involved into Kubernetes. We're not just going to talk about the AWS service, which most people would do in about 5 minutes. We're going to spend an afternoon and really talk about Kubernetes so you understand it. So we're really focused on getting you great. So I hope you enjoy this. If you're willing to hit the like button and signal other people to come here, please, great. And if you enjoy the content, please go out there and hit the subscribe button and hit the bell and maybe even invite a friend, because it costs a lot of money to put these together. But the team at Go Cloud Careers really wants to know that you guys have the best opportunities in life. And after sampling all the other certification materials that were out there, I felt compelled to do this and to do this for free. So give me that hashtag AWS Solutions Architect Associate. When I start seeing these things pop in, we will begin. I'm starting to see them pop in. Great. All right. So now let's start our boot camp. The first thing we really want to talk about here is the AWS cloud and how it's organized. So when it comes to the AWS cloud, we really can talk about something called regions, availability zones, local zones, and edge locations. So first thing I will talk about is regions and availability zones. We'll take all the mystery out of it for you. So here you can see in this graphic, we have the AWS cloud. You can see this large box in the center view, that blue box. That's a region. That is a huge area of geography. Think a continent, think a country, think a part of a country. Like in the US, there's 2 regions. Basically, you can think, or the main 2 regions are, the west side of the US and the east side of the US, but there's 350 million people in the US, so we're a pretty big country. But so you can think of that large geographic area as a region. And all an availability zone is a data center. That's it. It's a data center. So what is a data center? It is a building that's got lots of power cooling in it, and it's got routers and switches. It's got servers and storage and load balancers and firewalls. And when it comes to cloud computing, what you are doing is you are renting a virtual data center. But the cloud is still powered by the same data centers that organizations have had for the last few decades. It's just they now rent you space in it. So you can think of it as, instead of building a house for yourself, you check into a hotel when you're on vacation, maybe in Santorini, Greece, for example. Beautiful place if you haven't been there, or whatever the case may be. So now you get it. Large geographic area, region, data center, and those regions, availability zones. So the next component we'll talk about with regards to the AWS cloud and how it's organized is a local zone. So let's talk about why we have local zones, and we'll map it out architecturally. If you need to connect where you're at to the cloud, you're either going to do it over, say, a VPN or a private line or a software-defined networking WAN or a SASE WAN. But when you need to go from your systems to the cloud, it's going to be potentially over a large geographic area. So what does that mean? It means latency or your performance struggles when you have to connect to something that's not directly in front of you. It's one of the reasons private clouds perform the best, because it could be 2 to 3 milliseconds of latency or more just to get to the AWS data center where you're at. So if you have a latency sensitive application and you put it in the cloud, you will decrease the performance of that application. So there's really 2 options. One is you can host them yourselves in your data center. And the other option is maybe there's a data center to you that is closer than the cloud provider's availability zones. So that is what a local zone is. It is a data center between you and the cloud provider that's going to be much closer to the users to reduce latency. So you'll opt into a local zone, you'll create a subnet in a local zone, and you'll put your stuff. What do I mean by stuff? It could be your virtual machines, otherwise known as an EC2 instance on AWS. Azure calls them a virtual machine. Google calls them a compute engine, but it's the same thing. You put your load balancers in here, for example. And some of these local zones, which are just data centers that are closer to you, will offer, the ability to do more. Elastic load balancers, elastic cache, some databases and more. But the point is, putting a data center between you and the actual cloud provider. So what's this look like architecturally? So in this particular example that we have, you can see we've got this large geographic area called a region, And you can see we've got these data centers called availability zones. So what does that mean? We've got this local zone that's closer to you. So it's a data center, just like an availability zone, but going to be more close to you than the other availability zones that are out there. So let's talk about how you could use this. So in this environment, let's say we have a hybrid cloud. And in this hybrid cloud environment, we've got a data center on our campus. This is where our people work. This is the best performance we have. Now, the lowest performance will be over the wide area network to AWS, but we can actually connect to a local zone. So we can host some things in our local data center. We can host some things in the cloud provider's data center that's local to me, otherwise known as a local zone, or we can put it in an AWS availability zone. So that's really what we're talking about. So let's go through these so far. What have we talked about? We talked about a region as a large geographic area. We talked about an availability zone, and you'll have multiple data centers per region. And then we talked about a local zone, which is a data center between you and the cloud provider's primary availability zones to reduce latency. So what else? We also have to talk about edge locations. So what is an edge location? An edge location is another data center that is where, typically speaking, where internet service providers all make their connections. It's often called a point of presence. So what happens is when we need to use a content delivery network, say on the AWS cloud, and we'll get into depth about what are content delivery networks and how they work, etc. later when it's time to talk about content delivery networks. The AWS content delivery network is at something called an edge location. Azure would call it a point of presence, which is a much better name of it, but they call it an edge location. So in every major city, for the most part in the world, there's about 217 of them. At least at the time we wrote this content, AWS has an edge location. And in that edge location, what they have is a bunch of servers that actually cache your website information, and they have their own private backbone, which gets your network traffic off of the internet. So I'll show you what this looks like in a minute. So here's an example where we've got our systems that are sitting inside of an availability zone at AWS. And our website is both static contents being served from object storage, otherwise known as S3. Our EC2 instances or virtual machine are serving dynamic content. And we've got users at edge locations. So let me explain the way these edge locations work. Right now, let's say we have a user. Let's say this user is in Athens, Greece. My family's from a village pretty close to Athens, so let's say Athens, Greece. And the user wants to go to www.gocloudcareers.com. So, and we'll get into much more depth of this when we talk about content delivery networks and CloudFront. So the user will enter that www.gocloudcareers.com on their browser. Their DNS servers will give them the IP address or addresses to our website, and then their web request will be sent. Now, if it's the first time this day and the cache is empty, what will happen is the user's traffic will hit the edge location. The edge location will then send it to a regional cache, and if it's not stored on the regional cache, it'll be sent to the web information. And then what will happen is the website will respond. The website will respond. The information will be cached at the edge location, and then the user's information is sent to them. Now, let's say that first person his name was Spiro that decided to hit the edge location. Now in Athens, we have another person. His name is Aguilo. And now Aguilo wants to go to www.gocloudcareers.com. So Aguilo actually hits his local content delivery network in Athens, and the content delivery network says, I have the information. I'm going to give it to Aguilo, and I send it right back to you. And the content delivery network responds and pops it there. So that's why we have these edge locations sitting all over the world for the cloud providers. They're there to cache your web information, to take the load off of the environment. So large geographic area, region. Data center in a region or data centers in a region, they're availability zones. Local zone is a data center between you and the cloud provider to make it to reduce your latency and enhance your performance. And edge locations are internet point of presences to go out there and get your information. So I'll tie these three together. I just walked through the edge locations with you. So here you got an environment. It's me. When I was living in Palm Beach, let's say before I moved to this wonderful place called Port St. Lucie. Let's say that was my on-premise location. And the data center that I would connect to at AWS would be US East, which is over in Ohio, which is not local. So I might actually connect myself to, say, a local zone. If I didn't want to house the information in my data center, you can see the local zone would be, say, in Miami. So from Palm Beach to Miami, it's 100 miles. I don't have any kind of latency worth talking about. I can pop my systems in there. And then I can still backhaul my information to the AWS cloud, which is in the 2 availability zones that I might be using, which could be 1,000+ miles away, because that way we get the best performance from our local zones, and we can still use the capacity and scalability that exists in the standard AWS data center. So I hope that makes sense. Okay, so we will temporarily just do a brief introduction of the VPC, and believe me, we will spend a lot of time on the VPC, because not only are we covering the AWS Solutions Architect Associate in this training, we also have a lot of the AWS security certification in this training and the AWS Advanced Networking in this training, because we wanted to get what you need to be functional out there in the world. We really want to give you as much as we can. So now let's talk about the virtual private cloud. So if you actually can think about it this way, if you think of, cloud computing as basically renting space in someone else's data center, and you can really realize that when you go to the data center, the cloud provider, you get a virtual data center, which is kind of the equivalent of a hotel room inside of a hotel versus a house. So the virtual private data center that you have will be called the virtual private cloud. And basically speaking, the cloud is just a shared environment. There's a whole bunch of users, millions of users that are potentially sitting in the same data center, and they use software to create a virtual data center for you. And in your virtual data centers, where you'll put your servers, etc. So that's your virtual private data center. So, but they like to call it the VPC. So now you can look at it this way: the AWS cloud is a shared environment, and you can see how your environment is just a virtual data center inside of the data center. And that's what a VPC is all about. Now, we're briefly going to talk about the types of cloud architectures. And we'll talk about the strengths and weaknesses of each approach. So the first type of cloud architecture that we're going to talk about is, realistically speaking, a hybrid cloud architecture. Actually, before I do that, let's talk about a private cloud. So here's what a private cloud is. We have an organization, and they have their data center. They install cloud software on it, like VMware or Nutanix or IBM OpenStack, and that turns that data center into a cloud. And everything you could do on the public cloud, like AWS or Azure or Google, you could do in the private cloud, whether it be functions as a service or any of the things. It's all the same. The ability to expand and contract servers as you would need, like auto scaling. And in a private cloud, you are going to get the absolute best performance. Why? Because it's your data center, and you can control the network. You control the performance on the network. There's no wide area network latency. It's typically cheaper, by the way, too, the private cloud. The drawback of the private cloud is it's a lot of work to know how to manage a private cloud and design the private cloud. You need experts in networking, experts in security, experts in servers, experts in storage. And what happens in a private cloud is you need to be very focused on making sure your technology is great. And that takes a lot of technical expertise, which requires a lot of highly trained, highly intelligent people and employees, which cost a lot of money. Still, overall, it's generally cheaper to run a private cloud than the public cloud. But, in a private cloud, if you need additional capacity, you don't have it. So you can always scale out to another cloud in a hybrid cloud architecture, or, if your systems are in a public cloud, you almost don't have to worry about it. They're never going to run out of capacity, or for the most part, they never will. So understand that. So private cloud, you make it, you do it, you're on your own yourself. And many organizations use private clouds. And, many organizations use public cloud. So private cloud is a data center that you run yourself. Now, the next kind of cloud we'll talk about is a hybrid cloud. This is going to be ideal for most customers, and here's the reason why. In the private cloud, we can do any kind of networking we need, so we can create as much network speed as we want. We can make sure that we don't oversubscribe our resources, which is where the cloud provider sells more space and capacity than they actually have, on the basis that not all people use their information at the same time. Kind of like the way an airplane overbooks a flight. Kind of like the way your internet service provider typically sells 10 times more bandwidth than they actually have, because most people don't use it all at the same time. But that's okay. So in a hybrid cloud, you get all the benefits of your data center: almost no latency, the ability to run quality of service and traffic prioritize, the ability to supercharge your security with things like private VLANs because you have control over it, the ability to hire anybody you want to be your security people. And you connect that private cloud to a public cloud like AWS or Azure or Google, or multiple ones. So you put your super high performance compute in your data center, you put all that stuff that runs all the time in your data center, and you put all that stuff that might need a little more agility or scalability in the public cloud. Say a global retailer's website that needs to have auto scaling, say around Christmas, when people tend to buy a lot of gifts, for example, or big sales. So that in the hybrid cloud, data center runs great, plus the public cloud, and then you've got the best of both worlds. Here's what else is good about a hybrid cloud. If a cloud provider goes down, and cloud providers do go down, and you've got your data center, you're up still. So a hybrid cloud could be 50% data center, 50% public cloud, or whatever you want it to be. You can even set up a hybrid cloud where it uses what you've got that you've already paid for in your data center, and when you need additional capacity, it adds that capacity on demand on your cloud provider. So that is a hybrid cloud. The next environment is a pure cloud architecture. Here's what this is. You stick your stuff all in AWS, or all in Azure, or all in Google. You're inside of that private cloud, and when you're in there, you get some proprietary enhancements, which makes it easier to configure and easier to manage. The downside of this is, generally speaking, none of the clouds are going to be the best at everything, and you limit yourself to whatever that cloud provider has. If you use the proprietary enhancements, you get locked into that vendor, meaning if it doesn't work for you, it's hard to get out. And when that cloud provider goes down, and they all go down, it's just a matter of when, your systems are completely down. So that is a single cloud, a pure cloud architecture. 98% of organizations wouldn't do this because it's too dangerous, because all you need is your cloud provider to have a network outage, a security hacking event, or a control plane, and all the systems go down. And imagine you're a hospital and the tech goes down and people could die. Or your air traffic control and you're on a single cloud and they have an outage, the cloud goes down, and all of a sudden the planes have nothing to guide them. So pure clouds are there, but 98% of organizations are going to go to the next option, which is really a hybrid multi-cloud. And this is what 98% of organizations use. It is where they have some form of a data center and they connect to 2 or more clouds. And that way they can put their high performance things local. They can put their scalability needs in the cloud. And maybe, for example, the Google Cloud's better at some big data thing. Maybe Microsoft's better at AI. Maybe AWS is better in infrastructure. And I'm making that up pure academic terms. I'm not going to take a position on who's better, who's worse, because in tech, it doesn't matter. You choose the best application for your client's need. There is no such thing as the best technology. So I hope that makes sense. But in this case, the hybrid multi-cloud is pretty much what everybody's using. So at least now you know this. Don't ever think that it's going to look just like you would actually imagine. And this is what a lot of organizations are going to have. They're going to have their data center, and they're probably going to connect to 2 data centers inside of a cloud provider like AWS. So they are your major types of cloud architecture. So actually, you know what? I'm going to pause there and take some questions. We'll take questions for a few minutes, and then we will go back to the content. I want to make sure that all of you actually get it, you're learning, and you caught up with, because I know what it's like. You take a course and you lose something, you get lost along the way, and then everything builds on it. So is everybody with me so far? Do you all have any questions? Local zone is just a data center near you. That's exactly it. Everything we're talking about, an edge location is a data center. A local zone is a data center. An availability zone is a data center. But Arun, see, here's the thing when it comes to data centers. You can build your data center to provide high-speed networking like an internet service provider would. Alternatively, you could build your data center to do high-performance GPU computing if that's what you really wanted to do. You could build your data center to put caching servers out there, for example, like you would with an edge location or an Azure point of presence. But all in all, just a data center where you get to put your things near you. And because they're near you, you don't have as much latency. Good question. Chris, we can go to the next one. CloudFront is an edge location? No. CloudFront is a content delivery network, which is a web caching type environment to both protect you an organization from the distributed denial of service attacks and promote scalability of their website by responding to frequently accessed information. We will spend maybe half of a day or a day just on CloudFront. So we will get back to that in depth. But the edge location is where the CloudFront servers are hosted. Like CloudFront itself is a combination of servers and a network. And why would an organization use a content delivery network? Well, internet bandwidth can't be guaranteed. So if you stick your traffic on the internet, there's no guarantees that it gets to its destination. But if you can hit a caching server that has some of the content close to you, and then you could ride back on the private content delivery network to the source, you can get better performance in many, many ways. Chris, let's go to the next one. And while we're at it, before we get to the next question, I should remind you, we've got over 40 lab videos that I'd love you to sign up for. My team will pop a link for that in the description. Additionally, we've got a certification guide, which are the certifications that can help you in your career, especially if you want to be a cloud architect or AWS solutions architect, for example. And if you're having a good time, hit that like button. Chris, let's go to the next question. Is a content delivery network AWS CloudFront? No, we will spend a good afternoon on content delivery network. So a content delivery network is a network of caching servers. AWS calls theirs CloudFront. Akamai has a content delivery network. Cloudflare has a content delivery network. Fastly has a content delivery network. And we'll walk through NS lookup so you can see. And you'll even see that a cloud provider like AWS will use like Amazon will use multiple content delivery networks because a single content delivery network is a single point of failure. But it's going to take hours to go over content delivery networks. I can't do it in the chat box right now. But when the time comes, we will go over it. So just for right now, remember the edge location is where CloudFront is. Are local zones managed by the cloud providers? Yes, it's their data center. So it's just another data center that the cloud provider owns that, remember, it's close to you. Because the further I go, the more latency I have, the reduced performance I have. We can go to the next one, Chris. What's the difference between a local zone and an edge location? In practicality, not a whole lot because they're the same kind of data centers. In reality, the edge location is where the content delivery network is. So it's going to have, typically speaking, many more internet service provider points of presence and higher speed networking. And a local zone is another data center, but that data center is designed to be close to you, and it's designed to have more compute and storage, for example, than an edge location, which would be more of a network-based, network-based data center. Do you have to pay for content delivery network services? Absolutely. And they may reduce costs in some ways. And here's the reason. If you don't have a content delivery network, you may need many times more storage and much more transfer of your data. So sometimes content delivery networks will actually reduce your cost if people are accessing frequently accessed information. And we're going to have lots of fun talking about caching and content delivery networks. I can promise you that. So if companies are using a hybrid multi-cloud, that means you should all learn the cloud providers, AWS, Azure, and Google. Well, yeah, Jazz, here's the thing. Yes, you have no choice, but here's the thing, and it depends on your job. See, if you're a cloud architect, you're never going to configure the systems anyway. You're going to design the system, present them, and sell them. And guess what? Here's the good news. We're going to cover this in a multi-cloud way. And if you understand that a virtual machine is what a virtual machine is, then on AWS, you'll understand EC2 instances. On Oracle, you will understand a virtual machine. On Azure, they call it an Azure virtual machine. On Google, you'll understand a compute engine instance. When it comes to storage, if you understand block storage, you will understand an Azure managed disk or an AWS EBS VM, or whether it's in your private cloud, it won't matter to you. If you understand object storage, whether it's Dell EMC's object storage, whether it's AWS S3, Google's cloud storage, or Microsoft Azure's blog, it's the same thing. So it's like you could learn how to drive a Toyota and not know how to drive any other car, or you could learn how to drive a car. When we cover this, we're going to cover it from a actual cloud provider perspective. So you will know that if we talk about a technology, we will tell you the equivalent technology in most cases through this course that you could use on any other cloud provider. Because if you only know one cloud, you're not going to have the skills for any job in today's world, with 98% of organizations using more than one cloud. Are AWS local zones just a CDN? No, Tommy. AWS local zones are a data center closer to you. Why do you have a data center closer to you? Because it's going to reduce the latency for you going to the actual cloud provider's availability zones, which could be 1,000 miles away or more. Are local zones for caching purposes? No, local zones are your data center that you have low latency. Edge locations are used for caching purposes, but also internet presence, point of peering, and a private network. So it's never going to just be servers. In fact, if I can get this across to you, if you don't understand networking, you won't understand how any of these things works. And here's the good news. We have a completely free, and my team will provide you the link, AWS Advanced Networking course taught by 4 network architects, 3 of which are CCIE certified. The other one was CCNP certified. Obviously, lots of them passed the AWS exam as well. And that's free on our YouTube channel. But we'll get into some networking along the way as well. Where do the VPCs have to be? The VPCs are your virtual private data center. So in your own data center, you don't call it a VPC. It's just called your data center. In AWS, it'll be in their data center, otherwise known as an availability zone. So most of what we're going to cover that we have to, but what normal people cover in a certification is the name of a service. We're actually going to tell you what the tech is. And that way, even if you have to go through this videos twice, if you understand the tech, you'll know where to use the tech, and you'll be able to understand how to work with multiple clouds. So good question. What's the difference between a cache and DAX? So there is this DynamoDB cache, which is a proprietary cache for DynamoDB. Now, Matthew, and I hate to say this, but in reality, you're probably not going to be able to use DynamoDB in almost any environment because 98% of organizations are multi-cloud, which means MongoDB or Apache Cassandra would be what you would use in multiple clouds, as opposed to a Google Cloud Bigtable, DynamoDB, or anything. That's proprietary and honestly doesn't belong in most architectures. And we'll talk about when and where later when you could use it. So that is a proprietary cache for a proprietary database. A cache is basically something that stores frequently accessed information. So there's lots of caches, Matthew. There'll be a cache on your CPU. You may use a cache in a database. So let's talk about what a cache does, and then I'll get back to the content. We'll draw a cache. I'll draw a cache for you. Let me go back to my slides. So here's the way a cache works. And this is going to work in any environment. So let's say this is a server. And it can be anything. This could be a database. This could be a web page. And we'll talk about that. Now, let's say you have a cache in front of it. And this could be a cache for a content delivery network, a reverse proxy. We'll be using caches all over the place, and we'll go through various caches throughout this presentation. And let's say here's your user. So let's say my cat Cindy wants to go look at this tuna picture on the website. And what'll initially happen is, let's change the user to Cindy. User 1 will be Cindy. So here we have user 1, Cindy the cat. She wants to go see tuna. She got told by her buddies on Twitter or Instagram or whatever it was that there's a beautiful tuna that you need to see. So Cindy the cat goes to her computer, types on her pause to go to to go to the website hosting tuna.jpg. The first time Cindy goes to the cache, and the cache doesn't have tuna.jpg. So now the server responds and sends the file tuna.jpg to user 1 Cindy. Now there's this user 2 that also wants to access that same thing. Now user 2, her name is Sunny the cat. And now Sunny decides to go look at that same photo. So Sunny goes to the cache. The cache says, I have the photo of tuna.jpg. And then the cache actually responds back. And because the cache responds back, user 2, Sunny, got the photo. Now, what was so special? The first time when the user got there, they tried to get the tuna.jpg from the cache. The cache didn't have it, so that was called the cache miss. The second time, the information was stored in the cache, and when user 2 Sunny sent the request for tuna.jpg, it hit the cache responded. So because the cache responded, the web server or whatever it is hosting that image didn't have to respond the second time. So kind of keep that in the back of your mind. That is that's what the cache does. And there's lots of cache, content delivery networks cache. DynamoDB has their own proprietary cache with databases, which we'll really use in an industrial environment. We may want to use a memcached or a Redis cache. So there's lots of caches we could use. And admittedly, we are starting with the more networking, more architecture things. So some of these initial concepts are going to be harder than a lot of the things coming in later. And the last question I'll get to is, why will there be DynamoDB questions on the exam? We have to understand what the exam is. These exams that the cloud providers have are designed to get you comfortable and excited about their services. And they make much more money if you use their service than if you went to a MongoDB. So in a certification course, they're going to try, all cloud providers, every tech provider is going to try to get you super excited to use their stuff. Which is why, as an actual architect, you need to be able to know when to use the cloud providers things and when not to. Now, with every service we go over through, we will give you the information of this will probably work really well in any environment versus this is something you need to know for the exam, but please understand in the real world, if you're an architect, you probably can't use it for these reasons and when you could potentially use them. So I hope that actually answers your question with that. So we only answered most of the questions, and here's the reason why. We have about 10 minutes of questions that we can do each time, and most of the questions that were asked, we're actually going to cover. We just haven't covered it yet. So I love that you're here. I love that you're retaining this information. I love that you're asking questions because that means you're thinking. And if we didn't go over it, we will. And guess what? We'll have lots of time. So we're going to have lots of fun with this. So now we're going to talk about connecting to the cloud. And this is honestly a pretty important thing that most people don't actually understand. If you're going to put your systems on the cloud, you have to be able to reach them, right? So normally speaking, we've got a data center, which is often attached to the building. And if you've got your data center, which is a room full of servers and air conditioner powers and power and backup generators and storage area networks and load balancers and firewalls, routers and switches, etc. If that's all in your building, you don't need a connection to it because it's already there and you've got your fiber optic cables. But when you want to connect your New York data center, for example, to your employees that are in, say, Miami, because now you need a wide area network. And as organizations, network architects have been designing these wide area networks for years. No big deal. Now, if your systems are on the cloud and not in your data center, you're going to have to reach them. And realistically speaking, I want everybody to know there's two ways you can reach information. Way one is you get a wire between you and your provider. And basically every option we talk about, these are iPhone headphones, but if you get a private line, like a direct connection, which we'll talk about, it's going to be a wire. And, there's other types of wires or virtual wire connections that we can create. But the wire is basically a wire between you and the cloud provider. Option one. Option 2 is we can create an encrypted tunnel between your data center and the cloud and use private addressing. Super secure, just like the first option. And the other option is we use other types of secure VPNs like software-defined WAN or SASE. But here's the big thing. We can also reach things over the internet. So when you go on the internet, like when you reach a website, that's going through the internet. And why am I talking about this? Well, the internet is a dangerous place. Organizations are not going to put their mission critical systems and have them reachable by the internet because they'll be hacked within an hour. They can't do that. So for an organization to reach its private internal information, it needs a connection. And that's what we're going to talk about next. So we don't go through the internet to reach our systems in most cases. What we actually do is go through a private network to access our private system. So when you hear the term intranet, that means systems that are inside that organization's network. When you hear internet, it means the scary internet with everybody and every hacker in the entire world sitting there. So keep that in the back of your mind. So we are going to have to connect to the cloud with a private network of some kind. Otherwise, we won't be able to reach our systems on the cloud. So I hope that makes sense. So what are the ways we can actually connect to the cloud provider? The cheapest way is what's called a VPN. Here's what a VPN is. We take a public network, which is not going to be secure, and we create a private something through that public network. So if you ever hear about MPLS VPNs, it's a type of VPN. When you actually use a VLAN when connecting to the cloud provider on direct connection, which we'll talk about, that is technically a virtual private network. But typically when we talk about VPNs, we're talking about IPsec tunnels. So when we talk about this today, we'll talk about IPsec tunnels. So if you were to send information directly over the internet, you've got a couple of problems. The first thing is the internet is not secure unless you use encryption. So understand that. The next thing that you need to understand is if you're going to participate in routing over the internet, you need to have people that really understand the BGP routing protocol and some pretty big bad routers, because the internet routing table is like 900,000 routes and you're going to get it from multiple internet service providers. And internet routing is pretty darn complex. So unless you have a staff of Cisco certified internet experts, and not even most of them understand big internet routing, that puts it to the pool of that many of us that actually work there. I used to design internet service providers network, so it's my background, but kind of keep that in the back of your mind. Now, if you're going to send your information over the internet, unless you put it in some form of a VPN, you're going to need to have public addresses on everything, because private addresses can't communicate through the internet. But we don't have enough IP addresses for everybody to get a public address, at least with IPv4. And even though IPv6 is out there, it's been out there for 20 years, it's very slow to be adopted. Now, if you're going to connect your information, not only do you need, on both ends of the connection, you need to be on the same subnet. Ugh. How do we do that? Generally speaking, you can't, because one internet service provider and another internet service provider are going to be on separate address space, so they can't be on the same subnet either. So what we do is we create a VPN tunnel through the internet, and after that, we send our traffic. So let's look at what it really looks like. So let's say in this particular environment, we've got a data center in one part of the world and another part of the world. And actually, it could be anything. But let's say I've got a data center, say, in Palm Beach. Nice place, real good weather, warm places. And let's say we want to connect another data center to, let's say, Katy, Texas. We got our team member Alonzo out there. So it's a data center in Katy, Texas. So what can ultimately happen is the data center in Katy, Texas, were to connect to the internet. The data center in Palm Beach connects to the internet, and an encrypted tunnel is placed through the internet between Palm Beach and Katy, Texas. And that means, this router over here, if it wanted to be, to this router over here, can participate in OSPF routing. They could be peers, and they can pass private information through the internet. And it's encrypted. And here's what IPsec encryption gives us. Let's say this router is named Mike, just for argument's sake. And this router over here is named Alonzo, for argument's sake. When I use an encryption protocol like IPsec, Mike can confirm that Alonzo is who he claims to be. Alonzo can confirm that Mike is who he claims to be. And that prevents something called the man-in-the-middle attack that you may have heard of in cybersecurity. IPsec also uses a hashing algorithm, and we talk much more about this in the AWS Advanced Networking course, which is completely free on our YouTube channel. My team will provide the link. But there's a hash that basically says the message hasn't changed. So if I send something to Alonzo, Alonzo knows that I actually did send it to him, that it was in fact me, and the data hasn't changed. Why does this matter? Let's say a physician is trying to prescribe a drug, and they prescribe a drug as 2 milligrams, and someone changes it to 200 milligrams. Someone could die. So we need to make sure the message hasn't changed. And IPsec also provides something called non-repudiation, which means that if I say something to Alonzo, I can't go back later and say, I never said that. So that's where IPsec VPNs are. You connect to the internet on both sides, and they're there. But if you look at that, what's the weakness here? We'll talk. The weakness here is, the internet's not guaranteed. So if I get a hurricane, my traffic's not going to get through. If Alonzo has a brownout because they don't have enough power where he lives, and this happens all the time, guess what? He's not going to be there. If there's any congestion anywhere on the internet the entire time, our performance is going to be there. So VPNs are great because it's cheap. Internet access is everywhere. And we can set up an IPsec tunnel in a matter of minutes. Whereas if we have to buy a private connection, that could take a little while. So keep that in the back of your mind. Very easy to create, can be set up in minutes, but VPNs have no performance guarantees. And connecting to a cloud provider with a VPN is typically cheaper if you don't send a lot of data. But if you send a lot of data, it's going to be cheaper to use a private line or a direct connection, which will give you much, much, much better performance anyway. So if we're going to connect to AWS via a VPN, it's going to be, or connect two data centers to each other via a VPN. It's going to be called a site-to-site VPN. Now, in an environment, we can also create a multi-site VPN. And what would that be? Basically, let's say we took Palm Beach, Florida as a hub location. We could have a VPN to, say, Montego Bay, Jamaica, really beautiful place over there. We can have another one to the Cayman Islands, and Florida could be the hub in between them. That would be considered a multi-site VPN. Now, when you connect a VPN, you have to terminate the VPN on something. You just can't connect to something. It has to be terminated somewhere. So normally it's done by a VPN concentrator. With the cloud provider, they basically have a gateway that you connect to. It'll be a VPN gateway. And when you create an AWS VPN, IPsec VPN, or pretty much any VPN for the most part, what'll happen is you'll set these things up. They will go through an internet key exchange, which are the security keys that are going to be used for encryption and decryption. They will determine the type of security attributes for the tunnel, maybe the algorithm they use for the same encryption, the encryption type. And then you can typically set up your routing, which could be BGP or whatever it would be. In a private environment, you might use an interior gateway protocol like OSPF, for example. But when it connects to external organizations, you have to use an exterior gateway protocol like BGP. So we'll use BGP for this. So I understand. Now, one of the things I want you to understand is when you connect to AWS, they call it a high availability VPN. And I want to show you why they call it that. But I want to show you the practicality of why it's not going to be high availability enough for you. So let's say this is your data center, or this is your campus, or this is wherever you're at. I'll call it campus. Let's say this is where your employees are. And here's what AWS does, which is honestly incredibly cool if you understand what they're doing. So you've got two availability zones. Let's say you're using two availability zones in a cloud provider, two data centers. Not enough for a super high availability, but good enough for most organizations. You're going to have this VPN gateway, this VPN type device, whatever it's called. And what AWS does, and this is very cool, and this is why they call it a high availability VPN, is this virtual VPN concentrator will automatically create a virtual private network to the two different availability zones, which means, and this is very cool, if you have a connection from your router to this virtual, this virtual VPN concentrator, and this link goes down, you still have another connection to another availability zone. And I will tell you right now that this virtual device won't crash. As long as the cloud's up, it'll stay up. It's a logical link, not a physical router. Here's why this isn't good enough. Because if the link between your organization or your campus and the AWS virtual router goes down, you have nothing because there's no wire between you and them. And if this router were to die, guess what? If the router goes and the link's up, well, the link will go down because the router's not there. You still have no connection if the router's dead. So if you really want to design these with a high availability wide area network, what's going to need to happen is this. The organizations are going to need to have 2 routers, and they'll have to be across different wide area network providers, and they will connect to 2 different virtual gateways. They will have, and this could be done over a physical wire or a VPN, it doesn't matter, across different internet service providers. They will have these 2 virtual routers and 2 links, and that way either router at the campus could go, or either link could go, and you're still up and able to connect to your systems on the cloud. I hope that made sense. But this is why these things are so important to think about from an architecture perspective as these systems would be designed. Now, pretty much what goes into setting up a VPN is very simple. You make sure your systems are connected to the internet. You're going to determine which AWS virtual gateway you're going to connect to. And you'll pick a routing method where you put static routes or dynamic routing via BGP. And that's it. It's pretty much set up. Okay, so let's talk about the next kind of wide area network we can use. And this is what businesses do when it matters. So if you're going to put your systems on the cloud and you need real performance to get it to them, you're not going to leave your performance open to whatever the windfalls of the internet are. And honestly, all it takes is a pop star to send a tweet of their cat. And if this pop star has 50 million followers, poof, next thing you realize the internet can be congested. So when it matters, organizations use private lines. So a private line or a private wide area network connection, we guarantee your bandwidth. If you buy 10 gigabit per second, you know what you get? 10 gigabit. If it's 2 milliseconds across your link, it's going to be 2 milliseconds. It's not going to be like the internet where it's 5 milliseconds, 10 milliseconds, 7 milliseconds, 80 milliseconds, that variation. And certain applications like video and voice tend not to do well with variations and latency, otherwise known as jitter. Private lines more reliable. It is guaranteed. And you can take multiple private lines and bundle them together. And you can create something called the link aggregation group. And that way you can lose some of the links and still be up and bundle the performance. So let's really talk about what goes into it, and then I'll architecturally show you what it looks like. When you connect to a cloud provider or a wide area network provider and you're using a private line, if it's going to be Ethernet, it's going to be fiber optic. Now, if it's a short distance that you're connecting, say switch to switch, you can use something called multi-mode fiber. But when it is a long distance, you have to use single mode fiber. Because the cloud provider is a long distance from you, or the direct connection location that you'll be connecting to, when you use a fiber optic connection, you will need to use single mode fiber. So, going to be a test question right here. So, what specifications would you probably use for your direct connection? If it's gigabit Ethernet, it will be single mode fiber and it will be 1000 base-LX. So I'll say it again. You may see it on a test. For a gigabit Ethernet connection over direct connection, it will be single mode fiber 1000 base-LX. Now, and that's pretty much a standard protocol. Now, if you want a 10 gig connection to the cloud provider, you are going to be using 10G base-LR. And keep that in the back of your mind. And if you've ever worked with fiber optic connections, you know there's 2 labels. There's a send label, a laser, and a receive laser. And in your routing protocol, it's possible that one of the sender receives goes down and the other link is still up. So it could potentially take, 60 seconds, 90 seconds, or minutes or more to detect that you can't really communicate over that link because it's really dead because it only goes one way, not the other way. And if you know anything about TCP, for example, it requires, bilateral communication. So you lose one side of it, it goes down. AWS supports bilateral forwarding detection, that just like every other technology vendor does, and that gives you the ability to detect a downlink, which is great. When you send something to a cloud provider, you're going to be sending it over a shared connection, which means you're going to be dealing with something called a VLAN and an 802.1q tag. And we're starting with the harder stuff, the networking thing, so it's going to get easier as we go along. But if you don't know networking and you don't understand the networking, everything falls apart. So that's where we're going to start here. So it'll be backhauled. So let me kind of show you what this would look like real quickly. So this is what it's typically going to look like. You'll buy a connection to a co-location facility. And that's going to be called the direct connection location. And this box over here, right over here, where it says customer or partner space, that's the wide area network link you buy. You'll notice that AWS, where it says AWS space, has a network that goes right back to AWS, the AWS Global Network on the side of this. So what has to happen is you will basically need to take a wire that's going to connect your customer space and connect it to the AWS space. And this is something called the cross connect, where you're going to connect in a meet-me room and you'll basically have a switch or a VLAN. So it's the way it works. You connect to the direct connection location center. AWS is connected to the direct location center, and your cable needs to be run between your device and their device. That's called a cross connect, and that is the way this works. So there's some things that we're going to need to talk about when we go through these direct connections. So I just showed you that you've got the cloud provider stuff and you've got your stuff. Now, they can't just let anybody buy a connection into the building and then connect that network port of yours to AWS. Because what if you were bad? What if you were a hacker? What if you just tried to sneak in there and connect into the systems? So you can't let somebody plug into your systems without knowing who they are. It's called physical security. And they need to be a permitted user of the system. So in this particular case, you're going to need to get permission from AWS to go from your stuff to their stuff to get that cross connect. So what'll happen is you will go to AWS and you will ask for a letter of authorization. And basically you can request that letter of authorization either from the management console, there'll be a place to do it, an API call, or the command line interface. You will request that letter from AWS. If your application is approved, and it will be because they want to connect you, they will provision the switch port that you connect to at the direct connection location center, and they will allow those two cable to work. You'll download the letter, you'll give it to the service provider in the direct connection location, and they'll run that cable or the cross connect, which is just a cable between you and them. Now, when you connect to AWS, you're going to have two different links that you can connect to. You're going to connect to a private link, and you're going to connect to also, you have the option for public connections. So let me explain to you what I kind of mean like that. And then I'll explain them in depth. Bear with me a second. Take my little drawing board over here. We'll draw this out. Sometimes, working through it with a whiteboard to me is the easiest way to learn these things. So you've got let's do this. You've got your direct connection location. So this is your location, router. This is your router or switch at the direct connection locations facility. Over here is going to be the AWS router or switch. So this is yours. I'm going to call it customer owned, customer edge. Now this is going to be another router, and this is going to be the AWS. It's going to be considered the private edge. And then AWS has some stuff that's public and has some private. So this is your VPC. And then let's say, and your VPC is private, right? Oops. You want to make sure it's private anyway. And then AWS will also have some public services. Oops. So what will ultimately happen is you will buy this link between you and the provider. You'll get your letter of authorization, and that will enable that cross connect between you and the AWS router. And then you can use a public interface, and they can build you basically a virtual tunnel to things, say like AWS S3 or object storage. And you'll have another tunnel that'll be your own private network that's going to go back to your VPC. So I kind of think this will make sense to you. So now that you see that, let's talk about AWS and public and private interfaces. So a public virtual interface enables you to connect to all AWS public services in your region that you have the direct connection to. So what's that mean? DynamoDB, something like SQS, and any kind of public endpoint. And if you're going to do that, because it's public, the cloud provider is going to have to use a public IP address to be reachable from the public, and your address will have to be public because it's basically going to have to be routable, a globally routable address. And the way you'll reach this is by exchanging BGP with AWS. So that's something public. Now, a private interface is going to be the exact opposite. A private interface or a private virtual interface is going to be a tunnel to the resources in your VPC, just like a Valtio. And you'll advertise your routing information from AWS, but they only accept a very minimal number of routes. So you're going to need a good IP addressing plan, and your network architects are going to have to aggregate or summarize your routes to make it work. So let's talk about some more things so far. So a direct connection gateway. What is a direct connection gateway? A direct connection gateway is going to be an AWS service that enables you to connect your AWS infrastructure to your data center using a private link. The benefit of using that direct connection gateway is that it enables you to connect to more than one VPC, or for example. So you connect to the direct connection gateway, and that enables you to connect to various things. So you can view the direct connection gateway as a router with virtual links, just like we've been using in the data center for the last 30 to 40 years. So how does this work? A direct connection is you basically will get your direct connection and connect it to the direct connection gateway through an AWS delivery partner. Now, how many of them are there? There's about 60 of them in the US. Companies like AT&T, Comcast, Sprint, British Telecom. And, the partners will usually be based upon your region. And delivery partners will have their global infrastructure, and they'll terminate their networks inside of an AWS co-location facility. And that way you can connect to AWS. Now, when you connect to AWS, it is not going to be over a private wire. It's a private wire to you, but it's backhauled to AWS. So if you see this, and I want to go back to this, you are connected via a private wire to this. This is your stuff. And then you'll get a cross connect, which effectively is going to create a wire between you and AWS. You see it as a cross connect on those switches, but it's going to be at a layer 2 thing, so you won't see it. And then you see that this little black lines that go back to AWS. This could be you and 10,000 other customers that are going to AWS on that same link. So how do you keep your information private? You're going to have to do something on the network side to send that information to them. And what's going to happen is you're going to be sending them a VLAN. So what does that mean? So the way it's going to look is going to be something similar to this. So we're going to draw more switches here. I think it'll make it easier. So let's say on the switch, it's not going to work. Let me get rid of this fill. Bear with me for a second. I think this will help. Okay, so let's just say this is a port. So what a VLAN is a switch can have multiple ports. Oh wait, I have one. Hold, this will make it easier. So here's Here's an enterprise grade switch, and you can see it's got multiple ports on it. And you can see these all right now out of the box. Every one of these switches, ports in the switch can talk to each other. But what if security purposes you wanted only these ports to talk to each other, and then only these ports to talk to each other, and only these ports? You would create a VLAN. So going back to my example here and how this is going to work, here we've got a bunch of switch ports sitting in a switch. I'm going to double these intentionally. The top, we'll call it VLAN 1. And anything in VLAN 1 can talk to VLAN 1. Oops, don't want to get that 2 in there. And then over here, we've got anything in VLAN 2 can talk to VLAN 2. So we're going to connect to their switch at the direct connection location. And they're going to have a whole lot of ports and a whole lot of VLANs. So what's going to happen is they'll basically make a VLAN for you to connect to. Actually, I think this will be easier if I draw it this way. What I'm trying to do is just take about 500 to 1,000 hours of networking and condense it to about 5 minutes here. So what'll happen is when you place something on the wire, you see how this one says 1? This is going to be a frame that would leave the switch. When it leaves the switch, it's going to stick a tag on it. And in this case, we're going to put let's find a color for this. We'll put a yellow tag on it. And when the frame is pushed on the wire, the switch will pop this tag on it. And when the switch reaches its end destination, it'll take the tag off, and it'll pop this back into a VLAN 1 on the switch. And that's called the trunk port. So when you connect to AWS, or the switch connects back to AWS, imagine they've got thousands of these VLANs sitting here. And the way they keep your traffic off segregated is they pop a tag. Now, maybe VLAN 1 has a yellow tag, and maybe VLAN 2 has, oops, let me pop a tag. And maybe VLAN 2 is going to have a different color tag, because every VLAN has to be unique. And that's how it works. So VLAN 1 hits the wire. And when it reaches the far end switch, this is stripped off, and this goes back into VLAN 1. VLAN 2 hits the wire. They continue as a unit till they get to the end. When it gets to the end, this little tag gets stripped off. VLAN 2 is placed in VLAN 2. So I kind of hope that works. I tried to oversimplify a lot of networking in a short period of time, but so keep that in the back of your mind. Now, we can also do a couple of other cool things. When we use these direct connections, we're going to have to exchange routing information. What is routing information? It's how to reach your subnets. And we've got a good video on subnetting that my team can provide a link for. And we've got a good 8-hour video that me and Mark Milovanovic, 2 CCIEs, made for you on BGP. Can't cover it here, but my team can pop that in the chat box. Recommend you watch it. It'll help you a lot in your career. So now let's talk about these private virtual interfaces a little more. Remember, those private virtual interfaces go to your VPC. And the AWS Direct Connection Gateway, which we talked about, is a router for you to connect to, which enables you to connect to, say, different resources. Just keep that in the back of your mind. Now, when we're actually sending our information over a direct connection, we can also encrypt it as well. And here's what I mean by this. We can run IPsec over a direct connection, or we can encrypt at layer 2 using something called MACsec. And if you want to learn more about MACsec, you can just look at the IEEE specification 802.1AE. And for some more information about that, that's what I would do. So let's talk about our direct connection virtual interfaces. I talked about the private virtual interface and what we use it for to go back to our systems. I talked about the public virtual interface, and that's how to reach, to example, how to reach AWS public services such as DynamoDB. But I didn't talk about a transit virtual interface. And a transit virtual interface enables you to take your direct connection on-premises environment and connect it to something called a transit gateway. And AWS has transit gateways, which are basically routers that you can also connect to. And here's an example of what this could look like. You can basically take your data center, you connect to your direct connection location center, and you connect to your VPCs via these private connections on the left. You can connect to transit via this transit VIF, and that's going to connect you to transit gateways, which can take you to, say, other VPCs or other environments. And you can use a public one, which you don't really see here, to connect to some AWS services, for example. So let's talk about why you might want to use a direct connection gateway. Well, if you need to connect to multiple, say, environments to your VPCs, you could run multiple connections. And if you run multiple connections, you've got multiple connections, which means multiple direct connections to pay for. So that's one thing. If I have 4 10 gig connections and each one's connecting me to something different, I've got 10 gigs to access service 1, 10 gigs to access service 2, 10 gigs to access service 3, and 10 gigs to access service 4. Now, or I could, and that we bought 4 private lines and we've got 40 gigs. By comparison, if I've got one 10 gig connection and I split it with the direct connection gateway, the max bandwidth I can get is 10 gigs, and I can share it to those other 4 things. So I could potentially get 10 gigs if those other virtual links aren't doing anything, or I can get a maximum of 10 gigs. So, keep that in the back of your mind. A direct connection gateway will reduce the number of links that you need, so it will reduce your costs. But it will also reduce your performance, so it's based on what you actually need. So if you connect via a direct connection gateway, you're going to get reliable, low latency performance. And that's going to be a whole heck of a lot better than you would get over, say, an IPsec VPN over the internet. And it's going to give you some security because it's a private connection, which is more private than the internet. And you can now encrypt that too, and it gets really good, really fast. So I hope that helps. I covered a lot of networking. I won't be able to answer all the questions on networking, but I'll do the ones that we can, and most of the ones we'll actually cover as we go through this program. But let's take some questions for a few minutes, Chris. And before we do, I want to remind you we've got over 40 labs, real good labs for you to do in your spare time. You can get them in the description of this video or the chat box. We also have a certification ebook that we wrote for you, the kind of certifications, if your goal is to, say, be a solutions architect or a cloud architect, the certifications that will build your brand and make people more inclined to hire you versus the certifications which may scatter your brand, scatter your efforts, and will keep you getting hard because it'll make somebody not see you as where you really want to be seen. What's the difference between a direct connection gateway and a NAT gateway? A direct connection gateway is a router that I use to create a private link between you and the cloud provider. And NAT gateway takes your private addresses and converts it into a public address for them to go out on the internet, much like a firewall does. So you may be at work, and if you do an ipconfig/all on a Windows machine, ipconfig/all, you'll see that you may be coming from a 10.something.0 address base, a 172.16 address base, or maybe a 192.168.1/0 address base. They're all private addresses that can't be routable on the internet. So a NAT gateway will take your private address, translate it into a public address, so you can go out to the internet and your traffic can come back. But they're totally unrelated to what we're talking about. But we will get into NAT and NAT gateways. Direct connection gateway gets you to the cloud. Is message digest the same as a message signature? Not really. So message digest, something like message digest 5, is a type of hash. So and we don't typically use this type of hash anyway for this reason, and I'll talk about why. So message digest is something that can be hacked in a matter of minutes with a modern GPU. But what's the point? So with a hash, here's what happens, and we can't get into all the math in this course, but because it's PhD level math, it's really cool stuff. But here's what you need to know: when you put something into a hash, it always comes out. A consistent input comes out. So if I put a letter A in, and I have a 256-bit hashing algorithm like SHA-256, the letter A will come out as 256 characters of something. Every time the letter A goes into the hash machine, the same output comes out. So why do I do this? Because I can guarantee if I put a message in, you can guarantee that the message hasn't been changed by comparing the hash. What's super cool about these one-way hashes like MD5, even though MD5 is outdated, is so if A comes out as 256 characters of numbers, you can't go from those 256 characters to figure out that it was really the A. So imagine being able to put a banana in something and have it come out as a Mercedes. But you couldn't take the Mercedes and turn it back into a banana because you wouldn't even know that it was a banana in the first place. So that's the hashing that's typically done in IPsec to make sure that the message hasn't changed. And so imagine somebody puts $1 billion in their bank account, they're real rich, and somehow someone changes the $1 billion to $1 and siphoned off the other $999,999,000, they wouldn't be too happy. So that's why we use hashes to make sure the messages haven't changed. Does a local zone have a VPC or just an AZ? So local zones have VPCs. And here's the thing. If you remember that the VPC is nothing more than a virtual private data center that sits in a data center. So a local zone is a data center near you. An availability zone is the main data centers that's far away. So yes, you can definitely have your VPCs. You can create subnets in that VPCs that's specifically going to be associated with your local zone, the same way that you would create subnets in an availability zone. Really great question. And Prab, as you like to go by, I'm so happy to see you here today. Look forward to seeing you soon in class 2. Okay, wow, that's pretty great. So I guess we will get back to the content. I'm giving you the rough content first, so it's going to get easier and more fun as we go along. So I figure we all start with lots of energy. So I want to know that you're awake, alert, and oriented. I come from internal medicine, and we always are obsessed with checking that. So I'd like to know that you're still here and awake. Give me a hashtag, please, AWS Solutions Architect Associate. Hashtag AWS Solutions Architect Associate as one word. And that will really help you there. And that way I can know that you are awake. And also, if you're enjoying the video, please give it a like. Please subscribe to the channel. Hit the bell to be notified of new videos. And check out the descriptions of our videos. There's a lot of free resources in all of them. Free guides on your career, free guides on how to pass interviews. Lots of descriptions of our videos have these things. So please go get them. Is a direct connection the same as a VPN? Well, yes and no. In practicality, the direct connection is technically a layer 2 VPN, but not really. So a VPN that normally we think about is an IPsec tunnel, where a direct connection is kind of like buying a wire between you and the end location. You own the wire, you've got guaranteed bandwidth, guaranteed performance, guaranteed everything. So they're not really the same. Good question, though. All right. So now let's talk about link aggregation groups, something I always love talking about. So what is a link aggregation group? So if you need high-speed access, you're going to need to use a direct connection. And sometimes you can't get enough performance in a direct connection. So what if you need more than one connection? If you do 2 separate connections, now we've got to do some cool BGP magic, and I'm okay with that. I love BGP, but it adds to the complexity. If we do more than 2 if we have 2 wires in a layer 2 environment, one wire will be natively blocked by spanning tree, so we can't use both of them. But if we can bundle multiple little wires into a big wire, that's what a link aggregation group is. So in order to make this work, we're going to have to have 1, 2, 3, or 4 identical links. That means same speed. So if I've got a 10 gigabit link, I can't have a 10 gigabit and a 1 gigabit link. They all have to be 10. They also have to be the same latency, which means if AT&T's link is 2 milliseconds of latency and Verizon's link is 3 milliseconds of latency, or vice versa, I can't bundle a Verizon link with an AT&T link. I'm going to need to put all these links together, same speed and latency, which usually means same provider. So in networking, we have a saying, in high availability architecture, we have a saying that says 2 is 1 and 1 is none. One cloud, considered reckless by many organizations because it's a single point of failure. When organizations buy a wide area network to AWS, they're not going to buy 2 links from AT&T and hope that the AT&T network doesn't have a catastrophic outage. They will buy 1 link on AT&T and maybe 1 link on Verizon or NTT or CenturyLink or somebody else. So with the link aggregation group, if we need to bundle 4 links from, say, AT&T, chances are we're going to need to bundle a backup 4 links with, say, a Verizon. Keep that in the back of your mind. So by default, a AWS link aggregation group will stay up if any of the connections in the bundle fails. So that's default. What if you have 4 links on this link and 4 links with the backup, and 2 of the links fail on AWS, on, say, AT&T, but all 4 of your links are in Verizon? Wouldn't it be better to send your traffic over Verizon, which has double the bandwidth than AT&T? Well, you'll need to deal with that, to traffic engineer that, to make that happen. Because by changing, and there's some tuning things that you can do on your link aggregation group, like the minimum number of connections for the link aggregation group to stay up. So what does this really look like? Let's go whiteboard it out. I'll show you what a link aggregation actually looks like, and then I'll show you what it would need to look like if we needed to do high availability. So let's say we've got an Ethernet switch over here, and we've got another Ethernet switch over here. So let's say this, I'll make it on the fatter side for a line. I'm going to say this is 10 gigs. So instead of leaving that as 10 gigs, I'll have another one which gives me 20, another one which gives me 30, and another one which gives me 40. That will look to the routers and switches as a single 40 gig link. Let me try and make this more transparent. And that means, you don't have to deal. So what it'll see, it's going to see this as one big link, as 40 gigs. And that's totally fine. But if all these links have to be the same performance, that means they're going to have to, for the most part, be all on the same wide area network provider. That wide area network provider becomes a single point of failure. So what you'll ultimately do is, if it really matters and you need this kind of bandwidth and you're setting these link aggregation groups up, and this is the kind of client I work with, you're typically going to have one link aggregation group, which is, say, 4 10 gig links on one ISP, and then you're going to have another 4 gigs, 4 10 gig links on another ISP, and that way you've got ISP failovers. So kind of hope that makes sense. So that's what we're really talking about with regards to link aggregation groups. Now let's do a basic networking review, basic stuff. So this is something you all really need to understand. It's something called the OSI model. And this OSI model really is a standard way for people to describe technology. And the reason we must do this, we have to, is that if I speak to you in Greek and say "Πώς είσαι σήμερα," and you're speaking to me in another language, say English, if you don't speak Greek, we're not going to understand. Now, one of the reasons I never use acronyms in real life, and one of the reasons that is they cause errors. So the networking people were very smart. They said, look, if we're going to talk about the network, we have to all describe it the same way. We can't have a virtual machine, which AWS decides to call EC2, and Google calls it a compute engine instance, and Azure calls it an Azure VM. We have to have a standard name. Well, when it comes to networking, we need standard names. So we talk about the 7-layer OSI model, and let's talk about what it is. At the physical layer, that is our wire. That is physical. So I got a fiber optic cable between two switches. We send photons on that fiber optic connection over via a laser or pieces of light. It's there. If we are on what do you call it, a copper cable, like an Ethernet cable, standard Ethernet cable, we're sending electrons. We're going to call it bits that we're actually sending over it, but that's the way these cables work. So layer 1 is the physical layer. Layer 2 is the is the hardware level, the card. So every device has a physical address. Well, the wire itself doesn't have an address. It's just cabling. So layer 2 is the data link layer. So if you think of the Ethernet card sitting in your notebook, that Ethernet card is a hardware card that connects you to the network. That is the data link layer, otherwise known as layer 2. Now, guess what? Your card actually has a hard-coded address. It's called a MAC address. So if you're in a Windows system and you do ipconfig//all, you'll see the physical address called your MAC address. You will also see something called so you will see the MAC address. You will also see the next level up, which is the IP address of your system. So layer 1 is literally mean a wire. Layer 2 is actually the data link layer, or frames that we're sending, or MAC addresses. Layer 3 is the logical addressing. So the IP address. Before everybody used IP, we had AppleTalk addresses and CLNS addresses and IPX addresses. So layer 1 wire, layer 2 card, layer 3 network. And at the network, we send packets. At layer 2, we send frames. At layer 1, we send bits. At the next layer is how we send the data. So do I send the data reliably using TCP? Am I sending a ping or a test message, which is Internet Control Message Protocol? Am I sending real-time streaming data via the RTP protocol over UDP or UDP? So that's layer 4. Now, for the most part, networking is layer 1 through layer 4. So when you deal with a network engineer like me, or someone that used to be a network engineer before being a network architect, everything we dealt with was, is it cabled layer 1? Are the Ethernet ports plugged in, or are the ATM or frame relay devices plugged in and hard-coded with the right, link layer address? Do the devices have the right IP addresses at layer 3? And is it TCP traffic or UDP traffic or ICMP traffic? So that's really all networking people think about. But we're going to go up. We also have to control the connection between the two devices, and that's done via a session layer protocol. And at the session layer, we talk about sockets. Now, we may be dealing with encryption, such as TLS encryption, which was the replacement for the old SSL. Encryption is done at layer 6, or the presentation layer, and the application layer is what you use. Open up Google Chrome, that's at the application layer. Your TLS encryption was a connecting between you and, say, a website. When you see that little lock and it's HTTP-S, it's done at the presentation layer. The session layer controls the connection. The transport layer is that TCP, UDP, ICMP kind of thing. The network layer is your IP address. The data link layer is the MAC address in your system. And the Ethernet cable you have is the physical layer. Oops, didn't mean to do that. I have some. So let's talk about giving an IP address to your VPC, IP addresses in your VPC. So if a device needs to be reachable, it has to have an address. If I want to send a mail to somebody and I put it in a letter, I need to know their name, their street address, their street number, their postal code, the state or country they're in, that kind of thing. Otherwise, how will the mail person know how to deliver the mail? Well, same thing in networking. You connect to something via its address, and every address that's going to be talking to everybody else needs to have a unique address. Now, even your mail has to be unique. You could have everything. It could be on 123 Main Street. And but the zip codes are going to be different, or the postal codes. So keep that in the back of your mind. When it comes to IP addressing, there's two forms. We have the form which is reality for now, which is for the most part IP version 4. And we have the future version that's been the future version for 20 years called IP version 6, which is predominantly used at today's point for putting IP addresses on mobile phones. But hopefully at some point it'll be used, because we kind of challenged with IP addressing for v4. So when you provide IP addresses for your VPC, it's internal to your data center. So what kind of IP addresses do corporations use inside of their data centers? Private addresses, meaning the addresses that were specified to be private. So if you want to learn about the private addresses and where they're at, you can go to the IETF.org, the Internet Engineering Task Force, and look up RFC 1918. That's the actual specification for private addresses. And that's what we network architects look at. That's what people read when they have actual specifications, when they do like a Cisco certified internet network exam. And my number is 7417 when I passed that exam 20 some years ago. So the addresses that are specified here are going to be the 10.0.0.0/8, the 172.16.0.0 all the way to 172.31.0.0/16, and the 192.168.0.0/16 address space. Remember, these are private addresses and they are not globally routable. In today's world, everything we're going to be using is classless IP addresses. We don't deal with classful addresses anymore. But for argument's sake, the 1.0.0.0 all the way to the 126.255.255.255/8, that was a Class A address. In case you were to see that on an exam, it's not reality for real. There's classless interdomain routing, but now you know. For Class B addresses, it begins with the 128.0.0.0, and it ends at the 191.255.255.255. And they're all /16s. We have the Class C addresses, which are the 192.0.0.0 all the way to 223.255.255/20, all /24s. And of course, the IP multicast addresses, which were the Class D addresses, which are 224.0.0.0 all the way to 239.255.255.255. So that's academic. That's why we covered it. That's why I went over it quickly. So in today's world, we use classless IP addressing, which means subnetting and supernetting. So Mark and I did a 6 or 7 hour or some really long subnetting workshop. We had a couple of Cisco certified internet experts doing it for you because we wanted you to get it for real. So we did that. My team will drop a link to that in the chat box so you can see that. So you'll be given a CIDR block, which is the whole range of IP addresses, and you'll have to chop it down and subnetting this down. So why do we use subnetting? I mean, what's the point? Well, the point is that every router needs to be on every interface on a router needs to be on a different subnet. For the most part, every Ethernet card in a server needs to be in a subnet. And I could use 4 ports with the /8s and literally burn up and waste 16 million IP addresses and never be able to use them again. Or I can have 4 ports in a router and subnet them to /30s, and you lose 16 addresses versus 16 million addresses. So you get the point. It's about efficiency. That's why we're subnetting. So what? And in that video, that subnetting webinar that my team talked about, they will teach you how to subnet. We spent hours and hours and hours doing it. There's also a BGP workshop you should see. But in practicality, what is it really that we're doing? It's really this. Let's say I gave you the CIDR range of 192.168.1.0/24. You could chop that into multiple smaller subnets. Say, for example, the 192.168.1.0/28. And then you could consider maybe a 192.168.1.16/28. And then the next subnet you could use would be 192.168.1.32/28. The next subnet you could use would be 192.168.1.48/28. The next one you would use would be 192.168.1.64/28. And that's really what we're talking about. And you can see I took a network and subnetted it down to show you /28. So if I only gave you that single /24 subnet, which only really could support a total of 256 hosts, or -2, minus a 254, you can see I've taken that block and I've subnetted it down into quite a few different subnets. And this is how we efficiently use IP addresses. We use the right kinds of subnets, and we do classless internet domain routing. Now, and again, we covered it in that subnetting workshop. I can't cover it here. When you send routes to AWS or any cloud providers, they're limited to like 100 or 1,000. So you can only send them a small number of routes. Now, I'm going to tell you, a modern enterprise has 5,000 routes in the routing table. And a cloud provider is like, well, we can take 100 from you or something small like that. So if the IP addresses are designed properly, you can basically summarize them. And I'll show you what we did here. And by summarizing them, it reduces the memory and the CPU utilization on your routers. And what does this look like? Well, it looks like this. Like if we only had 100 routes that we could share with a cloud provider over BGP, and we had these /24 subnets, these 4 of them, we could send 4 of these. But what happens when we've got 14,000 of these? But we could take these 4 and summarize it into a single route. So depending upon how we summarize the routes, we can limit how much information the cloud provider needs to know, or another provider, which can give us traffic engineering. But that is way outside of the scope of a solutions architect associate. We're talking, network architect, CCIE level things for that. So please watch the video, and that'll at least get you there. But that's why we have to do these things. Now, lastly, I'll briefly introduce the concept of an IPv6 address. So an IPv4 address is a 32-bit address. So what does that mean? It means the total addresses I have are 2 to the 32nd power minus 2. So there's that. And that's because each bit is either 0 or 1, on or off. So people that designed IPv4 and others kind of realized, the internet, what they designed it was, a private research, military university kind of thing. There weren't a lot of users on it. No one expected everybody to start using the internet. Every house to have 2 and 3 computers for the most part in many parts of the world. People to have IP phones that have IP addresses on it. Refrigerators which text message you while you're at the supermarket telling you what you need to buy. Your TV that's pulling Netflix and Amazon stuff, and maybe some houses have multiple TVs, etc. So no one really realized that the internet was going to grow behind the few billion addresses that it initially had. No one. So if a 32-bit binary address, which was 2 to the 32nd power minus 2, wasn't enough addresses, they needed to fix it. So instead of a 32-bit address of 0 and 1, they came up with a 128-bit address that was in hexadecimal address space. So binary is 0 or 1. Hexadecimal is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A alpha, B Bravo, C Charlie, D Delta, E Echo, and F Foxtrot. So now we have 16 to the 128th power. Now you can see we've got lots of addresses for all these wacky weather sensors that are out there, car sensors, self-driving cars, IP-enabled drones, mobile phones, you name it, and it's there. So that's kind of where we're coming from. I think there's even toaster ovens that'll actually talk to you. So there's that. So now we're going to get into the VPC. And here is where we're going to get into a lot of the geeky stuff. After this, it gets real easy. So seatbelt in, muscle up, and we'll get you there, all of you. So the components of your virtual private data center, which they like to call virtual private cloud, is going to be your routing to the internet via an internet gateway, different types of ways to kind of NAT your information out to the internet and come back, which will be NAT instances, NAT gateways, etc. We're dealing with public IP addresses. We'll be dealing with things called endpoints. We'll be dealing with how do you connect multiple VPCs to each other. We'll talk about some packet filters, otherwise known as access control lists, like you'd use on a router, but AWS calls them network access control lists. And we'll talk about like the host-based firewall that comes with AWS services called a security group. So we'll begin with, the routers have a routing table in them. And in order to go to your destination, every device in the world, what it does is it sets up a routing table. And what's a routing table really? A routing table is just a list of destinations. So if I've got a router with 4 links, to reach the 192.168.1.0 subnet, go out this link. To reach the 192.168.2.0 subnet, reach this link. To reach the 172.16 subnet, go out this link. To reach the 10.1.2.3.4, go out this link. And that's why the routers build a routing table, is they build a map. So if you're going to be able to send traffic around your cloud, you have to know how to get your traffic from point A to point B. And this is why we need virtual routers. So that's, realistically speaking, what we're actually talking about is the virtual router and the virtual router itself. So the routers will need this map. So what's this map going to look like? You're going to see a routing table, and it's going to look like this. It's going to say the 172.16.1.0 subnet is local to me. But to go to reach the 192.168.0.0/16 subnet, use that PCX-123456 link. But to reach this one critical subnet, which is more specific, even though it's inside of that aggregated route, 192.168.1.0, go out the left link, please. PCX-654321. And then you'll see something called the 0.0.0.0/0. That is a route that basically says, if you don't know where to go here. And that's going to go to the internet gateway, and it'll say like IGX 123456 or whatever that number is. That's the map. So how do you build the map? Well, you have to build it somehow. So there's going to be a couple options you could use. Option 1. Let's say you got a network which has got 5,000 routers. You manually go to all 5,000 routers and you configure them with 15 lines, 15 statements as to reach this, go this way, to reach this, go this way, to reach this. So now you're going to have somebody SSHing into a router and lidding and cutting and pasting, thousands of lines of routes to 15,000 devices, for example. And as soon as one link gets cut, you're now, not only will the traffic not know how to heal itself, but you're going to manually have to go to all 15,000 routers, and you're going to manually have to reconfigure them. And when that link comes back up, you're going to have to go back and do it again. So clearly, static routing doesn't work very well or doesn't scale. So what is a static route like? For any of you that are old enough to remember you wanted to go visit your friend's house, so you looked at a paper map, and you said drive 3.5 miles and then make a right on 123 Mulberry Street, then drive on Mulberry Street for 2 miles and make a left onto Main Street, and you printed yourself a list of directions. That's a static route. Then on the way to your friend's house, there was a roadblock because of construction or a car accident or something, and you didn't know where to go. That's static routes. In today's world, we have these little things called GPSs. They're on our phones, or they could be in our cars, depending upon the cars we have. And now you're on the way to your friend's house, the road is blocked, and you make a right, and it says recalculating route. Please make a legal U-turn here, go here, and then you get to your destination. Well, I get lost when I drive my car. It's pretty bad, so the GPS is my friend. I also love routing, and I spent most of my life designing routing. So something I like. So when it comes inside of organizations will use what's called an interior gateway protocol. And inside of an organization, we're going to use things that are designed and optimized for speed. Now, when we connect to organizations outside of our organizations, we're going to connect to them via something called an exterior gateway protocol. Now, here's an example of basically the way a cloud provider would be laid out, or the way a data center an business's data center would be laid out. You can see that inside to their organization, they're going to have a bunch of routers and switches, and they're going to run a routing protocol like OSPF or ISIS. or potentially EIGRP, but that's proprietary, so we don't really use much of it in today's world. And then when they connect to another organization, they connect to each other via BGP. Why BGP? We use BGP because it gives us what we call a lot of nerd knobs, and enables us to tune and configure and traffic engineer our traffic. It gives us control over the routes we take in and the routes we come out. So when you connect to an external organization, they'll be in a different autonomous system than you, and you'll use BGP. When you connect to the cloud provider, they are not you, so you use BGP. When I connect to 3 different internet service providers and share routes, you use BGP. But the cloud provider is different to you. And how do you know they're different? If you note, every organization will have something called an autonomous system number. In this example, I used private ones, but you'll have your autonomous system number. The cloud provider will have theirs, and you'll connect to them via BGP. That's how you'll do dynamic routing. So AWS, like all cloud providers, will allow you to use BGP because it's the only exterior gateway protocol we have. Test questions to remember. BGP uses TCP, the Transmission Control Protocol, port 179. I'll say it again. BGP uses TCP port 179. Why did I say that twice? First, I wanted you to know it's a TCP-based connection-oriented protocol. And if you have a firewall between you and the other person, and you don't allow or open TCP port 179, BGP will not be able to establish a peering relationship over that link, and you won't be able to reach anything. So please understand that. So if you use a direct connection, and if it matters, you're going to use a direct connection when you connect to AWS, you will need to use BGP. If you use a VPN, you probably should use BGP, but you don't have to. You could do static routes. Now, AWS supports this BGP community called NoExport. Here's what NoExport is. If I were to tell Chris something and I tag my routes with the community NoExport, Chris couldn't tell Alonzo, who's my chief marketing officer, something. So that's NoExport. If I didn't have the community NoExport and I connected to Chris via eBGP and sent him a message, and he connected to Alonzo via the eBGP and sent him a message, Alonzo would get the information that I sent him. So AWS enables you to use that community to not become what's something called the transit autonomous system. AWS BGP implementation, the BGP implementation will enable you to traffic engineer traffic, meaning you can manipulate the weight, the local preference, the AS path, the specificity of the routing information. Now, understand it's a very light BGP implementation, but you're going to have to dress wisely and see somewhere routes. Mark Milovanovic and me produced an 8-hour BGP training session. It's completely free on our YouTube channel. I'll make sure my team drops that in the link for that. So here's BGP has this concept of transitive and non-transitive routing. So here's transitive routing. I've got my data center. Chow, who's a wonderful cloud architect that works with us, has her data center, and Alonzo has his data center. In transitive routing, I tell Chow how to reach my stuff. Alonzo tells Chow how to reach her stuff. Chow tells me and Alonzo how to reach her and each other. And that means Alonzo can talk to me because he knows how to reach me. Alonzo will see in his routing table his route, which is the 192.168, 1.0/24, Chow's 172.116.0.0/16, and my 10/8. So in transitive routing, Alonzo can reach me. If I wanted non-transitive routing, which we happen to have in VPC peering, which we'll get to soon, or we would have in, say, IBGP, here's what would happen. I would tell Chow about my routes, and she would tell me hers. Alonzo would tell me, would tell Chow about his, and Chow would tell Alonzo about hers, but I wouldn't be told anything about Alonzo from Chow because it's non-transitive. Say we have the BGP community now export. That means I can reach Chow and Chow can reach me. It means that Chow can reach Alonzo and Alonzo can reach Chow. But in non-transitive routing, I can't reach Alonzo because I don't know about him, and Alonzo can't reach me because he doesn't know the routes either. So I hope that makes sense. And we'll get to much more depth on that with BGP peering. Actually, Chris, I think here's a good time to pause, take some questions, and then we'll go back to the content. What is meant by one wire being blocked with spanning tree? Maybe explain what spanning tree is in the context of link aggregation group. So FB, if you'd like to learn about spanning tree, there is an IEEE specification on spanning tree. And we also have a completely free CCNA program. So I can't get too deep into spanning tree right now because it would take many hours, but I'm going to walk you through and show you why we need spanning tree. And I think this will help. So we're going to do a little architectural drawing over here, and I'll show you why for switches they must use a protocol called spanning tree, and why if we have routed links we don't have to worry about this. So here's the way a switch works. The way a switch will work is, let's say I've got a destination. Hold on. Put up. I may have a frame that comes into the switch, and let's say its MAC address is 12:34:. That's not going to work. Well, I know how we'll do this. Let's say I have an Ethernet frame, and its destination MAC address is 12:56:67:89:01. So let's say I've got a MAC address. What a switch does is this MAC address comes into the switch. The switch sends it out every single port except the one it came in on. And then when the packet gets to this switch, it'll send it out all ports on that switch except the one it came in on. So I've got one frame here. I've got one link. Here's what happens. Let's say this switch has 100 ports, and it goes out this link. It gets sent out 100 ports, and if there's no problem, everything works. So if you just got here and you haven't seen what an Ethernet switch is, it looks something like this. So packet comes in on, say, one of these ports, and it goes out every port in the VLAN except the one it came in on. I hope that makes sense so far. So if I've got one link, I've got no problem. Now, at layer 2, if I have two active links, I want you to understand what's going to occur. Let's say the frame starts here. Frame hits this switch. It goes out this port. Now, this switch will send it out every single port on it, send it out every port except the one it came in on. So it's going to now send it back to this switch. Now, when the frame gets back to this switch will send it out every single port except the one it came in on and send it back on this switch. And this switch will send it out on every port except the one it came in on. And what ultimately happens is the switches will have all this broadcast traffic, because every time there's an ARP that gets broadcasted out or all unknown traffic, and then all these links will be filled. So when it comes to link traffic in Cisco, and did I not share that? Apologies, I've been meaning to share this. So let's walk through this situation again. I have a single link that's up and working. So sorry. So frame comes into the switch. It sends it out to the next switch. The next switch sends it out all ports except the one it came in on, and it dies. I'm going to do that again. Single link. Single link hits the switch. It goes out all ports except the one it came in on, at least till the switch is nowhere to send it. And then it goes out all ports on the switch. Life's good, right? We've got one link. Now, I've got two active links. Here's the problem. Frame comes into the switch. The switch sends it out all ports except the one it came in on. So the switch sends it out all ports. So it's going to send it out this port and this port if nothing were to be blocked. Now, when this frame comes in on this link, it's going to go out this way. And then that switch is going to send it out all ports except for the one it came in on. So it's going to loop, and it's going to loop, and it's going to loop, and it's going to loop. And switches do this with all unknown traffic or broadcast traffic. So a host sends an ARP who has this MAC address, gets sent out. So what will ultimately happen in switching is this traffic will just loop and loop and loop and loop until it fills up, literally speaking, all the links. and then the thing falls down. It's called the broadcast arm. So what spanning tree does is it blocks one link, because if it comes in here, it can't go back, and we don't have that broadcast arm. So, plus it drives the CPUs like crazy because they have to process all the broadcasts. So it fixes it. Now, if you've got two links and you can't use the link because it has to be blocked, so you prevent a broadcast arm, you only have one active link. What a link aggregation group does is they bundle all these links so they all look like a single link, so that to the switches between them, it's only a single link. So now, frame comes in, unknown, goes out. This one port, switch sends it all our ports, and it doesn't go back. That's why we can create a link aggregation group, and we don't need to mess around with spanning tree, because it's one wire versus two wires. I hope that made sense. That is a pretty complicated topic, so we covered it fairly heavily, and when we did the CCNA. So please go back to that if you'd like more, and my team prompted that there for free. It's free training we did. What is a session cookie, and how is that related to the browsing experience? Well, it has honestly nothing to do with what we're talking about now. But by definition, a session cookie is typically going to be a temporary cookie that's going to be put in your browser, and it's going to stay there until you close your browser. The point of using a session cookie is to keep track of what you've done on, say, a website. Maybe keeping you logged in, keeping the things that are inside of your shopping cart there. So when I go to PetSmart to buy Bonkers cat treats, because these little tuna lollipops that my cat likes, I start to order them, and then my wife says, please cook me dinner, and I cook my wife dinner, and I go back to my browser, and it's still there. That's typically why you would use a session cookie. It's there to kind of provide a better, more seamless and personalized browsing experience. So it enables websites to remember key information during the session. Good question there, but not really AWS content, but that's all right. Chris, we can go to the next one. Well, Miguel, so GBP, do you mean the Great British Pound, or do you mean BGP, the routing protocol? So I'm going to work on the assumption that you're using BGP versus a VPN. A VPN is a private connection inside of a public environment, so an IPsec tunnel through the internet. BGP is a routing protocol, which is how the routers calculate how to send your traffic to the best destination. And that's how you connect to external entities. So if you have a VPN, that's just going to create a virtual wire over the internet for you. But the routers won't know how to send your traffic from point A to point B without a fully populated routing table. So you'll either have to manually go assign the routes to every single device, or you'll use a dynamic routing protocol. And when it comes to connecting to the cloud providers, it must be BGP. And you had said BGP. Good. So I did a good guess there. All right. Well, we'll get back to the content then if there are no more. And I'll fill my water here because you get dry talking for lots of hours. And then we'll get back to the content. But before we do, I want to make sure that you get all the stuff that we have to offer in this session completely free. Please check out the description of these videos because there's lots of freebies for you that are going to help you. But there's over 40 labs that we've done. And we want you to go follow through with these on your own time. And if you sign up for the lab, then the week after the session, we do some free personal AWS mentoring. And you want to be part of that, you'll be notified just by signing up for the free labs. So get the free labs, work them on your own time. We're going to go 3 hours per day for 10 days. That's 30 hours. So we need to get very deep and more deep in the tech content, which is what I'm concerned about. So go get that. We also have a completely free certification guide for you. And again, it's completely free. And it'll talk about maybe the certifications you'd want to be a cloud architect or a solutions architect. Because most people get the wrong certifications, and it actually hurts them more than it helps them. It keeps them learning all the skills other than the career they actually want. and it makes the resume look like they're a combination of a physician, airplane pilot, lawyer, police officer, dog walker, as opposed to being out there looking like you've got the perfect skills and you've focused your training and efforts and you've got lots of depth. So we've got that for you. And again, it's completely free. So they're in the description of this training session. My team has popped it in the video. Please go out there and get the BTP on our YouTube channel. Please go out there. And, we do this free and we do it periodically because I interviewed 1,000 AWS certified people and I asked them basic questions, and sadly they knew how to configure it but not answer things. And people hire you for your knowledge of what is the system, how does it work, why to use it. So we do this free. I know most people can't afford live training, so we do it free and love doing it. So if you're having a good time, please give it a like. Please subscribe, hit the bell to be notified, and please share with friends. Share the wealth of this knowledge. There's lots of jobs out there, despite what you've heard. And when you've got the right skills, the world's your oyster. So please share this free training with many others. And then I'm going to start as soon as I see some hashtags. So give me a hashtag AWS Solutions Architect Associate. We'll get back to the content. And my team even put the free AWS Advanced Networking Bootcamp. And the free CCNA Bootcamp, you've got 2 to give you some extra networking knowledge. All right, so as soon as I see some of those hashtag AWS Solutions Architect Associates, I know you're here. I saw the first one come in from an associate of mine. Thanks so much, Preb. Really happy that you're here, along with all of you that are here. All right, so now we're going to talk about internet gateways. Well, I want to make it really simple for you to understand. Do you know what a gateway is? It's another name for a router. Your default gateway is where you go when you don't have a route. Hope that helps. An internet gateway is a router that connects to the internet. So in AWS, you connect to virtual routers versus physical routers, but it's the same thing. So when you want to get your systems reachable from the internet, like your web servers, or perhaps a VPN concentrator, for example, that's when you need an internet gateway. Now, when you connect to the internet with an internet gateway, it's going to connect you to the internet. So what does that mean? It means your systems are reachable on the internet, which means if you do not have a well-designed demilitarized zone, they will be hacked. And it means that only stuff that you want to be reachable from the internet should be. Maybe a VPN concentrator, maybe a web server, but all that private stuff should not be there. So different subnets, route filters, firewalls, etc. You're going to need all of it. So, beyond that, the way you're going to make this work is you'll attach an internet gateway to your VPC. That's our internet router. You'll create a default route, which says if you don't know where to go, send your traffic to the internet gateway. You'll put a public IP address on the gateway, and then your systems will be reachable. Now, if any of you do, and if you actually take your computer and you type netstat, let's not go there, but you'll be able to see that your PC, if you do an IP config /all, or you IP configs /all on Windows, or IF config on, say, a Mac or a Linux system or a Unix system, you'll be able to see your IP address and your default gateway. It's the same thing we're talking about here, nothing different. So, realistically speaking, it's going to look something like this. You've got your stuff. Anything that needs to be reachable will have a public IP address. It'll have a route to the internet gateway, which will go out on the internet. And that's why you can see in your routing table here, you've got your private subnets, which are local. And then you've got your, I don't know where to go, 0.0.0.0/route, which means send to the default gateway, which is the internet gateway. So that's all an internet gateway is, a router that connects to the internet. So next, egress only internet gateway. So what does egress only means? It means stuff can go out, but not in. Okay, so why would you use that? Let's say you had systems that needed to go out to the internet and patch themselves. and download, say, the newest patches for Ubuntu or the newest patches for Red Hat or Linux, etc. But you didn't want them to be reachable from the internet. You'd use some form of an egress-only internet gateway. That's it. That's what all that is. So in IPv6, you don't need NAT. So we've got enough IP addresses. So we don't really have private addresses. It's mostly public addresses. So with IPv6, we can create a gateway which basically says go to the internet and then come back, and your stuff is allowed, but you're not reachable from the internet, meaning someone can't go from the internet and come back to you. So if we do that with IPv6, it's called an egress-only internet gateway. And an egress-only internet gateway is basically like being behind a firewall, sort of, being allowed to go out to the internet and come back. Since we're on gateways again, I'm going to talk about a virtual private gateway. And an AWS virtual private gateway, often called the VGW, is going to be an AWS resource that enables you to connect your AWS VPC to your on-premise. So normally speaking, you would connect a VPN concentrator to a VPN concentrator, or a firewall to a VPN concentrator, or a router to a VPN concentrator, or your PC to a VPN concentrator. So the AWS virtual private gateway is an AWS-designed, AWS proprietary VPN concentrator. And that's how you can make your connection. And the connection can honestly be any kind of connection you want to use, but often a VPN. And here's a visual example of how they work. So you might have your corporate data center that's connected over a direct connection gateway. You could have your data center connected to different virtual private interfaces that you could see. You can have another IPsec tunnel that's going to your a VPN that's coming in through the virtual gateway. They can be different IPsec tunnels or what have you. So there's just lots of different ways that it's basically a virtual router to connect you to two different locations. So because a virtual private gateway is like a VPN concentrator, you basically, each VPC can only have one virtual private gateway. So what you do is a virtual gateway will be attached to the VPC, and then you can establish a whole bunch of VPN connections or multiple private lines to the virtual private gateway. And the AWS virtual gateway will establish two types of connections, either a VPN or private line. So we can also create a VPN to another network. So because that virtual gateway is kind of like a VPN concentrator, you can use that to establish VPN connections to maybe your on-premise environment. You can use it to connect to, say, Azure and Google. Remember, 98% of organizations are multi-cloud, so you're going to be using things like this. And it's going to create a VPN connection, which is going to basically use it for a VPN connection, which is usually using an IPsec tunnel. And because you're using an IPsec tunnel, you can put your routing anything you want on either side, and you can determine whether you're going to use BGP or a static route. Static routes aren't going to scale because you're going to be manually configuring stuff, and it's just going to be a nightmare. You'll make more errors, and when a cable gets cut, they won't naturally heal around it, so you don't want that. So here's another example of what it could look like. You could have your region, and you could be in, say, two different data centers, otherwise known as availability zones. You can create multiple VPN connections between different environments, like you see on the right side, connect to the VPN gateway, and use that as a router to connect your location. So it's an option for you to use the cloud as a wide area network in certain cases, and allow other organizations to use the cloud as like a hub and spoke environment, and multiple environments can then reach each other through it. So when we're dealing with a private line or a direct connect using it, we're going to connect to the virtual interface called the VIF. And what we'll do is we'll utilize the direct connection virtual interface, and then the virtual gateway will provide us a private dedicated network connection from the on-premise to the AWS. Now, that private line using the direct connection virtual interface and this virtual private gateway is going to give you very high performance, guaranteed, because it's a private wire. By comparison, if we were using VPNs, it wouldn't be guaranteed. So remember that the virtual gateway allows you to connect multiple VPCs to your on-premise environment, and many organizations will chop up their organization into multiple virtual private data centers. And why might they do that? So in a normal data center, you can really micro-segment your network. You might take your network and chop it up into mini VLANs. You can't really do that on the cloud. You don't have a lot that you can do. So many organizations will take their organization and chop it into 10, 50, 100 or more virtual private clouds. And then you can connect what you need or don't need via these virtual private gateways. And you've got layer 3 routing and firewalling, things you can do in between them. So kind of hope that makes sense. So now let's talk about NAT instances. So a NAT instance is a virtual machine that does NAT, that translates one address into another address. And you can basically use an internet gateway plus a NAT instance to take your information and send it to the internet and allow it traffic. And a NAT instance is potentially useful in certain circumstances, but in most cases, a NAT instance is something that you're probably not going to use that much anymore. And you're probably going to use a NAT gateway, because a NAT instance also needs an internet gateway. That's extra devices to manage. And a NAT gateway will give you internet access and do network address translation at the same time. So what's really going on here with NAT? If you'll recall, anything on the public internet needs to have a public IP address. But anything in a private network needs a private IP address. So how do you go from the private world to the public world? Well, either you've got your routing right, and every device that you have has a public address, and we don't have enough public addresses for every person in the world and every device in the world. Or you take your private address and you translate it into a public address when you go out to the internet. And there's lots of types of NAT: one-to-one NAT, one-to-many NAT, static NAT, dynamic NAT, or something called NAT overload. And if you're going to be a network architect or a cloud architect and you were in our cloud architect training program, we'd get into that. But that could be 10, 20 hours of stuff with just to go through NAT, let alone this rest of the content we need to do. But so let's talk about what a NAT gateway does. It provides a router to the internet, and it connects you to and it does NAT. Takes your private addresses to it. And it's something called NAT overload, often known as port address translation. And why is it NAT overload? I'll show you right now. Well, maybe I can't draw that on here. Oops, I don't even know what happened there. I better not play too many buttons here. So let's say the NAT gateway's external subnet is 1.2.3.4, and you've got 1,000 users in that private subnet. It will translate all 1,000 users into 1.2.3.4, but it will utilize different port numbers. So the address might look something like this. I can maybe draw addresses on another slide to kind of put it into context for you. I'm drawing these slides on dynamically. How do we do this? Okay, so let's do this. So if the external address with NAT overload, we might have a 1.2.3.4 port 2023. And then the next user might be 1.2.3.4 colon 2024. I don't know why that's looking so funny. And what you can see is this colon enables us to use the 1.2.3.4 with one set of ports and another set of ports. And the port numbers that we're using gives us the ability to create additional addresses or equivalent of addresses. So understand that. So NAT gateway takes you to the internet, allows your traffic to go out to the internet and return traffic to come back, but you're not reachable from the internet. Internet gateway is a router that connects you to the internet. You go out to the internet, your traffic can come back. An egress only internet gateway is a NAT gateway for IPv6. Think that and keep those three. And they're basically the three you'll actually see on your exam. So now, let's talk about the concept of an elastic network interface. An elastic network interface is the equivalent of an Ethernet card sitting in your virtual machines, often called as EC2 instances. By default, when you launch a virtual machine, it's going to have a network card in it, a virtual network card. And the default network interface in any AWS environment is going to be considered ETH0. But if you wanted more than one network card in your system, or because you want to connect to multiple subnets or dual home that host, you just pop another network card in it. Same way you've done in the data center for the last 40, 50 years. Dual home. And there's lots of reasons you would do that. So kind of think of that in the back of your mind. So an elastic network interface is a virtual network card. So now let's talk about elastic IP addresses. So inside of your corporate environment, your VPC, you're going to have private addresses. When you go to the internet, your internet-facing things like your website have to have a public IP address on it. So the load balancer that's going to be front-ending your web servers has to have a public address on the outside of that load balancer, for example. So how do you get them? Well, normally you call your internet service provider and you buy or register a public IP address. And there's other people you can buy blocks of people for IP addresses from, same way you can buy a BGP autonomous system number. But on the cloud, AWS has a pool of public IP addresses. They're called elastic IP addresses. So what happens is when you need a public address, you borrow it from the pool, you pay for it. AWS gives you the public IP address called an elastic IP address. I didn't make up these names. And then after that, when you're done with it, maybe a year later, you shut off your load balancer, you give it back to AWS. So that's it. And if we've got a NAT environment, we can have one public address via NAT overload, otherwise known as port address translation, provided to lots of devices. So keep that in the back of your mind. We also might use an elastic IP, maybe as a secondary address for certain things that we might put on an interface. So I hope that makes sense. So an elastic IP address is just a public address you get from AWS. Now, endpoints. All cloud providers have endpoints. So what are they really? You need to connect to something. That's an endpoint. Like if you were going to connect a wire to something, you can't just leave the wire dangling in the air. You need to connect it. So that endpoint is where you connect it. And we're talking about logical things. So we have two ways that we can actually understand things, connect to things. We can go out to the internet, come back, or we could just get a connection between them. Could be a virtual wire, could be a physical wire. So let's talk about what this actually means. If we go to the internet, actually, I have a picture that I drew. Let's talk about this. If I wanted to take my data outside of my environment, I have two ways to do it. I can go out to the internet. Now, I'm going to go out to the internet, and the internet's not a secure place, so I'm going to have to encrypt it or something to make it better. And the internet has no bandwidth guarantees, meaning you could get 100 gigs or nothing based upon whatever the internet has. You can go out the internet, and you could come back to, say, an AWS service, say object storage, otherwise known as S3. You could do that. But you're going from this thing, which is in your VPC, which is on the Amazon network, which is safe and secure, all the way out to the scary, dangerous internet with the security risks and no bandwidth guarantees. And then you're going to come back into the secure AWS. Well, that would be ridiculous. So what you can do is basically AWS can make you a virtual wire called an endpoint, and it's going to connect your VPC, which is your virtual private data center, directly to an AWS thing, all without going to the scary, risky internet. And the internet has no bandwidth guarantees. So you're going to want to use an endpoint to connect to certain AWS services. So we'll talk about the different endpoint options that we actually have. So the point of these endpoints is security, reduced latency, and keeping your information. So let's talk about some endpoint benefits. They enhance security because you're not going out to the scary internet. They enhance your performance because to go from AWS to AWS on their private network is going to be fast because they can guarantee performance of their network, but they can't guarantee the public internet. It's a better performance. Management. Well, it's a lot easier to not be thinking about NAT gateways, internet gateways, going in and out of the internet to access our own stuff. And it's much more secure. And generally speaking, the cloud providers charge you, for traffic that you use, although that's getting a little better on certain cloud providers. So keep that in the back of your mind. So there's going to be two kinds of endpoints we have in AWS. We're going to have gateway endpoints, and we're going to have interface endpoints. Gateway endpoints are typically for, say, Amazon S3, otherwise known as object storage, and the Amazon proprietary NoSQL database called DynamoDB. An interface endpoint, by comparison, is typically used for AWS virtual machines, otherwise known as EC2 instances, AWS Lambda, AWS SNS, AWS Kinesis or Secrets Manager, and many of those things are proprietary, and you really can't use multi-cloud. And we'll talk about them when we go over the multi-cloud, when we go over those services, and we'll also talk about what you can use instead in a multi-cloud environment. So I kind of hope that makes sense. So how do we set up and use an endpoint? We pretty much go to the VPC dashboard in our management console. We select endpoints and we click create endpoint. No big deal. And then we're going to choose the kind of gateway that we need. We'll review, make sure we did it right, and create the endpoint. So it's really no big deal to set this stuff up. It's knowing what you want to set up that's more the challenge. So we'll begin with an interface endpoint. And an AWS interface endpoint is going to be a type of VPC endpoint that's going to allow you to privately connect your VPC to a supported AWS service. Now, when you use an interface endpoint, it uses something called private link via AWS private link, and it's kind of just like a virtual wire they create for you. Interface endpoints, what they really do is they create a virtual network adapter, otherwise known as an elastic interface between you and whatever you're connecting to. And that way, everything's simple and elegant. Here's an example of what it typically looks like. Maybe you've got a VPC that's got some proprietary service that you want to connect into, and you're using private link to connect to it. This could also be an AWS service on, it could be a certain service you want to connect to. I'm sorry, I'm looking at this diagram that my friend drew for me. So, basically you can see inside your VPC, you're connecting to an AWS public service. Thought this was another example that I had drawn for me of using this to connect to something else. So AWS has something, you're using this VPC endpoint, which is basically a network card and a private wire between you and this AWS service. So let's talk about some key features with AWS interface endpoints. Private connectivity. It's going to be private and secure. As I mentioned, it uses these network interfaces, and they'll be in the private IP address spaces. You can secure your interface endpoints with your identity and access management solution, and you can add some VPC security groups to it as well, which is kind of firewall-like. By using interface endpoints, it scales well. And for the most part, it just automatically scales to handle our traffic needs. Because these endpoints are not physical, they're logical. They typically don't go down as long as the cloud provider is up. And it's very simple management because we're not using NAT gateways and translating different addresses, etc., as necessary. So very simple and elegant way to connect to an AWS service. And lots of uses for interface endpoints, EC2, simple notification services, functions as a service like AWS Lambda. SQS, Kinesis, secrets managers, many of the databases, systems managers, lots of stuff that you can connect to with private link. And that interface endpoint uses AWS Private Link, and that's a networking service that enables you to basically securely access the systems in AWS. Private connectivity between VPCs, AWS services, what have you. So private connectivity, things that you can think about, and again, it's going to be that private network interface card, that elastic network interface on both sides. Data stays on your same thing. It is a logical wire versus a physical wire. So as long as there's connections in the cloud provider, it can give it to you. And pretty helpful. So how do you set up private link? Well, you create your VPC endpoint. How do you do that? You go to the management console, you select endpoints and click create endpoint. You choose whatever service you want to connect to. And you configure the endpoint. You give it a service name. You choose the VPC that you want to use to create the endpoint. You select the subnets in your VPC where the endpoint will be placed. You set up a security group to control who can access it. You review it and you create it. So it's no big deal to create these things. And it gives you good secure connectivity across the AWS cloud. So let's talk about some security considerations when we're dealing with private link. Use the security group. I mean, why wouldn't you? It's basically a host-based firewall that you can put on an interface endpoint to control access and restrict traffic. Create an IAM policy. So make sure that the people that have the right permissions can access it and nobody else. You don't want to give this access to everybody. Only people that should be accessing things are people that need it for the job. If you've got this kind of endpoint kind of situation going along the way, you probably should do some monitoring and logging. So look at your CloudWatch logs. Make sure you enable VPC flow logs. They're kind of like the equivalent of Cisco NetFlow to kind of see how and where your traffic is going. Set up your private DNS to ensure that DNS is enabled for the VPC to be able to get to resolve the traffic so it gets to the endpoints that it needs. So that was an interface endpoint that we talked about in private link. The other type of endpoint to talk about is something called a gateway endpoint. And that's going to be a high-speed access to an AWS service like S3 or DynamoDB. These work a little different. They actually place a route in the routing table. So the routing table will look and say, oh, to go to S3, go that way. Same thing as it would normally say to reach the subnet, go that way. So the way that works is you create an endpoint. It's going to create a prefix list for the endpoint. And the prefix list will look like a route in the routing table. And you'll see it as PL-something, something, something after the fact. And that'll be the route in the routing table for the endpoint. So you're going to use this for secure access for S3 often. And it enables you to set up policies. So you can maybe access, say, an S3 bucket. You can also limit the routing information to subnets that need to know how to reach the endpoint, because if you don't have a route, you can't reach it. So it's going to further enhance your security. So there's that. Now we'll talk about VPC peering later, but private link connect to a very specific service. VPC peering connect multiple VPCs, so totally different. Private link connect to an AWS service. VPC peering connect to another virtual private data center, either that you own or another company. VPC peering, you can connect a small number of other VPCs. Private link is connecting to a lot of AWS services, much more scalable. Private link is unidirectional, so goes in one way. Enables a consumer to connect to the provider. If you need communication to occur in both directions, you need to set up bidirectional communication. So if you use VPC peering to connect two VPCs, they share everything. When it connect to an AWS service, use private link. So now is the fun time to talk about VPC peering. I love VPC peering because it's kind of like BGP peering. So what is VPC peering? An organization may have multiple virtual private data centers. And how do you connect two or more data centers? You peer them with BGP, right? And that way you share the information that you want and you get connectivity between them. Well, what if you're a company? Let's say you're a computer manufacturer and you want to connect to the CPU manufacturers. And Intel's got their, what do you call it? Their, what's the word I'm looking for? VPC. And AMD's got their VPC. And you want to connect to Intel for buying Xeon chips for certain servers, and AMD to buy those super fast EPYC processors for your big high superpower servers. So you can connect to both of them. If they're on AWS, you can connect to them. Now, when you connect to an external company, you got all kinds of security things because the other company and you. Or you could have a company like GE, and they could have an aerospace division and a healthcare division and another division, and they could all be hosted on AWS, and they can reach each other through AWS, through the AWS network via VPC peering. So that's what's VPC peering. Or you could be super security conscious and put your finance people in one VPC, your accounting people in another VPC, your sales people in another VPC, your test dev environment in another VPC, and really reduce the blast radius so if something big happens, nothing really happens. So keep that in the back of your mind. So that's what is VPC peering. So here's a visual representation someone from my team drew. And in this particular environment, you've got your data center or your virtual private cloud. You're connecting to another virtual private cloud, and you've agreed to share stuff. That's VPC peering. So there's some things to know with regards to VPC peering. VPC peering is not transitive. I showed you an example before as it pertained to BGP, but I'll show you some architectures. All right, so when it comes to VPC peering, either we will have to do something to make hub and spoke work, because hub and spoke won't work by nature because, and I'll show you what a hub and spoke environment looks like, because VPC peering is non-transitive, or we need to fully mesh our VPCs. So if anybody's familiar with IBGP and you fully meshed your IBGP peers, that's the reason why. Or with IBGP, there was a workaround to IBGP being not transitive called the route reflector. So we'll talk about that in a minute. So when it comes to fully meshed, and I'll talk about, there's going to be a scalability problem, but I'll show you. So here's what a hub and spoke network is. And in transitive routing, you can see that VPC, B, C, D, A, E, F, G, kind of like a song that I've heard recently. But anyway, and in a normal hub and spoke environment, VPC talks to VPC-A, VPC talks to VPC-A, and in normal transitive routing, VPC-B can talk to VPC-C because they're going to be going over from here to here to here. That's allowed. But remember, in IBGP and VPC peering, what will happen is VPC-B will tell its routes to VPC-A, and VPC-A will tell its routes to VPC-B. VPC-C will tell its routes to VPC-A, and VPC-A will tell its routes to VPC-C. But VPC-B will not know about VPC's routes through A because the routing is non-transitive and routes aren't propagated. Likewise, VPC-D won't be able to reach VPC-C through A or B because it's non-transitive routing. So in transitive routing, it works perfectly. In IBGP, we need to do something to this VPC-A to make it be transitive if we want it to be transitive, and that's called a route reflector. And in BGP, we'll have the option to do Cloud Hub or Transit Gateway. We'll talk about that in a bit as a workaround to this. But normal VPC peering is not there, so we have to fully mesh our VPC peers. What does that mean? It means every VPC is going to need a connection to every other VPC. So pretty simple here, right? VPC-A connects to VPC-C, VPC-C connects to VPC-B, and VPC-B connects to VPC-A. So here's the traffic flow. If VPC-A wants to reach VPC-C, it sends it. VPC-C wants to reach VPC-B, no big deal, it sends it. VPC-C wants to reach VPC-A, they send it because they're all exchanging routes with each other. Here's the problem. When we have three of these, It's no big deal, but here's the formula. N times N minus 1 divided by 2. So in this particular environment, let's run through the math. We have 3 VPCs here, VPC A, B, and C. So we have 3 times 3 minus 1, which is 2. So that gives us 6, right? And we divide that by 2. So we've got 3 connections, which is here. Why does this become a problem? Well, what happens when N becomes 100 and 100 becomes 100? So now let me get my calculator out to show you exactly where the problem becomes. So now with this N times N minus 1 divided by 2, we have 100 times 99 divided by 2, which means for 100 peers, we're going to need 4,950 connections. Whoops. That's not going to work. That's going to be more than ugly. So kind of keep that in the back of your mind. So that is our options. We either fully mesh them or we do something to break the fully mesh rules. In IBGP, it's called the route reflector. We'll talk later about transit gateways and AWS Cloud Hub, which are ways that you can actually break the rule. So now let's talk about the AWS Client VPN. So let's say you've got lots of employees. Typically speaking, you put up a VPN concentrator and you allow your employees to remote access it, connect your VPN concentrator. Want to be on the cloud and you want a good VPN system you manage? You take an internet gateway and you get a Cisco VPN concentrator from the AWS marketplace. You can run a Cisco VPN service and your employees connect directly from that to AWS. You can use that same protocol across your 3 cloud providers. If you didn't want to use something made by the networking leaders like Cisco or Juniper Networks, AWS has a service you could also use called Client VPN. And that's basically a pre-managed VPN device that your remote workers can connect to, kind of like a software-based VPN concentrator. And, by doing it, you don't have to manage any VPN concentrators of your own. You have to manage the AWS deal with the AWS one. But you're going to use the AWS device and, it makes it real easy because you're just going to use the AWS thing. So it enables you to, create access control because it's going to integrate with the AWS Identity and Access Management or Active Directory, just like your Cisco router could authenticate with Active Directory as well. So it's going to do what the big providers have been doing for decades. It's going to enable you to create an access control list and a security group for your VPN device. Again, just like the industrial solutions by Cisco would do. And it'll do your monitoring and logging with AWS CloudWatch versus CloudTrail, as opposed to, say, the firewall logs that you would normally connect for your VPN concentrator. And the way it works is you're going to create a client VPN endpoint, and that's what the users are going to connect to. So when we talk about the AWS Client VPN, they got a couple of concepts we'll talk about. The target network, this is going to be the VPC subnets that you want to provide access to through the VPN. The rules, the authorization rules. The rules will define which users or groups can access which networks. There's obviously going to be the client configuration. That's going to be the configuration file that users are going to need to connect to the VPN endpoint. Then we'll create the VPN endpoint. And so that's pretty much it. So how do we set this up? We create a VPN endpoint, management console, CLI, what have you. We associate those target networks, which are going to be the subnets that you want to connect to. And you configure the authorization rules, like in your identity and access management environment. And you download the client configuration. And that's it. So I mentioned earlier with VPC peering and IBGP peering that it wasn't transitive. So how do you break it? Well, here's how you break that rule. So if your remote sites or your VPCs are connected via VPNs, we can use something called Cloud Hub. Cloud Hub basically is a BGP route reflector that enables you to have a hub and spoke environment where, say, Boston can talk to Washington and San Francisco can talk to Boston through a hub and spoke environment. Now, if you had private lines, you'd use something called transit gateway. And again, a transit gateway is a router that, just like Cloud Hub is a router, that's going to enable you to get past those BGP limitations of the transit routing. So Cloud Hub will enable hub and spoke transitive connections. You'll connect to it via BGP, specifically eBGP. So if you're connecting via eBGP from each location, meaning different autonomous systems numbers, BGP by nature is transitive unless you tell it not to be. Obviously, it's BGP that you're going to connect to, so you can filter routes that you don't want to be reached, for example. Or you could set it up where all VPCs have access to all routing. Routing information, meaning network layer reachability information. But now everybody can talk to everybody. And that's really the secret, is you connect to this Cloud Hub via eBGP, assuming you're using, assuming you're using VPNs. And by doing so, Sydney, London, New York, they can all connect to it as if it was a normal networking environment. So, but remember, Cloud Hub is only for VPNs. What if you need better performance, say a private line or a direct connection? Well, that's where you get into AWS Transit Gateway. And Transit Gateway is really like a router, but it's an AWS service that enables you to connect your cloud and multiple environments together in a way that's easy to manage. It centralizes then your networking, so very simple way to do things. Transit Gateway is going to look a whole lot like Cloud Hub. Now you've got private lines versus VPNs connecting your environments. And it's now allowing your environments to share routes. You've got transitive routing. So the way to really think about Transit Gateway and how it works is to remember it's a router that's used to connect multiple VPCs together. So you could buy a router from Cisco or Juniper or Arista Networks that has done this for the last multiple decades. This is just doing the same thing. Transit Gateway is going to be a regional, highly available AWS network construct, but it's a router. And by doing so, it enables you to do hub and spoke environments versus fully meshed environments and get into that n times n minus 1, 2 VPC peering problem, BGP peering problem. And that way you don't have to fully mesh your environments. And I showed it a little earlier, but here's another example. In a mesh environment, everybody's connected to everything. In a hub and spoke environment, everybody connects to the hub. So when you fly on an airplane, they use hub and spoke networks as a rule. I use the West Palm Beach Airport. I go to West Palm Beach. I want to go anywhere. I go to Delta. I take Delta to, say, Atlanta, and Atlanta to somewhere else because it's a hub. I want to go to visit somebody. I have to go to San Jose. I leave my house. I go from West Palm Beach to Houston, which is a hub for United, and then Houston to San Jose, that kind of thing. So that's really what we're talking about in a hub and spoke environment. They tend to scale very well. So think of the AWS network, Transit Gateway as, again, facilitating that. So here's how it works. It's going to create an elastic network interface, meaning a network card at each VPC, and which means it's going to need a subnet that you're going to have to put on it. And then, once you connect one or more VPCs to your Transit Gateway, you'll be able to reach each other. So your routing tables will have to be configured either statically or, more importantly, just use BGP to connect them. And that way you can connect your environment, your VPC-As to your Transit Gateway and let it do the routing. So with the Transit Gateway, you can create a site-to-site VPN connection to your on-premise environment or other VPCs. You can peer with other Transit Gateways in the same region or different regions. And a peering with direct connection gateway to where it basically enables you to connect with, say, a private line to on-premise or other clouds. Transit gateways will enable you to create multiple routing tables. They may call it routing instances, and attach different VPCs to different routing tables so you can control where your traffic goes. And only VPCs in the same routing instance can talk to each other. If you think of Cisco and you think of the VRFs, the virtual routing and forwarding interfaces, I think that'll help you actually understand these different routing instance type things. So again, that virtual routing and forwarding instances that Cisco uses. So why might you use a transit gateway? Well, centralized management, very simple, takes complicated technologies, enables you to go hub and spoke, makes it very easier for organizations that have multiple accounts for security purposes, to connect together. So, that type of environment. It can reduce costs because it's going to reduce the number of connections and peering points that you need to have. It can enhance your security because you've got good traffic segmentation and routing and route isolation you can run between, you say, the VPCs that you're talking to. So I think we probably should go to questions. Chris, I think we planned on stopping at 5, so we'll do maybe 10 minutes of questions, and I think I should get people out on time. Can we use one endpoint for multiple EC2 instances? Yes, you can use one endpoint for multiple EC2 instances. And this allows instances to basically securely access AWS services, multiple instances, without needing to use an internet gateway, go through the internet, or using that instance. Good question. Okay. How do interface or gateway? Let me try to understand this. How interface or gateway endpoints link to private? Okay. So maybe this will help. So interface and gateway endpoints are going to be two different types of endpoints. Basically speaking, interface endpoints use the private link service, and they connect to a lot of things. And for the most part, a gateway endpoint is going to connect you to basically S3 or DynamoDB. I hope that answers your question there. If not, please feel free to ask more. So, Mr. Gibbs, in order to install our own transit gateway, we get one from the marketplace and install it into the architecture. And how powerful of a virtual machine and network interface card do you need? Well, anytime we're going to deal with any type of a virtual router, we need to truly understand the needs of the traffic flows. So it all depends also on the architecture. So there's one of the big network security providers that is owned by a bigger company, but they have what's called, say, a single threaded firewall or router that they would use. So what does this mean? It means that it's going to need a very high frequency server with a high clock speed, because you can have 32 cores, but if you've only got a single threaded application, it's only going to use one core. So if we're going to use those virtual machines, we need a very high frequency CPU. And there's certain examples of, say, certain Xeons or certain EPYC processors that have got very high individual single core performance. And we'd have to specify that. We would also need to determine the amount of routes that we have inside of our routing tables and the frequency that the routes are going to be recalculated. So we're going to have to do that. Now, in order to do that, you're going to actually deal with a network architect who's going to do the sizing in their head. And you're probably going to have some network engineers that are going to run some scripts and do some testing, because this is one of those your mileage may vary. By comparison, if it's a multi-threaded application, we can use more cores on the virtual machine. So there's that. Generally speaking, you're going to use the transit gateway for most of these things that they're actually talking about. Now, if you're going to do a VPN concentrator coming in, that might be another story. You may want to get your VPN concentrator from a Cisco or a Palo Alto network, so somebody that's got big security stuff. that you've got a good relationship with. But transit gateway, for the most part, is something you're pretty much going to use with when you want to connect multiple VPCs, etc. Good question there, Prab. Of course, we can go to the next one. And get to the next one as soon as the question's up. It's a lot of work behind the scenes my team does. How many lab questions on their exam? Very few. So here's a secret. And I'm actually going to tell you the employer perspective, and I'm going to give you the CCIE perspective, and I'm going to give you the passing the exam perspective. You're going to have a very small number of questions related to configuring anything in any exam in today's world. It's going to be more on the technology itself. Now let's talk about the CCIE perspective. What if I told you the CCIE, which is the hardest exam in the world, and it has like an 80 or 90% failure rate, and over the course of 30 years, they've only had 65,000 people that passed it. They give you the configuration guide and the instructions when you take the exam. And yet almost everybody fails it. And here's the reason why. Knowing the configuration commands to do it is easy. Knowing what to design and what to configure and why you choose this versus the other one and evaluating on the trade-offs, that's what people hire for. And that's why when they give you a CCIE exam and they give you a complicated scenario to build, and nobody even knows where to begin the building. So there's that. Now I can tell you I've interviewed over 6,000 people in my career. What if I told you that I can find 1,000,001 people that can configure any lab environment in you want? But I go to hire them and I ask them a question like, okay, you want to be a solutions architect. You have a router and it's a virtual router that uses a single threaded application. What type of EC2 environments would you use? How would you determine your say single core versus multi-core performance? Or I ask someone to say, how would you design a demilitarized zone for your mission critical web app? Not how to configure an ACO. So there's that. So there will be lab questions and we'll go over them, specifically speaking, in those free downloads. My team will also do some maybe free hands-on AWS training or some tech training in the week after this is done and the third week. Because I do want you to get hands-on. But we've got a limited amount of time, and I know most people that I've interviewed can't pass the interview. And that's because the interview is based upon what you know. And it's what is the tech, how does the tech work, why you should use it, and it's evaluating the trade-off between various technological options versus how to configure the stuff. That's easy to do. I taught a 6-year-old how to configure a virtual machine or an EC2 instance in less than 5 minutes. But she didn't know what to configure, why to configure, and what she needed. That was the difference. Is there a certain criteria to choose between interface endpoints over gateway endpoints? Well, good question. So let's talk about interface endpoints and their use cases. Interface endpoints connect you to pretty much everything. So you're going to use the interface endpoint except if you're going to connect to AWS S3 or DynamoDB. So you can use a gateway endpoint for that. And if you want to basically use routing table to kind of do your decisions, you might use a gateway endpoint. And it's typically free of charge to connect to S3 or DynamoDB. By comparison, you've got a much more robust setup with an interface endpoint. And this is what you're going to use to connect to most AWS things, say an EC2 instance, SNS, Kinesis, what have you. And it's going to work over an elastic interface. So it basically is going to be very simple to set up for most things. So interface endpoint, pretty much everything. A gateway endpoint, maybe S3 or DynamoDB. I hope that kind of helps. I like that. Is it better to allocate security to the vendor? Well, Pedro, we have to determine what we mean by security. So, I mean, we're going to have a lot of security that we have to think about as security architects. So we have to determine what type of security policy the organization needs. We need to determine what assets the organization is protecting, the value of the assets. We need to calculate what is the cost of downtime to that business. And via, for example, some businesses lose $1 million a minute. Other businesses can be down all day and they lose $50. So we have to, and then we need to know what is the likelihood or risk of that organization being attacked. And we need to quantify that. We also have to think about what is the brand damage, say, as a security architect, if the organization was hacked. We then have to work with the organization to determine, is it better to transfer the risk, say, to an insurance company, mitigate the risk, or realize they can't afford to do the risk because no business can handle all risks and all threats. We have to determine that. When it comes to security, we need to determine our security appliances. And for the most part, we're going to get much more robust security appliances out of a security vendor like Palo Alto, Fortinet, Cisco, Checkpoint than we would from a cloud provider. It's the difference between a Swiss Army knife and a custom-made knife. Cloud providers do a little everything. Security providers specialize in that. We will have to think about what type of security event management systems we need to correlate all of our logs and all of our analysis. We will need to think about what our demilitarized zones need to look like, what we're exposing. We need to think about our physical security that's going to be going on and what we need to do there. We need to think about our network security, our end-to-end encryption strategy, our identity and access management. So you can't give that over to a vendor. You're going to have a team that's going to have some very competent security architects, and the cloud architects are going to need to know a lot of those. So security is critical, but the type of security and what an organization needs is going to be based upon business needs and business goals. One day I'm going to make a website with my beautiful cat, Cindy. She's like the cutest thing. At least I think she is. But, what are Cindy photos worth on the internet? Not a lot. Let's think about a drug company that's working on a new cancer drug. And if somebody gets access to that information, that company could lose billions of dollars by another company getting it getting it instead. So we have to determine what we're protecting. But security is an executive level responsibility. It is an architect level because architects are executives. It is a business leader responsibility. And I'm going to ask the next one. Do we have a lab for AWS security services? What if I told you that the most organizations are multi-cloud? Most is in 98%. And when it comes to security, it's not going to be mostly AWS security services. It's going to be a multi-security environment. So there are probably some AWS security things that you're doing in some of these labs, but you're not going to secure an enterprise customer with just AWS security or just Azure security or just Google security in 99% of cases. Chris, we go to the next one. Okay. What is a VPN concentrator? A VPN concentrator is a device that you actually connect to. So let's say we've got an enterprise. Pick any enterprise you want. Let's say we've got a global retailer like a coffee company that's got 10,000 locations. A coffee shop isn't mission critical, where if the systems are down for 10 minutes, they're going to lose millions of dollars. At the same time, let's also assume that, the performance of the networking in that coffee shop is not critical. So if we've got 10,000 coffee locations, they're going to use a VPN to connect to the main data center or to the cloud. So if in a data center, an organization may have 50 firewalls functioning as VPN concentrators, where basically the remote user connects to the firewall and creates an IPsec tunnel, and it's a device that does it. We could also be on the cloud, and we could have a bunch of virtual firewalls from, say, Cisco or Palo Alto that we put in our demilitarized zone, and we use them for remote access VPN. So a VPN concentrator is a network device that you connect to connect to a VPN. Good question. Any recommendations for exam practice questions? Honestly, there's lots of good practice tests that are out there. It's not a complicated exam if you understand the technology. And we don't provide this training. For the people that are taught, here's the name of something and here's how to configure it, but they don't know what it is or why it is, for example, it's going to be very hard. Now, I'm also going to tell you that we have another book that actually goes with this course. And inside of that, you may have some exam questions you can use. And it is a book that you can sign up for. It's completely free. Our team wrote it to give it away. And it will also help you prepare for the exam. So go through these videos maybe twice. Do some of the hands-on labs we recommend that'll reinforce certain things. Read that book, and then you can get any practice test you want on top of it. It's really no big deal. Get used to the way AWS asks questions, and you'll pass that exam. It won't be a big deal. How much network concepts should we learn in order to be a cloud architect? And what is the main difference between a network engineer and a cloud solutions architect in terms of the network? So, this is a great question. It's a very different job. I'm going to tell you right now, there is nothing in common between engineers and architects. Wait, what? So here's what an architect does. An architect designs systems to maximize business performance. An engineer designs systems to build systems, design systems, performance tune systems. So a network engineer will configure the routers. A network architect will design it. So let's talk about what a cloud architect does, and then I'll go back to to the networking side. You can ask me this question. You can ask David Lithiquim. So here's what we do as an architect. The first thing we do is we meet with the client's executive team and find the goals and vision for their business. If we don't know where the business is going, we can't design a solution. Now, many people skip this step, but I'm going to tell you right now, 70% of all cloud and data center architectures are disasters. They actually don't work at all. Tech works, but that's nothing. So this step is critical. The next thing the cloud architect does, and honestly, the network architect does, the enterprise architect does, the AI architect, is they look at how the organization operates. How does sales occur? How is the product or service managed? What does the supply chain look like? How does the organization get its raw materials? And we need to understand that, because if we don't understand how that business operates and we throw in new technology that changes the way people work, we'll break the organization. Again, many people skip the stage, and that's why 70% of architectures fail. Now, once we know the goals of the business, and then I'll get into the technical side of your question as well. But if we know the goals of the business and the vision of the business and how the business operates, we have to ask that client, how do you want the business to operate in the future? Because maybe they're, say, a global retailer, and they want to know the next time I go shopping at PetSmart for, lollipops for my cat, that I also buy cat beds, cat toys, so they can create a recommendation engine, for example. Well, when I know the business goals and the new process that they want sales occur, I can go work with that organization to create new business processes. The next thing a cloud architect would do would look at the organization's technology. It's AI, it's networking, it's data center, it's cloud, it's applications, it's security, even their voice and video systems. And we ask ourselves, does this actually get the organization to its goal? And if it does, we're done. No new architecture to create it. But if it doesn't, now we've got to go create a team of 15 to 50 people. And we will create a team of network architects and security architects and big data architects and AI architects and data scientists and cloud engineers and DevOps engineers. And we're going to build a team to design a solution that's going to meet that client's business needs, which the architect is focused on the business. Then the architect will create a statement of work. He'll determine, what kind of people need. Does the organization have the sophistication? We'll present that solution to key stakeholders. We'll get their buy-in. We'll help sell it to the leadership, negotiate the deal, and then we go off to a new client. So that's what a cloud architect does. By comparison, a network engineer goes on there and configures routers and switches and sets up the IP addressing on the switches and configures the routing protocol on the switches and plans the IP addressing scheme. So completely different jobs. Now, what does a cloud architect need to know? And honestly, I got a free guide on everything you need to learn as a cloud architect. Maybe pop that into the training. I wasn't going to talk about it today, but you guys asked the question. A cloud architect will need network design skills. Wide area network design skills, for example. What kind of wide area network to use? How do you plan your IP addresses? Understanding BGP. The cloud architect will need to understand compute and design, whether you should use a server or like a virtual machine, a physical server, whether you're going to use a container, what your container orchestration should be, whether you use functions as a service. A cloud architect will need to know the storage area networks, things like block storage, object storage, file storage, what they are, how to design them, how to use them. They'll need to understand security design skills. What's your data loss prevention strategy? What's your next generation firewall and DMZ strategy? What's your security policy needs to look like, for example? Some big data design skills, like how do you set up your data pipelines, your data lakes? What types of databases should you use and why? And then, of course, whether you should design a private cloud, hybrid multi-cloud, even AI design skills. Now, obviously, we teach them to our students, but those are the skills you're going to need as an architect. So, big difference. Now, if you wanted to be a network engineer, you need deep knowledge on networking. So, I have 10,000 hours just training in BGP, for example. How do you tune BGP for the internet service provider? How do you tune BGP for the cloud provider? How do you tune BGP for the enterprise? So a network engineer is 100% hands-on techie role. Now, the good news is the cloud is just somebody else's network in a data center. So I'll tell you, I've trained some network engineers and gotten them cloud architect jobs pretty easy, but they have to learn the business skills, the sales skills, the leadership skills, the executive skills, the business acumen, the business process reengineering, the CXO relevancy. So all of us can do it. I got people that I can give you that have been teachers that have been hired, that have been homemakers that have been hired, that were college waiters and waitresses, college students, geologists. Any of you can get any job you want, but you're going to need a lot of networking. Some of that's covered in the AWS Advanced Networking. A lot more would be covered in, say, a Cisco certification, but it's not the how to build. It's how to performance tune and how to design. And that's the biggest difference. One is on how to, and the other is on why. Hope that makes sense. Great questions you guys are asking. I can do one more and then I have to stop, but we'll have lots of time for you guys to really learn. Can you mention some good resources to study cases on to how different businesses are using cloud computing to solve various problems? Well, I can give you the example that 70% of organizations are a disaster. So there's that. So you can't just look at how one company designs their system. If you do, you're going to hurt your next client. And here's what I mean. There's what you call a reference architecture. And David Lithicum and I just created that. A reference architecture is guidelines on how you would set up a provider's stuff. But it's something that you can't use for every client because every client has different business goals. Here's what you need to understand. You need to understand how that individual business operates. I've got two banks and they both do things completely differently. I can't look at how one solved it for the other one. I've got two universities. They have a different way that their students go through the things. I've got one company that does boutique consulting here, but their people need to be experts on this and they need to be extra good at this. I've got another consulting firm that does something completely different. So what you really need to learn is kind of just like a doctor. And I used to practice internal medicine as a nurse practitioner before I moved into tech. I need to learn what is normal. I need to understand business. I need to understand the types of business problems that exist. I need to understand how macro and microeconomics actually affects the business environment. I need to understand how the industry trends are going to be in the environment. I need to understand business processes and business process reengineering, and I need to develop the wisdom. So, when we train clients in our cloud architect career development program, we give them various business things. They interview the executive. The executive tells them their business goals, their business pain points, and business challenges. Then they create a custom design, and they got to do what an architect does: document it, present it back, and sell it. So if you tried to sell me somebody else's business solution, you're not going to be there. So the best case studies that I could tell you would be the kind of case studies they use in an MBA program. Learn various business problems. And when you understand business challenges and have the business acumen and education and training to know how to solve these business problems, then you know what to do. But some things you need to be taught. You need to be taught how to fly an airplane. It's not something you're just going to figure it out. And, you're not going to practice medicine and just let me just see what happens. But this is something you just need somebody to show you. I hope I answered that because I really want to help you. Welcome back, everyone. This is Michael Gibbs, and this is day 2 of the free Go Cloud Careers AWS Certified Solutions Architect Associate 2024 Bootcamp. And this is going to help prepare you for the AWS Solution Architect certification. And this is an AWS full course tutorial. If you missed day 1, that's okay. You can still see day 1 of this boot camp on our channel. Our team will provide the link. You can go back and see it after today, and you'll be just fine. And in this free AWS certification training course, we're really preparing you for the AWS Solution Architect Associate slash SAA-CO3 exam. So we're going to have some fun here. At least I had some fun yesterday. We got to have a big discussion yesterday. And continuing with our discussion, we're going to stick with the networking, at least for the beginning of today. I want to get the harder stuff out of the way first. And that way, the rest of it becomes simple because everything really in cloud computing is networking. I mean, all of it. It's all based upon the network. So if the network doesn't work, nothing works. In fact, the first clouds that I worked on back in 93 and 96 and 99, they were all network-based clouds. So lots of networking things here that are super important. So I hope you enjoy this AWS certification free course because we really want to help you. So we'll begin in about 2 minutes or so. I know everybody typically comes in a little bit late. I run these things all the time. So if you want to invite a friend or know anybody that's interested, send a tweet, send an email, invite some friends. If you just got here today, we're going to be doing 3 hours of AWS Solutions Architect Associate training every day this week and every day next week. And the week after that, our team will invite some people to some hands-on live demos as well and answer any questions to try to help you even more in this free training session. So let me tell you about some other 3 free things we have to help you. Because we want to really make sure you understand the technology, what it is, where it's used, how the technology works. We want to make sure that we spend all 30 hours covering the technology. After interviewing 6,000 people, it's very easy for me to find someone that knows how to configure, but doesn't know why they're configuring it, what they're configuring, or the need for it. So it's still important if you want to be a cloud engineer or a DevOps engineer or somebody else that's got a hands-on position to get your hands dirty and get hands-on. So please download the completely free AWS lab demonstration videos. There's over 40 of them there. Good labs for you to do, get some hands-on experience, and I encourage you to do so. My team will pop them up there, and they are completely free. So go along and do those labs. In addition to that, we also have a free certifications guide, say, what kind of certification should you do to build your career? They're completely free. It's a free ebook our team wrote. And the reason we wrote it is so many times we see people that come to us with a ton of certifications and they have got a goal career, say being a cloud architect, and their certifications make them look like they're not. So here's a certification guide to tell you what you should do that'll help augment your skills and build your profile and make people want to look at you because they're going to see you as a leader in your field, a specialist in your field, as opposed to, say, someone that's confused as who they want to be. If you needed surgery and you went to a doctor and it said dog walker, gymnast, martial artist, flight attendant, and doctor, you wouldn't be impressed. But if you saw a great medical school and fancy degrees and residencies and fellowships and years of expertise, you'd want that person. So I want to teach you how to be great, and that's free in the certifications ebook. So go get it. So the last part of starting out today is me knowing that you are awake, alert, and oriented in this free AWS certification training. So please give me a hashtag AWS Solutions Architect Associate or a hashtag SAA-CO3. And we'll begin the course as soon as I see that coming onto the screen because I want to know that you're here and you're awake and you are ready to go. So I know I'm ready to go. I see people are coming from all over. I see people from Philadelphia, which is where I grew up. I see South Africa. I see Sacramento. I see Brazil. I love this. I see people in Mexico, spent lots of time in Mexico. It's a beautiful, beautiful place. I see people all over the world. So welcome, welcome. And if you're going to enjoy our content today, please hit that like button. And if you're enjoying what you're learning, hit the subscribe button as well. And then hit the bell to be notified of new videos because we've got lots of videos to help out with your cloud architect career, your AWS solutions architect career, your enterprise architect career, your artificial intelligence architect career, and many other architecture careers. We train lots of security architects as well around here. So now we will begin with the content. As always, we'll speak for 20 minutes or so, maybe 25, maybe 30. We'll take about 10 minutes of questions because we want to make sure that you guys learn and have a great experience. And I see all these hashtags, and we will begin. So if you'll recall, yesterday, we were working on networking, and the last thing we talked about were the transit gateways. So now we're going to talk about network access control lists or packet filters. So in any network, we have to find some way to keep traffic out of a subnet. On routers, we have access lists. On AWS, they call it a network access list, but it's really a basic packet filter. And with AWS, and here's your test question, we use access control lists or network access control lists to keep unwanted traffic out of a subnet. Later, we'll talk about security groups, and that's to keep traffic out of a host or service. And you will see that in the question. Network access list protects a subnet. A security group protects a host or service. So access control lists will either allow or disallow traffic based upon the configured policy you set. Now, when you put on an access control list, the default policy is to deny everything, just like a firewall. The normal firewall blocks all incoming traffic. And if you have an access list and there's no permit rules, everything is going to be denied. And when you create an access list, it's really like the old-fashioned Cisco extended access list, where you're going to specify the source and destination address, a protocol, and a port number. So access control lists are stateful, and we'll talk about what stateful means when we get to a security group. And I'll draw a diagram for you so you understand, because we have fun with our diagrams. But network access control lists are stateful, meaning the routers themselves, whether it be a virtual router in AWS or a Cisco router or a Juniper router or anybody else's routers, do not keep track of the data going in and out of the router with an access list, which means they're stateless. So on a practical perspective, you will need to apply an access list both on inbound traffic and outbound traffic. So keep that in the back of your mind. It is also important to note that with access control lists or network access control lists, the rules are processed in order. So the order matters. I'm going to show you what not to do. And I've seen this so many times. People say, Mike, I don't understand. No traffic's getting through my access list when I explicitly permitted something. So if I take you to this example, and I've seen this all the time, here's what you don't want to do. So let's say I've got an access control list on inbound traffic, and it says Rule 100, deny everything. Hey, Rule 110, permit web traffic in. Well, here's what happens when the access list is processed. The packet comes in, and it sees it, and it hits the access list that says denial traffic. The traffic's completely thrown out right there at that rule. And then what you'll see is after the deny everything, which means throw it all away, you got to permit something, but it doesn't work because it's already been blocked. So when you're going to create an access control list, here's the right way to do it. Create a rule that says allow TCP or whatever it is you want to allow in, IPsec to a VPN concentrator, TCP port 80 to a regular web server, TCP port 443 to HTTPS. So allow what you want. And that's it, because the rest is going to automatically be denied. And here you can see how we're allowing, the traffic in and the traffic out for a basic HTTP web server, just like a router that you get from Cisco. So next, I'll show you where this works. And we'll get to security groups in a minute, but the network access control list protects your subnets. Your security groups protect a host or a load balancer or something. So security group, think host-based firewall for a device. Access control list there. Now, you may have noticed that I had Rule 100 and then Rule 110. So remember, these things, access control list rules are processed in order. So don't do Rule 1, Rule 2, Rule 3, and Rule 4. And here's the reason why. As you work with these systems over time, you're going to need that, you have a rule and you're going to need to add another rule. And remember, these things are processed in order. So if you do 1, 2, and you need to add a new rule for rule 2, you're going to have to erase every other rule you have and then rebuild your access list from scratch. You don't want to do that. But if you did 10, 20, it gives you the opportunity to add, an additional 9 rules in between things in order. So always leave a good space between your rules. Okay, so let's talk about security groups right now. And a security group is like an access control list, but it's going to be applied to a computing instance. And it's very similar to a host-based firewall. And the difference between a firewall and an access control list is that firewalls are stateful. And we'll walk through stateful in a minute because lots of people are confused by this, but you don't need to be. And we'll make sure you're clear on it in a minute. So because it's stateful, and we'll show you, you only have to apply it on the one direction, which is inbound. And we'll show you what that means in a second. But if you get someone asks you, do you use a security group or an access list? You use both. And that's still not going to be anywhere close to enough for security, but you use both. You protect the subnet with a network ACL. You protect the host with a security group. So let's actually look at what I mean by stateful. I'm going to give you an example. We'll do it real time. And let me just draw this out. So in this particular environment, what you have is you've got a firewall. Okay. Now, what we're going to do here is we're going to walk through, kind of, an example of what this could look like. So let's say we've got a user, and the user sitting behind the firewall. I'll make the user very small. This is the troubleshooting coach at Go Cloud Careers. She likes to unplug cables, power off our OpenStack servers with her paws, but she also likes to use the internet. So let's see if I can flip this around. Okay, so this little girl decides she wants to go to the internet. And, where does she want to go? She's going to go on the internet. She wants to go to a website. Let's say it's tuna.com. Little Cindy loves tuna. And I've got the tuna bills to prove it. So the way a stateful firewall works, and a security group is a stateful firewall. Cindy wants to go to tuna.com. So she goes out. The firewall typically does her net. Her traffic goes all the way out to the internet, and tuna.com, gets the request. It's a TCP request. So little Cindy sends a TCP send to the website. Will you open a connection with me? And the tuna.com website responds to her send, and acknowledges it. Yes, I'll open a connection with you. And little Cindy, I want you to open a connection with me. So it'll send its acknowledgement as well. And then the packet is allowed through the firewall. I'm going to do this again because it's really important. Little Cindy wants to go to the tuna.com website. She goes out to the internet. As soon as her packet leaves the firewall keeps track of it. And the tuna.com's traffic is allowed back because Cindy initiated the connection and the firewall kept track of it. Now, over here, we have to understand the rest of this is over here. We have Hal the hacker. And Hal the hacker wants to actually get through the firewall to talk to Cindy. Hal the hacker hits the firewall and his traffic is automatically denied. And it's denied because firewalls block all incoming traffic, block. And except what was specifically permitted. But firewalls by default allow internal traffic to go out to the internet. And it keeps track of that traffic. And that's how it knows how to allow the return traffic to come back. So that's what people are talking about when they deal with stateful firewalls. The security group is stateful, so you only need to apply it in one direction. So let's talk about the interplay of a security group and an access list. So here you see we've got our internet gateways connecting us to the internet. We should have a firewall too, but this is a very simple diagram. There are multiple firewalls and other things along the way, but let's just say this for right now. So we've got our access control list protecting the subnet where our servers are. And then we've got a security group protecting those servers. So it's a combination. When it comes to security, it's really like an onion. You're going to need multiple layers and layers and layers of protection. So kind of hope that clears that up for you. So the next thing we're going to talk about while we're under networking is something called a transit VPC. So yesterday we talked about hub and spoke networking. We talked about the efficiency of it. There's flaws with hub and spoke networking too, because if the hub goes, you've got a problem. And that's why you typically use multiple hubs in hub and spoke networking with multiple connections to each spoke. But hub and spoke networking is very simple. It's just like taking that airplane. And that's why the airlines use hub and spoke networking too. I live around Palm Beach, Florida. I want to go anywhere. I go to my West Palm Beach International Airport. I then fly to a hub. A hub could be Dallas, Texas for Houston for Delta Airlines. For United Airlines, it could be Houston, for example. For American Airlines, I could go from West Palm Beach to Dallas and then Dallas to somewhere else. So that's your typical hub and spoke. And a transit VPC enables an organization to connect multiple VPCs to themselves through a transit VPC. So the transit VPC is basically functioning as a hub in a hub and spoke environment. And for example, an organization could have multiple VPCs and they could run a connection across the internet to these VPCs, or they could get a direct connection to each different spoke site, which they could do, just like you would do in a normal wide area network. You buy private lines, use software-defined networking, VPN WAN across your spokes. But in this particular case, you're using the cloud as your network provider, and that's why you would use a transit VPC. So the transit VPC is really a cloud router. And what happens is the spoke sites connect, via a connection, obviously, and they connect to the transit VPC via BGP. And that way routes are exchanged, or network layer reachability is exchanged between the individual VPCs. And all the information stays on the AWS backbone, which means it's secure. And it's not on that scary internet like it would be, for example, if you happen to be using, say, any type of an internet connection. So great way to think about this. So let's talk about some improving the performance of some of the things you're going to be doing in the cloud. We're going to talk about first placement groups, and then we'll talk about single root IO virtualization. A crazy name. I didn't make it up. We'll make it real simple. Explain it to you. We'll talk about things like Elastic Fabric adapters, Route 53, and we're going to talk about load balancers. So the first thing that I want to talk about are placement groups. So what's a placement group? Well, wherever your systems are, the further they are from each other, the greater the latency, which is why, for the most part, a data center on your building has the best performance, and it will perform better than a cloud that's, say, 1,000 miles away. There's other reasons to be on the cloud, like agility, but generally speaking, your best performance is next to you. So if you need high performance on the cloud or any data center environment, sometimes you put stuff closer together. Now, when you put stuff closer together, you trade off availability, because from an availability perspective, you want your systems as far apart from each other. But from a performance perspective, you want them as close as possible to each other. So there are times where you need to create a high performance and computing environment, and you might do that. So, for example, I had a bank that I helped build the fastest trading system in the world many years ago. And we had 2 racks filled with the biggest servers that we could possibly find, and parts of the data center. And for the most part, there was one, and everything was super close to each other, all on the same switch. And there was another one super close to each other, all on the same switch. And we had 2 of them, one primary and a backup. So that's really what we're talking about. So let's talk about the first kind of placement. And this is going to be called the clustered placement group. Best performance you're going to get on the cloud is with a clustered placement group. And here's why. You put your servers all in the same rack. Okay. Most of the time, your virtual machines are even in the same server. So if you've got if you're using one of these really cool epic, servers with these 256 physical cores and 5 solid logical cores, and your system's got like 8 terabytes of DRAM in it, chances are you got pretty good performance in that server. And you can put a lot of virtual machines in that server, and the data never even needs to leave the server. Talk about good performance. But I want you to think about this. You put all your stuff in the same server or the same rack. It's now in the same rack. The rack has something called a power distribution unit in it, where it gets power from the data center. If the circuit breaker blows on that power distribution unit, everything in the rack is dead. Now, often you use 2 power distribution units and you have servers that are plugged into both, but keep that in the back of your mind. Single rack, lots of stuff to go wrong. Switch fails, the entire rack is dead. Primary server fails, it's got half of your virtual machines. I mean, memory or a CPU failure or a hardware failure. Poof, crashed. You got nothing. But if you really need the best performance and you squish all your stuff in the same rack or the same server, you're going to get it. So that's what a cluster placement group is. All your stuff in the same device. And you can see in one of the data centers called an availability zone, you got all your stuff in the same rack. Really good performance. Because it's not like there's any latency going back and forth between your devices or minimum latency, but all your stuff's in a single basket super close to each other, so there's a lot to go wrong. So what do you do if you need good performance, but you need a little more redundancy? Well, this is where you get into what AWS calls a partition placement group. Here's what you're really doing. You're taking 2 or 3 racks in the same data center, and you keep a lot of stuff in, say, rack 1, a lot of stuff in rack 2, and a lot of stuff in rack 3. And the racks are relatively close to each other, and they've got high-speed fiber optic connections to each other, and you got good performance. Until that data center or availability zone goes, and you got nothing. But this is going to be what it's going to look like. Now, because all of your stuff isn't in the same rack, it's not going to perform quite as well as the cluster placement group. But it's going to perform pretty darn close to that because it's all in the same building. And this way, if you lose a rack or you lose a switch port or a switch, this has a lot better survivability. And as long as that data center doesn't go down, you're going to be up, operational, and good. So I hope that kind of makes sense. Now, the alternative is a spread placement group. And what's a spread placement group? Well, if we know that it's a little too dangerous to stick everything in the same data center, otherwise known as availability zone, we can put our stuff in maybe 2 availability zones across a couple of racks. Now, this will give us much greater availability than something like a cluster placement group or even a partition placement group, but it's going to come at the cost of performance. So what's that going to look like? It's going to look like this. We've got 2 availability zones and we've got stuff spread in multiple racks. So decent performance, but not optimal performance. Optimal performance is that cluster placement group. The partition placement group is kind of somewhere in between optimal performance and this, because it's still going to give you really good performance, but you've got a little redundancy in there. That whole data center you could potentially have. In a spread placement group, you spread the load across data centers. And if the data centers are close to each other and have good performance, it's still going to be relatively good. So kind of think about that. Now, the next technology I'm going to talk about, enhanced networking. So I hate these terms that marketing people make up. But in a virtual machine, and when we get to virtual machines, we talk about EC2 instances, I'm actually going to bring you into our data center, and I'm going to show you VMware at the server virtualization level and show you how virtual machines are created and what those hypervisors look like, so you really understand virtual machines or EC2 instances. Now, in a virtual machine, we have 2 options. Option 1 is we basically just use the CPU, the DRAM resources of the virtual machine, and everything is done on the CPU. But what if we need better performance? So in a traditional virtual machine, you have a virtual network card, a virtual graphics card, and their performance isn't great. Have any of you ever tried to video edit on a virtual machine? You're going to see it doesn't work so good because you don't have good GPU performance. Now, let's say, for example, I wanted to do AI on a virtual machine, and I need a GPU for the particular use case of my GPU, say an NVIDIA GPU, because I need CUDA. If I can't get a virtual machine to have its actual graphics card inside of the virtual machine, the hardware graphics card, I'll have poor performance. So there's a technology called PCIe pass-through, which enables you to take a PCIe card, like a network card or a GPU, and take that physical card and put that physical hardware inside of a virtual machine. And that way the virtual machine can have a real network card, like a 100 gig network card, or it can have, an NVIDIA RTX, say A6000 in it, or something like that. So kind of keep that in the back of your mind. So when we push a physical network card into a server, they call it single root IO virtualization. You may see it abbreviated as SR-IOV. All that means is you've got a virtual machine with a hardware network card placed into the virtual machine. That's it. And accordingly, a real hardware device will perform better than a software device. So the next concept we'll talk about as it pertains to high-speed networking is something called a virtual fabric adapter. And AWS invented a software network adapter that had a really good driver that can offer high network performance. It's been designed for up to 400 gigabit per second. At some point, it may get there, but keep that in the back of your mind. So those are some performance tuning things. So we're going to get into DNS next, but now might be an actual good time to see if anybody has any questions. So let's see if anybody has any questions. If not, we'll get back to the content. The first question is, what's the difference between a security group and a firewall? So a security group is a firewall, if you will, for a host. But a traditional firewall will protect your entire network. So maybe if we draw it out, because that's a good question. And I may have a surprise for you at the end of this thing that will help you understand that a little better. So stick around to the end. You may have some surprises that you aren't counting on that you might really be excited about. So let's look at it this way. In a normal cloud environment, I might have a load balancer split the load against, say, 2 next generation firewalls. And behind that, I could have either an internet gateway, or maybe I've got a web server over here, for example. And I'll show you the difference in how you would apply these. So let's say we've got a load balancer and 2 next generation firewalls, and then maybe behind that we've got a load balancer and maybe it's an IDS IPS system. And even though the next generation firewall has it, sometimes we use IDS IPS systems for logs and security. And I'm going to put my web servers in a subnet. So inside of the I'm going to protect the subnet with an access control list. And then I'm going to have my web server back here, which is going to be behind a load balancer, right? Because we're most likely going to need more than one. So I'm going to have a load balancer. Outside of the load balancer, we'll obviously need a public IP address because it's going to be reachable from the internet. So we'll call it E for a public IP address or external IP address. And behind the load balancer, we may have a web servers. And these are going to be sitting on virtual machines in most cases. So here's what you see. This firewall protects the entire network. Everything. These intrusion detection and devices will also cover, certain things. It may spot an intrusion or find an intrusion, for example. This is going to protect our subnet. And on this load balancer, we're going to put a security group here. And that's going to be like a firewall to the load balancer. And then we'll also put a security group on the web servers. And, you're going to look at this and say, what the heck? Why so many layers here? You have to understand that if you don't have these layers, you'll still be hacked. And even this is not going to be enough to properly secure the system. We're going to have to harden operating systems and create a good identity and access management strategy. And there's a lot more that we could do here to even further increase the security. But firewall protects everything. I can put a firewall between two VPCs. I can be a computer parts manufacturer, and I might have to get hard drives from Samsung, and I might need to get GPUs from AMD and NVIDIA, and I might need to get Ethernet cards or other cards from, say, Mellanox. So I might put a firewall between my computer parts, my server manufacturing company, and all the parts providers to protect me. I might use a firewall to protect an organization from external threats. But I might use a security group as an extra step on the load balancer to say, hey, if anything past the firewalls and the IDS, IPS, and the access control list, I'll use the security group thing. But the bigger, more industrial tools out there I'm talking about provide a much greater level of security. But the more tools you have, the better your systems will be. Does a VPC have an IP or only a suggested range? So we have to understand a VPC is your virtual private data center. You might need 20,000 IP addresses inside of that or more. I work with organizations that have hundreds of thousands of IP addresses. So you are going to have an IP. You're going to have a subnet. Each subnets that you're going to have are going to have their own range. And for example, a server subnet typically is going to be a /24 because you might have up to 250 servers, more than you think you need. But private IP addresses are free. Wide area network links typically only allow 2 IP addresses, but with AWS, you got to make it a /28 because they use IP addresses a little differently than most organizations. So everything that needs to be reachable will have an IP address on it. Everything. Good question. Firewall would be in a transit VPC. Well, what you would typically do is you would have the router in the transit VPC doing running BGP and handling the routing. But if you wanted to protect each VPC from each other, so if one VPC kind of got hacked, you didn't want the other VPCs to get hacked, you would potentially put firewalls between every VPC and the transit VPC. You could do that. Nice question. The internet gateway to the VPC, does it have an IP address? It must have an IP address. So the outside, so the internet gateway is going to have a public IP address to be reachable from the internet. So yes, it will have to. You can go to the next one, Chris. How should you design a landing zone for internet access and firewalls for applications? So you wouldn't design a landing zone for an application. You would create something called a demilitarized zone. And in that demilitarized zone is where you're actually going to set up your systems up. Now, how do you design proper demilitarized zone based upon your application? I typically spend about 800 hours teaching those things to my cloud architect students and network architect students. And that's why so that's where I would say to learn that. If you can't take that training with us, I would say you're going to need a security architecture training from someone, and it's not going to be covered something in, say, an AWS Advanced Security. It's just not. Some of it's covered in the CISSP. I'd say some of it, but a lot of it is really understanding security technology. So a CCDE from Cisco, they would talk about this. A CCIE security from Cisco, they would talk about this. But you have to evaluate what the application is. You're going to have to evaluate what it's worth, the application, the critical downtime, and as you have to understand, what is downtime cost? Is it $1 million a minute for this application? You have to understand what is the application protecting in terms of quantifying the security. And then you're going to need to build a business case around it and then figure out what you want to do about it, for example. Do you transfer the risk with, say, insurance? Do you mitigate the risk? Which risks do you just accept? Those kinds of things. And that will determine how many layers of next generation firewalls you use, ITS, IDS, IPS systems, which SIEM systems you're going to be using along the way, how you're going to harden the operating systems of your servers themselves, what traffic needs to be in and out, those demilitarized zones, and there's a lot that goes into it. But it's beyond the scope of what we can talk about here because of time. Good question, though. So, Mohammed, when you've got overlapping IP addresses, you have to do something about it. Either readdress your overlapping IP addresses or use network address translation, because you can't have two devices talk to each other if they have conflicting IP addresses. But so the transit gateway is not going to natively do it. But a transit VPC can handle overlapping IP addresses with very careful net design. So, Ref, you said you worked in 20 years establishing, maintaining racks and servers and managing VMware infrastructure. Now everything is cloud-based. So where is the expertise going to be? Well, it really depends where you want to be and what you want to do. Everything that the VMware data centers have been doing is no different than the cloud. I mean, seriously, it's 100% the same. It's the same physical data centers, the same racks, the same load balancers, the same everything. So it's just whether they use a VMware hypervisor or their own hypervisor. But all in all, it's going to be the same. So the key here is understanding that there's going to be a lot more automation in the racks and managing the servers. So if it's going to be cloud-based, you're going to have the opportunity to whether you build the stuff or whether you design the stuff. So I don't know what your actual goals are. And depending upon your actual goals, I could give you more guidance. The best thing I could say is attend one of our live webinars or do one of our career question and answer sessions, because I want to answer it and I will answer it. And normally speaking, every Monday I do free question and answer sessions. And every Thursday I've got a webinar on Zoom, and you can ask as many questions as you like that on careers, and I would love to answer it. But because this is certification based, we can't really talk about the future of careers at this point, but potentially later. But I will definitely help you with it. But I can tell you, AI architecture, cloud architecture, enterprise architecture, security architecture are probably some of the best careers moving forward. And my team can pop a link in a chat box of why we feel they're the best way. And I just wrote an article that was just published in a magazine today. It was on LinkedIn where I was tagged. Maybe my team can drop a link to that as well. Is it considered a firewall for EC2? A security group it's sort of it's what you would consider a host-based firewall. So what do I mean host-based firewall? So a host-based firewall protects a host. A traditional firewall can protect the entire system. So yes, it's a firewall for an EC2 instance, for example. But that doesn't mean you might still not want to put a host-based firewall on your EC2 instances. Maybe use a security group to protect your instance, and maybe your endpoint also has a host-based firewall, some anti-malware software on it, and it's going to have some other things attached to that host as well to keep it secure. Okay, so let's get back to the content. And we are now going to talk about DNS, our Route 53. So why do we have the DNS, or the domain name system? Here's the thing. Every device on the network needs an IP address. And if you've got a memory like my wife, where you could just give her a number, 3.14.76.21, and that is an IP address. I have no idea who owns it. My wife could remember every single one of them and go, oh, this cat site, let me enter that number. Of course, my wife learned Spanish in 2 weeks because her translators couldn't understand our thoughts, so she's a super genius. For the rest of us, I know that it's very easy to type www.gocloudcareers.com. And I don't have to think about the 2 IP addresses that we have of the 2 web servers. So DNS helps us map a name to an IP address. And there's a lot of things that are here. So here's an example of how this might work. You've got a user that enters www.amazon.com on their browser, and it sends a request to the DNS server, who has the IP address of Amazon.com. And DNS will return the IP address for Amazon, and then you're there. So I'll teach you actually how you can find the IP address to this later today because we're going to go check it when we talk about, or if not, we'll talk about it when we get to content delivery networks. But here's an example of, I went to my PC and I did an NS lookup, which is how you would check the name to an IP address. And I typed NS lookup www.gocloudcareers.com. Those 8.8.8s that you have are my DNS servers. They're actually Google's EKS DNS servers. That's great DNS service. And you can see these are the two IP addresses of our website, a primary and a backup. So now that you understand what that is, and actually, if we go back to this, which do you think is easier to remember? www.gocloudcareers.com or 192.0.78.137. And at least the way DNS is set up, and we'll talk about it later, if the first web server were to fail, DNS would route you to the second address. And that's another reason we might be using DNS. So let's talk about what goes into a domain name. We've got a host name. That's that name of the end device. So we also have the domain name. And that's going to be the domain name that we're talking about. And I'll discuss this in a minute. And then we will have the top level domain. So what's that going to look like? So www, in this case, would actually be the host name. It could also be mike.ec2, but whatever. In this case, we'll say www is the host name. The domain name is going to be Go Cloud Careers, and the top level domain is .com, .net, .edu, .anything it's supposed to be in today's world. So that's what goes into a fully qualified domain name. And when a domain name has everything, it's called the fully qualified domain name. So the way DNS works is it has DNS records. They're also called zone files. And what are DNS records? They're really just a particular set of instructions that are located in the DNS server and how they work. So the records are going to be in a format that's called DNS syntax. And realistically speaking, it's a text file that sits on these DNS servers. And there's going to be a couple things that exist. There's going to be something called a time to live. You may see it as a TTL. And that's going to be how often your DNS servers will refresh the records. So you've got a choice of short TTLs or long TTLs. And normally the time to live is measured in seconds. If I set the time to live to 1 day, the DNS server would not refresh itself for 1 day. So what would be the advantage of this? Well, if it was 1 day, those DNS servers don't have to do a lot of work. They're attached to a certain number of people, and once a day they get a little text message, and they're sitting there happy. They're relaxed. They're not doing anything. Of course, if something happens, you might not know about it for a day. So that's not going to be good for your availability or anything like that. By comparison, if you set your DNS records very short, the TTL very short, those DNS servers do a lot, but they will find an error quickly and they will refresh it and get it better. So you're going to have better performance and availability. So an organization needs to think about the scalability of their DNS system and what they're trying to do. Now, we're going to talk about the DNS record types, and I'm going to talk about something that you really should consider. If we're going to be talking about AWS Route 53. And I want you to understand that if we have a multi-cloud environment, which 98% of businesses do, say a Nutanix cloud and AWS and Azure, and we use AWS DNS Route 53, and AWS has an outage, our Google will be down, and our OpenStack cloud, our Nutanix cloud will be down. So if it's really going to matter in real architectures for real large global important enterprises where downtime matters, you can't use Route 53. You'll have to go to a DNS vendor like F5 and put your own DNS servers in all clouds. So if it's going to be critical, like a multi-billion-dollar architecture, and that's all I work on, you're going to have to manage your own DNS infrastructure. But if you're looking for the convenience of somebody managing your DNS infrastructure for you, and you're not that scale, AWS, assuming your business is going to only be on AWS, which again, 98% of businesses won't be, has this managed DNS service called Route 53. So keep that in the back of your mind from an architectural perspective. So now we're going to talk about various records. The first record is going to be called an alias record. And thankfully, this works for all, all DNS providers. So An alias record is something very similar to what you would think of a CNAME record, but it can be used to point to a DNS node. So if I want to map www.a.com to www.b.com, where when the user goes www.a.com, they automatically get transferred to the new website, www.b.com, you create an alias record. And you may have noticed companies change names or grow over time or buy a company, and you go to the old website and they transfer you to the new one. Well, that's either going to be done with the CNAME record or it's going to be done with an alias record, depending upon whether it's a subdomain or primary domain. The next DNS record type that you should know is something called the certification authority authorization record. And that enables domain owners to specify which certificate authorities are allowed to issue certificates for their domain. Maybe you get a certificate from the Amazon. Maybe you get it from GoDaddy. Maybe you get it from another company. There's lots of certificate authorities out there. And that's what your CAA record is. And why? Because if you're supposed to be getting a certificate from GoDaddy and it's being generated by Holly the hacker, you got a problem. Don't use it. So that's what that record's for. You're also going to see something called the TXT record. And a TXT or text record is used to store text information for a variety of purposes, maybe verifying domain ownership, providing some email sender policies, and implementing other services that are going to require textual data. You'll also see something called the PTR record. PTR or pointer records are going to be utilized for reverse DNS lookups, allowing the mapping of an IP address back to a domain name. So if you know the IP address, meaning like somebody tries to come and hack you, and you see their IP address, and you want to contact the ISP that they're at and get them banned, you might use a PTR record, for example. Now, you'll also have another record called a naming authority pointer record, and that will be an NAPTR. I didn't make these up. And they're often used alongside something called an SRV record for advanced DNS routing needs. Now, there's another type of a record called the Sender Policy Framework record or an SPF record, and that helps protect against email spoofing by specifying authorized mail servers for a domain. And if you know who your mail servers are supposed to be, when you get an email from your boss that says, "Hi, it's the CEO. Please go to the Apple store. I'm short on time and go buy some gift cards and I'll give you money back later," you'll be able to know that that didn't come from the CEO. And if you ever get a text message like that or an email message like that, and it happens all the time, it's called CEO fraud, know that it's not real in most cases, unless you've got a manager that constantly asks you to go to the Apple store and buy gift cards. You will also see something called an NRV record, and this is called the Negative Response Verification record. And it's not super common, but it's designed to authenticate negative responses in DNS queries and ensuring that the responses are indeed from authoritative sources. So these records that we've talked about each fulfill specific functions in DNS management, from domain verification to email security to directing traffic for overall security. Now, I talked about why, in a multi-cloud environment, you need to have your own DNS infrastructure. But if you wanted to use the Amazon one and your services are good, and you're one of those 2% of the customers that are only in a single cloud, you can use AWS Route 53. And it's a great DNS service. It just is. But if you've got 3 clouds and all your DNS is managed by one cloud provider and they're down, you lose the benefit of the other 2 clouds. So keep that in the back of your mind. Architecture is all about trade-offs. Is the trade-off right for your business? So when it comes to AWS, they use Anycast service, which is really good. Anycast provides low latency and it supports health checks. So what is Anycast? Because this is going to be something that confuses so many people, but it's really great from an availability perspective. So let's map it out. If you'll recall, every IP address in the world, it needs to be unique if it's going to be reached. So let's say DNS, and I'm going to use Google's DNS addresses because I know them, and Google's own DNS is, is Anycast as well. So let's talk about how Anycast actually works. You're going to have 2 servers that are going to have the same DNS information on them. They're going to be identically configured, and they're going to have the same IP address. What? Huh? Mike, didn't you say that every IP address out there needs to be unique? And I said, yes, there is. And that's completely true. But for right now, just work with me. And this is how these DNS systems create some real high availability as they use Anycast. So we're going to walk through. So let's say we've got the internet over here. I can't seem to find my cloud that I'm actually looking for. So we'll just, I'm going to make a big circle for the internet. So let's say this entire thing over here is the internet. And this is why Anycast is so cool. Now, let's say you got a user over here. You got a user, and this user's in Florida. And this user over here, they're in Tennessee. And let's say this DNS server is in Florida, and this DNS server just happens to be in Tennessee. So, and the reason Anycast provides high availability is this. So I want to go to the internet, and I want to know who has the IP address of www.gocloudcareers.com. So I enter that in my browser, my PC does a lookup, and it says, go to 8.8.8, Mike. So I go to 8.8.8, and I get a response. Now, this is why it's so cool. If this DNS server were to go away and die because the server crashed, guess what will happen next? And this is what we do in most high availability situations. So my PC is configured, go to 8.8.8.8. So my PC goes to the internet and it hits the DNS server, which happens to be in Tennessee. And then it gets a response back from the DNS server, and I know how to go. So by using Anycast, what happened so far is my DNS server went away and all my PCs are configured for the same DNS address anyway. So my service is up. What makes this even better is we've got some users. There's a great business school at the University of Tennessee at Martin. I know some phenomenal business school and professors that teach there. And they want to go to the internet and they go to their Tennessee web server and they get a response. But if this thing were to crash, they'll go and they'll hit the Florida web server. So that's the point of Anycast. It gives you great performance, and it also provides high availability. So in any environment where you're going to use high availability DNS, it's going to be an Anycast setup. And whether it's Google's DNS servers that you're using, or AWS's DNS servers that you're using, or Azure's DNS servers, they're all going to be Anycast. But like I said, if you've got a multi-cloud environment, you need to have your own infrastructure that can survive a cloud failure as well, even though these cloud providers have really good DNS services. So there's some other DNS records that you need to know, and we'll talk about them as well and what they actually do. So we talked about most of these, but these are some records you should think about. The A record maps a name to an IP address. The AAAA record maps a name to an IPv6 address. The C name record is if you were to enter training.gocloudarchitects.com, you'd be forwarded to training.gocloudcareers.com. So, it's that kind of thing, so that you get the information no matter what. The MX record is for mail. We talked about some of these other records already, but keep these in the back of your mind. These are the DNS records that, generally speaking, you should know for your career. And they're also the DNS records that you should know what they are for your tests and exams as well. So AWS supports that A record. They support CNAME records, as we talked about. AWS supports NS records, our name server records, which these are going to be the name servers that will be responsible for your DNS zone. These are the authoritative name servers that propagate your official DNS information to the main DNS servers across the internet. I mentioned the MX record is going to say which mail servers can accept mail for your domain. When it can email, you have to have an MX record. The start of authority record identifies the primary name server for the domain. the responsible party for the domain, and it has a timestamp that changes anytime you update the domain, and the number of seconds before the zone should be refreshed. Amazon Route 53 supports both IPv4 and IPv6 addresses. And DNS, all DNS, including Amazon's Route 53, does something called the health check. And I want to draw that out for you because this is a very important concept. And not everybody understands it, but if you do, you'll be much better prepared to not only pass an exam, but actually be able to be functional and work. So here's what a health check is. Let's say this is server 1. We'll make a couple of servers here. Server 2. Server 3. And this could be a router doing a health check, a load balancer doing a health check, DNS doing a health check. So in this particular environment, let's say it's going to be DNS. I don't care whether it's DNS or a load balancer. They all do the same thing. Now, let's say these are all 3 web servers that we want to use. We got 3 of them right now. It's exciting, right? So DNS, let's say traditionally, it sends 33% to server 1, 33% to server 2, and 33% to server 3. Now, these servers could be in different clouds, different data centers, or they could all be in the same data center. Just we've got a weighted routing policy that does 33% to one, 33% to the other, and 33% to the third. Done. Now, here's where it gets pretty interesting, and it's going to get exciting. Here's the way this works. The DNS server will issue a health check, and here's what it's going to do. The DNS server will query server 1. Server 1, are you there? And server 1 says, I am here, I am present. So DNS will consider server 1 to be good. Immediately thereafter, DNS will question server 2. Server 2, are you there? And server 2 says, I'm here, I'm part of the party, I'm having a great time. DNS says, server 3, are you there? Server 3 says, woohoo, having fun here at the pool party, serving my web content. So everybody's happy. And this goes on all day. The DNS asks the servers, like, are you there? They say, I'm here, and everybody's happy. Now, somehow, server 1 crashes. And DNS says, server 1, are you there? And server 1 doesn't respond. So, of course, DNS, tries a couple of times and says, server 1, are you there? Server 1 doesn't respond. DNS says, server 1, are you there? DNS doesn't respond. So what happens is DNS will look at this server as dead, muerto, Bethameni, whatever language you want to think about it in. And DNS will then know, don't send any more traffic to server 1. Send 50% now to server 2 and 50% to server 3. Now, if DNS does a health check and server 1 says, I'm back, then DNS will share the load all over again. So that's the concept of a health check. Hope that kind of makes sense. So now we're going to talk about the types of routing policies you could do on AWS Route 53. Guess what? For the most part, you can do these same routing policies on Azure's DNS, Google's DNS, F5 DNS, any kind of DNS situation you want. So we'll talk about these policies and typically speaking when you would use them. The simplest DNS policy is called simple routing. What's simple routing? You've got one server, right? Or maybe a couple of servers. And you basically pop a simple record that says, if you go to 1.2.3.4, go to this server. I should say, if you want to go to cindythecat.com, and I don't know if that's a real website, but I've got a cat named Cindy the Cat. So if you go to cindythecat.com, it takes you to, let's say, 1.2.3.4. Let's pretend that was Cindy the Cat's website. It's not, and it's a public address. So it's just an argument. And don't go looking for Cindy the Cat at that address. So keep that in the back of your mind. Simple record. So you can think of it as something like this. Send the traffic, maybe go cloud architects directly to our web servers. Simple. So let's talk about another DNS policy called weighted routing. And weighted routing is how you can effectively choose how much traffic you're going to send to different resources. You would use weighted routing if let's say you have a data center right now on a private cloud, and you want to have 50% of the traffic go to the servers in your data center that are already paid for, and send 50% of the traffic to the AWS cloud. That way, you could have two clouds running, your data center private cloud and the AWS cloud. If your data center crashes, guess what? AWS could take over with auto scaling the entire load. If AWS crashes, don't worry, you don't lose your traffic because you still got your data center. You could have it with two cloud providers, 50% to AWS and 50% to Azure. Azure goes down, 100% of your traffic goes to AWS. AWS goes down, 100% of your traffic goes to Azure. That's weighted routing. And why might you use weighted routing? So you might use it for multi-clouds, but let's say your application developers tried something new, and one of your deployment methodologies is send 15% of the traffic to the new application and 85% to the old application. And if it works well, the traffic that went, the users loved it on the new load balancer where the new web server is. They loved it, and it works. Then right after that, you point everybody to the brand new application and all the brand new servers. So you might do that for, say, a weighted routing. I think they call it a canary deployment. I'm not an applications person. I'm a cloud architect, enterprise architect, and network architect. But there's an application deployment methodology. I'm pretty sure it's called canary deployment, where you send it to, say, 10%. If it works, you send it to everybody else. So let's talk about the next approach, which is something called latency-based routing. If you want your users to have the best performance, you want them to have the lowest latency. So the way latency-based routing works is DNS will look at your IP address, and they will send you to the website that's closest to you. So if I'm in Florida and Atlanta, Georgia has my website, they'd send me to the one in Atlanta, Georgia, as opposed to the web server in, say, London, England, or Tokyo, Japan. It's going to go to the nearest region. So that can often improve your performance, and that's called latency-based routing. So it's really about this. If somebody wanted to come to Go Cloud Architects from Australia, it would be better to send them to the load balancer that's closer to them. Very simple to understand. So hope that makes sense. So now let's talk about failover routing. This is pretty simple to understand. Failover routing is when you create an active setup and a passive setup. So for example, let's say that you had 100% of your systems in the AWS cloud. Let's say you had 100 web servers, for example, in AWS. And you had them in 2 different availability zones, but you wanted some kind of really cool backup. Let's say you had 10 web servers sitting in Google right now, running actively all the time, but nothing happens. You could set up a routing policy where if AWS were to fail, DNS would run those health checks and determine that AWS is down. It would then shift all your traffic over to Google, which has 10 servers running. Those 10 servers would immediately pick up the load. And then auto scaling would bring those 10 servers in the Google Cloud to, say, the 100 servers. And within 45 minutes, your data center is 100% up on another cloud and partially up in between. You could also set up a failover routing policy where, you've got your data center. And if your data center were to fail, go to the AWS cloud as a backup. So you've got lots of options in your architecture of how you design these. And DNS will be a significant tool on how you do it. So, for example, in a diagram we drew for back when we were at Go Cloud Architects, we just train more than just cloud architects. We train all kinds of architects, and they work everywhere now. So we're Go Cloud Careers. So if you put www.gocloudarchitects.com into Route 53, and the primary site would be unavailable, it would be deemed unhealthy, and all the traffic would go to the secondary site. So let's talk about geolocation routing policy. Geolocation routing policies route the user to the website that's closest to them by looking at the source IP address. And there's lots of reasons you might want to do this. So it's going to see where you're at. So If I am in the Bahamas, it's going to send me in a perfect website to a website in the Bahamas, maybe a website in West Palm Beach or Fort Lauderdale or something that's going to be pretty close. Geolocation. But I want you to think about this. Let's say you're in a part of the world that has many different languages. Geolocation knows which country you're in, and it could potentially send you to the right website. Think about that. It's kind of cool, especially for multinationals. So we'll also talk about something called a multi-value answer routing. And I have a hard time using multi-value answer routing, and here's what it does. It's kind of like a simple record, but it enables you to go to multiple destination servers, and then at random, it determines where it's going to send your traffic. Send this to the first one. Flip a coin, send it to the third one, that kind of thing. So for me in architecture, the better your plan is, the more likely your architecture is to succeed. Most architectures fail, like 70% of them. So the better your plan is, the better your results are. When you have no idea and you leave it up to random, that's not a plan that I really want to follow in most cases. There's still times to use this, and if it's appropriate, I'll use it. But in most cases, it's better to know where your traffic is going. Now, the next one we're going to talk about, realistically speaking, and it's one of the last things, is going to be geo-proximity routing. And what the heck is geo-proximity routing? This is an Amazon thing. And it lets Amazon route your traffic resources based upon the location of your users and your resources. And what it does is it takes different geographic regions of the world and it'll shrink them or make it bigger by something known as bias. And you get to determine what that is. So it's a unique one. You see, you've got these geo-proximity maps, which part of the world is. And you could make region 2 bigger or smaller, and that's how it's going to route your traffic. Hope that makes sense. So let's talk about DNS-based load balancing. So at the server level, you're going to use load balancers. At the network level, your routers may load balance either per packet, per flow, based upon the routing protocol and the way your routers and switches are configured. Actually, you know what? Before we get to this, let's do some questions, and then we will get back to DNS-based load balancing. Okay. What would cause an NS lookup to give a forbidden address? So a forbidden address could be caused by a few things. The DNS server could be configured to block queries for that address. There could be a firewall rule that's blocking the DNS queries to your server, or there could be an ACL involved. They're typically the reasons you would get a forbidden address. I think, Chris, we can go to the next one. What may cause some clients not to pick up an IP address when configuring DHCP, even if the config is properly done? So we're not really talking about DHCP now, and we haven't talked about anything related to that. But here's the way the DHCP process typically works. A host sends a DHCP discover packet, and this DNS servers respond, and then the host accepts one. So there's lots of things that can occur. There are times when the DHCP server is off of the local LAN. And DHCP, by definition, that discover packet is a broadcast. So the routers that actually are on that underlying network need to be configured to forward that all Fs broadcast to the appropriate DNS servers. With a Cisco router, that would need to be configured as a helper address. There are other times where the DNS servers are just not reachable because there's a networking problem. Now, there could be no IP addresses that are left in the DHCP pool as well. Or a client could be misconfigured. You could have that virtual machine configured to actually have a manually assigned IP address versus a DHCP assigned address. Or you've got some kind of security access control list or firewall that's blocking your DHCP traffic. They're your primary reasons where you won't pick up a system, an IP address via DHCP. What is the diff? Simple record and geolocation and weighted. So I'm not sure what you mean by diff. So let me talk about a simple record. It just maps a single IP address to a domain with nothing complicated in there. A geolocation record routes traffic based upon the geographic location of the user. So it's going to send them to the most appropriate local server or the closest server. A weighted record sends traffic across multiple addresses. So send 50% to AWS, send 50% to Azure. That's a weighted record. I hope I answered your question correctly. I didn't know what you meant by diff. Use case of public zones and private zones. So private zones, are for inside of your network. So in any corporation, you're going to have your intranet. And that's going to be all the private IP addresses and all that organization's private stuff. So I might have an internal server that's in my network that's got, say, a 172.161.7 IP address in the /24 range. But I might not know how to remember that IP address. So I might have DNS that says, hey, go to Cindy the Cat's tuna server, for example. And inside of your VPC, you might want also to do something similar too. So let's say you want to be able to reach certain virtual machines or a database by their fully qualified domain name. That's when you're going to use a private zone. By comparison, if you've got a publicly facing website or a publicly accessible load balancer or a publicly accessible API or a publicly accessible email server, that's going to be in a public zone because that's going to be reachable via the internet. And that's going to provide global accessibility for the people on the internet versus your internal users. Okay. What is the role of public and private keys, and how do you find them for an SFTP connection? So, public and private keys we will discuss when we discuss security, but it's related to setting up encryptions, and we'll talk about it with certificates. We'll also potentially talk about it with email signatures if we get to that. Which DNS we use for weighted routing in case of multi-cloud? Well, it depends on your architecture. So the key with architectures is there's never one option. It's always based upon what you need. If I have two clouds, say two availability zones in two different clouds, and I want to use both clouds, I'm going to use weighted routing. 50% cloud provider A, 50% cloud provider B. Cloud provider A goes away, send the rest to the other cloud provider and let auto scaling take care of scaling out the system, and we're good to go. I might have a disaster recovery environment where I have, let's say, 500 servers running normally, and that's going to be a small number, and I put 50 servers running in the other cloud. And I may have that active standby kind of thing. So cloud provider A gets 100% of my traffic. Cloud provider A disappears. I go to the other cloud and let auto scaling fix it, and within 45 minutes, we're up and running. That could be used for disaster recovery, sort of that warm standby approach, but it could also be used for active and passive routing as well. So what's the goal that you would use in multi-cloud? That's really the key. All goes down to what your goal. There's the other option we could choose too. Is DNS only used to communicate between a load balancer and an EC2? Absolutely not. DNS is used everywhere. Anytime you want to connect to any machine on the internet by its name, you use DNS. Anytime you want to determine which cloud provider you're going to go to, you use DNS. So lots of reasons to use DNS. How to route to multi-clouds? What is the median? Well, what are you trying to do? So, you can route to it. Well, do you want to have private lines between your clouds? Do you want to have IPsec connections to your other clouds? Do you want to have a software-defined WAN, which gives you, almost private line-like protection? Do you want to use a SASE WAN and get firewalls and encryption and some software-defined networking at the same time? What is the way you want your traffic to go? You want one prioritized over another prioritized, and that stuff you would do with BGP. But what is the goal? And that's really the key. So I can tell you that with a network architect, how they would route to multi-clouds is about 1,000 hours of training to really get to that BGP and that really heavy. And that's why a CCIE certification takes 2,000 to 5,000 hours of study and preparation time to get there. But everybody is multi-cloud. So you could do some of it via DNS if you're dealing with web servers. But what if it's internal stuff? And and even if you have 3 clouds, you're going to have to synchronize your data, and that's going to be dealing with your routing protocols. It's also going to be dealing with your wide area connections. So if you ask a more specific question, like how do I route and send 50% of my traffic to A to 50% to B, I can tell you. But how do you route to different clouds? That's where you're actually getting into something that could be 50 different or even 500 different scenarios. But the median is really for managing routing, and it's kind of a centralized control plane tool for network orchestration that's going to handle some of it. But you need to know what your goal is long before you think about using median versus BGP versus a software-defined strategy, that kind of thing. Good question. What's the difference between latency routing and geolocation routing? So latency routing is based upon the server with the lowest latency in terms of milliseconds, for example. Geolocation routing is the one that's closest to you. So they're going to be very similar. So if you think about it to this, the latency-based routing is based upon your geography. The geolocation could be something different. So let's say you're in a country. And let's say you're in Canada. And there's and let's say Montreal is predominantly French, right? But Toronto might actually be, more English and less French and more English. So you might want to, and this is a great question, Miriam, you might want to know where your user is. And that way you route them to the English one or the French one. Or say you're in South America. And Argentina speaks Spanish, but Brazil speaks Portuguese. So you wouldn't want to have a user in Brazil get a Spanish-speaking website. You'd want them to go to the one that's big in Portuguese. So that can be an example. There's some cultures in the Middle East that speak 3 and 4 languages, for example, and you want to send the users to the right place. That's typically where you're doing it. So give you a little more information. Latency-based is to give you the lowest traffic, the lowest latency and best performance. Optimize server response time. By comparison, geolocation is based upon the geographic location of the user. Can give you content or languages that's location specific. Or there are times where you need to comply with a regional policy. Your traffic can't go out of this country, that kind of thing. That's where you would use geolocation as well. Good question there, Miriam. And I know you will like that. Can I elaborate on the difference between geolocation and geoproximity? Sure. Geolocation is based upon your geography. So I'm in Brazil, I get a Portuguese website. I'm in Chile, I get a Spanish website. Granular routing. By comparison, geoproximity routes traffic based upon the geographic location of the users and resources. And you've got ability to shift traffic sort of towards resources. You're using geoproximity to optimize performance and balance load by adjusting that proximity bias. And lets you get pretty and able to really tune your flow of your traffic by specifying a bias. So I hope that makes sense. Any more, Chris? Geolocation routing and link to base routing. So I'm not completely sure I understand your question here, but I have a thought. For anything that's beyond the simple DNS questions that we're trying to cover now, in our AWS Advanced Networking Bootcamp, which you can get completely free, I'll have my team drop the link. I think we spend 3-4 hours on just DNS concept, maybe even 5 or 6 hours. So we've got a lot of content on there. And Tunde, I think that might actually be best to guide you, since I'm not sure I completely know what you mean.
I almost wonder if they mean latency-based routing. Maybe there's a language and the way maybe he's said it, spoke it too fast, or it stutter on their jitter on their end.
Oh, okay, okay. Then let me.
I'm just looking at. I'm thinking latency-based, link-based. Like maybe that's what they meant.
Yeah, exactly. Okay, let's do that then. So, geolocation-based routing is to route traffic based upon a geographic location. So you get the right language, for example. Whereas latency-based routing is based upon the lowest latency. So if this website has less latency, go there. And it's typically based upon your source IP address. But the geolocation is making sure that you get the right one with the right language. You mentioned that AWS DNS would not work if AWS fails. Azure DNS would not work. Correct. If Azure fails, which DNS would you use in a multi-cloud solution, since you will not use AWS or Azure? So, Canner, it depends on the organization. Most organizations at the enterprise level actually use F5. They've been making the DNS servers that most enterprises use. You can also create your own DNS system using Bind. I think that it's on Linux servers, so it's been out there. But there's lots of ways you can do it. But you got to look at it. It's the same thing when we get to Kubernetes. If we use the Amazon Kubernetes service and Azure goes down, then our AWS and our Oracle clouds won't work either. So you got to use something based upon what you need. But typically speaking, F5 is a vendor that's well known in the DNS space. And you can put DNS servers in each one. Alternatively, there's other providers like Cloudflare provides great DNS service, but then Cloudflare becomes your single point of failure. So if it's really big and it's really going to matter, you're going to get an industrial solution. You put your DNS virtual machines in all your cloud providers. Okay, so a couple thoughts. If you're having a good time, please like the video. Maybe subscribe to the channel and hit the bell to be notified of new things that we can do to help you for your career. Because we are going to spend 10 days going pretty geeky and deep in content. I don't get to get geeky. I'm an architect. Most of what we do is at the business level. But because we're having fun getting geeky, I want to make sure you still get those hands-on labs and time to do them. So please download the 40+ labs that we have for you. It's not a download. You'll sign up. You'll enter our content delivery system, and you'll be able to watch the labs and do them on your own. Please download them. My team will provide a link for this in the chat box, as well as a description of this video. Give me a hashtag and that says AWS Solutions Architect Associate, so that I know you're here, that you're not sleeping, that you're not hanging out eating cookies, which sounds really fun to me, even though I don't eat cookies, or playing with your cat, which sounds fun to me. I got a beautiful cat. But let me know you're awake, alert, and oriented with the hashtag AWS Solutions Architect Associate, and then we'll get back to the content. Do internet gateways also use Anycast like DNS servers? No. You need to know exactly which router you're doing. So if we were doing a router and a wide area network, there are types of first hop redundancy protocols that we could use. Things like HSRP or VRRP. And they are Anycast-like, but they are not Anycast, and they are used for routers. Internet gateways, again, are going to be a logical device, though. So logical devices typically don't go down, but routers use different technologies as a rule. Okay, I'm saying this. AWS, that'll sort of work. Lots of these AWS Solutions Architect Associates, some hashtags AWS. Well, okay. As long as I'm seeing these AWS Solutions Architect Associates, I know you're awake. And that way we're having some fun. So, and let's get back to some content. So now let's talk about Route 53 DNS-based load balancing. So how does it work? DNS-based load balancing just sends your traffic to multiple other devices. It could be different load balancers, different web servers, what have you. So how does it work? DNS or Route 53, if you're using AWS's DNS, would respond to your DNS queries with a different resource based upon your load balancing methods. So it enables you to load balance your application traffic across different regions of AWS, different cloud providers, if you will. And it works via health checks and DNS failover, just like we showed you when we walked over a health check. So if you weren't here for the health check piece, go back. We actually walked through health checks, and we'll probably do it again under load balancers. So there are, realistically speaking, two types of Route 53 DNS-based load balancing, and they're really routing policies. And they can be simple policies, and they can be complex. The simple method just takes two or more resources and load balance it, puts one in primary and one in secondary. And if we're using this, Route 53 will always replies with the client's IP address of the resource in the active, unless it fails a health check, and then it goes to the secondary resource. Now, the complex DNS routing policy is going to take more things into account. It's going to look at latency, and then it will send the DNS response with the response to the server with the lowest latency. And this is on the client where it's coming from. So remember, Route 53 is a global service. So with clients, they'll hit the DNS authoritative server and their region. So I hope that kind of makes sense. Simple, basically primary backup. Complex, send it to the resources that maybe have the least latency, which means best performance. So how do you set up DNS load balancing? Well, setting up anything is relatively easy in the AWS cloud or any other cloud provider. So the first thing you need to do is create your health checks. Create a health check for your resources. And, if you've got a web server that's going to be open on TCP port 80, make sure your health check opens TCP port 80. If you've got a web server that's going to open on TCP port 443, then it's going to respond on TCP port 443. Then you got to create your DNS records. So create your DNS records. And then set up a DNS policy, like create a failover routing policy. For example, if you want a primary and a secondary. Designate your primary resources and your secondary resources. And you're going to specify what happens under which circumstances. Set up your health checks and link them to your DNS records so it knows what to quote. And then just validate your configuration. So pretty easy thing to do. So here's a graphic that someone from my team, I think, drew. So in on the left, we see an environment that's healthy. The DNS is going to say send it to your two different regions. Send half to US East and half to US West. Now, figure two, send it load balancing between AWS regions. You can see that US West had an outage, and it's going to send all traffic to US East. So that's really what we're talking about here. Or better yet, in a high availability situation, you might be routing to two availability zones in AWS and two availability zones in, say, Azure. And that way you're pretty covered for lots of attacks that can occur. Or lots of problems like a network failure on a cloud provider, a control plane failure on a cloud provider, or a hacking event, which happens to a cloud provider. So I mentioned health checks. Another example graphic that we pretty much have set up is here you can say you've got two systems. The first one saying, are you there? The server responds. The next one is there, and it doesn't respond. So it gets marked as unhealthy, and it gets removed from the rotation. So whether you're using AWS Route 53 or you're using any DNS system, there's going to be a lot of logging and monitoring capabilities that you can use, especially if it's an industrial grade system. Route 53 enables logging of your DNS queries, things like capturing the domains or subdomains that requested it, the date and time of the request. So you get to see who went to and actually requested information or performed the DNS query. With AWS, you will get action logs in CloudTrail. And CloudTrail, which we'll talk about later, is for auditing, where CloudWatch is for monitoring. We'll talk about that later, but you can kind of understand that. It will monitor domain registration. The Route 53 dashboard will give you insights into domain registration status, including information on, say, domain transfers and when your domains will expire so you can renew them on time. And you can set up your health checks. Here's an example of what a health check might look like. You could basically query the Go Cloud Careers website, and you can see that all servers will be healthy. For example, if we're using AWS Route 53. So you can monitor the Route 53 resolver endpoints with CloudWatch, and you see what's going on, the volume of the DNS queries being processed. And that'll give you some insights into your traffic. And you can see, you can get some information that's pretty interesting. You'll be able to look at certain features and really see what's going on with your systems. Okay, well, now we're going to get into one of my favorite topics, which are load balancers. And no network architects don't normally work with load balancers. I love load balancers. And the reason I love load balancers is they enhance performance and they enhance availability. And anytime you have something that can make systems work better and be more available when the users need them, now you're talking some stuff that's exciting to me as someone that comes from a heavy infrastructure background. So let's talk about what a load balancer is. In the normal world, a load balancer is a physical device that will distribute your network and application traffic. And in a data center, you call F5 and you're going to get some big, robust load balancers, and they're going to be there. In the cloud, it's a software-based service that actually to distribute traffic among different systems. Load balancers are awesome because they can help with scalability. So imagine this. I've got one server with 64 cores and a terabyte of DRAM, and it's not enough. I've got two options. I can change that server to a 128 core server with 2 terabytes of DRAM, and now I've solved my performance problem to a point. But what happens when the server crashes? I've got nothing. And, once I get above an actual 256 physical cores in today's world and say 6 terabytes of DRAM, I'm out. I'm done. There's nothing else I could do. What happens if you're Google? What happens if you're Amazon and you get millions and millions and millions of requests? Not a single server can do it. Enter the load balancer. So what the load balancer does is enables us to add a little more servers. 10 servers, 20 servers, hundreds of servers, thousands of servers. And if you're going to deal with a company like Google, they may have 1 million servers out there for doing their web stuff, or more, actually, probably a lot more. So if you think about that, and a lot of that sharing the load gets done with load balancers. But it's better. Let's say I've got 5 servers underneath the load balancer. The load balancer determines one of the servers is dead. It's okay. It distributes traffic to the other 4. And in the cloud, we can add another one on demand with auto scaling. And that way, it improves our availability. So load balancers are good stuff. So when we talk about load balancers, they're going to come from, realistically speaking, 2 categories: network load balancers and application load balancers. A network load balancer is going to operate at layer 4 of that OSI model that we talked about. So it's going to be the IP address, the protocol, the port number. source and destination. That's it. So 192.168.1.1 wants to talk to 1.2.3.4. Port 443. And I just made up the 1.2.3.4. I don't mean to be using a public address. Probably should, for example. So that's what a network load balancer does. Now, is only looking at the TCP or UDP, the protocol source and destination address and port numbers. That's not a lot. So network load balancers are fast. So you want to load balance between huge servers, you need a network load balancer. Want to load balance between firewalls or network devices, you use a network load balancer. Well, there's a gateway load balancer, which is very similar to a network load balancer, but that's the concept of what these things are. They're big and bad. But it's like anything else. If I asked you to do 2 plus 2, you could do 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. It's nothing. That's why network load balancers are fast. Now, what if I asked you to calculate a derivative in your head? Could you do that at the same speed that you could do 2 plus 2? Or any kind of advanced calculus you want, or advanced statistical metrics? That's going to take some time. It's okay. You got to think about it. You got to slow. It's a bigger workload. So the application load balancer is smarter than the network load balancer. But it's like asking it to do calculus versus simple addition. So it's going to be slow. So there are times when we use an application load balancer. When a load balance between microservices, it's perfect. Want to look deep into, say, somebody wants to go to a web server and you want to look inside of the header and the HTTP methods, push, get, that kind of thing, application load balancer. So application load balancer, super smart, but not fast. Network load balancer, super slow, or super fast, but not as smart. And there's times where you're going to need to combine these load balancers to get speed and intelligence at the same time. But that's way beyond the AWS Solutions Architect Professional, and we'll never be able to finish this course if we talk about it. Well, that's the kind of stuff we teach our architects. So when we talk about AWS's load balancers, they had to make up their own funny name. So to them, it's Elastic Load Balancer. If you want to be able to communicate with your clients, it's either going to be a network load balancer or an application load balancer, because they understand that, and that'll be the same terminology you can use in every cloud provider. You don't need to call it a cloud load balancer with Google or an Azure load balancer. Call it what it is. Your clients will understand you and they will thank you. For the test, remember the silly marketing name. So Elastic Load Balancers kind of auto scale. They use an IP address. So make sure you've got enough IP addresses. They can load balance across availability zones, which means data centers. Load balancers support health checks. So, and they can also terminate SSL connections. And let's talk about that. So if you want to hit a web server and you're using HTTPS, that's encryption. And encryption is incredibly computationally expensive. What do I mean by that? It uses a lot of CPU resources. So if your web servers have to terminate the HTTPS, their capacity to work will be much less. The fact that an AWS load balancer, most load balancers, can actually do the HTTPS encryption and terminate those connection requests means they can offload a lot of the work that your web servers do to these load balancers, which means your web servers can also scale much greater. So load balancers are awesome. So when we deal with load balancers, there's a couple of terminologies you need to know about. The first one is called the target. What's a target? The target is where the load balancer distributes the traffic. So it could be an EC2 instance or a virtual machine. The target could be an IP address. But if the target's going to be an IP address, it's going to have to be either a private address, as specified in RFC 1918, or it's going to have to be in the shared address space environment. And that's the 100.64.0.0/10. You can see that in RFC 6958. All you have to do is Google ietf.org, RFC 6598. You'll get that whole specification. If you want to read the private IP addressing scheme that was designed by the Internet Engineering Task Force, like all CCIEs do, go to the ietf.org and look up RFC 1918. But RFC 19 private address spaces are the 10.0.0.0/8, the 172.16.0.0/12, and the 192.168.0.0/16. You can also see that on our AWS Advanced Networking, our subnetting workshops that we do, which are free. My team will provide links for that. And even a CCNA free course, which we have on our channel to help you with networking knowledge. So we talked about a target. Now, what if you wanted to route it to a group of servers instead? Well, AWS enables you to create something called a target group. So send the traffic to the group Cindy the Cat's Toys, and then every one of those servers in Cindy the Cat's Toys gets the share of information. Now, when you deal with a network load balancer, because a network load balancer looks at the TCP source and destination and the protocol and port number, if we've got a user, say Sally hits server 1, Sally is going to be on server 1 for her entire duration. Now Billy Bob comes in and he gets naturally sent to server 2, and Billy Bob will stay on server 2 the entire time. Now Costandinos gets sent to server 3 and he will stay on server 3 the entire time. And that's often called the sticky session. And the way network load balancers work, that always happens. Now, if we're using an application load balancer instead, the application load balancer will route each request to the server with the lowest load. So might send it to server 1 the first time, server 2 the second time. Remember, these application load balancers are smart. So if you need some sort of session persistence and you need to make user 1 stay on server 1 the entire time, you can do that. And it's called the sticky session. And the way these load balancers will do that is they'll use a cookie. They'll put a cookie in the browser to track the connection, and that way they send it to the same server. So different ways to achieve the same things. So whenever we're using a load balancer, we need a health check. Because if we want to share the load between 50 servers, but 2 of the servers are dead, that means 2 out of 50 times the traffic is just going to be dropped. And those users aren't going to be happy. And we want everybody to be happy, right? So we got to make sure our systems work. So the way that's going to work is with a health check. I know I did it under DNS, but perhaps somebody wasn't here when we covered it this morning. So I'll draw it out one more time and I'll show you the way it could be in a load balancer environment. So we might have a load balancer here. Let's say we've got big bad servers. Let's say these servers have a couple of terabytes of DRAM in them, and say 256 physical cores. So we could have a VM1, VM2, VM3. Let's have VM4 too. I'll give you a containerized example too, because it really doesn't make a difference. And what's going to happen is the load balancer will say, hey, server VM1, are you there? And it's going to say, woohoo, I'm here. I'm having a good time, having a party, serving up content. VM2, are you there? Yeah, I'm here, serving a party, having fun over here. VM3, you there? Yep, I'm here. President accounted for, all's good. VM4, are you there? Now, this happens for a period of time. And then the load balancer says a health check. Server 1, are you there? Yeah, I'm here. Server 2, are you here? No response. Server 3, are you here? Yep, I'm here. Server 4, are you here? Yep, I'm here. Runs the next query. Virtual machine 1, are you there? Yeah, web server 1, I am happy. Virtual machine 1, virtual machine 2, web server 2, are you there? Nope, no response. Virtual machine 3, are you there? Yep, virtual machine 4, I'm here. Happens a few times, and then the load balancer says, this virtual machine 2, not in existence. Let's mark it out and only send traffic to virtual machine 1, 2, and 3. Now, this is really no different than if this was an application load balancer and this was a container. Container C1, C2, C3, and of course you could use a network load balancer too. But containers usually have less resources. You probably use an application load balancer in most cases, and the load balancer would share traffic amongst the containers. It's no big deal. It's the same thing. It's a lot like DNS. Did I share that on the screen, hopefully? So I hope that makes sense. So if it pops up on your exam, AWS has something called the classic load balancer. And it can either be a network-based load balancer or an application-based load balancer. It's a legacy platform, and AWS doesn't typically, what's the word I'm looking for? They don't typically recommend it, but it has all the features and functionalities for the most part of any other load balancer. I don't think I shared my screen when I was trying to show these load balancers and health checks. And if that's the case, I'm sorry. So I'm going to do it again. So let's go back into this environment. Two different very simple architectures for load balancers, virtual machine-based load balancer and a containerized load balancer. So you'll have maybe a network load balancer with these virtual machines because they all have, say, 256 physical cores and what do you call it? Let's say 4 terabytes of DRAM, and they're running on bare metal. So server 1, are you there? I'm here. Server 2, are you there? Yep, I'm here. Server 3, are you here? Yep, I'm here. Server 4, no response. Server 1, are you here? Yeah. Server 2, are you here? Yes. Server 3, yes, I'm here. Server 4, no response. That happens 3-4 times, and then the web server, the load balancer says, web server 4 is not here, so only use server 1, server 2, and server 3 for our traffic, and it'll keep running it. Same thing. We could have a microservices-based application running in a bunch of Kubernetes containers and Docker containers, for example, where it's orchestrated, say, by Kubernetes, that kind of thing, or whatever we want. And the application load balancer will send to the first container, the second container, the third container, the first, second, third. They will also run a health check. Container 1, are you happy? Yes, I'm happy. Container U2, are you happy? Yes, I'm happy. Container 3, are you happy? And your function, are you there? Yes, I'm definitely here. All's working well. Server 1, are you there? Container 1, yes, I'm here. Server 2, no response. Server 3, yes, I'm here. Server 1 to the health check, are you there? Yep. Server 2, no response. Server 3, yes, I'm here. Container gets marked as unhealthy, and the container no longer gets traffic. And then the load balancer distributes traffic between container 1 and container 2. So now, when we talk about the AWS network load balancer, understand it's not a physical device. It's a logical device, so it shouldn't go down in most cases. And we can use it to multiple targets. They could be virtual machines like EC2 instances. They could be containers, or they could be IP addresses. These things are fast because they're network load balancers. So think millions of requests per second and very low latency. We can also use it. So keep that in the back of your mind. High performance. Now, some of the things we can do with AWS network load balancers, which are kind of cool, is we can put a static IP address on it. And we have to, and here's why. So you've got your virtual machine, right? And that's going to be the place where your virtual machines are at behind the load balancer. We put a public IP address on the load balancer. That's what we put in DNS. DNS is a record that points to the IP address of the load balancer. And behind that load balancer, your website is going to be sitting on, say, containers or virtual machines. So keep that in the back of your mind. It supports a public IP address or more. Obviously, it's going to have to if it's going to be an internet-facing load balancer. And it typically preserves the client's source IP address. And that's going to be necessary in there's certain cases if you need to see the backend application needs to see the source IP address of the client. There might be reasons for security and other you might want to do that. Load balancers provide what's called zonal isolation, and they're designed for high availability and fault tolerances by supporting multiple availability zones. And they run health checks like I showed you, like all load balancers do. Most good load balancers, along with the AWS load balancers, will terminate a TLS connection. Like I said, offloading that HTTPS off of the, the web servers themselves will enable them to scale. And it's also integrated with private link network load balancers. So they support enabling private access to certain services that might be hosted on AWS. And you can even load balance across availability zones. Now, Whenever we deal with load balancers, there's a couple of terms. There's typically something called a listener. And the listener is the process on the load balancer that's going to be looking at connection requests. It's going to be looking for that. And the target group, or the target, is where those requests are sent. It could be a virtual machine. It could be an IP address. It could be a function as a service, like a Lambda function. And then each target group will specify a protocol and port number where the traffic is going to be routed. So with our load balancers, we can set up rules. And the rules will define how the incoming connections are going to be routed to the target groups. And of course, no load balancer would be worth anything without a health check. So how do we set these things up? What's necessary? Well, you create a load balancer. You can go to the Amazon management console and look up and select load balancers. You create a load balancer. Now, if it's a network load balancer, you're going to click choose network load balancer. Then you're going to name the load balancer, Cindy the Cat's load balancer. And you're going to determine, do you want it to be internal, meaning inside of your private internet stuff, private IP addresses behind it, or external or internet facing. You'll configure it as internet facing. That means it's going to be out to the internet. You'll pick an IP address type, IPv4, IPv6, or both. And you'll add a listener. You'll configure your availability zones that you want to use. Or you potentially can pick an IP address for the load balancer and the selected availability zone. You configure your target groups, which is where you send it. Again, it could be a virtual machine, an IP address, a function as a service, like a Lambda function. And then you register your targets. You review it, and you click create, and everything's done. It's pretty simple stuff. So you have the ability to put protection on your load balancer like a security group. So that enables you to provide a little bit of protection. Up until about 6 months ago, it wasn't supported on Amazon. Couldn't figure out why, because it's a basic function, but they now allow security groups on other load balancers. You can also apply an IAM policy to control access to the load balancer and its resources as well. An identity and access management is really determining who you are, determining what you're allowed to do, and then keeping track of what you've done. And we'll talk about that much more. So our load balancer will connect to Amazon CloudWatch for monitoring. And you can also connect it to AWS Cloud Shell for logging, say, API calls and requests for auditing purposes later. And very cool with these load balancer, along with most, is they will terminate TLS connections for security. That was the network load balancer. So let's talk about the application load balancer now. The application load balancer is a layer 7 of the OSI model load balancer. And this is designed for advanced routing needs, such as path-based routing. And it's going to integrate with various AWS services. So, the way these are going to typically work is you're going to have a load balancer, and they're going to have listeners, and they're going to have rules. And that's how they know where to send your traffic. And they'll all run health checks like we talked about earlier. We talked about how those health checks work. So application load balancers are smart. So let's talk about the features of the AWS application load balancer. It provides content-based routing, meaning you can route your traffic based upon the content that's being requested, whether it's host-based, path-based, or HTTP header-based. They support WebSockets, things like HTTP/2 support. By supporting WebSockets for full duplex communication, it provides some improved performance. Just like the network load balancers, they will terminate SSL connections, which means offload the work from the container or the web servers, which makes them scale better. They support advanced request routing, and that's supporting routing rules based upon, say, HTTP headers or methods or query string parameters and the source IP address. So again, these are smart. They're doing a lot. It can work with the AWS certificate manager for your SSL or TLS-based certificates. It can integrate WAF, as a AWS proprietary firewall that you could use. Although in an enterprise environment, you'll most likely be using next generation firewalls, because not only can they block things, they can look for patterns of anomalies and stop attacks in their tracks. So they're very advanced. People that make next generation firewalls that are used in enterprise security are companies like Cisco, Palo Alto Networks, Fortinet, Checkpoint. There's a few others as well. F5 makes some. And you will get these from the AWS marketplace, and they are the kind that you could use on AWS, Azure, and Google or OpenStack all at the same time and in your data center and have the same systems. And they typically provide very robust protection, more than you would get from, say, a cloud native firewall. But these things you can also support one. And there's nothing to keep you from using a next generation firewall and an AWS WAF in your solution as well. Application load balancer, the AWS ones, supports sticky sessions or that session affinity. We talked about it with regards to a cookie. And they support target groups, and you can route traffic to multiple target groups, containers, virtual machines, IP addresses, Lambda functions, what have you. Application load balancers can integrate with auto scaling, and it will adjust the number of, say, virtual machines or EC2 instances you will need based upon the load on these systems. And they integrate with logging and monitoring. And quite frankly, when you're dealing with a cloud provider, unless you want to go to a load balancing system like from an F5 for, say, a reverse proxy, you're going to want to use these. And even if you go into a more robust load balancer or a reverse proxy from something like F5, you're still going to need the Amazon load balancers to load balance because they'll be in virtual machines. And by nature, virtual machines aren't high availability devices. These AWS application load balancers will have that same listener function like we talked about and the same target group that we're talking about. So you'll define rules, and the rules you define will determine your routing. Path, host, headers, some kind of query parameter. So how do you create the application load balancer? You create it. So you go to the load balancer section, you click create, Cindy the Cat's ALB. And you set the scheme, internet facing. Listeners, or let's say the cat's web servers are on port 443 because she's going to sell tuna and other cat goods. You never see what my cat does with her paws on my PC. It's kind of scary. And then you'd select your availability zones. Then you set up your security settings. So maybe you put a security group on the load balancer. Maybe you put a certificate, and you can get a certificate from anywhere. But you could use the AWS certificate manager to get a certificate, or other companies like GoDaddy, etc. And then we need to configure our target groups. Okay, so let's take a break, answer some questions, and then we'll get back to the content after we answer some questions. Let me fill my water here because I've been talking a lot. Can you set up DNS on 2 cloud providers so we don't have a single point of failure? Well, you have to have a robust DNS solution. So if you choose an industrial grade DNS solution, the kind we've been working with for 30 years, and you would normally have your DNS server, say, in 10 different data centers for an organization that has it, you've got DNS. You take those same servers, stick it in every cloud provider that you have, you've got a robust DNS solution that will work no matter what, and you won't have a single point of failure. Because you own it. That's going to be different than trying to manage and integrate Amazon's DNS into Microsoft. It's not very challenging to manage DNS. Why do you see Cloudflare being the fastest, faster than AWS CloudFront? So here's the reality. There's no such thing as the fastest. It might be the fastest where you're at. So everybody's going to go say, I have the newest, I have the best, and it's a bunch of marketing fluff. All businesses that matter use more than one content delivery network. If you go to NS Lookup right now and do an NS Lookup, some of you will find that Amazon's using Fastly. Some of them will find that they're using CloudFront. Some of you that are finding they're using Akamai. So they're all good. And it's your mileage may vary. But, to go out there and say that Cloudflare is the fastest, I don't think that's a reasonable thing to say. I can show you times where it's the fastest. I can show you times where it's the slowest. I can tell you times where AWS is the fastest. I can show you times where it doesn't matter. So the key is not having a single point of failure in your content delivery networks. In the AWS Solutions Architect Associate, they'll say use CloudFront. But even Amazon themselves wouldn't just use CloudFront. They'll use multiple content delivery networks. So the real key is don't use more than one. Don't use a single, a single content delivery network. If you do, you're going to find yourself in trouble. Can an application work balancer work without a target group? It's got to route to something, typically a target. I don't really configure them because I'm an architect, but so I'm not 100% sure. Part of my architecture as an architect would be, okay, here's where we need our application load balancers. Here's where we need our network load balancers. Here's where we need to use both to get speed and performance. And let's figure out where those are going. But the actual configuration, that would be something a cloud engineer would do. And it's just not something I have experience with. But should you put a load balancer before or after the firewall? You might have to do both. So in a cloud, in a data center, I can put two firewalls directly together and they run a heartbeat between them. But they're physical devices. In a cloud, actually with AWS, I think with Palo Alto, you don't need a load balancer, but if you're using somebody else's, you will. So I might need a network load balancer to load balance between my firewalls. I might have a second set of firewalls where I'll need another network load balancer for my firewalls. I might then need another network load balancer in front of two IDS, IPS systems. And then I will have another load balancer behind my firewalls where the web servers are. But you might have an application load balancer inside of your network because they're an internal application that you won't have firewalled off. So it really depends on what you're trying to do in your architecture. And I've given you a whole bunch of different options. And you may need a combination of all of them or none of them based upon the client you're dealing with and what their goals are. But generally speaking, put your load balancers behind the firewalls. Do you need a elastic IP or public IP address if your system placed in the firewall? It depends what you're trying to achieve. So if you've got a firewall in front and then you've got a demilitarized zone and the load balancer is public, then that load balancer will definitely need a public IP address on it. But by comparison, if it's a load balancer inside of your internet, and maybe you've got 20 HR servers, for example, well, that traffic isn't going to go through the internet. That traffic is going to go through your wide area network, which, like we talked about yesterday, direct connections or VPNs, for example, that you could use. And then you would not put a public IP address on that. So kind of think about that. It depends where it's placed and it depends on what your goals are. So, Ref, I think you're actually asking the wrong question. So the question is not how a bank would use a load balancer versus how Netflix would use a load balancer. And I get where that's actually coming from. But here's what you need to be concerned with. What is the organization's business goal? What is the organization's business processes that they need to have? And what is the technology that drives that organization into improved business performance? That defines my architecture. The tech doesn't drive the architecture. The business needs, workflows, and business processes drive the architecture. So you're going to have to start by that first. So that's the key. So I might have a bank, for example, that's creating a super high performance compute environment that has a critical low latency application that's an internal application where they may have 50 servers with 256 cores and 8 terabytes of DRAM each and NVMe rated arrays in them to be super fast, to create a low latency something. Low latency auto trading system, for example. By comparison, they may also have a website and they're going to use a load balancer across their publicly facing websites. They may also have an application that needs incredible high performance and intelligence. So they may place some network load balancers in front of application load balancers and load balance between the application load balancers, and then say have microservices behind them, if that's the way their application is. But what matters is not the technology. What matters is what problem are we trying to solve, and then we do it. The same way where a physician has to interview the patient, determine what their medical challenge is, make a diagnosis and a plan, we're doing the same thing in architecture. What is that client's business goal? How does that business operate? What's normal for them? What's abnormal? What is that business pain points? We have to make a diagnosis and then build a plan called the architecture. So I can have two banks that are going to use the technology completely differently. So if we learn from, for example, what others have done, we're ultimately going to be learning how to solve someone else's problem. We have to learn at the problem at hand. What is the problem we're trying to achieve? How does that organization operate? And that's when we train cloud architects or enterprise architects. The role is 50 to 75% business. And it's not covered in the certification because, and I'm giving you far more than the certification has there. The certification is kind of a name of a service and how they configure it. Architecture to make the design answers that you're actually asking the question is examining the organization, understanding where they want to be 3 months from now, 6 months from now, 9 months from now, a year from now, 5 years from now, 20 years from now. Examining the way that business operates, the business processes, like how is a product made? How does the supply chain operate? How is a service delivered? How is it supported, etc. And then determining, is that the way we want it to be, or is that not the way we want it to be? If it's not the way we want it to be, it's working with that organization to find their strategy and helping them craft those new processes. And then evaluating the technology they have. Is the technology going to get them there? And if not, what technology changes do we need to support those goals? And only then can we even think about the architecture. I hope that makes sense. So what defines if you need a network load balancer or application load balancer is the size of the destination. So the choice of a network load balancer or application load balancer is defined by the type of traffic you have and the required features that you need. If you have high performance systems, big systems are huge systems, you're going to want, and you need high performance, you're going to use a network load balancer. Got servers with 256 cores. These are big servers that demand big performance. You're not going to want to slow it down with an application load balancer. But what if we've got, and there's lots of applications out there and lots of things businesses use. But if we've got an HTTP or HTTPS website, or we're going to be dealing with WebSockets, now we need intelligence. So that's when we're going to use an application load balancer. So we need to kind of understand the goals. Chris, we go to the next one. Will a load balancer work with global accelerator? Sure, it will. We can use a load balancer with global accelerator, and we'll talk about global accelerator later. But global accelerators basically gives you a static anycast address that's going to route your traffic to the optimal endpoint. But yeah, we could load balance that kind of stuff too. What kind of a load balancer do you need with auto scaling groups? Any of them will work with auto scaling groups. So application load balancer, network load balancer. And when do you use the network load balancer? So network load balancer, high performance, low latency. Application load balancer, we need smarts. Routing in between, say, microservices, looking at the content of an HTTP request, WebSockets, that sort of thing. All right, so in keeping with our theme, let's get back to the content. But I need to know you're awake. So Couple things I want to tell you about. If you haven't gotten the book on which certifications are going to be good for your career as a cloud architect, that kind of thing, please get the certifications guide. It's completely free. And actually, I'm going to have my team pop a link to how to become a cloud architect or solutions architect. It's a free ebook we wrote, because a lot of these questions I'm actually getting are so good, especially some of the questions by Ahref and a few others. But they're putting the cart before the horse. And that's okay. We all start there. We all get excited about the tech, and we have to figure out the business components later. But in order to work, we need to get the business. So if you download that completely free e-guide on how to become a cloud architect, it'll talk about everything that we need to learn and those skills. And it's a free ebook anyway, so why not get it to do that? If you're having a good time, please like the video. Please hit the subscribe button and the bell to be notified of new things that we've got to help you in your career. And I'll get back to the content now, but not without a hashtag. I need to know you're awake, alert, and oriented. So give me a hashtag SAA-C03. So Sierra Alpha Alpha dash Charlie 03. For those of you that like to use the phonetic alphabet. Maybe you were an airplane pilot or a firefighter or something like that. So now let's talk about gateway load balancers. We're on load balancers. I like load balancers. So gateway load balancer is a network load balancer that is used for the directing traffic to virtual network appliances or security appliances. So if you need robust security, you're not going to be using your cloud provider's firewall. You're going to be getting an industrial next generation firewall from a security vendor. It's a time where you would use a gateway load balancer, for example. And a gateway load balancer kind of feels like a bump in the wire. We're going to do, say, some inspection where a set of firewalls we can service multiple VPCs. And this opens up a lot of opportunities for security as a service. And what it's going to typically look like is as follows. You may have your load balancer here, and you may have people that are coming back and forth. And what you can see is this load balancer creates this little tunnel between this gateway load balancer and your appliance. It uses something called AWS calls a Genevieve encapsulation. For any of you that are used to GRE tunnels, that generic routing and encapsulation method, where basically you tunnel something across an IP network, that's what we're really talking about. So you'll have your sources that are the target before the load balancer, and that'll go all the way back to whatever's behind the scenes. Hope that makes sense. So how does a gateway load balancer work? Well, a lot like a network load balancer. But the gateway load balancer is going to be an endpoint that's going to be consumed by your hosts, load balancers, virtual machines, what have you. And it's going to force traffic to be sent towards the gateway load balancer. So it's going to create that private tunnel between where you're at and the security appliance. And it's going to encapsulate all the traffic to the security appliance. When the security appliance receives the traffic, it's going to decapsulate it, meaning get rid of those tunnel headers, inspect the traffic, and then re-encapsulate it and send it back to the gateway load balancer subnet. And again, it uses that Genevieve encapsulation. And it works with many of the security providers you would deal with. So when it comes to an industrial grade, high performance, high security environment, you're typically going to be dealing with the main security companies, and you use like a gateway load balancer for this. Most companies would be Cisco, Palo Alto Networks, Fortinet, etc. And it enables you traffic inspection to kind of see what's going on. So let's look at what you could see it looking like as another approach. You can see you've got your applications, and they would be behind this load balancer endpoint. And you might even send it all to, say, an inspection VPC to be looking at all the traffic as it's going in and out of the internet. And you can see you've got your VPC that's going to have traffic inspection. You can see you may have an inspection VPC where everything goes. So companies need to know sometimes for security and compliance reasons where their traffic's going. And these gateway load balancers really help a lot with it. So think about this. Inspection of your outgoing traffic from your VPC to the internet. It's going to give you a lot of information about your traffic and the type of traffic and what's going on. And, find malicious traffic as well. The security appliance will receive that encapsulated traffic, decapsulate it, inspect it. And when it's done, it'll send the traffic to the load balancer. So when would you use the gateway load balancer? If you need efficient traffic management, meaning seamless traffic and scaling of network traffic, and you need high performance and consistent latency across multiple virtual appliances like firewalls, this is your go-to load balancer. If you need enhanced security and inspection, and who doesn't in today's world, the gateway load balancer helps you work with big security providers and their services to improve your security. If you want to add some high availability or fault tolerance, you need a load balancer, right? And the gateway load balancer will help with that as well. And it can be relatively cost effective and simplifies your infrastructure. And it's going to help reduce your infrastructure cost by optimizing the resources that you're using and cleaning up your network architecture and making maintenance and updates a little easier. So there's that. Now, I did talk about sticky sessions before, but maybe we talk about it a little more. So I mentioned with network load balancers, your traffic goes directly to the same end server each time. But with application load balancers, they go each time to the server with the lowest latency. But if you don't want that to happen, you use a cookie, and the cookie will enable the server to come in. So Cindy the cat goes to tuna.com, for example, and they have an application load balancer. So they put a cookie in her browser, and that way Cindy ends up on server 1 when she's trying to buy her tuna. So that's realistically what's going on. So keep that in the back of your mind. And that way you can be stuck on a single server. Now, why would you care? Some servers require state and you to be attached to that same server, and they can't go through all the other servers in the application. So if it matters, you're going to use sticky sessions, and it's basically just a cookie. And you can see what it looks like here. Without sticky sessions, users keep going all over the place. With a sticky session, they're given a cookie, and they stay on the same server each time. So sticky sessions rely on an application cookie at the HTTP or HTTPS headers. The client cookies can either be maintained in web and generated by the web application itself, like an application-based cookies, or they can be maintained and generated by the application load balancer. That's called the duration-based cookie. Application-based cookies allow the load balancer to take advantage of the already existing session cookies. And using these cookies, an application load balancer pins the client session to the same target throughout the entire session. Duration-based cookies are used in the case where the web application doesn't natively support a web cookie. And in this case, the load balancer will pass the cookie to the client and maintain that sticky session. So when you should use sticky sessions, you may want to enhance the user experience, because sticky sessions are going to ensure a smooth, uninterrupted user experience. And it's being really crucial for stateful interactions like shopping carts. It'll improve your efficiency. By consistently routing user requests to the same servers, a sticky session will optimize resource utilization, and that's going to enhance your application performance and scalability. It can also increase your security and your reliability. Because a sticky session provides encrypted stable connections, it's going to be crucial for secure error-free transactions. So let's talk about load balancers. Internal load balancers versus external load balancers. All right, so what do I mean by this? I'm going to draw this out because this is where a lot of people get confused on the difference between intranet and extranet. So this is the way a normal environment looks. let's say this is your secure data center. Now, this could be a physical building. It could be your VPC. It really doesn't matter. This is a secure data center. None of this is part of what I'm doing now as part of the AWS Solutions Architect Associate, but it's critical architecture knowledge. What do you want to allow in this secure data center? Absolutely nothing. No traffic from the outside world should be allowed in here unless you have to. And let's say this is going to be one subnet. Let's say this is an HR application. You don't want that exposed to the internet. And this could be a finance application. Ugh. This could be a finance application. There's going to be lots of applications that an organization have. If we have 5 HR servers, we'll just argue a couple over here. You know what we're going to need to load balance in between these servers internally? A load balancer. So we might have a load balancer in front of these things. Bear with me. Load balancer. This stuff is internal to our VPC. Same thing we'd have, let's say we only need one finance server. Out here, we're going to have some kind of a firewall type architecture. And this is not what it would look like. We'd need a lot of layers. But this is a firewall type architecture that we might have. Behind the firewall, we might have a network load balancer. Well, it wouldn't go behind the firewall. The firewall would be here, and the firewall will block all incoming traffic. So all incoming traffic is blocked at the firewall. Now we might take the firewall and create a subnet off of the firewall and pop a load balancer over here. Say a network load balancer, it doesn't matter. And then behind the load balancer, we might have some web servers. Web. So when you look at this, there should be no traffic that comes into here. Nothing should be coming in. So this load balancer is an internal load balancer because it's inside your organization. Now, we also have this firewall, which protects everything here. The firewall has a subnet, and the firewall says this subnet allows TCP port 443. Why TCP port 443? Because that's HTTPS traffic. So this is only going to allow 443 to DMZ load balancer. And that's all it's going to allow. So the firewall will allow port 443 traffic to this load balancer. The firewall will block everything coming into the systems. So this is an internet-facing load balancer. This is an internal load balancer. Okay, well, the next thing we're going to talk about is CloudFront, which is a rather lengthy topic. So, Chris, let's see if anybody has any questions right now. None yet? Okay, then we will cover CloudFront. Now, I might want to get all of you involved while we do CloudFront. In fact, I want to do it right now, and I want you to enter the information inside of your system. So I want all of you to open up a command prompt. On Windows, you type CMD. On a Mac, you open a terminal. On a Linux system, you open a terminal. And I want you to put the answer in the chat box. I want you to type up NSLOOKUP, NSLOOKUP, www.amazon.com. And I'm going to see if I can find a way to share my screen here. Because let me see if I can do this. Okay. Okay, can everybody see my window right now? Go to a command prompt and type NSLOOKUP www.amazon.com. Press enter. And I got this. If you do this on a Mac or a Linux machine, it's going to give you the actual CloudFront of Amazon.com. I'm using a Windows machine, and I've never used a Windows machine in my entire life. But if you will actually use your Linux or your Mac, or you type NS lookup www.amazon.com, at the bottom of it, you're going to get something that looks very funny. And that's going to let you know whether you're on CloudFront, whether you're on Akamai, or whether you're on actually, say, Fastly. So share in the chat box what you actually got, www. or NS lookup www.amazon.com. Tell me which content delivery network you actually have. Are you going to see Fastly? Are you going to see CloudFront? Or are you going to see Akamai? Let me know in the chat box what you're saying. And I know there's some latency between what I'm saying and you're saying. So I'm curious to see what you have to say in the chat box of what you're finding. You see Frontier, Adrian. Okay. Some of you others will see this as well. You see CloudFront. You see CloudFront. You see CloudFront as well. And interesting, I can share you mine now. Apparently, in order to get to do anything fancy in Windows, you've got to go to Windows PowerShell versus just the command prompt. So I'll share with you what I have. And there's a reason I want you to see this. Chris, hold on one second. Me share. And if you don't know what to do, let me show you what to look at. You can see, if you look up Amazon.com, you can see my DNS providers, which are Google. They're giving me this. This is the ugly name. And then this is the name. And what you're going to see is there'll be a CNAME record. And for example, you're also going to see this. This is Frontier. So why are you seeing some users on CloudFront and other users on Frontier? Why would you see this? Tell me in the chat box why not everybody that Amazon using is on CloudFront. And some of us are on CloudFront. Some of us will be on Fastly. Some of us are on Frontier. Some people may be on Akamai. So why? And keep sharing it in the chat box. Why is it that Amazon is using more than one cloud content delivery network? See Fastly. You're seeing lots of them. And here's the reason why. Because a single cloud is a single point of failure. A single content delivery network is a single point of failure. And the cloud provider themselves is not going to only use their own content delivery network. And, that's the difference between certification and a reality. In certification, they're only going to teach you the one. But when it matters in real business, they're going to be using multiple content delivery networks. So it's not who's got the best technology. It's what's the right technology for the business and how do we design these things for redundancy and scalability. That's what matters. So keep that in the back of your mind as we go through things. We try to give you the overall example of how businesses would do it for real, not just what would be done in, say, a certification. So now let's talk about CloudFront. CloudFront is the Amazon branded and Amazon owned content delivery network. And a content delivery network is a geographically distributed set of servers that's going to provide fast access to your internet content. Organizations use content delivery networks to reduce bandwidth costs, to reduce the load on their servers, to reduce the latency, and protect themselves from distributed denial of service attacks. So let's talk about content delivery networks. They can really help protect against a distributed denial of service attack. And we'll talk about how that works as well, because they won't send, and we'll talk about it more later, but they won't send illegitimate stuff to the servers. And we'll talk about DDoS and how it protects. They also can promote enhanced availability. And here's why. Let's say I've got a web server for a static website. The user actually requested the information. The information is cached on a CloudFront server. Now the website goes down for 5 minutes, but somebody requested the same website that was already in the cache. The cache answers, so it's there. So I kind of hope that makes sense. So CloudFront or any content delivery network will improve website hosting performance. And CloudFront is a combination of a network, a high-performance network that connects you to caching servers. So it's not just the servers. All those caching servers are completely worthless without a network behind them, because they wouldn't be able to reach each other. So it's a network and caching servers. And the way it's going to work is when a request is made, the location will be determined, and it will be sent to the closest CloudFront server or content delivery network server. And those servers will cache the content, and we'll walk you through examples. So the first request is going to get sent to the CloudFront caching server. If the caching server has it, it's called the cache hit. And the content delivery network will send it right back to the user, and life's good. CloudFront's a great content delivery network. I don't want you to think it isn't. It's a wonderful content delivery network, but if it's high availability, you're going to need more than one content delivery network. So if you hit the, say, CloudFront content delivery network, and your web information isn't stored on the content delivery network, the information will go to the source. The source will answer it, and the content delivery network will cache it for the next time. So that's the way this is going to work. So here's a situation that I'd love to show you. We've got a client, right? The client is going to a website. It's a static website that's hosted on an S3 bucket, an object storage bucket in AWS. Sends the request to CloudFront. CloudFront doesn't have it. It's called the cache miss. CloudFront sends the request to the S3 bucket. S3 bucket answers, sends the asset to CloudFront. Now another user on the bottom wants to go to get that website or that image or whatever it is, and CloudFront responds. So that's how it enhances scalability. That is a major help. Because let's say we got 1 million requests for the same page. Web server only responds once. Content delivery network does the rest of the responses. So CloudFront is a content delivery network, so it provides caching and website scalability. Caching can really offload something. I want to get you guys to imagine this. My wife, for some reason, has been wanting to go see Taylor Swift and watches Taylor Swift videos on YouTube all the time. Apparently, I know how popular Taylor Swift is. If Taylor Swift got a new cat and then tweeted the cat and posted the cat on Instagram and every other media channel in the world, imagine the web server that's going to host that photo of Taylor Swift's cat. Could get millions of requests globally for this cat, literally speaking, in minutes. But she tweets it. It goes on a server that gets requested. The content delivery network caches that information. And after the request from each content delivery network location, they all get to see photos of Taylor Swift's cache without the website responding. Think about how much that can help with scalability. So if we're talking about CloudFront, it's going to integrate with numerous AWS services, because you could have a website on S3 for static content. You could have dynamic content on virtual machines, say EC2 instances. You could actually want to use CloudFront in front end various load balancers, that kind of thing. And CloudFront is constantly used for web services because that's what it's designed for. So This is a common environment for a web server environment where you're going to have dynamic content that's going to be hosted on virtual machines, otherwise known as EC2 instance, and you'll have a load balancer in front of them. And you might have static content like videos or cat photos or whatever our product photos are sitting in an object storage bucket or S3. And that's how the systems will be cached. The source of it is considered an origin. So let's talk about some key concepts with CloudFront. There are three main components to understand. And they're going to constantly show up on an AWS exam. It's going to be the distribution, the origin, and cache control. We'll first talk about CloudFront distribution. When you set up CloudFront, you'll set up a distribution. Your distribution is going to be that weird looking ugly name that we talked about over there that you could actually see. So let me do this. I want to make it clear to you what this actually looks like, and then we'll talk about what we actually talked about today. So Chris, please share the Windows PowerShell right now for me. You see this ugly looking address over here where it's the two addresses you might see, that kind of thing? That's ugly looking, right? But that is going to be the CloudFront distribution name. So think about that. Who's going to remember this name? And who can remember this? Delta 3 Alpha Golf 4 Hotel Uniform Kilo 62 Yankee November.cloudfront.net. I'm not going to remember that, but I can remember www.amazon.com, and I go buy cat treats from them all the time. So, kind of think about that in the back of your mind. So if you don't want this and you want something pretty, was there a type of a record that we talked about when we talked about DNS? Yes, there is. It's going to be called the CNAME record. So what you can see is, or an alias record, you can map www.amazon.com to another one of these ugly content delivery network distribution names for Frontier. So hope that helped there. So that's what you'll fix. You'll create a CNAME record and an alias record to make something pretty to the CloudFront information, to the CloudFront distribution. Now you also have to set up a CloudFront origin. What's the origin? The origin is where the source of your content's coming from an S3 or an object storage bucket, an EC2 instance or a virtual machine, or an elastic load balancer, meaning a load balancer, or your website. And mind you, I will constantly try to go through the real terminology plus the AWS terminology, because if you understand the real technology, you'll know what to do on Azure, Google, Alibaba's cloud, Oracle's cloud, or what have you, because you'll understand the tech. And it's all pretty much the same. So when you're dealing with a cache, and a content delivery network has caching, you have to think about the control and the cache and your architectural options. So by default, CloudFront will cache data for 24 hours. Now this means if your system is cached at one of those edge locations on a server, and you change your website, somebody might not see your website for a whole 24 hours. Now, if your website doesn't change very often, and it changes once every 3 months, and nobody notices it and a new change for 24 hours, who cares? By having the cache at 24 hours, your web servers don't have to do a lot of work, because those caching servers remember it, and your web servers can be sleeping or napping half of the time. But if we change the cache to a small period of time, and we change the website 20 times a day, the users will see new changes, which is great. But every time that cache expires, all those new requests are going to have to go to the new server, and that means the servers are going to be much busier, working a lot harder. So it's the architectural trade-off. Do I want to reduce the load on my servers and use less servers? Okay, I can increase the TTL. If I change my thing frequently, I'm going to have to increase the load of my servers by decreasing the TTL, but my web page will be seen with every change we make. So hope that kind of makes sense to you all. So how does somebody set up a CloudFront? They set up web servers and they put content on them. Then they create their CloudFront distribution. AWS will give you that ugly name that I showed you. And then you either accept the ugly name or you create like an alias record or a CNAME record, and then AWS will provision your edge locations, and then you're going to have a good solution here. So if you'll recall, on the first day when we talked about AWS and how it's organized, we talked about a region being this large geographic area. And we talked about data centers being called data centers in this region, and data centers are called availability zones. I didn't make up, these are all marketing terms. And we talk about specific data centers, which are typically internet point of presences called edge locations. And that's where, that's exactly where your information is housed. So walk through another example of this with CloudFront. Let's say we've got 3 different edge locations in different major cities. In edge location 1, one of the users wanted to read, the article that I was in CIO magazine. And they went to our website, www.gocloudcareers, and they looked at some of the places that I've been in, places like Tech Republic and Tech Radar and DevOps Magazine and Data Center Magazine and Information Week and other magazines. So lots of people, maybe they went to our website to see it, which articles I wrote for which magazines. So user 1 goes to www.gocloudcareers.com, and they hit that edge location, and user 1 is over here. It gets sent to our cloud hosted systems, and it gets sent back to the edge location and back to the user. The next time somebody wants to go see that article from the same edge location, they go straight to the edge location, and the edge location sends it back. So it really can reduce the load, but that's not going to help the user sitting in Athens, Greece. So the user in Athens, Greece hits the cache and says, I want to see, Mike's articles. I wonder if Mike read any articles in Greek. And I speak Greek, I don't really write magazine articles in Greece. Not that I wouldn't. So the user in Athens goes to www.gocloudcareers.com, and it's not there. So it hits the local edge location and say Athens. And then it's going to hit the regional cache. Then it's going to go back to the source. The information is sent here, and it's over there. And then right after, let's say Nico in Greece went to the edge location, Nico texted his buddies, Aguilo, Costa, and a few other people. And then when Aguilo and Costa decide to hit that edge location and say Athens, Greece, they get sent the information without the web server. So that's kind of how these systems work. So understand that CloudFront or any content delivery network can have a massive impact on your website performance. Content is cached. Now, CloudFront has over 217 points of presence for these caching servers. That's pretty awesome. Pretty much most major cities in the world. And when CloudFront is used, what will happen is the request will go to the original source through the AWS backbone as opposed of necessarily the internet, so better connections. And CloudFront can have what's called persistent connections, and it'll maintain connections with the source. So, there's not going to be a need to start a new session every single time for every new web request. So it's a great content delivery network like many others. Now, on this content delivery network, like all content delivery networks, you can put a WAF firewall, a web application firewall, and some form of a DDoS protection. Amazon has their DDoS protection called Shield. Every other one has their own DDoS protection as well. But CloudFront can really do wonders to protect against DDoS attacks or any content delivery network, and that's one of the reasons organizations use it. How does a content delivery network help prevent a distributed denial of service attack? So here's what a distributed denial of service attack. We have how the hacker infects, say, 100 computers on the internet. And then he tends those 100 computers to go send as many requests as they can to you, to send more requests than you could potentially handle. That's a distributed denial of service attack. So let's say my web servers can handle 10,000 requests per second. And how the hacker sends 1 million requests per second. My web servers can't respond to legitimate traffic, and they're dead. They're just overburdened. Now, if I had auto scaling, perhaps we can add 10,000 new servers to deal with this hacking event until HAL infects another 100 servers sending requests, but that's neither here nor there. And that can help us mitigate it, but that's going to get real effective, although we could use it in terms of an emergency. But here's where content delivery networks like CloudFront come to the rescue. If how the hacker is sending invalid, illegitimate web requests to the server, which is very commonly done, the content delivery network's kind of smart. Let's look at those web requests. They don't belong. Let's just block them. And then the servers don't get overwhelmed. So it's one of the many things that content delivery networks do very well. Plus, CloudFront can provide encryption in transit of your data. CloudFront can enforce your SSL or your TLS protocols. CloudFront will integrate with the AWS certificate manager, so you can use certificates generated by AWS, because there's lots of certificate managers out there, or certificate authorities out there. And CloudFront, like most content delivery networks, will support server name identification and custom certificates. So you can also use CloudFront for private content. So lots of times you would be using CloudFront to serve a public website or an internet-facing website. But what if you only wanted to restrict access to a certain number of individuals? Maybe you've got a private application only for paying members or subscribers. You can do a couple of different things to allow certain people to access it. When you set up the origin access identity, which is where the stuff is coming from and let's say you have an S3 or an object storage bucket that actually is providing the website, you can restrict the S3 bucket to certain key individuals. So that way people that paid for your system can access it. You can also send a signed URL or a signed cookie to restrict access to a public content delivery network. So I kind of hope that helps. You can also do geo-restriction on a content delivery network. So what might that be? Geo-restriction is also known as geo-blocking, is a feature of the AWS content delivery network, and others do the same, that enforces delivery of your web content to clients in specific geographic regions. So why might you do this? It enables you to serve your content to people that are interested in your information and deny clients from uninterested environments. Now, let's say you provided a service that was not considered acceptable in certain parts of the world. You might want to geo-restrict those certain parts of the world so they don't blame you for your service or fine you or something like that. So every country has their own what's appropriate, what's not appropriate. I'm not here to judge the world. I take everything in context. Culture determines everything. But geo-description or just blocking may keep you from getting legally in trouble if your content is accessed in the wrong parts of the world. So what's an example of this? So here's an example. You let someone access the information because they're allowed. Maybe someone in this particular case from Egypt wants to go to a server in France and they're allowed. Or maybe in this particular case, you don't want a user coming from Egypt to a web server in France and you can block it. Egypt's a beautiful place. I don't know if you've ever been there, had lots of times there. It's really, really great. But this is just a particular example of different countries with different laws that may or may not allow certain things. So just an option to think about. And it's just a country picked at random. So how does geo-restriction work? Well, what happens is there's a database of IP addresses that are associated with each region and country. And for example, if you were to whitelist only Germany and a user from the United States tried to access it and only Germans were allowed in German websites and people from the country of Germany were allowed, they'd be blocked. And by default, when you're going to get a user that's denied access, CloudFront will give you one of the 400 codes and it'll say 403, which typically means forbidden. Geolisting either works via whitelisting or blacklisting countries. Whitelisting means allow, blacklisting means block or deny. And it can be implemented to deny access to only specific content or certain subfiles because certain things could be allowed and not allowed based upon where you're going. So in order to implement geo-restriction, you will need to use some form of a third-party restriction service and integrate them with the CloudFront. So you may remember proxy servers where there was a service that would say you can't go access this, but it was a specific company that proxy servers would connect to. Same kind of thing. So why would you use geo-restriction? Legal compliance. And make sure that your content is going to adhere to legal rules. And also licensing agreements maybe as well. Security enhancements. If certain people are never going to buy your stuff, and you know that, why would you not only reduce the load on your server, but allow yourself to be seen by those that aren't going to buy your stuff or access your content or need your content or use your services? Because when it comes to security, use the principle of least privilege. Don't give access to something if they don't need it. So that's going to be from a security posture perspective. Content localization as well. Oh, that's another one. Deliver region-specific content for better audience relevance. Let's say you're in the Middle East. There's a lot of languages that are spoken, okay? And I spent lots of good time over there. Some countries speak Farsi. Other countries speak Arabic. Other countries speak other languages. But I got to tell you, if I go to a website and I can't understand it, it's going to be hard for me to be comfortable. But if I get the one that I can read, that's another thing. So that's another reason you might want to use geo-restriction. So that actually brings us to about 5 p.m. So let me open it up for questions. See how you're doing. Are you all having fun? I know I'm having fun. I love teaching. And let's see if you have any questions. How do you determine the cost of CloudFront compared to other services? You call all these cloud providers, you negotiate with them, you negotiate with all your other CDN providers, and then you determine the costs. Just like anything else. You go to 3 car dealerships to figure out who's going to give you the best price on the car. And when it comes to dealing with multiple service providers, well, this service provider is giving me this, and what are you willing to do? So I hope that helps. Pick up your phone and call the sales reps. Welcome, everyone. This is Michael Gibbs, and we are back for day 3 of our AWS Certified Solutions Architect Associate 2024 program to help you pass the AWS Solution Architect certification. And this is an AWS full course tutorial, and this is our summer version of our free certification course training online. So we're here again, and I'm excited to be here, and I'm thrilled to see all of you. So tell me where you're from. Let us know in the chat box. I am in South Florida today, and I'm enjoying the very hot weather that we're getting this summer. Went outside this morning, and it was so sunny. It was kind of nice. So let me know where you're at. Before we begin, I want to remind everyone that, we're going to be focusing 10 days, 3 hours plus each day to cover the AWS Solution Architect Associate Certification with TLR, and we're going much deeper. We'll get into many of the things from the AWS security certification. We've been covering some of the things already from the AWS Advanced Networking certification. We have some new AI machine learning things in there because they're going to become more and more important. So we'll be talking about them as well. And, we do have over 40 labs for you to get hands-on, and I want you to get hands-on. So please sign up and register for the free labs and go do them when you have a chance. So I definitely want you to get that. And I also wrote a certification guide. It's an ebook that our team and I wrote on certifications that will help you in your career, especially if your goal is to be a cloud architect or a solutions architect. I have to tell you, I see some resumes sometimes and they're terrifying to me because people worked so hard to get certified and they learned 14 different people's careers, but they never learned their own. And it's kind of sad because it's hard for them to get to their goals. So I want you to go and know what to learn and when to learn it. So go get that certification guide. Let me see where you're all from in the chat box. I'm seeing San Antonio, Texas. I've spent some time there. Austin, Texas. Fantastic. Nigeria. Love that. We've got lots of wonderful folks from Nigeria, most likely here as well. We have people from Calgary. I did a lot of work in Calgary with, was it TELUS many years ago? India. We have lots of people there. Adrian Griffith, you're in Barbados. That's about as beautiful as it gets. That's a great place to be. I haven't been to Barbados in a while, but I always loved it. George in Miami. We're probably pretty close. I'm curious where you're actually at. I used to spend a lot of time in Southwest Miami by FIU many years ago in my youth. Really great place. Tend to love it around there. Let's see where else you are all from. Phoenix, Arizona for Adrian. Fantastic. Bo Fa in Bo, Cameroon. Fantastic. We have Eddie who works for us in Cameroon. Anna Marie in Argentina. Haven't been there in a while. And Aussie in the UK. Fantastic. I used to actually go there almost every week for work. And Dover, Delaware. That's an area I know real well. I actually did 2 master's degrees at Widener University just over the line in Pennsylvania in Delaware County. So spent lots of time in Dover, Delaware as well. Alvi in Karachi, Pakistan. That's fantastic. Always wanted to go there. Never managed to get to Karachi for some reason. Work just never got me there. I have to fix that somewhere along the line. And yes, and Sacramento for Preb. It's so good to see you out there. And Miguel in Miami. Well, we should start some Miami contingent here. And Samuel in Lagos, Nigeria. That's wonderful. Batu in Boston. And Satya in Philadelphia. My wife is actually in Philadelphia. We keep a house in near Nazareth Hospital because a lot of times we go visit our family there. And Rick over there in Tunisia. Wow, that's really fantastic. Hey, I love this. I love when we get so many people to come together from all over the world. And that's the whole point of doing this, to build a community, helping people get to their goals. I see Mexico. I haven't been to Mexico in a couple of years, but that's fantastic. So please give me a hashtag AWS so I know you're awake, alert, and oriented. And then we're going to begin. We have an ambitious agenda. We're going to go for 10 days straight. And after that, we'll probably do some, free hands-on mentoring sessions with you as well, because we want you to get a really great experience here and learn as much as you can. So we'll go for approximately 20 minutes, 30 minutes. We'll stop for about 10 minutes of questions. The goal is to do 20 minutes of questions an hour if you have them. So we will begin as soon as I see those hashtags AWS popping in. I see the first one from George. Thank you so much. And Adrian, wonderful. Now I'm seeing them coming in. Lots of my hashtags AWS. So I know you're awake. Ebenezer, so good to see you in New York City today. And Tundi, fantastic, Rick. So, okay, I will get back to the content now. So welcome, everyone. So we're going to begin by discussing Global Accelerator. And Global Accelerator is an AWS service that improves the performance for customers regardless of where their location is. And what it does is it tries to get you to move traffic over the AWS global network, as opposed to taking longer to the internet to get there. If you'll recall, I said on the first day that internet bandwidth is not guaranteed. What happens when you send your traffic to the internet is, let's say you leave AT&T and your website is in, say that you're going to is in Japan. So AT&T may connect to British Telecom, and British Telecom may connect to Vodafone, and Vodafone may connect to NTT in Japan. So you could literally go for 4 or 5 or even 10 or 15 internet service providers to get to your end destination. And while your internet service provider has to guarantee you what you get to them, it doesn't have to guarantee that through their network or even on any other network. So if you're on the internet, you're not going to get the same kind of performance you would get as if you were on a private network. So that's why organizations build their private intranets. That's why they get things like direct connections versus a VPN, because they need guaranteed performance. So what's really going on with Global Accelerator? And there are really 2 types of acceleration. There's going to be standard acceleration. We'll talk about what this is in a minute. And that's going to make your application available and work well for users that are going to be globally. And what it'll do is it'll send traffic to the newest region. And where does it actually send the traffic to? It typically speaking sends the traffic to the nearest edge location. And what is an edge location? It's an internet point of presence where you've got your content delivery network and all your internet service providers are in the same building. So hopefully that makes sense. And now we're going to talk about a custom routing accelerator. And here's where you choose where to send your client traffic. For example, maybe you want to know which server to send your traffic to amongst various options. So how does this work? Well, AWS is going to have 110 points of presence across 50 countries. An internet point of presence is basically where you've got 50 internet service providers that all bring high-speed connections into a building. And they put their switches in the building. And then when you want to connect from, say, AT&T Verizon, because they're all in the same building. All that's necessary is to run a fiber optic cable between the two provider switches. So by putting all your internet service providers in a single building, they can connect to each other's switches via something called the cross connect. And that way, they don't have to have connections everywhere. You just connect to these 100 locations. Every internet service provider, for the most part, goes into these 100 locations or much like that. And then poof, you just run cables between them. So I kind of hope that makes sense. So the way that's where you're going to be coming into. So when you use AWS Global Accelerator, you're actually going to advertise 2 public IP addresses and 4 if you're going to use IPv6. We'll talk about more how this is going to work. So how's all this stuff work? So ultimately what happens is the IP addresses from these edge locations are going to be advertised into the global BGP routing table. And then it's going to use Anycast to find the closest locations. So each client will reach its normal edge location by its IP address. Now, Anycast gets people all kinds of confused. I talked a little about Anycast a little bit when I was describing DNS, but Anycast is used in a lot of different things. So we might as well actually what kind of whiteboard this out. I really want you guys to really understand this. So first, let's talk about what an internet point of presence actually is. And I can show you what this is. Because without this knowledge, like unless you were a network engineer, it's just going to be hard to understand. So let's say this is your internet point of presence. And what'll happen is you'll see a router coming in over here. And let's say this could be NTT. It's a fantastic phone company that's in Japan. This could be Telefonica in Spain. Another great, what do you call it, internet service provider. In the US, we have, say, AT&T. We have, say, Verizon. And what happens is all these internet service providers and more, they have wide area connections that go back to their own networks. They connect to, obviously, routers on their domain. So you've got all these devices that are sitting in here. And when you want to connect 2 of these devices, because they're all in the same building, it's going to be the coolest thing ever. All you have to do is you just run a cable in between these things, and that's your cross connect. Want to connect AT&T to Verizon? No big deal. And that way, systems from the Verizon network can connect to the AT&T network. You got a cross connect. Want to actually connect Verizon over to Telefonica in Spain, which is coming out of Spain? No big deal. You had a cross connect. And this is what these kind of environments are going to look like. There's going to be lots of internet service providers. Now, it may not just be a wire. They may bundle multiple wires in a link aggregation group. And we talked about link aggregation groups. And obviously, of course, they're also going to be, well, it's not going to go well. But the point, they're also going to be coming like this. But the point is that everybody's going to be connected to anybody that actually has a cross-connect agreement. And that's how these buildings actually are internet point of presences tend to work. So now that you understand that, that's where these internet point of presence comes. Let's actually talk about, the way this Anycast is actually going to work. So let's say with Anycast, we advertise an address. And the address we're going to advertise is 1.2.3. Actually, let's not use a public address. That could actually be used. This is a 10.1.1.1. We're going to use a private address for this so we don't accidentally publish somebody's public address. So, and this is really where you're going to jump onto the AWS network. So let's say you're going to have this that'll be advertised by the Global Accelerator. You'll also have another one of these on the Global Accelerator. And in between this stuff, you're going to have actually, let's move this over a little more. And in between these systems, you've got the internet. So what'll happen is you're going to have your this is your user, and user's going to have this same IP address in two different places. The user will not see both places. The user will go to the router, and the local router will determine which one to get to. So that based on whatever BGP is telling this router over here, this router will know whether to go here or whether they should go here. Now, if this were to just disappear, goodbye. That wasn't supposed to happen. If this thing was to just disappear and it went away, the router would see the route in the routing table to this. So realistically speaking, this is what's going to be going on. But let's add a little more for you to really truly get this. And then what'll happen is once it jumps onto AWS, AWS is going to have their own routers. And they're going to have their own routers, which are going to have then their own links, which are going to go back to their own network. But the point is, this is the private network back here. And all this stuff out here is the internet. So that's how the background of this internet routing is really going to be running. So you can also look and see where these points of presence are. You can see they've got them for the most part in most major cities or most places that you need to be. So you'll post an address, and this address could be advertised all over the world. And if you're in Sydney, you'll pick up the location that's in Sydney. If you're in Argentina, you'll pick up the one that's in Argentina, or vice versa. And if that's not there, you'll go to the next closest one, because that's the way Anycast works. It's a way to provide better internet routing and high availability at the same time. So what'll happen, the client's going to reach the edge location, and AWS Global Accelerator will use your load balancing setup that's going to send your traffic to one of your resources. And that could be a load balancer or a virtual machine, but it's going to use that private network that I wanted you to see. That kind of stuff's not even talked about in the certification, but if you don't understand it, you won't be able to understand how it works. So I wanted to kind of cover that for you. And your traffic is going to be directed based upon the kind of accelerator used. So with the standard accelerator, you can improve the availability of your internet applications that are going to be used by a global audience, because you've got lots of places to jump on, and you've got that multiple endpoints with the same IP address. With the standard accelerator, with standard accelerator, global accelerator will direct your traffic over the AWS network to endpoints in the region that's nearest to your clients. But the traffic is going to be based upon the accelerator you use. If you use the custom routing accelerator, it allows you to choose your own application logic. So you can route to either multiple users, a specific virtual machine, or an EC2 instance, and you still get the benefits of Global Accelerator. So when you need custom routing, it's going to be perfect for applications that are going to require consistent servers. Online games are an example where you'd want to be on the same server each time. And so why would you use Global Accelerator? Well, because it's connecting you directly to the AWS network through the internet at the closest point of presence. And because it's going to use its private network, once you reach that point of presence, it's going to give you better performance. It's going to give you lots of flexibility, and it'll give you the ability to maybe load balance your systems via Anycast, where it's actually sending users based upon the part of the world to a different location. So I hope that answers the question about Global Accelerator. Now, let's start talking about storage. If we're going to have a cloud, we need obviously the network, because the cloud won't work without the network. We're going to need compute, something to do the work, and we're also going to need storage. So let's talk about storage. So we'll begin with, what is storage? Storage is where the data is. And there's going to be two kinds of storage that we need to talk about. There's volatile storage. If the DRAM in your computer is volatile, and what do we mean by that? When you shut your computer off, whatever's in the DRAM is no longer there. But when we deal with cloud providers, The storage on the virtual machine itself, that instant storage that it comes with, is both very fast compared to block storage, but that's neither here nor there, but it is ephemeral or it is volatile. So you create a virtual machine or an EC2 instance. You delete that virtual machine, all the storage is gone. And there's lots of times where you may want to delete a server, but not lose all its data. So we have to use some form of non-volatile storage. Non-volatile storage, for example, is your hard drive. Now, it can be slow or like a slow magnetic drive. It could be medium speed like a standard SSD. It could be high speed storage like an NVMe SSD drive. But whatever the case is, storage is either going to be volatile or non-volatile. Now, when it comes to non-volatile storage that we're going to use in the cloud, guess what? It's the same three types of storage we've used for 30 to 50 years. Block storage, object storage, and file storage. This is nothing new. The names are going to change with the cloud provider, but it's standard data center storage. So we'll begin. What is block storage? So block storage is a type of network-based storage. So first, it's accessed over a network. So when we talk about block storage, it's accessed over a network. This is very important to know. If your network speed is 1 gig, you can't get faster than 1 gig on block storage because it's not in the server, it's accessed over a network. Now, what happens is you take the data, and the data comes in, and it gets broken down into blocks. And each block is going to have its own unique block identifier. And the blocks will be placed anywhere on the network, wherever it's most efficient. So I want you to think about this. And why do organizations like cloud providers love block storage? If we can take the storage out of the server or decouple the storage from the server, and we can store it anywhere we feel like on our network, we can scale. Because now the servers are no longer limited by the number of hard drives you put in them. Hard drives are somewhere else. And what these storage area networks look like, they're going to see these giant boxes filled with hard drives with RAID arrays, and we'll talk about RAID. And there's all these servers in there. So you need more storage. What do? You add another machine, plug it into the network, and you've got more storage. So it's incredibly scalable. So that's why I've been using block storage in the data center for about 20 years. And that's why when we go to a virtual data center like the cloud, they're going to be using block storage. So keep that in the back of your mind. Take data broken down in blocks, and it's stored that way. So the next type of storage we talk about is object storage. So let's say, object storage is another type of storage area network, but it's a little different. With object storage, we take our data and it gets broken down into an object. Now, when the object is stored, it's kind of just dumped into this environment. But what happens is when the storage is just dumped into there and it's got an object unique identifier, there's something that's very database-like that says, Mike's picture, Cindy.jpg, is in this location, in this storage environment, this register, what have you. So it's very database-like. So when you look at object storage, even if we make folders and things like that, and it looks real, then we have to understand that it's going to be an object, and it's not going to have any hierarchy. It's going to be flat, and it's very database-like. What makes object storage so special is the metadata. So what is metadata? Metadata is data about data. So when we're dealing with object storage, and we have an object that's got an identifier, and then we've got something that tells us what's actually in that object, now we've got lots of options because we can query that data, metadata, we can search it. We can look into an object and say, I only need this 10% of the data, and reduce the load on the network, for example. At the same time, we can put in a big data environment, and because we have data about the data, when we catalog that data later, all kinds of things, it gets really good. But you have to remember, object storage isn't normal storage. You're not going to mount it as a hard drive on one of your virtual machines or EC2 instances. It is different storage. It's what you call worm storage, which is write once, read many times. And here's the reason. In traditional object storage, and AWS and the cloud providers will try to modify that to make it feel more like normal storage for you. Every time you take an object, it'll be modified. So, and create a new version. So if anything just changes even a fraction, we'll create a new version. So why is this such a big deal? Well, let's say you've got a server and the server's got, 256 cores and 8 terabytes of DRAM. If you're going to use that server with, say, Red Hat or any other operating system, but it's a business, you probably use Red Hat a lot of the time. And you actually look at it. If you've got 8 terabytes of physical DRAM, you're going to have a 12 terabyte swap file. And a swap file is virtual memory. And what happens is if your system runs out of DRAM, it writes to the hard drive. So if you've got a server with a 12 terabyte swap file, and that swap file changes 50,000 times in a minute, you will have 50,000 12 terabyte objects. And you just paid millions of dollars in storage for less than 1 day's work, not an hour's work. So think about that. So object storage, and we'll talk about it, is used for software distribution, backup and archival purposes, and big data because of its metadata. So the other typical type of storage that we have is file storage. So file storage is traditional storage. The hard drive in your computer is traditional storage. It uses a normal file system like NTFS that Windows would use, for example. Can be mounted by any kind of device. Can be over a network, for example, with an NFS file share for, say, a Linux system or a Unix system, or a server message block share on a Windows system. Of course, you could use a Linux system to serve Windows by using Samba, which is basically SMB on Linux, but that's there. And you're going to see it's going to be hierarchical. You may have a folder that says root, and then you've got a folder that says homes. And under homes, you've got one that says mgibbs. So kind of keep that in the back of your mind. So now let's talk about the AWS versions of the storage. Why did I teach you this? Because if you don't know storage, you can't work anywhere. And more importantly, everybody's multi-cloud, 98% of the people. So if you know block storage, object storage, and file storage, it's the same thing on any cloud. It's kind of like getting your eggs at, say, Aldi versus Publix versus Albertsons. Just eggs, just in a different store. Maybe they have different names for it. So let's talk about object storage on AWS. And that is going to be called Amazon Simple Storage, otherwise known as S3. What is it? It's object storage. And it's going to be integrated in many AWS services. It's considered high availability storage. They'll tell you 4 nines availability. That means 99.99% of the time you'll be able to access it. What that means is about 52 minutes of the year you won't be able to. And that's, okay for most purposes. What is really cool about S3 is the durability. And, all the cloud providers have high durability. What is durability versus availability? Availability is having access to it when you need it. Durability is, will I be able to get my data back if anything happens? So let's say the Amazon cloud goes down. When it comes back, you should still have access to all your data. So, they talk about 11 nines durability of the data, and that means that it's 99.999999999. I think that was 9 nines past the decimal point. It's hard to do these live. So, and any kind of notification you'll get on Amazon S3 will be via Eventbridge, which for the most part is the old CloudWatch. So, where would you use S3? Backup and archival for your organization's data. Maybe you're sending your data to the cloud before you put it onto your systems. You've got a static website that's not going to change. It's a beautiful place to put it in an object storage, otherwise known as S3 for AWS. You want to distribute video or media or software. Object storage is the way to go. It's good for disaster recovery planning because you're storing images of, say, virtual servers and things in it. And it's good for big data analytics because of that metadata. So Amazon S3, when you set it up, you organize it into buckets. The buckets are just for us in our head. There's no such thing as folders in object storage, but it's for us. Now, each bucket that we create is basically going to be a container for, say, files that'll be stored as objects on S3. And when we deal with this, the buckets are going to have a top-level domain name space, meaning they must be globally unique and can be accessed by their DNS name. This is another reason for, object storage. It gets a fully qualified domain name. And because of that fully qualified domain name, it's very easy to just use as a website or click this and the person will download it via standard web browser. So when you create your bucket names, they can have up to 63 characters in length, and that could be including letters, numbers, hyphens, and periods. It's noteworthy that the path you use to access the files on an S3 isn't necessarily where the files are going to be stored. That old buckets and those little folder things you're creating, those delimiters, that's for us in our minds. It's not related to object storage. Object storage just dumps it into storage and puts a database-like pointer to it. So, and really when we access a URL, our file is really a pointer where the database is actually stored. So you can almost think of object storage as like a huge database. And that's why in certain circumstances, you can run SQL queries on the data in your object storage. So remember, it is not like traditional storage. It's organized like a database. Now, you can create any kind of delimiter you want. And by doing so, it feels normal. So, here's a fake folder that I don't have it on S3, but I'll pop it into the chat box so you can see what it looks like. I could create something like this, and that's going to look and feel like a standard Unix directory, and it's in the chat box. I just dropped it in there. But so let's say I made a video s3.mp4, but it's not really there. That's for me to be able to reach it, but it's in that whole dumping ground where they just throw everything there and have a database pointer to it. So we're going to talk a lot more about S3, but at least we introduced block storage, object storage, file storage. We gave you a little info on S3. Let's see if there's any questions. And if there are, we'll answer some questions. And then we'll get back to the fun. I love teaching. So to me, this kind of stuff is fun. Chris, let's see if anyone has any questions. While I wait for Chris to pop them up, I wanted to ask you that if you're having a good time, if you can hit the like button, subscribe to the channel, and hit the bell to be notified of others. Please tell other people about this YouTube channel and this training because, we spend a lot of time, effort, and money putting these together, and we want as many people all over the world to access this free training. And look at the first one. How do you hide master and schema credentials while architect developers are creating an application stack via IAC? So, we're not talking about Terraform today in any way, shape, or form. That would be something else. And Terraform is not an architect thing, but I can give you some basic information. To hide, master and schema credentials while creating an application stack via infrastructure as code with Terraform, you can do the following. Under environmental variables, you can store sensitive information in environmental variables and reference them in your Terraform configuration. There's also the Terraform Vault. And HashiCorp has a vault to securely store and where you can store and access your secrets. You can also store them in the AWS Secrets Manager. And, those are some ways that you could do it. But, make sure you're using IAM roles and policies to grant Terraform its necessary permissions. How to design and play a PC game? Well, that's going to take a collaboration. So first we need to know what the game is. Then we need to know what the goals of the game are. It will take someone like me that's a cloud architect to basically put a team together. And I would bring in some application architects and ask them how they would design the application. I would bring in some good data architects and database architects to try to determine where we need to keep the data, what kinds of databases will scale and their recommendants for scaling and performing it. Then we're going to bring in a network architect to make sure that we have the networking that has the latency that it needs to be. Beyond that, we might be mining that data and we want to mine that data to make some business recommendations and new sales to our clients. Plus, we may want to use some machine learning on that. So that means we're going to be bringing in some AI architects, and we'll also be bringing in some data scientists, for example, to come look at this. And then we're going to, obviously get the client's recommendations, the client's goals, get our architects together. And in about 3 to 6 months, you'll have an actual architecture that could make something like that happen. And then it's a matter of setting up the governance structure, setting up the statement of work, determining what type of people you need to have to both deploy these systems and then manage these systems after the fact. Then it's getting the key stakeholders to make sure they're going to support it. Then it's about finding the budget for it, creating the budget, and or bringing in investors as needed. That probably means building a small scale proof of concept and proving that there's something worth. So it's going to be something big like that. So, that's the kind of thing I would teach the students in our cloud architect career development program or enterprise architect career development program. But you have to understand, not only is that a training program where we take people in and they can stay on the program until they're hired, it's at least 900 hours of training. So you're asking a question that would take the next 2 weeks to answer. So I appreciate the question though. And we could teach you how to do that in our architecture programs. Can 100 EC2 instances be merged into a single instance? Well, yeah, it depends on what they are. So they have like these little micro T instances that have less than one core. And let's say you have them on the AWS. I think they call them I-3 instances. They're the ones they call general purpose compute, and they run the Intel Xeon E5-2670 V3 73 or something like that, V3s. Well, let's say we had 48 instances on that one per virtual core, because those systems, let's say, have 24 physical cores. And then we have another one that's got another 48 virtual machines on it. Heck, let's add another one that's got another 48 virtual machines. We can easily take every single one of those virtual machines and move it to one of the new AMD EPYC servers. And we could probably put, about 300 or 400 little one-core servers on that single virtual machine. But again, we have to analyze the use case. Are we better off with a whole bunch of little mini servers and a load balancer? Is it cheaper for us to use 500 mini servers and load balancers than it is one big server? If we use a single big server versus having 200 of them, now we've created a single point of failure. So what is it we're really doing? So anytime we get into compute, and we're going to talk about compute tomorrow, but anytime we get into compute, we have to determine, is it a single threaded application? Is it a multi-threaded application? Does the application do better with higher frequencies or more cores? And, it's not just the frequency and the clock rate. There are certain applications that do better on different processors. So we really have to take our applications, know what they need to be, and then test their performance on various systems, because everything looks good in marketing documents. I have a firewall that's supposed to do 1 gigabit stateful throughput, and it does. And then I turn on any of the advanced security features, and it goes down to 80 megabits per second of stateful throughput. But the brochure says, gigabit per second. And that's pretty normal. So that's why you're going to have to test any application on multiple processors to determine, and memory types of memory to determine where you're really going to put them long term. But yes, you can do it. What is called invisible storage? So invisible storage is a made up word. I don't recommend you using it ever. I recommend that using standard terminology, and that's how you avoid errors. And for example, I had a student one day that actually got a job, and he said, "Mike, I got a job. How much money should I ask for?" And I said, "What's it about?" And he said, "VM." And I said, "You mean working on virtual machines? Do you mean working on voicemail systems? Or do you mean vulnerability management?" And he started laughing and saying it was vulnerability management. So if you use standard terms. So what is invisible storage? It's basically ephemeral storage, meaning storage that goes away, or the storage that's sitting on your virtual machine itself. But once you get into jargon and you get into slang, you really can confuse a whole lot of people. So I just recommend calling it either instant storage or ephemeral storage, which are the two industry standard terms, and you'll be in good shape. What types of data storage are there for the 3 storage type? We have object storage, which if you're on AWS will be called S3. If you're on Microsoft, it'll be called Blob. And if you're on Google, it'll be called cloud storage. The next type of storage we have is block storage. So AWS calls it elastic block storage because they like to stick the word elastic in front of everything. Azure calls it, say, a managed disk. And file storage, which we'll get into soon, is really for basically where you store things on a hard drive or a folder. So what do you store on what? Well, on a server, let's say you were going to run on a physical server itself, or you actually got a bare metal server and you wanted to run everything on the bare metal, most likely you're going to run the hypervisor on file storage because that's what's going to be in your server. If you wanted to have a high performance Linux system, and for example, and you had a super low latency application for a bank where a nanosecond of latency could equal $50 million a year, so you're trying to scrape those nanoseconds together, you wouldn't use a virtualized environment. You'd put your operating system directly on the hardware because that can give you about a 5 to 10% boost. So in that situation, you could be storing your databases directly on the file server. So anytime you want to store directly in the server with file storage, you can store anything. Now, block storage. What is block storage? Block storage is network attached storage, which we're going to talk a lot more about. But it looks and feels like file storage to a server. It's not. It's a virtual hard drive that's sitting, someplace else. But to the server, it feels like file storage. So you can use that. You can put anything on block storage. Now, I want you to remember this. Block storage is going to be slow. And they'll talk about it being fast, but it's relatively slow compared to other storage options. But it's not in the system. So the system thinks it's a hard drive. So where do you use block storage in the cloud? You use it anytime you want information on a virtual machine that isn't going to go away when you delete the system. So if you have a database, you will use block storage. If you have a web server, you'll use block storage. If you have an HR application, it'll be sitting on a virtual machine running block storage. So block storage is for is a virtual hard drive, so you'll mount it to your virtual machines. You can mount it to your containers as well. Now, when we get into file storage, I initially talked about the file storage that's inside of your system. But file storage could also be over a network. So if you had 50 servers that wanted to access the same information at the same time, that'll be file storage. If they're Linux systems, it'll be NFS, or the AWS branded version of NFS, which is EFS. Now, object storage, that's the last type of storage. What do we put there? I want to back up my data, I stick it on object storage. I want to create an image of my virtual machines, I stick it on object storage. I make a video of Cindy the cat, I store it on object storage, and I send the link to that video of Cindy the cat to all my friends. Object storage, like Google Drive, which you may use, or Microsoft's, what do they call that? The drive that comes with Windows, that comes with Office, that type of a drive as well. That's all kind of object storage. So you might also put a static website on object storage. So I think I give you a little more than you asked for, but I wanted to make sure you got it. Can data be both block and object storage? You can store your data on block storage, object storage, and file storage. Basically, your block storage would be what your hard drive would use. You might put it in file storage and share it with many other systems at the same time. And object storage is where you'd back it up. But you got to remember, the servers are not going to use object storage. They're going to use block storage. Where servers are going to use file storage that are sitting inside them. But no, you can have all three up in the same time, but with different purposes and different applications. It's not going to be attached to the system. Difference between S3 and EBS and RDS. Okay, S3, object storage. EBS, block storage. RDS is a database. a relational database system. So don't mix the two together. In one case, you've got storage, and in another case, you've got applications. We'll cover databases and database management systems like RDS when we cover the database information. And we actually haven't covered EBS yet either, but we will. Okay, so actually, before we begin, give me a hashtag, AWS Solution Architect Associate. Give me a hashtag that, and that way I know you're awake and I will get back to teaching. Have to make sure you're not sleeping. Okay, so now let's talk about some S3 storage tiers. When you store your information on S3, there's a couple ways you can actually do it. So object storage is object storage, but AWS can market object storage in multiple different ways, and they can give you different levels of access to your information. So that's really what storage classes are. You'll have the opportunity to have reduced availability of your storage if you wanted that for cheaper prices. You'll have the ability to store it in a location where it might take you a half a day to get access to the information if you wanted to get a cheaper price, or you'll be able to store it where you can get access to it anytime you feel like it. So when do you choose which? When you understand your organization's data patterns, capacity planning, understanding your systems is truly, truly critical. So, and it's OneDrive. That's right, Brian. Thank you for object storage on with the Windows system. So, let's talk about standard S3. Standard S3 is going to be Amazon's high availability performance, meaning 99.99% available, meaning it should be up except for 50 minutes of downtime per year. High durability, meaning your data shouldn't get lost. We'll call it high performance. Although no cloud storage is high performance for the most part, except for Lustre. And it's going to be used for standard for frequently accessed data, meaning you're going to use your data, you're going to pull it back. And why is that? It's designed for data that you're going to use frequently. So let's say you're a magazine and you've published an article, right? And an article is stored on object storage for some reason because it's like lots of graphics on it. For a period of 30 days, everybody's going to look at that video, for example, right? And the article, and they're going to read it a lot. So you want it in an area where you can get it anytime you want. But maybe 90 days later, nobody accesses that data, or when they access it, it's occasionally. So you want to pay less to store your data and pay each time they access. And then maybe there's a point where that data is never going to be seen, but we have to archive it for legal purposes. So we'll stick it in some cheap archive, and if we need it, we'll pay to get it. So understand that's why they have these storage tiers. So we first talked about the normal storage tier. You store it, you pay one price, and you can access it anytime you want. The next phase down is going to be something called Amazon S3 infrequent access. It's got good availability, same as S3, the standard, just as durable. Your data won't be lost. Performance will be the same, and you get a cheaper price to store your data. But when you want your data, you have to pay to receive it. It's instantly available, but you have to pay. So we started at the top, standard with the highest pay, and but you can access it anytime you want without no cost. This was infrequent access, where you pay less to store it, but you pay to retrieve your data. So you're going to use that in a pattern where you don't need your data as often. Now, the next type of storage that's going to be a little cheaper, and this is going to be Amazon S3 infrequent access one zone. So what's that? It's infrequent access, meaning you're going to pay for retrieval. You're going to get a lower price to put it there. But it's going to be in one data center versus two data centers. And because of that, your data is less likely to be available when you need it. It'll have reduced availability. So if you might not need access immediately to your data, and you're looking for a cheaper price, with this S3 infrequent access option, both you get a really cheap price to store your data, you get a reduced price because it's not always as available, and then you pay to retrieve your data. So again, you don't use this with data that you need a lot. And the next is going to be S3 intelligent tiering. And this is where AWS is going to monitor your data, and they're going to try to auto move you to what it thinks is the most cost optimized platform. But you're asking somebody else to put you in the lowest cost pricing. Not sure that that's necessarily the best way to do it. You really want to plan your finances and manage yourself. To VJ, who just asked the question, you need to know these? Yes. There's almost no architecture on the Solution Architect Associate certification, but there's a lot of product questions on, what's this versus what's this versus this. So we're going into that product detail here. And then otherwise, we're going to actually talk about technology as well. So we've covered the 3 forms of infrequent access and the automatic version for you. The next type of S3 is something called Amazon S3 Glacier Flexible. And this is, and basically this is designed for data archival purposes. You can get something called the vault lock to make it immutable. And what's immutable mean? It means it can't be changed. So you're a bank or a hospital, and you have to store your records for 7 years, and no one can change these records for some years. You can store it on Amazon S3 Glacier and set up the immutable, and then no one can change it. So when the government or the Joint Commission on Healthcare tries to investigate you, or the SEC when they do their normal audits of hospitals, or SEC does audits of businesses periodically, or those kinds of things, you can just hand them your data. So can you keep that in the back of your mind? Hospitals get audited all the time by a Joint Commission of Hospital Accreditors to make sure that hospitals keep their accreditation. So they need these kind of forms. So with Glacier Flexible, which is the old traditional Glacier, it's designed to make sense financially if you're going to access some of your data 1 to 2 times per year. Your data can be retrieved in minutes to hours when needed. So with S3, you can get it anytime you want, and you don't need to pay for it. Here, you can get it in minutes to hours. So it's not going to be instantly there. So if you need it for business purposes, it's critical. No, you don't have to worry about it. So there is another form of S3, and it's called S3 Glacier Instant Retrieval. And this is going to be for low-cost long-term storage. So it's instant retrievable, meaning you can get it when you want it instantly, just like you could with standard S3. And the access cost at the time that we made these slides was 68% lower, according to AWS, than in S3 infrequent access. But, there's a retrieval fee. So there is that option. And then here's the lowest cost storage on AWS, and it's S3 Glacier Deep Archive. So relatively low cost storage. It's optimized for archiving data that can be received in, say, 12 to 24 hours. It's designed for information that's not accessed more than annually. And the data is stored in 3 data centers, and it's for long-term storage, like for regulated industries. So there are your S3 options. And, cost management of these things is important, because in the cloud, it's very expensive to store data. The example is, I'll give you an example. In my personal data center, I have a 93 terabyte RAID array that I use for our videos. It was about $5,000 to set that up. On the cloud, it's almost that price every single month. It's like $3,000 to $4,000 on a cloud provider to store it every month. So if you bought 2 of them and had 1 in 2 different data centers, it's $10,000 for a RAID array that an organization could purchase. Or on the cloud, say $36,000 a year. For 3 years is $100,000 versus $10,000 to buy it. So this is where we have to be really smart about where we start our data, and that's why we're talking about these options. So now that we understand these options, you got your standard S3 for stuff you're going to access all the time, and an S3 infrequent access for things that you might use periodically, and we've got this Glacier stuff that's cheap. How do we put the pieces together? So this is where we deal with something that you would consider a storage lifecycle policy. And what does that mean? It means that you put it in an environment and set up a policy. So let's say you're going to need your data all the time for 30 days. You put it in Amazon S3. 30 days later, you're going to need it periodically, and you're looking to cut your storage costs down. No big deal. Put it in S3 and frequent access. I don't think I'm going to need that data for a year, and if I only do, I'm only going to need a little of it. Stick it in Glacier and cut your storage costs. So that's going to be called a lifecycle management policy. You obviously can do this on all cloud providers, and you will in an architecture we're trying to optimize cost. And it's configured when the people set it up. So Amazon has something they like to call versioning. So with object storage, anytime an object's modified or in any way, it creates a new version. That's standard object storage. You go buy it from any object storage vendor, that's what you're going to get. But most people aren't very familiar with object storage. And they wouldn't be thrilled with the idea that if they were writing a Microsoft Word document, it was stored on object storage, and they saved it every 10 minutes, that every 10 minutes they'd get a new version of it. And in the cloud, when you pay for storage, you might not want to pay for 10 darn versions of the single thing because you changed it 10 times inside of 30 minutes. So they automatically delete, or at least to use, the multiple versions that are there, unless you want to use it. So if you want to use S3 versioning, they bring you back to normal object storage, where anytime something's touched or modified even a little bit, it creates a new version. So if I were to write a document and store it in an object storage, let's say I called it CSA.docx, Certified Solutions Architect, and I saved it the first time, the second time I had version 2, third time I had version 3. And, it may make sense sometimes to store 154 versions of your document. Why? You corrupt the version number 154, you go back to version 153, and you're good to go. And there's times that you might want to do versioning. So Amazon enables you to label versioning to work as it was by default with object storage. So there you go. It's an option. What they call it a feature. So with S3, we have the opportunity to do something called multi-factor authentication delete. So what's this mean? In business, you don't want a user to really delete your key stuff, right? And it happens all the time. So I've got a user that wants to delete something. So with multi-factor authentication delete, they go to delete the photo, send you the cat.jpg. And then the customer is sent a multi-factor authentication challenge. And it could be like a text message, or it could be the kind of thing that you're looking for where you've got like a Google Authenticator or a hardware token card. And then you give them that one-time password, and then the object is deleted. And that prevents a hacker, for example, that gets access to your username and password from breaking into your system and deleting your critical data. So setting up multi-factor authentication delete is pretty important. So how do we secure our information on S3? You, realistically speaking, have two options. The main option you can do is something called a bucket policy. And this is going to be your preferred method, and it's going to be fairly granular. And it's going to be based on identity and access management lists, management, and not a network-based access list that you would see on, say, a router or a network ACL in AWS, but an access control list that you would have in, say, terms of permissions, like Unix permissions. And it's going to be a JSON script that'll have a policy that'll determine what people can or can't do. Now, let's talk about encryption. If you're going to store your information, it should be encrypted so nobody else can get access to it. So anything sensitive, you should actually encrypt, and keep that in the back of your mind. So with AWS, they now traditionally encrypt your data for you, but they didn't until recently. But when it comes to encryption, we have a couple ways we can do it. So we're going to talk about the encryption options. What is encryption? Encryption is if I take one thing and I turn it into something that's an undecipherable text, unless you've got a secret decoder ring. So there's lots of types of encryption that are used. Encryption is used in military communications. Encryption is used on your iPhone. But encryption's been around for a long period of time. Quite frankly, if I spoke to somebody in English and then translated it in Greek and there were no other Greek speakers in the room, that would be encryption. if there, because nobody else would be able to decipher it. Now, if I brought in a Greek translator and I had somebody speaking to me in English, and I spoke to somebody in Greek, but there was a Greek translator telling everybody else what I meant in English, that would obviously not be good encryption. Well, basically, we encrypt with a secret key, and then the user has the same secret key and they know how to decrypt it. So that's what encryption is for the most part. We'll talk more about encryption in other places. But realistically speaking, we can encrypt the data on the client side and we can encrypt the data on the server side. So we have that option where we're going to store it. So we have options with regards to the key management systems. We're going to have the SSE-KMS. And this option is going to be a complete key management solution. The user will manage the master key, and the key management system will manage the data key, and the key management system will provide an audit trail of who and how and when the data was accessed. So that's not the slide I was looking for. So, and how your data was accessed. So realistically speaking, in this environment, you've got your master key, and then there's the data key that's used to decrypt and encrypt the data. But you manage the master key and everything else is done for you. Now, the next option is give more of this key management stuff to AWS. And in a high security environment, you're going to give less of your key stuff to the external provider. But in a lower security environment, you may look for somebody to actually manage everything for you. So the next thing that we have is SSE-S3. And this is going to be an AWS complete key management solution. Amazon's key management solution will manage all the keys. It'll automatically rotate your keys. So in case a key gets compromised, it won't stick around too long. And every object will be encrypted with its own encryption key. It's a great automated system, but generally speaking, in high security environments, you don't want anybody to manage your keys for you. So in this particular case, especially the master key, the SSE-S3, AWS is going to manage the master key, the data key. So much, much, much easier. And then next we will get to SSE-C. And this is an environment where you've got complete autonomy over your encryption keys. The customer manages all the keys. So this is what you're going to see in a high security environment. You're not going to be giving your key management system away to anybody else. So in this particular case, customer manages everything and provides everything and secures their data. Think high security environments, we're going to have that. So let's talk about some things. Yeah, let's go for a few more. Let's talk about some more things for S3. We can tune S3 to improve our performance. One of the things that we can do is pre-signed URLs, and we'll talk about that. We will talk about multi-part uploads. We will talk about range gets, and then we will talk about cross-region replication. And then I will open it up for questions. And while most of the questions that we're going to take today are going to be related to this content, Alam actually asked a very dangerous question, and I want to answer his question at the next break, because that's the difference. What he needs to know here is super important, and I think other people may need to know it as well. So I want to make sure I get to that fairly quickly. So let's talk first about these optimizations. So the first optimization is something called a pre-signed URL. So when you put an object or something into an object storage environment or AWS S3, you're going to need to enable private access. You're going to need to enable access to the object. And do you want to allow other people access into your object storage and have a whole bunch of permissions and usernames and passwords out there? Or can you just pre-sign the file that you want to give them, and you sign it with your encryption key, and you give temporary access for maybe 24 hours or something for the person to get their file, and they no longer have access again? So pre-signed URLs are going to be used all the time. And when you sign a pre-signed URL, the way you sign it will determine the expiration. And certain types of expirations, certain types of signing things are going to be potentially, more secure. So they'll give you different times. So these are the types of ways you can sign a pre-signed URL when you send it to someone to retrieve something via object storage. You can sign it with your IAM instance profile, and that's good for 6 hours. You can sign it with the token securities token service, which we'll talk about later when we talk about the security section, which is good for 36 hours. You can sign it as an IAM user, and that's going to be good for, say, 7 days. You can give a temporary token, and that's until it expires. So it's a pre-signed URL. The next thing I want to talk about is a multi-part upload. So let's talk about things over a network. When you send data over the network, it doesn't always get there. Sometimes the network has an error and the connection is lost. So when you're sending a lot of data, the problem becomes worse. So imagine you upload 4 terabytes of a file, and then the internet connection or the session gets torn down because of a little congestion at one point on the internet for, say, 30 seconds. And now you've got to resend that whole 5 terabyte file. And the next time you send it, it gets cut off at 3.5 terabytes. And you got to go resend it again. So when you're transferring large files over the internet, where internet performance isn't guaranteed, there's so many things that can go wrong. Now, if I'm sending a standard photo of my cat Cindy and it's a 50 meg file, that's not going to be a big deal. It's going to get there. But, if we were to take a 400 megapixel photo of my cat Cindy and now it's a 5 terabyte file because it was in some kind of crazy resolution and crazy things were added to it, that's going to be hard to move. So you have an option of either try to send it all at once, and if any part of it doesn't get there, you got to send it all over again. Or take what you have and divide it into smaller pieces. Piece 1, piece 2, piece 3, piece 4, piece 5, what have you. Piece 1 gets there. Okay, then you send piece 2, and then you send piece 3, and then you send piece 4, and you send piece 5. Or you can send all 5 pieces at the same time, and if any one of them gets lost, say piece 4, you just resend piece 4. So that's going to be a multi-part upload, and that's going to be a recommendation from Amazon. What's it going to look like? It's going to look like something like this. You got a big video, and you chop it into small parts. With S3 will do this for you. And then you push it, gets put together back when you store it. So this is going to give you a lot of control, and it's going to improve the transmissions of your files across the internet. So last piece we'll talk about is something called cross-region replication. So what's this? Let's say we are in, say, North America, right? We've got our data in North America, and we want to replicate it to a bucket into a place in Japan. And every time I store something with data in one site, I want it to move to another site. Exactly, that's going to be cross-region replication. Imagine we have an object storage-based website. I update parts of the website in the US, and instantly the Japanese website's updated. So by doing so, if the data is in Japan, we're going to pay less cross-regional transfer charges, which we'll get to at some point. But here's the thing with Amazon or any cloud provider. Anytime you have to go across areas or regions, you've got to pay extra transfer fees to use the system. So sometimes it's cheaper to store your data in 2 places and let people in 2 places access their data more locally. That could be another reason why we use cross-region replication. And here's an example of that. Okay, Chris, I'll take a few minutes of questions right now, and then we'll get back to the content, and when we get back to it, we'll get to instant storage. How to choose labs for solution architect because you're confused. There may be many labs which are related to DevOps. Well, I'm so glad you asked this question. Do you want to know what a cloud architect or a solution architect does? We do the following steps. We go to our client and we ask our client about their business goals, their business pain points, their business challenge, where they see the business wanting to be now, 5 years from now, 10 years from now, and 20 years from now. When we understand the organization's vision, The next thing we do is going to be as follows. We're going to learn the organization's business processes, especially if we're doing our job right. How does the organization operate? How are products made? How are services delivered? What have you? How is the customer supported? And then we ask that client, is this the way you want the business to work in the future? And they say, no, we want to change these parts of the business. That's why we brought you here. So then you work with the client to determine the ideal way something could be. I think yesterday or the last time I asked this, let's say you have a retail store, like an online retailer like Amazon. And they determine that to increase sales, they want to create a recommendation engine that's going to look at all the things you've purchased in the past and your hobbies and your Facebook and your Google and whatever you have out there and make customized recommendations for you. And I'm sure Amazon has their own recommendation system. And I'm also not going to say they're going through your social media, but theoretically that was the case. So that's the new way we want the customer to experience the system. The next thing we do as solutions architects or cloud architects or enterprise architects or AI architects is we go to that organization and we bring in a team of, say, engineers. They're going to help baseline that systems and evaluate the tech and its performance levels like CPU utilization, memory utilization, disk storage, security vulnerabilities that they find. Then after that, as an architect, I'm going to now build a team of an architecture team. And I'm going to create a team and say, okay, to get the customer to do this, we're going to need to improve their data environment because their data sources aren't good. They need some data hygiene practices. We've got to clean up the data. So I bring in a data scientist and I bring in a big data architect. I then say we're going to need low-level network performance, really good network performance with low latency. So I bring in a network architect. The next thing I realize is, we also need to optimize the communications between point A and point B, and I bring in a unified communications architect. I bring in a security architect to make sure the systems are there. Together, I lead that architecture team along, and I lead that architecture team into a solution. I then lead that architecture team into documenting the solution. The next thing that I do, Alam, is I go socialize that solution or talk about that solution with key stakeholders in various business units and get their feedback. After their feedback, I tune the architecture, and then I get together with the account team and we present that architecture to the client and sell that architecture to the client, and we negotiate the deal with the client. Then we write up a statement. We should have written up a statement of work, determine what type of resources are necessary for the project. And as soon as we're done that, we leave. So, as solutions architects, we don't ever touch the technology. We don't code, we don't configure, we don't do Terraform, we don't do sysops, we don't do DevOps. So a solution architect lab would be to create a technology blueprint to help a bank, improve some new service, or help an airline manage fuel costs by leveraging artificial intelligence to make fuel price predictions based upon news cycles so they can purchase options at another time. So, these are going to be there. And, it's not related to the certification. This is the job. And that's why, and I wasn't going to talk about it, but that's why we have our cloud architect career development program to take people that are either certified and not certified and train them to be architects. So these aren't labs you're going to find out there on the internet. These are labs that you would get in either an MBA program. These are labs that you would get in our cloud architect career development program. These are labs that if you were taught by David Lithicum and he teaches our AI architect program, he would do. This is architecture. So this certification is going to be a good certification because it's going to teach you the AWS services. We're also going way beyond that to teach you some of those network and a data center things. And this certification will help you get an interview. Just make sure you actually learn what an architect is and what an architect does and get the skills that you need to do what I told you. Because they're not going to be hands-on labs. You just can't learn how to design for a business that way. If Amazon EFS is used on premises, can S3 be used on premises? So here's the thing. EFS, and we're going to talk about EFS, is network storage. Network storage. It's network file storage. So in your data center, you could pay AWS for EFS and then bring it over your wide area network to your VPC, or you could just use file storage in your data center and pay much less for it. So when you go to EFS, it's managed for you. So you pay a lot more for it for lack of complexity. But if you're going to use it on premise and you have your file storage on premise, you don't have the latency of the cloud, which is going to be poor performance compared to what you could do locally. and it's going to cost a whole lot less for better performance to do it locally. So you wouldn't use EFS on premise. Now, realistically speaking, and if an organization needs good object storage performance, they're not going to use S3 either. They're going to buy object storage from Dell EMC and have it in their data center. Now, if they wanted to, if the organization has a good direct connection to the cloud, they can use information that's stored on S3 back in their data center. In a hybrid cloud, we would do this kind of stuff all the time. And they can even use, and we'll talk about storage gateways and how to do that as well. But if you've got the option to be in your data center, why would you choose a solution that's 1,000 miles away that's going to perform half of what you can do for double the cost? But it can be done. So in order to make it work, you're going to have to use a storage gateway for S3. What is the likely role of a security architect? A security architect will do everything that I just told you as an architect, but what they will be doing is designing the security solutions. And I've trained lots of security architects as well. So they will be going to the organization and they will be evaluating the assets that they have. What are their assets in terms of physical assets, intellectual property, data, whatever it is. They will quantify that. They will then determine the next option will be they will determine the organization's threats. Then they will evaluate the organization's vulnerabilities. Then a security arc would evaluate the organization's people and test those people and kind of see would they fall into social engineering scams. The security architect may also bring in a penetration tester to try and hack into the systems to find the weaknesses in the system. The security architect would work with that client to figure out what their data needs are and work with them to prevent a data loss prevention strategy. The security architect would work to find the security policy of the organization. And at a high level, what needs to be done on the physical security side, what needs to be done on the policy side, what needs to happen in an incident, for example, who are the incident management team, who communicates during an incident, which legal teams are involved, etc. The security architect might be working with lawyers to determine governance, risk, and compliance to make sure that the organization is there. The security architect would be designing the end-to-end encryption strategy, for example. The security architect would work with an identity and access management strategy to really determine that organization's identity and access management. And then, of course, the security architect, like any architect, will be delivering presentations, selling things, selling the vision, determining the people on the price. So just like the cloud architect, but they're focused on security, where the cloud architect is focused on everything. And that's why they've got to bring in all these extra architects, like security architects, to support them. Good question. All right. Well, let's get back into the content. The reason I wanted to get that, and I'm pretty passionate about it, is, I've trained cloud engineers and made them cloud architects, and I've trained, nurses, mental health techs, and teachers, and it takes about the same time to train both of them, because architecture is about system design to optimize business performance, and engineering is about building systems. So kind of keep that in the back of your mind. Okay, so let me know that you're awake, alert, and oriented by giving me a hashtag AWS. And now I'm going to talk about instance storage. So I'm going to talk about it very briefly, and then I'll get into elastic block storage. Instance storage is the storage that's sitting inside the server. And this is blazingly fast. Blazingly fast. And the problem with instance storage is that it's ephemeral, meaning that it actually gets deleted when you terminate your EC2 instance. So that's what that invisible storage was that person was asking about. Here's what it's going to kind of look like. It's in the virtual machine itself, but it's deleted when you terminate it. So if we're now talking about block storage, we already talked about object storage and what it's used for. Let's talk about block storage. Because you can't go into the servers and the cloud providers and stick your own hard drives in, and because anything that's on instance storage or ephemeral storage in the server gets deleted, the only thing that you can really work with is block storage for your virtual machines. Have a database, that's hard drives, going to be block storage. have a web server, its hard drive is going to be block storage. So kind of hope that makes sense. Now, block storage is the fastest storage we're going to get on the cloud. Is it fast? No. But it is the fastest we're going to get on the cloud. There are times that organizations will not be able to deal with the performance issues of block storage because it's so slow, even if they call it fast. I'll give you an example. The fastest IOPS, and we'll get to that, we can get in block storage with AWS, and that's pretty fast for block storage, is 250,000 IOPS. I can buy a RAID card for my server and get 19 million IOPS for a server sitting on my desk if I wanted to. So big difference between the high performance storage and you can get in the data center versus block storage. But on the cloud, this is the fastest we get. So we got to fall in love with it, or at least use it because it's our only option. And we often use these in private clouds too because of their scalability. So because the files are written in blocks, in much like file storage is, when we deal with block storage, it's going to feel like a virtual hard drive to the computer. It scales incredibly well because if we need block storage, though, all the cloud provider does is they buy another RAID array filled with hard drives, plug it into their network, and it is up and running. So it makes it very easy for them to create this dynamically huge storage pool. It is highly reliable, and it's because it's block storage has been around for a couple of decades. It's tried and true. And, they'll say that their storage is available 99.999% of the time, which means except for 5 minutes downtime per year. Now, because it's the fastest we can use, except for Lustre, which we'll talk about, it's going to be optimal for high throughput, high transaction workloads. And because we have to pay for it, the cloud providers will give you multiple performance options, from really horrible performance to good enough performance. And good enough performance gets real expensive real fast. So because block storage is network attached storage and it's got to be somewhat high speed and low latency, it's typically inside of the data center and not over a wide area network. So for example, it's associated with a single availability zone, but it's going to be backed up to another availability zone. And when you're dealing with block storage, you can back it up into a snapshot. And what is a snapshot? It is a bit-by-bit identical copy of the system. And when we get to databases, we'll talk about going from snapshots to a live system. But it'll be backed up as in a snapshot. And where do you think these snapshots are backed up in archival? Where do we put backup on archivals in the cloud? We put it in object storage. So their block storage volumes or elastic block storage volumes will be backed up into S3. So let's talk about choosing the right type of block storage volume, elastic block storage volume, EBS volume, whatever you want to call it. What do we have to think about with storage? We have to think about performance. Now, when it comes to storage, we're going to have two things to think about: latency and throughput. So latency is how long it takes for something like basically start or finish, that kind of thing, to go from point A to point B. Throughput is how much stuff you are going to move. So I got two cars side by side. Card one is a Ferrari and it's fully maxed out, and I want to go drive a quarter of a mile on it. The Ferrari is in my left hand. In my right hand, I got a tractor trailer. So these two are on a track and they do a race for a quarter mile. Who do you think gets there first, the Ferrari or the tractor trailer? Well, the Ferrari goes straight off the line, zoom, and it's there. The tractor trailer starts, and it finally gets there. So latency-wise, the Ferrari has less latency than the tractor trailer. Now, throughput is how much stuff it can move. So kind of like torque. So when we talk about storage and we talk about throughput, it's how much stuff we can use. So in that Ferrari, how big's the trunk or the boot or whatever you want to call it in your country? Not that big. Now in the tractor trailer, I can take 60,000 pounds of stuff with me or something like that. So let's talk about the throughput of these two devices. I got to go from Palm Beach to New York City and move a load. Do you take the Ferrari? Do you take the tractor trailer? Well, with the Ferrari, you may have to go back and forth, 50 times. With the tractor trailer, you go once. So that's the throughput. So we're going to measure latency in input and output operations per second. So they will call it IOPS. And what is it? It's how many times you can read and write to the disk in a second. The more times you can read and write, the less latency. Now, throughput is going to be the amount of data that's being moved. So that's typically measured in megabits per second. So we'll talk about the fastest you can possibly get on the cloud. And that is EBS provision IOPS. It's called IO2. IO2 is a form of EBS provision IOPS. It is the fastest. That could likely be a test question. Now, this is the highest performance you're going to get with AWS. It's the lowest latency you're going to get with AWS. It's good for workloads that require high input and output operations per second, like a database. It's good for applications that are low latency. Here's the performance we're going to get. 4,000 megabit per second. Not bad. The NVMe drive in your PC is probably 7,000 megabit per second and just a PC, but this is the fastest we're going to get. Input and output operations per second is maxed out at 250,000. Probably less than the NVMe drive in your PC, but that's the fastest we're going to get. And on the cloud, potentially this might be the fastest of all the cloud providers because it's relatively good. EBS provision IO2. So keep that in the back of your mind. The next speed down is EBS provision IOPS, IO1. So the 250,000 IOPS was IO2. EBS provision IOPS, IO1 is 64,000 IOPS. So they still call this high performance SSD storage. It's relatively low latency. It's still good for workloads that require some medium to high input and output operations per second, like a database. It's good for applications requiring low latency. But 1,000 megabit per second and 64,000 input and output operations per second. So it's not real fast compared to a hard drive that I can get in a server in a data center with 19 million IOPS. But it's still relatively good for normal workloads and some databases. So the next level of storage performance down is going to be EBS general purpose SSD, and it's called GP2. And this is standard SSD drives as opposed to the more modern and high performance NVMe drives that are plugged into a PCIe interface in a server. So these give you a decent value in terms of price performance. It's great for a boot VM where you're going to just boot the operating system because it'll stay after a reboot, and then maybe use an IO2 for where your database is stored, because it's going to give you some decent IOPS or input and output operations per second, but it's going to be less than the PIOPS, which is already low. It's going to give you some moderate throughput at about 250 megabit a second. And it's good for a transactional workload. It's great for a development and a testing environment because it's relatively inexpensive. And, it's in that environment. If the performance is a little less, you might actually be fine. So the next one we're going to talk about is something called EBS throughput optimized hard drive. And that is ST1. ST1. And this is magnetic storage, old-fashioned hard drives that spin around. And it's going to be anytime you're dealing with magnetic drives, input and output operations per second are going to be very low. But because these magnetic drives are in actual, they're in a RAID array, you get about 500 megabit a second. And for a lot of stuff, that's a good throughput, actually. Better than the basic SSD storage they're giving you, double. So it's pretty good for throughput intensive workloads like pushing video files around. This would be a great place to store it, but not if you need low latency. Huge log files, perfect for this. Anytime you've got sequential read and writes. And the last form that we're going to talk about block storage wise is EBS cold hard drive, and that is SC1. Cold is SC1, and that's going to be your lowest cost. It's magnetic, so it's going to be very high latency, low IOPS, and the throughput's going to be 250 megabit per second. So relatively slow. You don't want to use this unless it's for things that you don't need to access frequently. Okay, so Now we're going to get into something pretty important. And this is more of a certified solution architect professional content that we're going to talk about now. Actually, a lot of what we are is, but I want to give you more. So I mentioned that the storage performance on the cloud isn't very good. So how do you make not very good better? Well, this brings us into RAID, or redundant array of inexpensive disks. And we'll talk about what that is. So where did RAID come from? Well, it actually started a long time ago. Here's the thing. Small hard drives, like a terabyte or 4 terabytes anymore are considered small, they're real cheap. But you buy a 20 terabyte drive and it gets real expensive. And you know what? You could generally buy 2 10 terabyte hard drives for a lot less than a 20 terabyte drive. And you can definitely buy 3 10 terabyte hard drives for a lot less than a 30 terabyte hard drive. So what we did many years ago is we combined multiple hard drives together to give us better speed, redundancy, and better performance. I want you to answer this question because you were already part of it yesterday. Did we talk about anything yesterday that can enable an organization to improve their performance by sharing the load across multiple devices? And that way you've got better speed and better performance. Did we talk about anything like that? It also enhanced availability. Pop it into the chat box. Pop it into the chat box. That way I know you were listening, because we talked about a high availability device yesterday. Spread your load across a bunch of servers. While you do that, I'll find some water. Tell me, I'm waiting to see you guys answer this. George, exactly. We talked about a load balancer. Good job, VJ. We talked about load balancers where we had this device that shared the load amongst multiple servers. And if we had 4 servers that each had 4 cores, together we had 16 cores, right? Okay, so RAID is nothing different than load balancing across multiple hard drives. So good, you're paying attention. So now that we get that, and I'm glad you're seeing this, let's talk about RAID. RAID aims to take multiple inexpensive devices, pop them together to get better speed and better performance. And you'll see this everywhere. Every data center uses RAID. I use RAID for our video storage because good performance, lower cost. So RAID volumes will make multiple hard drives look like a single drive. The same way a load balancer could make 10 web servers look like a single web server to the outside world, where you get one IP address which DNS points to. So there's RAID 0, there's RAID 1, there's RAID 5, there's RAID 10, and everything after that, like RAID 50, RAID 60, they're kind of variations of this, except for RAID 4, which actually was designed for SSD drives. And I see we have Mark Trimble in the audience, and he's an expert on this kind of stuff, along with many, many other things. Somebody is really great out there with a lot of knowledge. So let's talk about RAID 0. RAID 0 is basically put a couple of hard drives together and just put data, write half of your data on 50% of the drives, exactly like a load balancer. But data is a little different than the servers in the load balancer. If I put 50% of my data on hard drive 1 and the other 50% of my data on hard drive 2, and I lose hard drive 2, I don't have anything left. I got nothing. Deep with the Zaba, as we would say in Greece. Nothing. So with RAID 0, we pop a couple of hard drives together, we get real fast performance. We get maximum capacity. But if we lose any of the hard drives in the RAID 0 array, we got nothing. So if we need ultra fast speed, we'll use RAID 0. But if we do, back up, and back up some more. So here's what RAID 0 kind of looks like. So pretend where it says RAID 0, pretend that is a RAID card, which is a hardware device like a load balancer that shares load across multiple hard drives. And actually, hopefully you're getting from this but the same technology keeps getting reused. They just changed the name of it. So, and that's going to help you stay focused long term. If your fundamentals are good, you'll always know where the new technology is, because it's going to be something else you worked with in the past. So with RAID 0, you can say, we store our data in blocks, right? So instantly the block goes to the first hard drive, then it goes to the second hard drive, then it goes to the first hard drive, the second, the first. And that way we're striping our data onto 2 drives. Maximum performance here, best you're ever going to get. But lose either one of these hard drives and you got nothing. So it's less bad in a cloud computing environment. Here's the reason. These things auto back up themselves. And if it's backed up to another availability zone, if you lose anything, you can recover your data a little quicker. But still, RAID 0 is generally considered too dangerous for business. So now, RAID 1. In RAID 0, we put our data on both. And I said that caused, no redundancy. So the exact opposite of RAID 0 is RAID 1. Basically, anything we put on one hard drive instantly copied to the other hard drive. First hard drive or EBS volume goes away. No big deal. I break the mirror and I just tell it to use the second one. So that's going to be maximum availability. But I've now got to write my data on one and the second one. I'm not writing my data on 2 drives, so I didn't get any speed benefit. If I have one hard drive, I've got to back it up as one. If I have 10, I need another 10. So I think you can see RAID 1 gets real expensive, and it doesn't give you any enhanced capacity, but it gives you a lot of availability. So if your application demands mission critical availability, some flavor of RAID 1 is awesome. If your application needs maximum performance, you're going to need some form of RAID 0, which we'll talk about soon. So we'll get to there. Now, what is RAID 1? It looks just like this. You see a mirror image on each hard drive of all the blocks that are being stored. That's why RAID 1 is called mirroring. So the next type of RAID I'm going to talk about is going to be RAID 5. So if you're a cloud architect like me and you're designing an OpenStack cloud or a Nutanix cloud or even a VMware cloud, and Mark's in there, Mark's got lots of VMware experience, they're going to be using some flavor of RAID 5 in the data center. So you need to know what RAID 5 is, but you won't be able to do RAID 5 on the cloud. And here's the reason why. Remember how we talked about block storage being slow by comparing to, say, those RAID cards you can stick in a server? Well, because of that, anytime you add any kind of redundancy in your RAID, it's going to add a little latency. And we can't slow down the already slow cloud EBS volume. So RAID 5 is not going to be allowed in the cloud, but you might need it in a private cloud. So RAID 5 does a combination of striping and backup all at the same time. Well, it's not exactly backup, but it's like backup. We'll talk about it. And what happens is, let's say you need at least 3 drives. You put data on every time you write data, 2 drives out of the 3 will get data, 1 will get some backup or parity information. The next time you write the data will go on 2 different drives, and there'll be one that gets backup information, something to that. Well, because the drives are going to rotate. I'll show you what I mean in a minute. By doing this, organizations get greater speed and greater performance. So here's what it would look like, and maybe this will make it explained. So here's a traditional RAID 0 environment where the first time I write my data to the first hard drive, then I write my data to the second hard drive, then I write it to the third data, and then I write this backup data or parity data to the fourth hard drive. The next time I maybe store data on the first hard drive, then maybe the second hard drive, then I put some backup or parity data on the third hard drive, and then I put real data on the fourth hard drive. The third time around, I add data to the first hard drive, then some backup data to the second drive, then some data to the third drive and the fourth drive. The last time in this 4-drive environment, I write data to I write backup data to hard drive 1, and then data to the drives 2, 3, and 4. Now, why is this an advantage? Well, if I lose any one of these drives, All we have to do is remove it from the RAID array, pop in a new drive, and the information that was on the missing drive is built back up from all this parity data or backup data that's sitting inside of all these other environments. So that's why RAID is good. There's also a RAID 6 configuration, which is a version of this, but it uses 2 parity drives. So that's why I said there's a lot of these that are coming out of it. So can't do this in the cloud, but you'll be using some of this as in the data center or a private cloud. So RAID 0, max speed. RAID 1, 100% redundancy. So that brings us into RAID 10. Now, RAID 10 gets pretty expensive, but gives us the maximum speed and the maximum availability. So this is cool stuff. So what is RAID 10? Well, we create a RAID 0 array because that gives us a backup speed. We create a backup RAID 0 array, and then we run RAID 1 or disk mirroring between them. So really good performance, really good backup. And this high speed and super high redundancy makes it incredibly popular amongst organizations like big banks or environments where seconds of downtime can mean millions of dollars. So here's an example of what that looks like. Here you've got a RAID 0 array for these 2 drives, and then you've got another RAID 0 array for these 2 drives, and then basically between them you're running RAID 1 or mirroring. So that is RAID. Now let's talk about file storage on AWS, and we will talk about the Elastic File System. So the Elastic File System is a scalable file system. It should be. I'll tell you what it is in a minute. So if I have 100 systems that all need to access data all at the same time, I put it on file storage. Maybe I have 50 servers that all want to share the same information. Stick it on a file server. So you have an opportunity to build a file server, say a Linux file server, and share a folder. And then you have an NFS file share. Or if you don't want to manage a server yourself, and you can create the Amazon branded version of the network file system file sharing service. So same kind of concept that we've been dealing with for decades. Just Amazon now manages these file servers and they branded it so they stick the word Elastic in front of it. So now you understand what is EFS. So it's a managed system. So what's the benefit of these managed systems? If you add storage, it's just going to grow dynamically for you, so you don't worry about running out of storage. So that's why they like to call it Elastic. So when we talk about EFS, we're going to have 2 options. We're going to have a standard option. It's going to be your normal storage. It's going to give you good performance. And we have another version called infrequent access. What's that? Just like with object storage, you pay less to put it there, but you might need to pay to access it, that kind of thing. So we're going to have 2 options with our Elastic File System, meaning Amazon branded NFS. We've got a burstable option, which is the default, which means you've got information and you burst, and as long as there's bandwidth, you can use it. And provision throughput, which is where you know what you're going to use and you plan it and you're guaranteed to get what you've got. And if it matters, you're going to provision it and you're going to know. It's not like you don't need to do capacity planning if you want to build a high performance architecture that actually isn't going to cost a fortune. So you want to know how to do this. So here's the key to remember with Elastic File System. Because it's like NFS, it'll be POSIX compatible. So you can use it with things that require that. It's going to be scalable, give you good throughput, as good as you're going to get in the cloud, and be relatively low latency. And it will just scale for you, so you don't have to worry about running out of storage. So realistically speaking, here's where you're going to use it. If you've got multiple systems that need to access the same file storage, like in this particular example, you see where you have this Amazon EFS. That could be a Red Hat system running NFS, or it could be a Ubuntu system running NFS, doing a file share. But then you've got to manage the server. But in this case, you're just having an Amazon managed file server for you. So EFS is a cloud-based auto-managed version of an NFS service. So that means NFS, which means it's going to be used by Linux and Unix systems. Okay, so because block storage isn't real fast, what happens when you need high performance on the network? So we'll talk about that in a minute, but let's talk about Windows file servers. So I previously said that Windows uses server message block, right? Or you can, which means that with a Windows server, it's by default. If you wanted to use a Linux system, and I have lots of my students do this from time to time, have a Linux system share files with a Windows system, you have to run server message block on a Linux system, which means Samba. But anyway, so Amazon has some fully managed Windows file servers for you as well. And what are they? Windows file servers that Amazon manages for you. So if you're in a Microsoft environment, and most enterprises are, and they think they have things that they want to use with Microsoft file systems like quotas or Active Directory, and pretty much everybody uses Active Directory, the Amazon FSX system will work because it is a Windows file server. They just manage it for you. And when you're dealing with Amazon FSX for Windows, it's going to provide encryption both in transit, meaning from the time it's sent to the times it's received, and at rest, meaning at storage. So this is a good option if you don't want to manage your own Windows file servers. So pretty much it's pretty simple. You basically create your FSX file server, you configure your file shares, and you're going to connect it to whatever your systems need it. So standard Windows stuff. The key to remember is it's fully managed. So you're outsourcing management of the server, which means things like hardware provisioning, patching, and backups they do for you. So it reduces the burden of managing a server. And when you outsource it to manage, it could cost more or less based upon your people costs and how you run it. But there is that. So because it's a Windows server, it's going to support server message block protocol. It'll integrate with Active Directory, which is pretty much the enterprise-wide identity and access management systems most use, and is also compatible with a distributed file system. So Windows applications, Windows workloads, this is a great file system to use in the cloud if you've got Windows servers in the cloud. The performance is, it's going to be based off of SSD storage, so it tends to be, as good as anything else you're going to get, but it can scale to thousands of concurrent connections. So is pretty good in terms of that, in terms of what you're going to scale out there for. So the key to remember is it provides data encryption in transit, so that's going to be great from a security perspective. It's going to integrate with the AWS identity and access management tools if you're using them, which will most likely be federated into Active Directory. It'll be integrated with the AWS key management system. And, these are standard servers, so they tend to comply with HIPAA requirements, GDPR environments, PCI DSS requirements, at least in the way Amazon manages them for you. They are replicated, the data is replicated across multiple availability zones for high availability, and it gives some good backup and restore capabilities against data loss. So in terms of how does that integrate with other services, that's the key. It connects so easily. So if you've got a hybrid cloud and you've got a direct connection and you wanted to access this stuff on the cloud, like the person asked earlier, when he asked, could you do access EFS? This is kind of that same kind of thing. This is the Windows equivalent of EFS. But it might be better to store your information locally, about higher performance, lower latency. So in an enterprise, they've got a lot of file sharing. This will take care of that. So, and the key is all those Active Directory things, all those quotas, you've got that because it's Windows servers. Lots of times people use this kind of thing to back up a database, especially in a Windows environment. You could use this type of storage for media and entertainment because it'll support like the kind of media workflows that systems would use that require high throughput and low latency. You can use this to serve web content across multiple servers at the same time. So how do you set this up? You sign up for an AWS account. You create your file system. And when you do that, you specify, say, the storage capacity, the throughput, and other configuration options. You integrate it with your Active Directory, or you create a new one for your permissions. You mount the file system wherever it needs to be. And then you just access it with a standard Windows tool. And you can manage and monitor your systems, of course, with the command line interface, the console, specifically the FSX console, or the software development kit if you want to do it over another system. Okay, so let's talk about another AWS service called Data Sync. So lots of times you'll have an on-premise environment, you're going to have a cloud environment, you're going to have stuff. So how do you keep your data synchronized? Well, there's lots of ways to do data synchronization, but AWS Data Sync does have their option for you, and that's going to be a managed service that's going to make it easy to automate and accelerate moving data between, say, on-premise and AWS. It can sync your data between different AWS storage services. So it's AWS's native tool. It's designed to handle large-scale data transfers. And what happens is AWS Data Sync will enable you to automate the process to transfer your data back and forth. So less manual intervention, less custom scripting. It'll handle the complexities of data transfer, including, theoretically optimizing the network, validating the data, and error handling. And it works with multiple storage services, S3, EFS, FSX for Windows, FSX for Lustre, which we'll talk about, which is where you get to high performance, and Amazon FSX for OpenZFS, if you're familiar with that file system. It also works with NFS systems, so pretty much everything. Now, it does actually encrypt the data in transit, which is great. And again, at rest where it's going to be stored. And by doing that, it'll integrate with the AWS key management system to manage the encryption keys. And it can work with, AWS IAM controls for identity and access management, like who are you, what you're allowed to do, and then keeping track of what you've done. Where it can help with data validation and integrity, because Data Sync will perform data integrity checks to ensure that the data that's transferred is going to match the source. So you want to make sure that you're getting the right data. And it'll verify the data during and after the process. And that way you've got data consistency across your clouds, what have you. You can schedule it and automate it. So you can run scheduled transfers at, say, 2:30 a.m. to make sure that it's done at the time where the networks are least used. So periodic data backup, synchronization, archival purposes, this is going to help you automate that. Now, when you're transferring data, sometimes you don't want to transfer everything. You may want to exclude certain files or include certain files or directories, or the patterns of where things are going. You've got that option too with AWS Data Sync. So I'm going to talk about it here because, it's kind of hard to where you would classify this, but it's not really storage while we're going through the storage section. So keep that in mind. I'm going to talk about the AWS Migration Hub. And that's going to be a service that's going to be a single location that you can use to track the progress of your applications moving across AWS. It's going to help manage and monitor your migration process, and it's going to provide some visibility into the status and the metrics of each project. The last thing we talked about was synchronizing your cloud environment. So, in this case, with the Migration Hub remember, the key feature here is you've got a centralized dashboard. So you're going to be able to look and see what's being moved and how it's being moved, give you kind of that unified view. So it'll help with discovery and planning efforts with regards to migrations, because it integrates with the application discovery service, which we'll talk about later at some point. We're just going to figure out which applications you have. It can help you group related applications to try to know which stuff that needs to be moved together. And it gives you the ability to kind of track the migration of applications, which is one of your bigger challenges when you move to the cloud, unless you do a lift and shift. And it'll provide metrics and reports. So, whenever we're doing something, we have to define what is success, right? And we need to know what's working. So we're going to need lots of details, like the number of servers that have been migrated, what percentage, what amount of data has been transferred, what errors and things we've encountered along the way. And this is going to help with that. So it's really about progress tracking. Track the progress. What's going on here? What's going on? Because these migrations can be relatively large, and they might need several program managers and a lot of people to do it. So kind of think about that. So Migration Hub also assists with automation and orchestration of certain tasks. So certain repetitive processes, if you can automate that, it's going to reduce the risk of manual effort and errors, assuming you know what you're automating. So now let's talk about the AWS transfer family. And that's going to be a fully managed service from AWS that's going to help you transfer your data from, say, your data center to the cloud. And it's going to support lots of protocols to make it easier to migrate, share, and integrate your data with existing systems. So we're talking about the AWS transfer family. It'll enable you to use, say, SFTP to securely transfer your files. You can use FTTPS, which is FTP with TLS encryption, to improve the security. It also supports your ability to transfer files over standard FTP over an unencrypted connection. But if you don't have to use that, you probably don't want to in today's world. And it enables you to store things on, say, S3 or the EFS or the Elastic File System if it needs to be viewed by multiple systems at the same time. So these transfer family can basically help with data migration, move it to the cloud, share data with external partners or systems. And it's quite helpful for backup and recovery purposes and compliance. Okay, well, we are going to go into next databases. And we've got lots to talk about in databases, lots and lots and lots of getting geeky, so it'll be fun. So I'm going to stop now to see if there's any questions. How to detect ghosts, meaning using AWS. I mean, how can we control the motion camera to detect ghosts using AWS? So honestly, I don't even know what you mean by ghosts. So I'm assuming it's a joke, but I really don't know. Though Chris does like ghosts a lot. As an architect, how do you do cost management for customers, speaking of AWS services? So you really have two things going into cost services. And I'll tell you why the cloud costs have gotten so crazy and why the cloud, David Lithicum's numbers, and they sound pretty accurate to me, cloud computing costing about two to 2.5 times more than it would to do it yourself in the data center. So what goes into this? So what goes into this is as following. It is a matter of knowing what we should put on the cloud versus not put on the cloud. Because certain things, if you've got an application that runs 24 hours a day and it's heavily utilized, it'll cost you a lot more to go serverless than it would be to put it in a monolithic application sitting in the data center or the cloud. And it would be cheapest on the cloud if it runs hard. Likewise, we've got a sporadic event-driven application, and it's sporadic, not paying for systems to run using a serverless environment and only paying when we need them. If it doesn't run a lot, it's going to be very cost efficient in the cloud. So the first part of cost management is knowing what to move to the cloud versus what not to do. And if you don't understand the network in the data center, you won't know that. So there is that. Next, you need to really understand your system. So this is where capacity planning comes into play. If you know that in your data center and you've got a retail and you're a global retailer, for example, and in your data center, you've got a website and that those web servers are utilized at 6% all year long in your data center, but then they go up to 100% during Christmas because that's the busy time of the year near Christmas. Then when you go to the cloud, you don't put those same systems on the cloud. You use something where they'd be running at, say, 70% versus 6%, and then you let auto scaling do its job. And if you know what your systems are, you can say, I'm going to reserve this system for the next 3 years and get a discount. So there's some of that. But a lot of it's knowing what not to put on the cloud. Certain things are just going to be 10 times more expensive on the cloud. For example, if you're just hosting a few virtual machines, I can go to Dell right now, and for about $300,000, I can buy a server with 2 massive AMD EPYC processors, each with 128 cores. I can put about 6 terabytes of DRAM, and I can put an NVMe RAID array. And if I were to use that same system on the cloud with similar storage performance over the course of 3 years, I'd be paying several $1 million versus a few $100,000 to buy it from Dell. So knowing if I've got something that needs that performance, don't put that in the cloud is the key. So the next part of it is designing the architecture right. So if we know what we're designing and we know what the end business goals are, we're going to make sure that the costs are going to be optimized. Then we have to really think about it. And the reason we're hearing so much about cost optimization right now is the majority of the cloud architectures that are there are really bad. And what do I mean by really bad? 50 to 70% of all cloud architectures companies have spent a lot of money on and gotten no business benefit. So that's why people are complaining about the cost. If I were to give you if an investor said, give me $100 and I'll give you $1,000 back, I'd say, how often can I give you $100? And I'd buy more of it. If I gave somebody $100 and $1 came back, like most people with their cloud investment, then I'd be really worried about cost. So it's less of what the cost is, and it's more about what the customer's actually getting from what they're spending on it. So you need to be very understanding of your customer's business so that any technology that you actually implement actually helps their business, and you'll be in a much, much better shape for it. So then it's using the right service. If you understand your applications, you know when to go serverless and when not to go serverless. So that's really the key, using the right size systems, knowing where the company is going and knowing how to deploy it correctly, and knowing how and where to place your systems and which technologies are there. Now, I'm going to tell you right now, what I just told you, don't think that's done in one day. Don't think that's done in 1 week. And don't even think that's done in 1 month in a big global enterprise architecture, the kind of architecture I would work on, or a David Lithicum. This could take 6 to 12 months to figure all this stuff out. So it's not like in a certification where you think you're going to get asked somebody about a WordPress website and they're going to come there. We architects work in companies that have hundreds of thousands of employees and data centers all over the world and work in billions and billions of dollars a year of revenue. That's why they pay people like us to design their systems. So they understand it's going to take a fair amount of time to get this. So there's that. And then the rest of the cost management is, once you've deployed the systems, you monitor these systems. And can you reduce the size of systems? Do you need to provision systems? Okay, you're using more capacity. Can you reserve it? We put this application on the cloud, and this one on the cloud is costing us way too much. Can we bring it back to the data center? So that's really what you're talking about. How do you explain AWS services pricing as an architect? You don't. So here's the key. As an architect, you are in sales, yes, but you also have to be a trusted advisor. So one of the ways of being a trusted advisor is to let the sales rep or the account manager talk about the pricing, and you don't. And that's why, for the most part, if someone goes to a physician, the physician doesn't collect the co-pays or the money from the patient. They have the receptionist do it or a billing person do it. So you don't explain AWS service pricing. Your account manager discusses the service pricing. You will be there, parts of the negotiation, but you focus on what you can do for them. You focus on what is the return on investment capital that the organization is spending. They're spending money. So what's it going to do for them? So if you analyzed an airline's purchasing fuel cost and you find that they can save, $3 billion with some tech, and the tech costs $1 billion, they're going to buy it. If you did the business case and looked at the tech and said, yeah, we can figure out when that airline can purchase fuel price contracts to get the cheapest price, but the tech costs you $50 million and it's going to save $1 million a year, you don't invest in the tech. So you focus on what you can do. You focus on what that architecture does for them. You focus on how it improves employee productivity or product output or optimization of the supply chain. And you let the pricing people talk about the pricing. And that way you stay a trusted advisor. Because the second they know that you are too concerned about price. That's the second, they view you as sales, and then they don't trust you. And the real thing as an architect is you need to be able to tell a client, this is not right for you. I've done it. I've done it numerous times where a client said, should I do this? And I say, I can build it for you. And if you want it, we'll give it to you. But I don't think this will help your business. I don't think it's in the best interest of you. And in the end, they thanked me, and they called me back and said, Mike, design what would be in the best interest of me. And I was happy to do it. And then they wanted it anyway. But you gotta really treat the end customer the way you'd want to be treated. And if you do that, you'll be good. And I'm saying this because the architecture world is very small. There's not a lot of us out there, and we all know each other. So kind of keep that in the back of your mind. And that's an incredible question. And I'm glad you asked it, Kabenga, because if you didn't, we wouldn't have been, it's the kind of thing that you don't think about. And I hope that really helps. Data architect will reduce the spend. Data is one of the services that cost a lot, right? Well, everything in the cloud costs a lot. Networking in the cloud costs a lot. Normal networking, I buy a connection from point A to point B. And if it's 10 gigs and I don't use it or do use it, I pay one fee. When you were dealing with data coming in and out of the cloud providers for a while, not only did you pay for the 10 gig link, then you had to pay a daily penalty called the port fee to have the link. And then they actually charge you to use the link that you already paid for. So, that gets expensive. A server on the cloud right now, you can get an AWS i3 instance. And if you max out all the cores, it's going to cost you about $1,100 bucks a month. You can go to Amazon right now and buy that same server refurbished for $400 versus $1,000 a month. So, I mean, knowing what to put on the cloud in there, everything on the cloud is going to cost more. But data is important. Data is a place where the organization spends money. And, optimizing data because the data architect did it in a right way is definitely good. And regarding Ghost, actually, Sapiro, Chris loves Ghost too. So I totally with you 100%. And I'm going to get back to the content. So for Basan, I am not a DevOps engineer, and DevOps and architecture are very different from each other. But DevOps engineers will have a lot of coding in their world because they're merging development and as well as operations. I can recommend not going towards sysops unless you want to do the maintenance on the systems. There's nothing wrong with sysops, but it's the lowest paying technology career out there, one of the lowest that are out there, and it's going to be as much work, if not more work, than it would take you to become a DevOps engineer. So something to think about. And we've got a video on why we don't recommend the AWS SysOps certification. I would watch that as well. Okay, so let's get back to the content. So databases are pretty big. So I need to know that you're awake, you're alert, and you're oriented, because not only are we going to talk about the AWS, the little stuff they would put in their certification, we're going to talk about relational databases. We're going to talk about NoSQL databases. We will talk about the features and functionalities of the main databases that you can use in a multi-cloud environment. And we're going to have fun with it. So it's going to be a lot more, about 4 or 5 times more than you would normally get in a certification, because I want you to know something. So give me a hashtag AWS so that I know you are awake. Okay, so let's talk about databases. So to begin, what is a database? A database is going to be an application that allows you to store a lot of information. The key here, which is different than databases other than just throwing stuff in a drawer, is the database makes it easy to look at your data, sort your data, run calculations off of your data, report off of your data, or share your data. So it's the exact opposite of like throwing everything in a drawer and trying to search for it. You can think of the database as these beautifully organized things that you can help find anything. And in today's world, databases are absolutely critical to modern applications. So AWS will have basically three kinds of databases, and we'll also talk about data lakes later. They will have relational databases, and we will talk about what they are. They will have NoSQL databases. They will have databases that are used for data warehouses, and we will talk about data lakes as well. So let's talk about relational databases. So what is a database? What is a relational database? First, I'm going to tell you right now, it's the most common form of database. And it provides storage for information that's related to each other. And data is, for the most part, stored on a spreadsheet. It's like stored the way it is on a spreadsheet. You've got rows and columns. So very structured. Now, relational databases adhere to this concept of an ACID model. And it's an acronym that stands for atomic, consistent, isolated, and durable. And what does that mean? It means that when a transaction occurs in a database, it either occurs or it doesn't occur. It's an all or nothing thing. That the second I write something into the database, every other database in that system has the identical data in it. So it's immediately consistent. It's isolated, meaning that one transaction will not impact another transaction. And it's durable, which means the data in the databases will not be lost. So Amazon's going to support a lot of relational databases. They have their own proprietary Amazon Aurora, and we will talk about that. We will also talk about MariaDB, which is another common database. We'll talk about Microsoft SQL Server. We'll talk about MySQL. We'll talk about the Oracle database and the Postgres database. So think of the relational database as a very organized structure, columns and rows. And what happens is the databases will have tables that is going to be very structured so you can see how things that are related to each other. So here you can look at this. Pretty simple. We can see the customer's name, their email, what they paid for something, their order information. And this is going to give business lots of information. Maybe they find that at a certain price, they can sell more than at another price. So, there's a lot of things that organizations are going to get from relational databases. So the key to remember is we've got tables. And tables are going to be the primary structure for storing the data. And they'll consist of rows and columns. Each table will represent a specific entity, such as customers or orders or products. And regarding the rows, and a row you typically may hear it as a record. Each row will represent a single instance of the entity, whatever that entity may be. So each row could be a single customer. Now, regarding the columns, each column will have a field that'll represent an attribute. So maybe it's the customer's ID, for example. And with databases, we'll typically have a primary key, and that's going to be a unique identifier for each row in a table. And it's the primary key that's going to ensure that each record can be uniquely identified. Databases may also have something called the foreign key. And this is going to be a field or a collection of fields that are going to be in a table that will uniquely identify a row of another table. So if you've got two tables, it's going to establish a relationship between them. And we can have relationships which are defined connections between two tables, usually through either primary keys or foreign keys. And, when we deal with this, it's like anything else where we can have a one-to-one relationship, a one-to-many relationship, or a many-to-many relationship. Now, the key with relational databases is they use a common language, which is great. So when you want to query or pull information out of the database, they use this concept of a structured query language. Makes it very simple. So there's SQL commands for querying data, updating records, and managing the databases. And for the people that use these systems all the time, they need to be querying them. As architects, we don't run SQL queries, but we may have a cloud engineer or a DevOps engineer that's going to be querying this stuff, or a data engineer or a data analyst that's going to be running SQL queries all the time. So the key to remember, we talked about the integrity of the data. Relational databases make sure that the data is consistent through a bunch of constraints. And relational databases, the tables on them are relatively flexible. We can easily add or delete or modify information without modifying existing applications. So we've got some flexibility in the way we manage data with these databases. And relational databases often can scale fairly well. They can scale vertically by adding a lot more power to the server. And some relational databases they all have some form of horizontal scaling by adding more servers, but it's not going to be the way you think. It's not like scaling a web server where you just add a load balancer, but that's okay. We'll teach you how to do that as well. Let me get to that. Now, relational databases tend to be fairly secure. They've got lots of security features, like things like identity and access management. You can authenticate to the system. You can encrypt the system, use any kind of permissions you need. The data is independent, meaning if you make a change to the database schema, it's not going to affect the data access methods. So you can evolve your applications over time independently of the database's actual structure. So I'm guessing you're starting to see that's why these systems are used so widely in business. So where do we use them? We use relational databases in e-commerce. So got a product catalog, it's in a relational database. Customer information in a relational database. Orders, inventory, probably in a relational database. In banking, every time you use your ATM card, something's got to handle those transactions, goes to a database. Your financial records, typically in a relational database. Your customer accounts, typically in a relational database. In healthcare, maybe some patient records could be stored in some, integrated into their electronic health record. Appointment scheduling could be there. Education uses them widely, student information, course enrollments, academic records, it's there. So if you want to hack into the academic records and change your grades to all A's, well, I'm not recommending this, but that's what you're really hacking into. And all those movies where the people did that. Governments, tax records for citizens, tax information, public services. So these things are used everywhere. Now, the first database I'm going to talk about is the Amazon branded one. I'm going to be straight with you right now. If you have a multi-cloud architecture, don't use this. Use something like an Oracle database or a MySQL database or Maria database or a Microsoft database that you can stick in all different clouds. Because if you use this, Amazon Aurora, it's kind of like me speaking Greek and Chris behind the speaking English, and Chow on the other side speaking Vietnamese, and Mo speaking Arabic. And when you translate information, some things don't translate. For example, I say please close the lights. In America, what does that mean? They say shut off the lights. So the problem when you use different databases, in some cases, it's going to be hard to integrate these systems. So in a multi-cloud environment, don't use Amazon Aurora unless there's some specific reason to use. So use something else. And remember, 98% of organizations are multi-cloud. So think about how often you could use this. Less than 2% of the cases in most cases. So just keep that in the back of your mind. So Amazon Aurora is a great database. It is an awesome database, though. It is an Amazon fully managed relational database. And it is Postgres and Microsoft SQL compatible, so it makes it relatively easy to get your data into it, but you're not going to want to run these systems side by side across different clouds. It scales. It's a great database. So what they tried to do is make it more like the Oracle database, more of an industrial database. So over a free thing like a MySQL. So they say it's 5 times faster than standard MySQL. They say 3 times faster than Postgres. That's the marketing numbers, but it's a great database. So it gives you some of the benefits that you would get with, say, an Oracle or a commercial database, but lower costs of like a open source database. But it's still useful in enterprise applications if the organization's only going to be on a single cloud. So like as a software as a service application, it's a good performing database. It's got good performance. And, they've really designed this very well, good storage system, highly distributed fault tolerant system. It's a great database. It really is. And if the world wasn't multi-cloud, we could use a lot more of it because it's a really great database. It tends to scale well, anywhere from 10 gig of storage to 128 gig with no downtime. You can scale at read capacity fairly well, and you can put up to 15, read replicas in it and multiple availability zones. So it's a robust database. It's designed to provide 99.99% availability. That may be okay for a business, or that may not be. Banks, hospitals, emergency services systems need to have 99.999% availability versus not 99.9, but it's a great database. And it's not that hard. It doesn't take that much to take your data and move it into these things if you're in MySQL or Postgres. But trying to keep 4 or 5 of these up and running at the same time and synced would be challenging. That's why people would be more likely to use a more open standard one. The key to remember with Aurora is it's managed. So what does that mean? It means you don't have to think about, provisioning it, patching servers, backing it up, recovery, scaling, because it's all done for you. So with a managed service, you lose a lot. You lose control. But it's done for you. So that's a trade-off. And architecture is the process of choosing trade-off. Is this the right thing for me? I lose this, but is it best for me, or is this other option good? So you're picking the best choices. Security. It kind of makes it easy to do your security if you're just in AWS, because it provides encryption at rest and in transit, and it integrates into your AWS identity and access management because it's all AWS stuff. And when you go with single proprietary things, it locks you into a vendor and makes it harder for you to do multi-cloud and potentially harder to innovate in the future, but it makes it simple. So always is an architectural option. So you might use Aurora with a web or a mobile application. You might use it in e-commerce, any place where you use a relational database. If you don't want to manage servers, you can use this in AWS. So good database. It's got a pretty interesting distributed storage architecture. So, it's decoupling your servers from your storage from your compute, just like on a block storage environment. But the storage kind of grows as you need it. So you don't have to think about exactly how much storage, which again makes life easier with a managed service. It like most of the AWS databases, it will back up your data, but this one continuously backs up your data to S3 and allows you to create your manual snapshots if you want for a point in time recovery. And you can restore your database from these backups or snapshots anytime you need. And because it's AWS, it's pretty elegant in the way that it integrates into CloudWatch, which is logging, CloudTrail, which is auditing, and the management console. So pretty easy to use. Okay, so that was the proprietary Amazon one. Great database, but you can't run it in Azure. And you can't run it in Google. So if you're in 2 or more clouds, it's going to be challenging. So now let's get into the first of the open standards databases. MySQL. You can use this in any cloud provider you want, or data center you want. And MySQL is probably the most popular open source relational database management systems in the world. It's used in a wide range of web applications, enterprise solutions. It's highly reliable. It performs relatively well, and it's pretty easy to use. And while it started out, I think it was with Sun Microsystems or even open source freeware, it's now supported by Oracle. So it's got, people that know data and databases behind them. So it's got good support on it. So it's a relational database. So that means it'll support, the rows and columns of the way you store your tables. It means you'll run structured query language queries on this. It means it's an ACID compliant database, which we talked about. And here's the thing. It's got all kinds of cross-system support. Runs on Windows, runs on Linux. Heck, you could run it on Mac OS. Not that you're going to put any server in the cloud on Mac OS, but the point is it runs on anything. So it supports multiple storage engines as well, like InnoDatabase by default, but there's other things like MyISAM memory. So you can use different storage engines based upon different use cases, and your database people you're going to want to work with that. It provides, regarding replication, it's got lots of replication methods. master slave, master master, group application, and that just refers to how these systems are sent out there. And this gives you the opportunity for high availability and data redundancy. Regarding scalability, there's others that scale better than MySQL, but it scales very well. Pretty large databases with high concurrency workloads. It's got good security features like user authentication, access control, and encryption. It's used in a wide variety of web applications. So, you'll see it all the time for dynamic web applications, content management systems, e-commerce platforms. There's even some people that do data warehousing and analytical applications on MySQL, although more often it'd be Postgres. It's used in a wide variety of enterprise applications that needs a reliable database that's efficient. It can use lots of embedded applications because it's fairly efficient code with a small footprint. And it's open source, so it's free. And there's a wide active community that supports it. So that's MySQL. Been around for a long, long time, decades, and it's free. So the next one we're going to talk about is Postgres. And it's technically PostgreSQL, but people typically call it Postgres. And this one is a database which is known for its emphasis on extensibility and standards compliance. And it's widely used in academic settings, industrial settings, because it's robust. It's often used as a data warehouse. It's a relational database, so it's got that ASA compliance, which we initially talked about. And it's pretty standards-based. It adheres very closely to the SQL standards. So most, SQL 2011 things, if you've seen that out there, features are supported. Regarding extensibility, it allows users to create some custom data types and operators and functions. And it supports all kinds of data types like JSON, XML, HStore. So lots of opportunities in the way the data is structured as well. Concurrency control. So it has this concept of multi-version concurrency control. So it can handle multiple concurrent operations without locking up the database. Some databases have to lock until the next transaction needs to occur. This can do them both at the same time. And it supports all kinds of replication, both synchronous and asynchronous. So logical replication for maybe fine-grained control over the data. So it gives you lots of tools with regards to how and where you're replicating your data. It has very good full-text search functionality, so you can run some powerful search queries. And there's geospatial support. So there are certain kinds of geographic information systems that are out there, and this tends to integrate fairly nicely with those systems. Used in plenty of backends for web applications, but because it handles complex queries and very large data sets, it's widely used for data warehousing, and we're using data warehouses for business intelligence. Gather insights from our data to guide the business into making better business decisions. You often see Postgres in financial applications because it's so robust in its processing abilities. You often see Postgres in scientific research. You got a lot of structured and data that you're popping into something like Postgres, and it's a little more flexible on some of the other data you can put. And let's talk about some good things about it. It's open source. It's freely available. It's got a strong and access community, and it's very high performance, and it's got lots of optimization features. So this is a big database out there, especially with regards to data warehousing. It supports, authentication, authorization, encryption, and auditing of the database. It tends to scale fairly well. So Postgres, very common relational database. You can use it on any cloud provider you want, any data center you want, all three at the same time if you want, just like MySQL. Now, another free open source database supported by AWS and pretty much anybody who want to put it is MariaDB. And it's open source, and it's created by the people that made MySQL. So The goal with MariaDB was to improve the performance and functionality of that they started with MySQL and improve upon it. So, that's kind of what we're typically talking about here. Is MariaDB is going to be highly compatible with MySQL. So matching the APIs, commands, and data structures, because it was made by the MySQL people, they wanted to make it smoother for people to migrate over. And it works with a tremendous number of storage engines like InnoDB, MyISAM, ARIA, Column Store. So lots of options and functionality here. Tends to perform a little better than MySQL. And it's got some extra features like thread pulling and some advanced optimization. And it's got better replication capabilities as well. Tends to be fairly secure with encryption, user roles, and enhanced identification methods, so to speak. Tends to scale relatively well by bigger servers or adding more, like read replica type servers. And it supports all kinds of replications. So another good open source database. It tends to be very extensible, so you can create plugins to it with various storage engines to extend its capabilities. And it's got a very strong community because it's open source that maintains this. Where might you use MariaDB? I'm hoping you're starting to sense a trend with these things. They're used in a lot of the same places, which is why I keep going over them. Web applications, the backend database, data warehousing you can use because it tends to scale well. Any kind of enterprise application that requires robust and efficient data management. Embedded applications is relatively small, just like MySQL, so small footprint. And it's an open source database. So we've covered these. Now, the last ones we talked about were open source. Now, this is not an open source database that we'll talk about next, but it will work in all cloud providers because Microsoft has their SQL server, and Microsoft SQL Server is used for Microsoft workloads, and Microsoft workloads are a lot of what's going on out there. So let's talk about Microsoft SQL databases. Amazon supports, the majority of them, like SQL Server 2008, 2012, 2014, what have you, good support. And if you're running Windows workloads, you're going to probably need an Microsoft SQL Server. So you can run them in pretty much all your cloud providers. There are about 4 versions of Microsoft SQL databases. There's an Express, a Web, a Standard, and an Enterprise. But you can think of it as Microsoft's relational database management system. So when you've got a Microsoft workload and you want to store, retrieve, and manage your data, you'll typically use Microsoft SQL. Scales real well. Lots of security features as far as Windows goes. And it integrates with other Microsoft services. Relational database engine. But they have this TSQL. They call it Transact SQL. And that's going to be an extension of SQL that was developed by Microsoft to give you additional procedural programming capabilities. It tends to scale very well with regards to high availability because they've got these always-on availability groups and database mirroring and log shipping to ensure good availability and disaster recovery when needed. Regarding security, it's got encryption, row-level security, dynamic data masking, and even integration with Active Directory. So it's going to integrate with your Microsoft authentication system, which is perfect when you're running Microsoft workload. So there's some integration services, which is going to be a platform for data integration. There's typically reporting services that along with this that you typically get, which is going to be a server-based report for generating software system. You're going to have an analysis service, which is going to provide online analytical processing for data mining type functionality. It tends to integrate well with some machine learning services, specifically the integration of Python and R scripts with SQL Server. In-memory processing, because it tends to do in-memory online transaction processing, and it has a column store indexes to give you better performance for transactional and analytical workloads. You'll see it in a wide variety of enterprise applications. Anything that's got robust data management, high availability in the enterprise that's Windows-based, you'll see this. It scales, and it scales well, so it's widely used as a data warehouse. And it works with, your typical ETL, extract, transform, load processes and type analytics. And it integrates with, business intelligence tools like Microsoft Power BI. So it gives you a really good information to be able to store the information, retrieve the information, and visualize the information. So it's a pretty big database out there. You may see it in web applications. So web applications that were built on the .NET framework typically use this. It could be used for financial applications as well because of the transaction support. So when would people really use this? Where is this advantage? Well, for Microsoft shops that are running, Microsoft servers and Microsoft desktops, and they've invested in the Microsoft programming infrastructure like .NET, this really is going to shine. It's got good performance and it scales. Now, we're probably going to go to next, the king and the queen of all databases, which is the Oracle database. Oracle's been out there for decades in databases. Probably the most popular, if not one of the most popular enterprise relational databases in the world. It has an extremely extensive feature set and functionality. It's developed, licensed, and managed by Oracle. Amazon supports multiple versions of the database, Standard 1, Standard, and Enterprise. Of course, there's nothing to ever stop you from just putting your database on a virtual machine, copying it over from the cloud, and running it on an EC2 instance. But this is the Amazon's, database management systems that, you don't have to do that with. So there's 2 versions of licensing supported by Amazon. And this could pop up as a question. So the 2 options are Standard Edition 1 and Standard Edition 2, or you can bring your own license. And that's if you already have a license for the database. You've got some license flexibility, Standard, Enterprise, Enterprise 1, Enterprise 2. But, Oracle database, you may hear it called Oracle DB. This is a very powerful multimodal database management system. It's used everywhere because it's so robust, high performance, and its features are so good. It's a multimodal database, so it'll support relational, document, graph, and key value models, allowing you to store and manage a whole lot of different types of data. This thing scales vertically, it scales horizontally, it can handle giant volumes of transactions and data. It's got very high ability platforms because you can do these real application clusters. It's got Data Guard and Golden Gate. So there's lots of things here to make these systems run high availability. Its performance is great. They've got some advanced automatic storage management in it and partitioning and in-memory processing. So this is what you're going to put in a big load enterprise application for an organization that's got budget for it. Got lots of security. You've got really fine-grained access control. It's even got a database firewall with it. Lots of encryption. And it integrates very well with other Oracle products. And a lot of third-party applications because this is such a popular database and so many enterprises use it. Integrating into this is going to be relatively easy. So you'll see this constantly in banking and insurance and financial services organizations. You'll see it as the data warehouse because of its ability to scale and its analytical capabilities. Any kind of big enterprise application, you'll see this. Telecommunications, for example, think of the amount of data that's generated in telecommunication networks. Like every time somebody places a call or a text or that, it's logged somewhere. You could use something like this there. But people use it because it's robust, it's high performance, and it's got a big feature set. And they've got somebody they can call, Oracle. So huge community of support, lots of data models, very flexible. On-premise, hybrid cloud, multi-cloud, people can use this. So that is relational databases. The next content I want to talk about is NoSQL. SQL databases. So I'm trying to think if we should do that. How we do that. Are there, Chris, there are a lot of questions there? Because if there are, I'll go to questions for the next 18 minutes. Otherwise, I will go and spend about 20 minutes on this. And bear with me, my team lets me know. Okay, so let's do this. I'll go over some NoSQL databases, and then we'll get to some questions. So we'll talk about NoSQL databases, or not only SQL. These are not relational databases. They are designed to handle a wide range of data models that go far above the limitations of a relational database. The relational databases are designed, typically speaking, for structured data. NoSQL databases, by comparison, have very flexible schemas, meaning you can get very creative with what you use. So you can start huge volumes of structured data, unstructured data, semi-structured data. So where you're at in the middle of a Netflix movie, great place to store this. My brother plays video games and he stops a video game and he can come back and he's in the same place. NoSQL database. That is where these kind of things play in. So NoSQL databases typically follow a key value pair structure. So things are kind of stored in that typical environment. But the key here to remember is that the schema is very flexible. You can change it, modify it, delete a structure, for example. So the next thing to remember is because these things are flexible, and because they also are a little flexible with regards to when you store data. Like on a relational database, we said they were consistent. As soon as you store a transaction, it's immediately available in any other databases that are participating there. In this particular case, what we're talking about is much more flexibility. And if I store data in a NoSQL database, it might take a second or two for all the other databases to synchronize. But think about it. Instant means really hard work on the databases. Doing it a little inconsistently over a little bit of time, well, then, that's where these are going to scale. That's another thing that makes it scale. So let's talk about some data models. NoSQL databases will support a wide variety of data models, including document models, key value models, graph models. And, there's this concept of the CAP theorem, where it's consistency, availability, and partition tolerance. NoSQL databases will give you the ability to prioritize, 2 or 3 of these properties. So by doing so, if you make the consistency a little less, you can scale a little better. You can make it more consistent, then that's going to cause a performance issue. How you would deal with partitions, how you would create high availability, all that's going to determine the workload on these systems. Now, how is data stored in a NoSQL database? Lots of different ways. Some use a format called JSON, some are XML, some are BSON. Each document can contain nested structures. So an example of that would be, say, MongoDB or CouchDB. Lots of times these are used as content management systems for a user profile or a catalog. We got key value stores. So we can store data as key value pairs, where each key is going to uniquely map to a specific value. For a Redis cache, for example, would be this way. DynamoDB would be this way. So RIAC would also be this way. So this is good for caching or session management or real-time analytics. You can also use a column-friendly store. and store data in columns and rows, allowing efficient storage in large data sets. Apache Cassandra is a good example at HBase. And we typically use this with time series data or big data analytics. One of the coolest things about Apache Cassandra is it's made to run on commodity servers. Add 50 servers, these things will write to all 50 at the same time. So really great when you've got a lot of write load in Apache Cassandra. Under the guidance of NoSQL databases, we also have graph databases as well. And these store data as nodes, edges, and properties to represent the true relationships between the data. An example is Amazon NetToom or Neo4j. These are typically used for social networks or recommendation engines or fraud detection. So let's talk about why people use these NoSQL databases. They scale and scale and scale and scale. They are very flexible. So you don't have to be so structured, and that's why you can use them for so many different things. They perform real well, and they support a whole lot of different data models, so you can choose the best NoSQL database based upon your needs. Where do you see NoSQL databases? Big data. So imagine having millions of Internet of Things spewing data all the time. Imagine storing information in social media. Imagine every Instagram post, for example, is what do you call it? A NoSQL database entry. Think about something like that. Real-time web applications, online gaming, online chat, NoSQL databases. Content management. Imagine you're a company that's got a huge amount of unstructured content, blogs, articles, and media. Again, NoSQL database. Beautiful use case. E-commerce. Storing a product catalog or customer data or order histories. Big. In social networks, managing your connections and your interactions and making recommendations of other users. Use case for this. So, NoSQL, flexible schema, dynamic data structures. Compare it to an SQL database, fixed schema, so predefined tables and columns and structures. NoSQL, add more servers. SQL Server or a relational database, typically speaking, add a bigger server and then add replicas, caching, queuing. And we're going to talk about how to scale a relational database tomorrow and a NoSQL database. Let's talk about data integrity. NoSQL typically prioritizes availability or partition tolerance over immediate consistency. SQL databases enforce that atomicity, consistency, and isolation and durability, so instantly consistent. And then let's talk about the complexity of the queries. NoSQL databases have limited support for complex queries and joins. SQL queries, by comparison, support complex queries, joins, and aggregations. Okay, so I think we stop here and take a few questions. Tomorrow, we will get into the various NoSQL databases, and I promise you, we will get into more than just DynamoDB. So let's see if there's any questions. When creating a 3-tier architecture, is it possible to use RDS and S3 together? So imagine it this way. You have the relational database that's storing transactions in your 3-tier architecture. And the relational database uses what? Block storage. But you might have, for example, static content for the web. You might have a web, some web servers, say EC2 instances, or a virtual machine sitting behind a load balancer for dynamic content. You might have static content sitting in S3. So you could be using S3 to serve the web content, and then you would say have some of the static web content and in a virtual machine for the dynamic web content. And then that intermediary layer, that business tier layer or that application layer, the business logic would run on application servers. So yeah, we could use them all. It's just a matter of using them in the right use cases. Which database would I recommend as a universal database? This is a great question. So I'm actually glad I learned internal medicine when I was younger before I moved into architecture, because I learned there that there's millions of medications that are out there, and it's about choosing the right medication for your patient's condition. And two patients, one patient might be allergic to one medication, and another one might not be. One person's body may be different and require a different medication. So I will never recommend any universal application, because you have to evaluate the business needs before you know what there is. So the most dangerous thing you can do, Gabanga in tech, is become, I'm going to choose this. And what happens is then you become a hammer in search of a nail, and everything to that is. So I want you to learn this. There's no such thing as the best technology. There are many businesses now that are investing heavily in mainframe because they are so good at what they do. There are businesses that are leaving the cloud right now to go back to the data center for good reason. There are businesses that are running to the cloud. There are people that went to DynamoDB and then realized that they needed something different. There were people that went to the cloud and had block storage performance and then had to figure out something different. So what I want you to think about is this way. What problem are we trying to solve? And then what tool do we use to solve it? So if you were going to do construction, my brother has different kinds of screwdrivers, and he uses small screwdrivers, and some with an X on it and some that are flat. There's other things that he uses for bolts on my car. You have to use the right tool for the right job. So every use case will dictate it. I love that you asked that question. So I really want you to think about that. The same way that a physician can say, everybody gets azithromycin for every medical condition. You have to evaluate the needs of the organization, their goals, the strengths and weaknesses of every single opportunity that you have, and then you have to pick the best based on the traits. How does a multi-availability deployment provide high availability with synchronous replication? And how will read replicas provide scalability with asynchronous recommentation? So tomorrow, Preb, and I'm glad you're asking these questions, I will talk about how to do read replicas and how to do caching and how to use queuing. But today, here's what I want you to think about. If you have your database in one data center and something happens to that data center, like a fire, and that data center goes down and your database is only in that data center, you've got absolutely nothing. But if your database is in two different data centers and one of the data centers goes down, you're still good. Now, if you're in two different data centers on the cloud, or even three different data centers in the cloud, and the cloud provider has a major routing issue or a major security event or a control plane failure, you're dead no matter how many availability zones the data centers you are. And that's one of the drivers behind multi-cloud. But the way they do this is when you have your databases into availability zones, they do synchronous replication. So that is going to be replicated in real time. So one availability zone or data center goes down, the other one can instantly pick it up. Now, read replicas typically do asynchronous replication, and the data replicated to the read replicas is often going to be slightly delayed, not real long. Slightly delay, and that can enable the systems to handle the read traffic and reduce the load on the primary database. Hope I answered your question there. If not, you know how to find me. How does asynchronous replication support consistency? That is a great question. So when we're dealing with asynchronous replication, to some degree, it's eventual consistency, meaning it's not instant. So there is going to be a small, minute period of time where there's a lag in that. So it will be consistent over time, but not immediately consistent. So might take a second to synchronize from the primary. You're thinking down the right direction, though. I like that. What are some of the disadvantages of using Mac OS for the cloud? So I really want you to understand a couple things. So when we're in the cloud, we're going to put our servers there. And what is a server? A server is going to be a very high availability device, meaning it's going to have multiple power supplies. So if one power supply goes, the server can stay up on power. It's going to be plugged into the network in a couple places. It'll have a special kind of DRAM. So when you have a server, it uses error correcting RAM. So if the server experiences a memory error, it'll fix that memory error dynamically as opposed to your system crashing. So that is a server. Apple does not make any servers. So that's one problem. So there's no such thing as a high availability Apple device in today's world. The Mac Pro that they used to make with the dual Xeon CPUs and error correcting RAM, that was $60,000 to fully spec out. That was a server grade system. But most Macs are not server grade. Secondly, Macs, you can't buy anything with huge capacity. What are you going to buy, a Mac Mini? So there's nothing with regards to server capacity that's there. Now, they do have these little dedicated machines that you can use on AWS if you want to compile code for a Mac. So there's that. The next issue is almost nothing runs on Mac. I mean, nothing's on Mac for the most part. What's it, 13% of the computers that are out there? So now you're going to put yourself in a weird environment. Most servers in today's world run on Linux. Most. Some servers run on Windows. So you're going to run your applications on something that you're really going to need to work for the majority of your users. So that's kind of the main reason. It goes to cost, performance. And here's the thing. I had multiple Macs and Mac Pros and even the highest performance workstations. And they couldn't meet the needs that I have. I had to get rid of all my Mac Studios that had 40 cores in there and things like 24 cores in there. It just wasn't strong enough. The GPU performance was there. So it just didn't work for my needs. And Macs, one of the good things about them is that they tend to work really well because they're locked into a specific ecosystem. They only work with a certain set of partners. And that's how Apple keeps their systems fairly reliable. And that's not a bad thing. Business systems have to support technology that's 20 years old that's still there. You'll go to many banks that have an old mainframe that they can't get rid of because it's critical to business and nothing else can do it as well. So when it comes to enterprise business, it's not about what's cute. It's not about what's fun. It's about what's going to work. And that typically means not Mac OS. Although there's applications for Mac OS in the cloud, there really is, but you're not going to probably put your database in there because you can buy a Mac for $8,000, but it won't perform as well as something else that you could get at a much lower cost. So before we get back to our free AWS course, let's just do a few things so I know you're awake, alert, and oriented, so I also know that you've got access to the other things that are part of this free program. So I want to make sure that you know that we are spending a good 3 hours every day for about 2 weeks getting deep into the concept. But we're not just talking about the AWS certification concepts. We're actually getting into the technologies themselves. We'll get into these databases. As you could see, we didn't just talk about the databases that were supported like you'd find in the Solutions Architect certification. Yesterday, we really talked about a lot of the databases. We talked about MySQL, for example. We talked about Postgres, MariaDB, the Microsoft SQL Server. We talked about the Oracle options. And then we introduced the concept of NoSQL databases yesterday. And now we're going to talk about some of the NoSQL databases that are there. So we're going to have lots and lots of fun. So I'm thrilled that you are here. We have about 40 plus labs that I'd like you to do outside of this course. Here's the thing. After interviewing 6,000 plus technology professionals, I can find anybody out there who can click a couple of boxes and build something. But what I can't find is someone that knows why they're building it, or what the technology is, or how that technology works, and when that organization should use it. So we're focusing a lot more on that now, because clicking the boxes is easy. And, you can easily read the vendor documentation on how to do it. And also, while you're at it, do those free labs that we're providing. Do it on your own time. So I want to know where you're from. Let me know where you're from in the chat box. I see some people in South Africa so far. I see some people in Cameroon so far, only because I know where you're at. I see some of these names I know, for example, are in Miami. I know some of these people that are here from experience by the names are in India or Mexico, but I know a lot of you are from all over the world. So let me know where you're at. I also want to let you know that we've got a guide on which certifications can assist you in your cloud architect career. So please download that guide. It is completely free, and it's going to be in the description of this video. So I want to make sure you actually get that. So now we're going to start beginning. So give me a hashtag AWS SAA, Sierra Alpha Alpha. Welcome, Samuel. Welcome, Anna Marie. Good to see you again, Samuel. Miguel, thrilled you're here. Tyrone's over there in Cape Town. He works for us. He's a rock star. Derek, I am always so happy to see you. Thanks so much. Nate Ricks, One Love. That's, I love Bob Marley, so it's a song that I absolutely love, and I feel that way myself. Cypress, Texas. Hasnat, that's pretty interesting. And George, yes, I do remember you're in Miami because we're local. And Mark, I know you're in San Francisco. AP in San Jose. I used to go out there every week. And Ben Kim in New Jersey. I lived there for a while. Adrian in Phoenix. I love this. Miguel in Colombia. I haven't been to Colombia in a while, but it's really nice. And Nigeria, fantastic. We've got a lot of Nigerian people in Baltimore, Maryland. That's the place I worked for. And Toronto, fantastic. And Chesapeake, Virginia. Well, that's a nice place, Nate. And Anna's in Argentina. That's another really beautiful place. Sao Paulo, Brazil. Michelle, Leo for our team works there. And Miami. Yeah, Miami's a great place. Lagos, Nigeria. That's awesome. And Preb is over there in Sacramento. And another person in Nigeria. I love this. I love how global we are. And another person in Nigeria. Samuel, that's absolutely wonderful. This is great. And Colorado, I've spent some time there. And I'm seeing these AWS SAAs are coming in. The AWS Solution Architect Associate. Thank you, Mark. Thank you, Miriam. And thank you, Samuel. So Ben Kim as well. I know you're awake and alert and oriented, so now we can get into the fun. I just had to make sure nobody was sleeping. Come from healthcare, and in healthcare, we always check, the person's orientation, the person, place, or time. So I know where you're from, and I know that you are here and present. So let's get into the fun. And Mark, always wonderful to see you as well. So let's talk about DynamoDB. And here's the thing. DynamoDB, which we're going to begin with, is a wonderful database, but it is an Amazon proprietary database. Given that 98% of customers in today's world are multi-cloud, Dynamo database is something you probably won't use in the real world multi-cloud environment. Not because it's not an awesome database, because it's really good. But, there's certain databases that you can put in all your clouds at the same time. And DynamoDB is just not one of them. But let's talk about it anyway, because there are certain use cases where you may want to use it. Especially if you've got a customer that for whatever one reason, maybe availability isn't critical to them. Maybe they prefer simplicity. They might find them in just AWS, and they may want to use these proprietary tools because they're easier to use, lower on the maintenance and the overhead side. So let's talk about DynamoDB. It is a fully managed NoSQL database, proprietary database by AWS. Fully managed means you don't have to think about your servers. You don't have to think that much about your storage infrastructure or performance. It's done for you. You're not patching hypervisors. You're not patching the BIOS of your servers or any of that stuff. Bear with me for a second. Okay, so there's some simplicity and elegance with this. Amazon will manage the operating system, the servers, the theoretical security in that system. DynamoDB is going to be stored on high-performance SSD storage, so it's going to be as good as you're going to get in the cloud. And it's a fully managed system that's designed to deliver fast and predictable performance. And because it's a NoSQL database, that's going to scale, and it's going to scale real well, like all of them. Now, they say DynamoDB has low millisecond latency. Every millisecond counts. And you can use this DynamoDB accelerator, which is going to be an in-memory cache. That can lower the latency to sub-millisecond if the data is frequently accessed and it's going to hit the cache. DynamoDB will encrypt all data by default. And you can back it up with almost no performance on the database performance, which is great. It can be set up for global cross-regional application, meaning you have it in the US and then you have it in Europe and they just synchronize themselves, which you could do with pretty much any database that you would work with. And DynamoDB typically uses tables, which are collections of data, that has items which are going to be individual records in the table, very similar to rows in a relational database. There will be attributes, which are going to be data elements within an item. And again, that's going to be similar to the columns in a relational database. We will have a partition key, and that's going to be a single attribute. And the value of the attribute is going to be hashed to determine the partition or the location of where the data is stored. DynamoDB will have something called the composite key, which is going to consist of two attributes, which are going to be the primary key and the sort key. And this is going to enable an organization to have multiple items or with the same partition key. But they're going to have different sort keys. If you're familiar with NoSQL databases, you know what I mean. DynamoDB supports secondary indexes, which means you can run queries on the 9 primary key attributes. So it'll give you lots of flexibility in querying the database. It also has the concept of a local secondary index, which will use the same partition key as the primary key, but it's going to allow, querying the database on a different key. Now, DynamoDB can support a fair number of data types, string data, numbered data, binary data, Boolean data. It can, support that like a list or a mass document type. And it can, for the set types that it can support, it's typically string sets or number sets or binary sets. Now, when you're dealing with DynamoDB, there's 2 ways you can kind of set it up. You can use auto scaling, which is going to give you capacity as needed. Or you can use provision throughput, where you tell it exactly what you need and it's going to be there for you. As a rule, if it matters, you need to know what you need ahead of time, so provision it. If you don't know what you need, that's when you would use something like an auto scaling. Now, there is an opportunity to deploy a cache. They call it the DAX, or the DynamoDB Accelerator. And that's going to be an in-memory cache to reduce read load on your systems. DynamoDB can capture changes to items in the table, for example. And you can integrate it with, say, AWS for real-time processing. If you needed to have these atomic type transactions that would adhere to, say, the ACID profile, like a relational database, where things are instantly consistent, you can do that. You can ask DynamoDB to be instantly consistent, but then anytime you make a NoSQL database instantly consistent, you're going to lose some of the scalability. And you're using these databases because they're more flexible, and they're more flexible because they also scale better. They scale better because they're not immediately consistent, so it reduces the overhead burden quite a lot. So where would you use DynamoDB? In the same place as you use any other NoSQL database. Gaming. High-performance gaming applications with a lot of data. IoT devices. You've got millions of these things out there, little weather sensors, and they're out there, and they're coming into a database generating constant data. Website management, content management, store large amounts of content like a social media provider could do. Of course, they're most likely going to use an open standard. So, some best practices with DynamoDB are to be efficient with your primary keys. Design the primary keys to evenly distribute the data across the partitions. Use indexes to optimize query performance. Plan your capacity ahead of time. Well, understand your read-write capacity units so you can provision it and provision it properly so it'll be there exactly what you need when you need it. Model your data. So model your data to minimize the need for scans and maximize the use of queries. And I hope that sort of makes sense. So next, Amazon has a quantum ledger database. We will talk about open standard databases too. The Amazon Quantum Standard Database, again, is another fully managed database. It's going to be a ledger database. And it's designed to provide an immutable and cryptographically verifiable transaction log, meaning the log and history will be there over time. The quantum ledger database is really good for applications that require transparent, permanent, and cryptographically verifiable histories and changes to data. So think about a financial transaction. You want to know it hasn't changed. Or supply chain tracking. If some product is delivered or at a location, you want to know that it's going to be there. So the key with quantum ledger to remember database, remember it's immutable. So it's not going to allow your data to be written over. That's why we'd use it. And how do you verify data that hasn't changed? Well, it uses cryptography, and specifically it uses a hash to prove that the data is what it's supposed to be and it hasn't changed. And quantum ledger database is an Amazon thing, but remember, it's managed. So they manage the infrastructure, the scalability, the backups, the maintenance. And, there is an advantage to using a managed service. You spend less time focusing on your infrastructure. Of course, you lose control. And it makes it harder for you to leave things when you need to. But, everything is a strengths and weaknesses, and architecture is about evaluating all the trade-offs between your options and choosing the best one for the needs of that specific business. Some things to think about, key features with quantum ledger database is it's got very flexible querying. It supports SQL or PartyQL. So you can really query your data fairly easily. It automatically scales. And, it's about as high as availability as your cloud provider is going to be because they're managing it in multiple availability zones. So you have that. You could use this for supply chain management to make sure that a product hasn't been stuck. Financial transactions, I mentioned. Potentially, you could use it for a healthcare record because it's tamper-proof. Anytime where you need compliance and audit requirements, things for a government public sector like a land permit, you don't want that kind of stuff changing. So I think that can be helpful. So now let's talk about how do we optimize our certain databases. What can we do? So we're going to talk about how to scale relational databases, and we may get to it later. There are open standard databases that you can use for NoSQL databases. For example, MongoDB, you could put your database servers in 3 different clouds. Apache Cassandra, you could also put your database in multiple clouds and data centers all at the same time. Now, Apache Cassandra can write to all nodes. And therefore, if you've got a very high write load NoSQL database, typically speaking, Apache Cassandra is what organizations use. If you've got a very high read load database, MongoDB gives you some incredibly good performance for that. And that's typically one of the things that organizations use to select each database. But there's other options too. So let's talk about some of the Amazon database optimizations. We'll talk about backups. We'll talk about how to scale things, etc. And we'll begin with backing up. So backups, when you use any of the AWS relational databases, and this could be MySQL, it could be Postgres, it could be DynamoDB, it could be anything. When the systems do their backups, they actually take your entire virtual machine and turn it into an image. So if any of you are familiar with commercial imaging software, Symantec had a product like Ghost. There's a couple of other, there's many other options that are there, like Marconium has an instance. But what you do is you take up the hard drive or the virtual hard drive, like the block storage drive, and it creates a little bit by bit identical copy in the form of an image. And that all that's necessary is take that image and relaunch a virtual machine. Kind of like taking the file that you have for a virtual machine in a VMware environment and moving that file to another server. So it does a very good automated backup, anything on AWS. Best kind of backup, honestly, you can do. And businesses use this kind of backup and software to do this themselves, but this happens automatically, which is pretty nice. Now, a backup will typically happen during a defined window each day. And when the systems are being backed up, as a rule, temporarily, for a very short period of time, the database storage may not be available. So it might not read or write for a short period of time. And it could also just degrade the performance of the database during the backup process. So you can also do a database snapshot. And you can manually tell your beta database, back up right now. And that will give you a point-in-time copy of everything that's on that block storage volume that you have. And it'll be maintained until you delete it. Now, what it really looks like, and I love these kinds of image systems, and I've been working with imaging systems for backups for decades because they're super effective. Here's an example of what you can see. So you'll have your database, and it's going to become just one file. And here's the thing. You've got that one file. And from there, poof, you can launch another virtual machine. So another database with all your data. So I tend to love that. So here's the thing. When you've got an image and you restore it, it's going to boot up a new virtual machine. So if the IP address on my current virtual machine is 10.1.2.3/24, or let's say it's a cloud one, so we'll use a higher number. We can't use the first few. So let's say it's 10.1.2.10/24 is your IP address. That's your image. When you relaunch the image, it's going to be in a new virtual machine. So if the image comes up in a new virtual machine, when you reboot or reset your database from the image, it's going to have a new IP address. And it will also have a new DNS name. So if you've got application servers pointing to the database, you're going to have to change that DNS name or the IP address that they're pointing to. And it usually is a DNS address for lots of reasons. So what's it going to look like? You take that database image, you launch it into a virtual machine, and poof, it's up. So if you're familiar with the concept of an AMI, that's an image of the system. If you've ever downloaded an operating system, like Windows or Ubuntu or something like that, and you get a .iso file, and then you take that ISO file and turn it into a bootable drive with all the install files, that's a system image. So that's really what we're talking about. Now, when we're talking about these databases, we want to encrypt them, right? We don't want to leave data on the database unencrypted. That'd be ridiculous. So what we can do is we can encrypt the storage volume, the block storage volume, or the EBS volume where the database's data is, and poof, your data is encrypted. Now, this is going to be done with the AWS Key Management Service. And we talked about the AWS Key Management Service earlier about how that, realistically speaking, basically can help you manage the keys that are used for encryption, decryption, that sort of thing. Now, AWS, thankfully, also can support what's called transparent data encryption. And if you're using one of the more industrial databases like the Oracle database or the Microsoft SQL Server database, they're going to support what's called transparent data encryption, and it's typically done with the Cloud HSM module. So here's what transparent data encryption is. The data is encrypted on demand and decrypted on demand. So you write it to storage. When it's written to storage, it's going to be encrypted. And when you access it, it's going to be decrypted so you can access it. And then when it goes stored, it goes back to being decrypted. And that's in addition to just, being able to encrypt a storage volume. And a Cloud HSM is going to be a hardware device. We'll talk about it for managing hardware keys. So when you think about that and you can encrypt when it's stored, you can also encrypt in transit. So if the data is encrypted when it's stored, decrypted when you access it, what you're accessing is not encrypted along the wire to you to them, or encrypted as it traverses the Amazon network, or encrypted as if you were to access over the internet. So you can also do what's called encrypted in transit. So you got encrypted storage, it comes out unencrypted, TLS encrypts it on the way to you, TLS then decrypts it when it gets to you, and then it's there. So how do we use any kind of TLS protocol? Well, there's these SSL certificates we tend to use. So let's talk about scaling our databases. So in today's world, databases are, realistically speaking, a mission-critical business application. I mean, as much as you can think of it, they're everywhere, right? So they need to perform. So how do you scale your database? Well, we've got the concept of vertical scaling and horizontal scaling. So scaling up or vertical scaling is very simple. My current server has 128 cores and 2 terabytes of DRAM. I move it to a 256 core server with 4 terabytes of DRAM, and I've got more power. So that's the easiest way to scale. But I can promise you, no matter what you do in a global enterprise environment, there's often no server that can handle an organization's database. You might need a bunch of them. So that's where we talk about scaling out. And some databases enable us to scale out a lot better. For example, Apache Cassandra, we can just add 100 of these 100 different servers, and they just glue together very easily. And they write on all nodes. Oracle's got some incredible scale out performance that's unbelievable. And other ones, like most of the relational databases, don't scale that way. So we're going to talk about how we scale relational databases. But just understand that no matter how much you go up in size of a server, at some point it's not going to be enough. So we're going to have to get into this horizontal scaling as well. So let's talk about scaling certain databases. NoSQL databases like Apache Cassandra, we can scale them via partitioning the database. And partitioning the database chops the database into multiple portions. And then the application itself has the intelligence to route between which and the partitions are there portions. So that's one way to scale it. Now with Cassandra, we can also add more servers. So Cassandra scales real well. And but that's really what we're talking about with partitioning. And you can partition a relational database or a NoSQL database. Now, scaling out relational databases is going to be very different than scaling out NoSQL databases. With Apache Cassandra, I just add new database servers, and it's so easy, and it scales so much. But for the most part, most relational databases don't work like that. Oracle's got the ability to do more, but most relational databases don't work like that. So we're going to divide our databases into read traffic, write traffic, and we're going to have to get a little creative in how we actually enable the relational databases to scale. But that's okay. I'm going to teach you how to do it. So let's talk about reading versus writing. Writing to the database is taking in the information. Reading to from the database is when you guys, ask questions of the database. So right now, I'm giving a presentation. I don't know, about 7,500 people have seen this presentation at some point during this week. And as I'm giving a presentation, which takes a lot of effort, and I'm thrilled to do it, and honored to do it, and privileged to do it to help you all, but it takes a lot of effort. People are asking questions in the chat box, and that's great. I want you to, but do you really think I can give 100% of my effort into giving a presentation and then answering questions in the chat box? No, that's not possible. So you see some real rock stars from my team, like Christopher Johnson, like Tyrone, like Eddie, who lives in Cameroon, in that chat box. And when you guys ask questions, they will take those questions, collate them, and then give them to me when I can actually pay attention on answering them. Well, we have to do the same thing for the database. So what we will do is we will divide our read work and our write work, because at some point it's impossible to do just both. So we're going to talk about what is a read replica, and then I'm going to show you how we use them. But for right now, you can think of Christopher Johnson and Eddie and Tyrone in that audience as a read replica. They're far more than that, but we'll call them read replicas for right now. So what is a read replica is we take our entire database and we make a basically identical copy of the database. And when we point our queries, our questions to the identical copy. So ask the copy database information about that what you have, and the primary database can then focus much more on writing information. And these two are synchronized in near real time. So we reduce read load with read replicas, and I'll map it out architecturally for you so you guys and gals all really get it. Now, you can look at it this way, and this might help you look at it. And we're going to go through much more examples. But let's say you have a basic 3-tier application where you've got a web server or multiple web servers serving up web content. You have the application servers running the business logic. And then our transactions are going to be logged on these read replicas. I'm sorry, on the database. So the transactions will be logged in that RBS DB main, and we will push the same information to the read replicas. So basically, they're going to able to respond to the queries or the reads. I'll map it out for you. We'll do a little architectural mock-up. But when would you use a read replica? When there's read activity, a lot of read activity. If I have 4 times the read activity than I have write activity, I need to use 4 times as many read replicas as my primary database. Now, if query traffic to the database is not slowing the database down, we might not need this. But if the database is busy and it needs help, add a read replica. So keep that in the back of your mind. Now, read replicas are not for disaster recovery. They are used for performance to offload the read load. Now, the next thing we're going to talk about is caching, and then we'll map it out and design an architecture together around this. Caching is when you put something in front of the database that when people access the same information, the cache answers. So we walked through various forms of caching earlier, but again, we'll do it again when we map it out architecturally. But here's the thing. Let's say I have a NoSQL database right now. But let's keep it. And what I have is a photo of Katy Perry and Taylor Swift's cat on it. And that was part of an Instagram post. And Katy Perry and Taylor Swift go out there. I know these names because my wife likes the 2 of them, and she dragged me to both of their concerts, and I do whatever my wife tells me. But that's neither here nor there. They both tweet a photo of their cat. And apparently it makes it to all the newspapers about their cat tweeted photo. So, you know, all the Katy Perry and Taylor Swift people want to go see this cat because they posted it. And any cat cuckoo like me that loves cats also wants to go see the cat because they likes the cat people. No, imagine 10 million people go look at this cat. You know, if it was a web environment, if we put the cache there, only the first few people would actually, depending upon where they're at in the world, would request a photo of the cat. The cache would store the cat in memory, and every time somebody wanted to see it, the cache would answer, and the web servers would be relaxing. It's the same thing we're doing here with database caching. So we're going to do database caching to smooth out read load. So read replicas, offload the read work from the database, and caching could potentially reduce the read load on the read replicas. Now, here's the thing with caching. If Joey is looking for one thing, and Sally is looking for something else, and Maria is looking for something else, and Aguilo is looking for something else, and Apostoli is looking for something else, then the cache isn't going to come into play. It's only when people are looking for the same thing. So if the people requesting the queries are all requesting additional different things, and you add a cache, the cache is going to slow your performance, not improve your performance. So this is why you can never design an architecture without knowing what your use is and how people are going to use it and your traffic patterns. So we have to figure out this on a case-by-case basis. So we'll talk about this, and I'll give you an example of what this looks like. In this case, you'd have your web servers and your app servers. And you can see we've got a primary and a backup in different availability zones. And we stick a cache directly in front of the database. So when it comes to caching, understand most people use either a Redis cache or a memcached. And if you wanted to basically build your own virtual machine cache and stick it in AWS and stick that same virtual machine in Azure and the same one in Google, you could. And that's what we do in private clouds and multi-clouds and all kinds of things. But if you were in AWS and you wanted a fully managed cache, if your use case supports caching, well, AWS has a fully managed cache for you. And of course, which are your 2 options? A Redis cache or a memcached, because it's just them running basically caching servers for you to help improve the performance of your systems. The difference is they manage the servers which means you don't have to think about patching the operating systems and everything else because they do it for you. But you lose control, or you do it yourself and you have control. Your use case will determine what's appropriate for you. Now, when it comes to choosing between Redis or Memcached, both options work. Generally speaking, Redis offers many more features, some real advanced data structures, very high availability, cool replication, failover, session persistence, and Memcached is going to be simple, but it's still high performance, but it's very simple. So it's a lower featured set type cache. So let's think about some use cases where you might use these. Let's say you want to speed up some application things. You might tend to use a cache like this. You want to get some real-time memory analytics. This will, because it's an in-memory database, actually, it'll give you some fast processing and analytics. Maybe you want to have a gaming leaderboard where people are playing different games and the scores are constantly changing. It could be used something like this. So lots of use cases for something like this. We could use it with relational databases. We can use it with NoSQL databases. We can technically use it in serverless environment as well, like with an AWS Lambda function, because we could use, like, say, Elasticache to quickly access data in a serverless application. And, by using the cloud providers managed cache, you're going to get, alarms for performance and things in CloudWatch. If all this stuff is on your own, you could ultimately use different, more commercial packages as well to manage these things across clouds. So we talked about read replicas, which is basically offloading read load. And then we talked about caching to offload read load. What about write load? So this is going to bring us into queuing. So imagine this. Imagine you've got millions of messages coming at you in a second, and you're catching them as fast as you can, right? You're getting them, and then you miss some. Why would you miss some? Because maybe your hands can't keep up with all the balls that you have to catch if things are coming at you, okay? So there's a couple of ways that we could actually deal with this. What if I threw you the first ball, thought you caught it, gave you the next ball, you caught it, and then I sent you the third ball? Would that be easier? So imagine how much work you'd have to be going back and forth, trying to catch things and jump all over the place. Your heart rate would go up, right? You'd start to sweat. You'd get out of breath. You'd get tired. Well, basically the same thing happens to the computer. They get too many messages coming in. The CPU hits at 100%. The CPU hits at 100%, and everything ceases to function. And it's the equivalent of dropping all the balls. So how do we deal with it? Throw one ball at a time. As soon as you get it, I give you the next ball. I give you the next ball. I give you the next ball. That's queuing. Queuing is basically forming a line and getting the things when you're ready. So when it comes to scalability, often decoupling things makes it better. You saw how we talked about scaling the data center by putting the storage in one part of the data center and the servers in another part, and using block storage, connecting it over the network. Well, same thing here. So what queuing does is a way to schedule your messages, which keeps you from losing messages, which is a very good thing. And it keeps the CPU down, which means your databases can scale even more. Offload the read work, offload the catching the balls until you're ready to do it. You're going to get a lot less sweaty and a lot less out of breath. See, here's how it works. The sender sends a message into the queue, and it hangs out in the queue. And as soon as the receiver is ready for it, it pulls the message from the queue. And then the queue drops the message after it knows it's delivered. So in the future, it has less messages delivered. So this is going to be something that's really going to help our system scale. There are lots of queues you could use. In a multi-cloud environment, you're typically using Apache Kafka. If you are going to allow yourself to be locked into a single cloud, with AWS, you would use SQS, which we'll talk about soon. And I promise you, at some point, when we cover these things, we will get together and we will put together an architecture project. So the Amazon proprietary managed system to support queuing is the simple queue service. And they enable two types of queuing by default. A standard queue, which is messages come in and out as fast as you could process them. And that's generally going to give you the best performance. The alternative is something called the first in, first out queue, which is I send message 1 in, you take it out. I give you message 2, you take it out. I give you message 3. So that will generally give you lower performance. And here's the reason why. Message 1 may be a small message. Message 2 may be a big message. So by slowing it down into the way they're received sequentially may not be the best for performance. So just keep that in the back of your mind. In this example, you can kind of see what would go on with your CPU. If you were catching all these balls, for example, your CPU, would be running up really, really high. And maybe, the stock market opens and people process a lot of trades, right? So when that occurs, you might lose messages that the CPU might be too high. And then there's a period where nothing happens and the CPU gets real slow. And then a period where it gets crazy and the CPU goes up to near 100%, maxes out, and the computer crashes. We don't like this. But by draining that queue, pop it in, take it out, pop it in, take it out, we can slow it down. And because we slow it down, we can make the CPU on your database be much, much smoother. So instead of going anywhere from, say, 20% to 90%, we can keep it at 40%, which is going to enable us to scale. So here's what I think we should do. I will come back, answer some questions for a few minutes, if there are any, and then afterwards, we're going to go have fun and we're going to architect a high performance, high availability database. What can say about masking data in the database? So there's a lot that can be said. So the first thing I would say is, what's the use case? What are we trying to achieve and why? But there's lots of times when we may do masking of data. For example, we may have a lot of types of data that could potentially personally identifiable information. We may want to take that data and aggregate that data so we can run a research project on it, but remove that personally identifiable information. So that could be a type of data masking. You could also see that as data anonymization, but there's other types of masking in this concept as well. But generally speaking, that's why we do most types of masking, at least from an AI perspective or a big data perspective or a research type perspective. Chris, let's go to the next one. How does API architecture and API gateway is implemented and used in database? Please explain in details. So that's part of the overall application architecture. So the key is an API is going to be used anytime you want one application to talk to another application. I'm going to have APIs everywhere. So we're going to have APIs on the routers on that network because you're going to be pushing and pulling configurations from that network. We may have APIs with our IDS IPS systems to be able to push and change things that are going on there. We will have APIs that are used to connect our database, for example, to maybe the application servers. But we may have APIs to connect our database to other things or even other things to support the database like queues. So asking how does API architecture work, that's a 400-hour answer for an application architect. So I'm not an application architecture, but I'll give you a little bit of guidance on this in the meantime. But, realistically speaking, you can think of an API as kind of an endpoint to kind of create or do something with a database. Maybe for your CRUD operations, like your create, your read, your update, and your deleting data in the database. And, we can think of API gateways as a place to receive the API client requests and then route the request or direct the request to the appropriate backend service. The API gateway may manage the authentication and authorization of the request itself by integrating into an IAM system. And an API gateway can also limit the number of requests that are going to hit that API so it doesn't exceed the API's performance. Or in a DDoS attack, if you get way too many people trying to push to an API, you can throttle them to make sure not too many get there too fast. Now, as a backend service, we could be dealing with APIs to be performing database operations. It could be involved in, say, data handling, like receiving and processing data, or returning results to the client via an API gateway. And in a manner like maybe a client sends a request to an API gateway, the API gateway would maybe route the request to, say, a backend service. The backend service then will interact with a database, and then the response might be sent back to the client through the API gateway. But that's just one use case. And APIs and API gateways and what they could be used could literally fill a 500-hour training session that an application architect would do. But I like the thinking. What is the advantages and disadvantages of vertical and horizontal scaling? Well, with vertical scaling, it's really simple to implement. You just put in a bigger server. And there's no code changes. There's no need to modify the application. There's nothing. Horizontal scaling, it depends. So if I've got a database like Apache Cassandra, that's designed to work on what's called commodity servers. Here's what commodity means. Cheap, couple $1,000 servers. So with Apache Cassandra, I just add a bunch of virtual machines. That's designed for horizontal scaling. But it all depends on the database itself. If I've got a database that can only write to one node, the master node, and I can't add additional horizontal scaling, I may have to make that master node huge vertically. And I might still have to scale out horizontally, because scaling horizontally can handle the load by offloading more servers. And horizontally loading also improves my availability. If I've got 50 Apache Cassandra servers, and 3 of them go out in an availability zone crash or a security event, I still have 47 more running. Whereas if I have just one big server and that goes down, so it's that. So horizontal scaling tends to remove single points of failure. And often horizontal scaling is cheaper than moving up into these big bad servers. But it also will make it life more complex with horizontal scaling. And it makes data consistency a little harder with horizontal scaling. So it's about really looking at it and choosing the best option for what the use case is. But, that's good thinking. What is the time frame of sending, queuing, and receiving, inserting the data? So it depends on whether the systems are ready to receive the data or not. Having said that, with Amazon SQS, it's typically milliseconds to a few seconds to send to the queue and for the message to be drained. Now, several seconds is a lot. Milliseconds can be a lot too, but depending upon the application. But the choice is the queue make sense? And how much stuff is what's coming in and what's the capability to receive it? So that milliseconds to seconds, that could be horrible or it could be nothing. So it's really based upon the application and what it needs. But generally speaking, with inserting or writing, that again is within milliseconds to a few seconds, depending upon the database loading configuration. But the latency, the service, the load, all of that's going to have a massive impact on what you're actually going to see. All right, so my team, read replicas, if you will, to keep it on the database theme, and we're going to go architect one together, have told me there's no new questions that have come in. So let's do this. If you're having a good time, please like the video. And if you're not a subscriber, please subscribe and hit the bell to be notified of new videos to help you in your career. If you haven't downloaded the labs or signed up for the free labs, go sign up. We have about 30 hours or so of live training that we're going to do. And I've got, 40 plus labs for you to do. So go do them too. So I want to make this a rich, full experience for you. And to know that you're awake, to know that you're alert, to know that you're oriented, please give me a hashtag. Hashtag SAAC03. SAA-C03. Sierra Alpha Alpha Dash Charlie 03. When I see that, we will start getting back into the content, and I'll just drink a little bit more of my alkaline water here. All right. So let's get back into the content here. I see you're all awake, alert, and oriented. So let's put some of the pieces together and how we can do this and how we can make it scale. Let me set up my whiteboard real quick. I've got pictures we professionally drew, but I don't think they're going to give you the same mileage as if we just go out there and we whiteboard it. So let's do this. Let's say this over here is our master database. And for traffic purpose, I'm going to show the way we do the traffic today. The traffic is coming in this way. So let's say we've got some web servers over here. Web servers. And then maybe we've got some app servers behind it. Oops, didn't mean to do that. Now let's say we've got a database over here. And this is your primary database server. And to make this look easier, we're going to be reading the data from the database over here, even though it would be another way, but just make it easy to understand. So somebody comes in from here, they hit the web server, they hit the application server, and they want to scale stuff to the database. So right now, this database is taking requests, and this database is requiring to requests. A million requests come in. It has to deal with the million requests and the million replies. And let's say there's also a million writes that come in. It has to do a million writes, a million requests for information or queries, and a million replies. The database is getting tired. It's exhausted. It's like a cat. It's like catching, balls every tenth of a second. It's going crazy. The CPU is high. So the first thing we can do is vertical scaling. So we were on a 64 core, and this is going to be a big database. Most of them don't use this, and 2 terabytes of DRAM. But I've worked with plenty of places that do. So now we're going to go from the 64 cores with 2 terabytes of DRAM. We're going to go vertical scale, and we're going to change this to a 128 core server, and we're going to change this to 4 terabytes of DRAM and a really good hard drive, and this thing is now happy. Now, guess what? It's not going to scale, because now that we have this, hopefully the business is going to grow and more traffic is going to come in. So a lot of what this database is dealing with is stuff's coming in at it to be written, and all of these requests are also coming in that need to be responded to. So now let's deal with the responding to. Let's say we've got 3 times the read load to the write load. So what do? We put 3 read replicas on here. If it's 4 times the read load to the write load, we use 4. So we'll call this an RR for read replica, RR for another read replica, and an RR for another read replica. Now, things have gotten a lot better. The data gets written to the database, and the database writes the data to the database. And every time someone sends information to a read request, these read replicas say, got you covered, I got your 6, don't worry, master database, you don't have to do this. So you can see how the database is relaxing a little bit, because now it only has to deal with writes. And these guys, these read replicas, are doing all the reads. So we've made our system very interesting and very relaxed. Now we need to think about it. And now this database is the front end to, give me a superstar that everybody wants to see what they do, or somebody with 50 million Instagram followers. So now a person tweets, a famous person tweets a photo of their super famous cat. This cat's worth like $1 billion. It's like the cool cat with 100 million Instagram followers because everybody loves the cat in addition to the cat's owner. So now everybody's trying to request the same cat photo. They're coming from all over around the world to look at this cat photo. Well, now these read replicas are getting tired, right? So we'll put a cache over here. And we're going to use the cache is going to go along with the read replicas. So now we have Chris wants to look at a photo of a photo of Snoopy. I don't know. He hits the read replica. He goes to the cache that's not in the cache. Chris gets a photo. The read replica says, I've got a photo for Snoopy or the data for Snoopy. The read replica sends it back. No big deal. That's the way it's supposed to. It's new traffic. Now everybody wants to go see the royalty cat. The first request goes through the app, hits the cache, hits one of the read replicas. The read replica responds, and guess what? Now the cache stored all the photo responds. Now the next 50 million people go to look at the cat that day, and it hits the cache, and the cache says, I got you covered. Read replicas, you don't have to work so hard, and it sends it back. So now we've integrated caching. We've integrated read replicas. So where do we put queuing in? So here's where the queuing is going to come in. And I want to kind of... So now we got that database, and it's happy. It's doing a great job. And now while we're at it, you know, those millions, the 50 million cat photos are going out there for the people that requested the celebrity's cat. And now the celebrity says, I have a special t-shirt with my cat's one-on-one signed paw prints in it, and you get a photo of me with an autograph. Now what's going to happen? Well, now we got a lot of things. First, we got people coming in to see the photos of that thing, and the read replicas and the cache are responding to that. But everybody likes these photos, so now they want to order 1 million of these things. So now they stick 1 million orders coming over here. And they all sit over here in the cache. And then the cache sends them to the database as fast as the database can do it. And by doing so, if the database can only unload 500,000 of these, and this thing has 500,000 left, 0.5, and then while we're at it, another 2 million orders come in, which the database couldn't ever actually deal with. You know, now we've got I'm sorry, this isn't the cache. This would be the queue. Bear with me. It was the queue that's going to store the messages. So initially we had 1 million. We had 1 million requests coming into the cache. The cache, into the queue. So all these requests came into the queue. The queue sent it to the database as fast as it could. Only 500,000 of these were drained, so we have 500,000, but we've got 2 million orders for that special cat memorabilia or whatever it is, and the what do you call it, the autograph. So now they also sit in the queue. So why is this? So that one thing is when the CPU is too busy, we didn't lose those 2 million orders. So that's why organizations use this combination. Queuing reduces the write load on the system. Caching reduces the read load on the read replicas or the primary database if you don't have read replicas. And read replicas, they actually offload the read load from the master database. So I hope that made life a lot easier for you. And if that helped you understand scaling a database, give me a hashtag database architecture so that I know that it helped, because I hope that whiteboarding really did a lot to make it clear for you guys. So now we're going into some industrial grade NoSQL databases. So as I mentioned, I love DynamoDB. It's a beautiful database, but in 98% of organizations, it's not going to work because they're multi-cloud. So if we need a database that's going to work across clouds, it's going to move us into things like Apache Cassandra or MongoDB. Now, Amazon has a fully managed Apache Cassandra database, Apache Cassandra compatible database for you. And it enables you to run your database, your Cassandra type workloads on AWS without managing your own Apache Cassandra servers. And if that's something you're looking for, then that's something that's going to work very well. Yorgos, it's good to see you here as well. It's going to help you in a lot of ways. So think of Keyspaces as an Amazon managed Apache Cassandra server. And it works and it's compatible with a Cassandra query language. And if you've got an Apache Cassandra workload and you want to move it to something that's fully managed in the AWS, that will work and it will work really well. So I hope that makes sense. While we're talking about Keyspaces, it's a way for you to run and migrate to something that's not there. And by not having to provision your systems, you won't have to patch it. You won't have to manage the servers. So it does add some simplicity and elegance to you. It tends to scale well because it's fully managed. They typically scale up, scale down, whatever you need and when you actually need it. And, it's a high availability system that integrates beautifully into the AWS identity and access management systems for access control. You can put it in your VPC for that kind of thing for network isolation, or at least it supports the Amazon VPC for network isolation, and it gives you good encryption at rest and encryption standard. Now, when you're dealing with these Keyspaces or Apache Cassandra, you've got two options: on-demand mode and provision capacity mode. On-demand is it just sort of figures it out. I don't like leaving anything that matters up to figuring it out. Servers have a hard-coded IP address. You don't let them float around. You need to know where your applications are pointing. Networks are manually configured. And if you know your systems and you've got good capacity planning, use provision capacity because you'll know you'll get it when you need it. On demand, you will most likely get it when you need it. But you need to know your things before you do an architecture. So with an on-demand mode, you pay for the reads and writes you use. You don't specify it. And it just gives you and accommodates for you. But provision, you know what your information is, and you will specify it and you will get it. And if you find you're using too much, no big deal. So kind of hope that we're here. So next, where we're going to head, we're going to start talking about getting data and stuff to Amazon. How do you get your data there? Well, there's one way you could do it, which is what a storage gateway is. And what's a storage gateway? So a storage gateway is a virtual machine that is Amazon calls an appliance. And basically, it's a pre-made virtual machine that'll either be used with Microsoft's Hyper-V, the Windows Server native hypervisor, or VMware, which is what most organizations actually use as their enterprise-wide hypervisor. And it's kind of great. So you mount the server in your data center. You've got your, say, direct connection or your VPN over to AWS, and it will just copy your data over for you. So if you've got a hybrid cloud and you want to keep two sets of data in two places, the storage gateway is awesome. So if you want to migrate to just the AWS cloud, the storage gateway is a great way to do it. Now, when it comes to storage gateways, there's really three kinds. There's what's called the volume gateway, a tape gateway, and a file gateway. And we're going to talk about all three. We'll start with the file gateway. That's going to be an appliance meaning virtual machine, that's basically a file server, and it will just connect it to the cloud. So it can be a Windows file server that you would use, and you would use the server message block protocol, or you can mount to it via server message block for Windows, or it also supports NFS for Linux. So you got a bunch of Linux and Unix systems, you connect to this file server via NFS, file share, and then it just copies your data asynchronously to S3, and it's stored as an object on S3. I mean, that's really cool. Have everything you want, make it your main file server, and you have it locally for the best performance, and it's all archived in the AWS cloud. So it's a really great option. And when the files become objects on S3, they're going to be encrypted with Amazon server-side encryption, so you'll get encryption. Here's another way, you can kind of look at it. Let's say you've got this environment where you've got this file gateway, storage gateway, whatever kind of thing we're talking about here. Graphic still applies. You take your application servers or your users, you mount that storage gateway as if it's a file server. Over your direct connect, it puts us to Amazon, stores it on object storage or S3. And then as we talked about yesterday, it might be something you need to access frequently for a while, so you keep it on standard S3. Then you might not need it very often, so you put it on S3 and frequent access, where you pay less, but you pay a retrieval fee. And then you may not almost ever need it, so you stick it on Amazon Glacier, where it's real cheap to store, and then you pay a retrieval fee to get it, and you have to wait a period of time to get it. So that's called, lifecycle management of storage, and especially in the cloud, where storage is much more expensive than, say, in the data center, we have to work really hard to keep our costs low. So I'll talk about an AWS file gateway. And that's basically very similar to what we're talking about as well. It's a file server. It's made to look and feel like traditional storage. And basically, it's a file interface. So if you've got a file or an object in S3, and you've got this file gateway, in the data center, you can pull it across that gateway, and it'll feel like a traditional file storage, even if it's coming from S3. The file gateway can also cache the information. So you've got this file gateway, you've got some information stored in S3. Let's say it's, it's a photo that everybody wants to see. What's a photo that everybody wants to see these days? Honestly, I don't even know. So let's say there's a celebrity cat out there that plays bingo, I don't know, and it wins bingo games. So if everybody wanted to see the celebrity cat, and we had a photo of the celebrity cat in AWS, we don't want to go across that direct connection every time and reach that celebrity cat. But if we had this file gateway in our campus, and we all mount and connect to the file gateway, the first person gets a photo of the celebrity cat that's playing bingo. The second person doesn't have to go across your direct connection to AWS S3 to pull it because it's locally cached. They just get it from the local server because somebody else wanted it. So that's one of those cool things to think about with regards to file gateways. And one really good thing about object storage in AWS or S3, it's very durable. I mean, they've got a really good backup scenario. So the chances of your data being lost on AWS are slim to none. That does not mean you shouldn't use a good offsite backup routine, but it means the data on AWS S3 is very durable. So good chance that you'll receive your data and they won't lose it for you. And because you're pulling things off of AWS from AWS, it's going to connect very nicely to things like AWS Backup, AWS Lambda, AWS CloudWatch, that kind of thing. Although, really think about this. If you're going to back up your data or do disaster recovery from AWS, you probably should back it up to maybe Azure or Google or somebody else, not AWS. So just think about that. The point of disaster recovery is what happens when all the systems go down. So don't put all your eggs in the same basket and expect the same people to go that what could have potentially went down on any cloud to be your disaster recovery people. So file gateways support encryption in transit, meaning between you and the cloud provider, and at rest, meaning when it's stored. They integrate beautifully with the identity and access management part of AWS. And you can set up the same kind of folder and file permissions that you could in any other file server, because it's going to act like a pseudo file server pulling objects from S3. If you automatically change a file, it'll upload it to S3, so your data gets synchronized and consistent across two places. So AWS File Gateway, it is beautiful for backup and restore, meaning have all your stuff in your data center, have it copied over AWS in two places all the time. So that's a great thing. You could use it as a hybrid cloud. You've got some of your users in the data center, some of the users in the cloud. You could use it for a hybrid cloud workflow where 50% of your data is on the cloud and 50% is in your data center, and you want to be able to pull what you need to. You want to archive your data. This is a good, easy to use solution. Disaster recovery, yeah. What if you basically had your entire data center and used AWS's disaster recovery by constantly backing up your data in virtual machines to Amazon? So file gateways are great. Basically, to set them up, you deploy the file gateway, that virtual machine. You either put it on your VMware ESI systems, Microsoft Hyper-V, that kind of thing. You connect your gateway to the AWS account that you have and configure your file shares. If you're dealing with Linux systems, you create an NFS file share. If you're dealing with Windows, you create an SMB file share, the server message block protocol, map them to S3. And then when the on-premises applications need to access the file shares using standard file sharing protocols, because they don't see it as object storage, they will see it as file storage because it's a gateway. And a gateway generally takes one type of thing and connects it to something else. And you've got really good data management with this file gateway as well. The gateway uploads the files to S3, stored as objects, and then it even manages the metadata and makes sure you've got good data integrity. So you can think of it this way. And you can also have, a gateway literally in the cloud, which you could connect to storage gateway service. You're connecting to the storage gateway service in the cloud. So you put this virtual machine in your data center. You've got this HTTPS type connection, which is, think TLS encryption. And you can store your information on the cloud. So very good situation. So now we're going to talk about a volume gateway. And a volume gateway is a service within a storage gateway that provides cloud backed up storage volumes to your on-premise. So you can attach to these volumes on your on-premise servers with something, say, like iSCSI, if you're familiar with the iSCSI way that's to attach to storage. It's basically the SCSI protocol that's encapsulated into IP packets. And this enables you to leverage the scalability and durability of your AWS cloud storage and still keep good local performance. And as I mentioned, it does cache volumes. So you can store your primary data in S3 and maintain access to frequently accessed information locally in a cache. You might use it to reduce the scale of your on-premise storage and still giving you decent performance to data that's going to be stored on the cloud because of the caching. Here's typically the way I had always thought of these when we drew this out. You've got your computers, your users are going to connect to this thing, and they're going to be pushing and pulling information across AWS. Those servers themselves are going to be connecting to the application gateway over here. Here's the gateway, and here's your systems. And it's that iSCSI protocol that's going to be used as like a virtual storage area network, if you will, access. So that's really what we're talking about over here. Of course, that was volume gateway cache mode. Now we're going to talk about volume gateway stored mode. So stored mode is where you're going to take your primary data and keep it locally. And that's going to asynchronously push it to the cloud. So when we talked about cache mode, that was assuming that the predominance of your data was sitting in S3. But if your data is predominantly local, but you want to back it up to the cloud, this is where your volume gateway goes into stored mode. And this is going to be ideal for applications that require low latency access to maybe an entire data set, because the latency is going to be lowest in your environment, lowest in the data center. That's why data center performance is always going to be the best. But sometimes we need the scalability. Lots of times we need the business agility of the public cloud. So local storage performance, back it up somewhere else. Keep going to the back thing. So it's going to look very similar to what you just saw. The systems are going to connect to the users will connect to the application servers. They'll be connecting to this volume gateway, but it's going to be in stored mode, and it'll still push the content to S3. But the point is, our local storage is here, and this is where we're going to get high performance access to locally. And it's still going to, so you're going to see this is going to be our high performance locally, and then it's going to store backups of this information in the AWS cloud. So that volume gateway we just talked about is going to be perfect for that hybrid cloud storage. The fact that you can connect to it via the iSCSI interface realistically means that your systems are going to have no problem to it. You deal with a Red Hat system, it'll mount iSCSI. You deal with an Ubuntu system, it's going to mount iSCSI. It's just a standard way to access storage over the Internet Protocol because it's based on the SCSI protocol. And this is excellent just for data backup, data protection, disaster recovery. And if you think about it, it's going to scale. Because when you have in your data center, you can just add extra to your storage area network. And the cloud's just going to grow with you. So it's not like you're dealing with, where's my redundant data center, redundant backup environment? Does it have enough hard drives? You don't have to worry about that. And when your data is stored, it's encrypted. And this way you've got low latency and you've got really good backups. This is a great environment for hypercloud. The next kind of storage gateway we're going to talk about is something called the tape gateway. So I don't know how many of you are familiar with tape backups. You've got a person swapping tapes, and then you take the tapes when you're done with your tapes, and you typically ship them off-site. So then you need some high security shipping, and then you got to store those tapes in a high security building. That's typically a tape backup environment. So the AWS tape gateway is going to do things just a little bit different, and it's going to work with an organization that's got a good tape backup infrastructure, but at the same time they don't feel like swapping tapes, shipping tapes, storing tapes. So this is a great environment. So a tape gateway enables an organization to use their tape interface, and they create these virtual tapes, and these virtual tapes are stored on Amazon. So I hope that kind of makes sense. So we uses the concept of these virtual tape libraries. So they emulate the physical tape. So all the backup applications a business has, where it's looking for a certain set of things, it's still going to work, but it'll work on a virtual tape versus a physical tape. So the same backup software works. In this way, you get the benefit of being able to put your backups on the cloud, not have to think about managing these tapes and when the tapes go bad and how you destroy the tapes when the tapes go bad. You're just sticking it in AWS, and AWS is a virtual tape for you. So very scalable, great environment, fairly cost efficient, because all these tape media, tape drives, tape this, tape that can somewhat get a bit complicated, and sometimes it can get expensive. But when it comes to cloud computing, what looks cheaper might be more expensive. So you really need to understand all of it before you actually build a business case. And of course, it's on S3, and we talked about S3 having that 11 nines availability, meaning 99 and the 99 for 9 decimal places planted after the 99%. So fairly durable data. The data is going to be encryption because it's also going to have access to the AWS identity and access management systems, which of course could be federated or pulling into the organization's active directories like they usually will be. And the way the tapes come in is it typically comes into the tape gateway, and then it gets stored in S3, and then it gets moved into Glacier, where you're going to have your cheapest performance, because chances are you're not going back to your tapes. So you want it to be in the lowest cost storage. And if you do go back to your tapes, it's because a catastrophe has occurred. So tape gateways, backup on archival purposes, disaster recovery. Tape gateways are also good because if you're in a regulated industry and you actually have to store your information somewhere else for a long period of time, it's a great way to archive your systems. Because if you're a hospital and you lose patient medical records, you got a problem. If you're a bank and you accidentally lose financial transactions, you've got a problem. So think about that. And this way you're not dealing with tape. So how does this get set up and used? So you deploy the gateway. Basically speaking, you install the tape gateway virtual machine on your VMware, your Microsoft Hyper-V environment. You can configure that gateway to connect to your AWS account. You create your virtual tapes. You integrate with your backup software, so you configure your existing backup software to use the virtual tape library presented by the gateway. And you do your backups. And then you archive it on Glacier from S3. And if you need it, you restore your data. I think we've probably gone on for more than 20 minutes, Chris. So maybe we will stop here, and then we'll come back and talk about some other options. Volume Gateway Store Mode. Data is local and high performance local, a store backup to AWS Cloud. Can you please detail some additional use cases? Access storage over the internet, cloud and backup in DR. AAE, I'm not 100% sure that I understand your question. So let's talk about some use cases, because the data is local. And this way you can get some local high performance and still back it up to AWS. So where would you use this? Well, if I have an environment where I want good disaster recovery, I want my local data backed up somewhere else, and backing it up to a cloud provider that's 1,000 miles away is perfect for business continuity in case we have a local hardware failure. If I want to have a hybrid cloud environment, it's perfect to keep my data synchronized. If I want to move to the AWS cloud, it's going to be pretty great because you can work off of your local high performance setup, and it's going to just asynchronously copy it to the cloud. So if I've got an environment where I've got under high regulatory compliance, so medical, publicly traded companies, banking, highly regulated environments, this is going to be an environment where we want offsite backups. And think about data synchronization. You can run an environment where you've got a hybrid cloud, and what happens if your data center fails? You want the cloud provider to be able to take over. And if the cloud provider fails, you want your data center to be taken over. So there's lots of good reasons to keep your data synchronized in two places. Hope that answers your question. If we want to store the tape backup, how long does it take? George, I honestly don't know, because I've never restored a tape backup because I don't work in operations. But we will talk about some extremely good ways to do disaster recovery and ways to speed it up versus slow it down. And it's also going to be based upon how much data the organization actually has as to how long it's going to take to reconstitute that data. And, if we're going to do it from a storage gateway, for example, it typically takes a few hours. But that's going to be the size, that's going to be dependent upon the size of our data and our network connections. Restoring data from a storage gateway to tape backup, again, is usually a few hours, but it's going to be really dependent upon how much data you have and the speed that you actually have to get your data from point A to point B. Oh, that's a good question, Derek. When would you use a tape gateway for backup when you can simply make an image and store the environment? So if you have an existing tape backup infrastructure, and that's realistically speaking what the organization is used to, it's the way they've done everything, and that's the only backup strategy they have. Sometimes changing an organization's entire backup strategy is going to take a while. It's going to take a brand new architecture, which means it's going to have to go through approval phases, and the executives are going to have to buy in on it, and the stakeholders are going to have to go through that. And it could take 6 to 12 months to do that, just to design the new storage and backup architecture and get it approved from all the levels in the business. So this is quick and easy. In real pragmatic reality, If I've got the ability to make an image of every single server I have and keep copies of those images on the cloud, and I could have a Terraform infrastructure as code script to basically bring up those things, and I've got exact copies of my machines, especially if I kept my databases synchronized, for organizations that can invest in that, it's going to be a much better solution than tapes. But sometimes we deal with people that have been doing something for a long period of time, and they don't have the capability or the wherewithal to make the change, or the sophistication to make the change, or the budget to make the change. That's when you use the technology they have. But Derek, I'm glad you thought of this, because it means you're thinking, why would I use this kind of clunky old thing when I have access to something better? Good point there. All right. Did you all like working through the database and kind of mapping it out and playing with it alive? I hope so. Let me know if you did in the chat box. So we'll get back to the content. If you've not downloaded the free labs or signed up for the free labs, please do so. My team will drop a link for that in the chat box as well as in the description. We're here for certifications, and we do lots of free certifications on our YouTube channels, and I can tell you, it saddens me when I get somebody with all these certifications in someone else's job. And sometimes I see a beautiful resume with exactly the right certifications, and it really makes me think very differently of them when I read the resume. So I want you to know this, so you know how to plan certifications for your career. So go get that free certification guide. It's in the chat box and the description. So we're now going to talk about, the AWS Snowball. And one of the ways you can typically get information to the cloud provider is basically by putting it on a hard drive and shipping it to them. So AWS offers these little virtual file servers they send to you. And basically it's this ruggedized container, and it's got a specialty computer in there with a 10 gigabit Ethernet port. And what you do is you plug in this little mini ruggedized file server to your network. You can put, say 80 terabytes on it. Well, it's technically 72 after you format it, but it's 80 terabytes of raw storage. You copy your information into the Snowball, which is just a file server, and then you ship it back to AWS. They ship you a server, you pop your information on the server, and you ship it back. And when it gets to AWS, what do? They store it in object storage. So you request the Snowball, they deliver the Snowball. The Snowball is just the file server. You load your data on the file server. AWS picks up the file server, sticks it on S3 object storage, and then you pull it off of object storage and do whatever you want with it. I am not sure if they have canceled the Snowmobile or not. I am not sure, but I want to give it to you anyway because it may still show up on an exam. So AWS also had this concept of a Snowmobile. What's a Snowmobile? Basically, it's a data center that gets shipped to you. You copy your information to the data center, and they drive the data center back to AWS. So it's a data center that can store upwards of 100 petabytes of data. So AWS basically takes a tractor trailer. They drive this thing over to you. You plug into it to your network. You copy your information, and then drive it back to AWS. They copy your information onto AWS S3, and then you pull your data off. That's another option. Another option we have is AWS Data Sync. And AWS Data Sync is a managed service that's going to simplify and automate moving data between, say, your on-premises environments and your AWS storage service. It can sync your data between multiple different AWS storage services. And it's designed for large-scale data transfers to do it in a secure and an efficient manner. And AWS Data Sync provides for automated data transfers. So it reduces the need of manually intervening and writing scripts to push your data. It handles the complexities of data transfer, so you might need to tune the network for it. You may have to validate the data. There may be some error problems and need to do some error handling. So it does all of that. And it supports lots of different storage devices. So S3, or storage services you could call it. So object storage, elastic file storage, or network file storage, FSX Windows for file server, so Windows file storage, FSX for Lustre, which is high performance file storage, Amazon FXS for OpenZFS, it's another file system. And that's the key thing to remember. So it really works with all kinds of different storage protocols. It'll integrate with the AWS key management system. So you're going to have your encryption, and it'll also integrate with the AWS Identity and Access Management Console to control, who can access your resources. So identity and access management is who are you, what are you allowed to do, and what have you done. So keep that in mind. It'll work with data validation and integrity checking, because it's going to perform data integrity checks to ensure that the data transferred is actually what you started with as the source. So that's going to be quite good. And it's going to verify data during the transfer process to maintain its accuracy. You can schedule it. You can schedule data transfers to run at a specific time of day. And why might you do that? So let's say you want to transfer data. During the day when the network is busy, you might not want to do that. But maybe the computer systems are getting minimal use in the evening, like at 2 o'clock in the morning, and that's when you want to send it. So that's why you would schedule these types of things. AWS Data Sync can also do data filtering. So maybe you don't want to back up certain things. It can enable you to do that as well. Now, as we're talking migrations, let's talk about another service called the AWS Migration Hub. And that's going to be a service that provides a single location for you to track the progress of application migrations across many AWS and partner solutions. So it's going to help you manage the migration process, give you visibility into it. Now, this is not an architect tool. This is going to be at the operations level, at the time when you're actually doing the work. But keep that in the back of your mind. If the organization chooses to use the AWS Migration Hub as one of their tools, it'll give them a dashboard about the status and progress of the migration projects. And this is going to help streamline, the management and migrations of things, because it gives you a unified view. There's lots of tools project managers can use in large-scale migrations, etc. But, this is an AWS tool. And it's going to integrate with a lot of the other AWS migration tools. So AWS has an application migration service to kind of help you move applications. It has a database migration service. If you were going to go off of, say, your Oracle database and wanted to use one of the AWS databases, of course, you could just take a virtual image of your server and move it to the cloud. And AWS Data Sync and lots of third-party tools. So you could use AWS Migration Hub in the discovery and planning phase. And maybe by looking at the applications. For example, you can group your applications in an environment that enable you to track the migration, progress of an entire application rather than certain individual resources, to get more of a holistic view, if you will. The service will provide metrics and reports on migration activities, including details like the number of servers migrated, the amount of data transferred, errors, warnings, that kind of thing. It'll give you information on progress tracking. So think about it as a tool to kind of help you, this migration hub, to figure out what's going on. And it can also help with some automation and orchestration, because it will support automation and orchestration of migration tasks. So some of those manual things can reduce manual effort as well. Now, next is the AWS Transfer Family. This is a fully managed service from Amazon Web Services that will enable you to transfer your files back and forth to AWS storage. It'll support numerous protocols, making it pretty easy to share and integrate data. So you can use, say, secure FTP. You could use, say, FTTPS, which is FTTP with SSL/TLS encryption. It'll also work the transfer family with old school, non-encrypted FTP. And the AWS Transfer Family will integrate with S3 or object storage, the AWS Elastic File System, which is the AWS managed version of the network file system. You can use it to help with data migration, because it can help get your data to the cloud. You can use it to basically do data sharing. So what I mean by data sharing, you may have your business that needs to share data with multiple other businesses, so it can assist with that. And it can be used for backup and restore. I'm going to cover Amazon work documents. You probably wouldn't see it in an exam, but you never know what you're going to see, so I'd rather just cover it. Amazon had their version of, say, Google Office or Dropbox, and they called it Amazon Work Docs. It was like a secure content storage and collaboration service, easy way to do document and editing. It was simple and affordable, and you could access it with a web browser or client software. Worked with Windows and Mac clients, so something to think about, something they have. All right, now we're going to get into some fun stuff. We're going to get into compute. The actual computational part of everything we do in cloud computing. So this is where the fun is. And we're going to first start with virtual machines. And I'm going to make sure that you understand virtual machines long before we talk about EC2, because if you don't, you're just not going to know where to begin. So first let me logically show you what a virtual machine is. We'll map it out architecturally, and then I'm going to take you to our data center, and I'm going to show you an actual physical server, and I'll show you the hypervisor and basically what is an EC2 instance from the inside out. Because if you don't know what it is, you're not going to be able to really understand what it is if you have to design it. So let's say let's map this out architecturally, and then we'll go to our data center. So let's say this is your actual physical server. So that's the server you buy from Dell or IBM or HP or anybody else. That's your server. Now let's say this is a big, powerful server. It's using AMD's EPYC processors, which are the fastest processors in the world. Let's say it's got 256 cores. And let's say it's got 6 terabytes of DRAM. And this will be about $300,000 for a server like this. Relatively inexpensive compared to the cost of running the server on the cloud. Now, most applications don't use 256 physical cores or 512 virtual cores. They don't. In fact, many applications won't even use a full core. So one of the things that happened many years ago was we said, well, our data centers only have so much power, and we don't have anywhere close to enough electric to even deal with the the things that we need to deal with, let alone anything else in the electric infrastructure. But that's neither here nor there. So we could buy 50 servers that all have, say, 4 cores each, and they all use the same amount of electricity, and they all take up rack space. Or we could buy one server with 256 cores and chop it down into multiple smaller servers. And this is how all your systems are on the cloud. So what happens is you put what's called a hypervisor here. And this will be a type 1 hypervisor. And what the hypervisor does, and there's no operating system here, it's the hypervisor, it's like a mini operating system. It will enable you to create little mini servers off of this main server. And by doing so, I could create an additional server with 4 cores and 8 gigs around. I could create another server with 32 cores. So it enables you to create multiple virtual machines. So here's the way these virtual machines are. Well, let's say this is a 16-core virtual machine. And they're logical cores, not physical cores. And let's say this has got 64 gigs of DRAM. What it does is it takes those resources out of this. Now, this virtual machine will have its own OS, its own applications, and whatever the application dependencies are. And I can have many of these things. And, what I could do is I actually get what's called logical cores, because these cores split our hyperthread. So if I have 256 cores, each virtual machine is a virtual core, which is technically a half of a core, although it can perform almost as well as a full core under certain circumstances. So out of this, if I've got 512 physical cores, and there's a reason I want you to understand this, If each one has 16 cores, I would do 512 divided by 16, which could mean I could run 32 servers on this system. Now, do you see this? This first server, this could actually be customer A, and this could actually be customer B, and this could be coming from customer C, and this could be customer D, all on the same physical server. And in some ultra high security environments, you will not be able to use a server like this in the cloud. But by default, this is what you're getting. Your systems are on the same system as other customers, and they're all sitting on that virtual machine. Now, one of the things that cloud providers generally do, and internet service providers typically do, is they work on this statistical calculation that this system has 16 cores, and this system has 16 cores, and this system has 16 cores, and this system does. And what's the likelihood that all 4 of these virtual machines are going to use all their CPU performance and all their DPRM performance at the same time? Not a lot. So while the cloud provider could technically sell 32 actual servers at capacity, they may sell 65 or 70 servers on here. And that's called oversubscription. And they may do that because they know that most users, statistically speaking, won't use full capacity at the same time. So if you ever hear about cloud computing having bursty performance, it's because sometimes these systems get busy because they typically sell more than they actually have. And this is common of your internet service provider. It's normal. It's part of their normal business model. And even airlines do it because they know a lot of people won't show up to a flight. So they sell maybe 10 or 20% more seats than the plane can handle. And then it usually works out. And if not, they're like, who wants to get to leave the plane and get money? So that's the way this works. So now I still want you to understand a little more of what this looks like. So let me bring you to my data center. In my house, which is my data center, I've got an OpenStack cloud. I've got a VMware cloud. We've got all kinds of tech around here. But here is a traditional server with a hypervisor. This is a Dell. It's actually a workstation, but it uses the same processors that the AWS i3 instances use. There are all this Xeon E5 2670 V3. Note that this system has 24 physical cores. And you can see up in the top of this how much resources are free on the system because we've got 24 cores operating at 2.3 gigahertz. We've got a total of 56 gigahertz, so to speak, or 55, 56 gigahertz to use. We've got 128 gigs of memory. Some of it's being used by the hypervisor, and you can see that, 80% of the server storage is used. Now, I want you to see that. You can see this system's not being used. So in the data center, we're going to create a virtual machine. What's it going to look like? Well, we'd create it. We would tell it about the virtual machine we need. Let's give it a name. I'll call it Cindy the cat. I have a cat, Cindy. She likes to unplug servers. Guest operating systems, let's say it would be Linux. Guest OS version, we would pick the operating system version. Red Hat Enterprise Linux, probably what I would be using in a business case. We can set it up for standard, and then look what we can choose. The first thing I want you to see is I now have the ability to delegate 48 processors cores. Wait, we only have 24 in the server. So when you get a virtual machine on the cloud, it is a virtual CPU, which is meaning is it's not a full CPU core. So understand, 16 core virtual CPU in the cloud is not going to perform as good as 16 physical cores in the data center, which is 32 virtual cores. So you're going to have to adjust your sizing accordingly. But the way this would work is you would get a virtual machine and determine how many cores your application needs. Let's say in this case it's 4. You would look at how much DRAM your application needs. Let's say it needs 16 gigs. You would tell it how much of the hard drive that it needs to take, and that's going to take it from the internal storage here, at least in this environment. You would give it a boot device to boot up, which would be, say, Ubuntu desktop, and then I would just build the system, and I'll let you see how the system boots up, and then I'll cancel this because you don't need to see me install Ubuntu. But here we've got the virtual machine. And guess what you're going to see? It's going to boot up just like any other computer. I'll let you see that. You can see what it actually feels like. And now you can see that it's going to load up. I'm going to stop it at here. But wow, that just looked just like a standard server, right? It's a server inside of a server. And that is the basis of cloud computing. Now, we don't need to see the rest of this occur, but I wanted you to get that. Because if you didn't understand what that was, anything else that we would actually show you wouldn't make sense. So I hope that actually worked. Made life easier for people. So I really want you to get a good experience here. If you understood that, and now you know what a virtual machine is, give me a hashtag VM. And I don't like acronyms, but I know everybody's not going to want to type a lot. So give me a hashtag VM. And then I know that you understood that, and it helped. All right, so now let's talk about the AWS branded virtual machine. On AWS, you still have the same virtual machines that we have had since 1999, the VMware invented. So here's what's different. AWS made a new name for it. They call it the Elastic Compute Cloud, otherwise known as EC2. If you talk to an end client, it's the virtual machine. And how do you determine what size you need of virtual machines? It's the same way you've done it for the last 2 decades. How many CPU cores do you need? What are the frequency of those cores that you need in terms of, say, single core performance or multi-core performance? Do you need a graphics processor in it? Do you need accelerators for parallel computing? How much DRAM do you need in it? What kind of storage capacity and performance do you need? What kind of network performance? Now, AWS has these little marketing-friendly little terms that you can look at, and they size their instances by marketing names. Like an i3 is considered, I don't know why when we made this, it was considered high-speed storage. Now it's considered general compute. But the point is they come up with a name. Typically speaking, a G-series virtual machine has a GPU in it. They have some things that are memory optimized. I'm going to give you the reality. None of that matters. What matters is your CPU performance, your DRAM, your networking. So what you're going to need to look is the CPU cores you need, the DRAM performance that you need. Excuse me one second. All right, apologies. Something made me sneeze and cough. So when we get our virtual machines on AWS, they're either going to be Linux virtual machines, Windows virtual machines. We're going to go to the marketplace and say we need good security, and we're going to go get a Cisco firewall or a Palo Alto firewall. And they also do support Mac OS virtual machines. Now, the way these Mac OS virtual machines are is they literally run on the data centers. They've got racks and racks of little mini Mac minis. But why would you use an Apple virtual machine? Well, you might use it if you're a developer. You need to compile code for a Mac, and you don't have a Mac. So, there's times in a place where you might want to use an AWS virtual machine, but they get very expensive, those Mac virtual machines. So when you get a virtual machine, you've got multiple options. You can take the virtual machine you have in your data center, that file for it, convert it to the Amazon file, and just launch it directly in the AWS cloud. If you had VMware or Nutanix, you could run VMware on a server in the cloud and just move your virtual machine as is and use the same VMware tools to do it with a bare metal server. You could also just launch an Amazon pre-made virtual machine. So launch a Red Hat 8.0, Red Hat Enterprise Linux 8.0 server. Boom. Click a button and it's launched. So they're pre-made. So when we deal with Amazon, we're going to have this concept of an Amazon machine image. What is it? It's the Amazon branded name of a virtual machine image. So VMware had their images. Everybody has their images. So when you deal with an Amazon machine image, it's going to need a storage volume. Think EBS, where you're going to store your information. And we can get these Amazon machine images from a lot of places. There'll be lots of systems that are going to be pre-built by AWS for a variety of needs. Now, we might need an extra high-performance reverse proxy and get one from, say, F5. We may want to stake DNS servers in multiple clouds, so we get them from all the clouds marketplaces. We might need a high security appliance that we get from Cisco or Palo Alto or Fortinet. In enterprise security, we will be, typically speaking, getting one of those things. We might need an IDS IPS system, and we're going to get it for something like that. So there's going to be pre-built machines in the AWS marketplace for a tremendous number of business uses. You'll be getting them. Or you'll just take one of your systems that you have, say a VMware virtual machine, copy it over, and turn it into the AWS format. You upload your virtual server. Now, what are the components of an Amazon virtual machine image? An operating system, launch permissions, and a block device mapping that's going to specify the storage volumes to attach to the system. So, OS, permission, and storage, like any other virtual machine in the entire world. One of the cool things is you can take your machine image and you can copy it to a different region. You can create a snapshot or a quick mini backup of the image, and you can use this for backup, disaster recovery, and there you go. You got lots of these options. Excuse me. So let's talk about automating the first boot on your virtual machine. So think of it this way. When you just launch a basic virtual machine, it's not going to have any software on it. So it's going to have nothing other than Linux. So we have the opportunity to launch what's called a bootstrap script. And what is a bootstrap script? It's a simple script to install applications, manage your software, patch the operating system, and very simple. It could be a bash shell script, a Windows parallel script. It could be an Ubuntu system, and in the location you can do a sudo apt-get update and update the system, that kind of thing, and you could specify it. You could have your system install maybe an Apache web server as it boots up. And so, just have it set up. So patch the operating system, install the Apache web server, do this, and come up. So we can automate the boot very easily. So if you think about creating an input script to make the system the way it would be, and businesses have been doing this stuff for decades and automating, Windows rollouts when they install the systems to their users, for example. We can automate systems with, you can use the AWS Systems Manager. You can use run command or an AWS automation documents to execute commands remotely on a system. When you use infrastructure as code, which means Terraform because everybody's multi-cloud, or the AWS CloudFormation, if you're only going to deal with AWS, and you can define your instance configurations, the bootstrap scripts within your CloudFormation template or Terraform template. And that way you could launch like 10,000 virtual machines in a matter of minutes. And that's one of the reasons infrastructure as code is so great. You could use it with, say, AWS OpWorks and use some kind of Chef or a Puppet configuration to automate software setup in your virtual machines. So there's lots of options. Now, when you get your systems, these virtual machines from the cloud, basically have a couple ways you can purchase them. On demand. So occasionally you'll hear people say you don't need to do capacity planning on the cloud, it'll work. Well, that's true if you don't care what it costs. And actually it's not true, because even if you don't do capacity planning, it won't scale when you need it and it won't perform right. But if you know what you need, you can purchase it. If you know you're going to be in a house for 3 years, and the landlord would give you a 40% discount because you give them a 3-year lease, not that they would, you might basically say, I know I'm going to be here. If you didn't know how long you were going to stay in a city, and it could be 1 day or 1 week or 1 month, you'd stay in a hotel. So that's really what we're talking about here. When you purchase your virtual machines, you need to know your utilization, how much you're going to need, and for how long you're going to need them. So on demand, think of it as real expensive. You have no idea what your needs are, and you're going to pay out the nose for them. That's an on-demand instance. By comparison, reserved is, please give me a discount on my 3-year rent or my 1-year rent. So if you know what your needs are and you go to any cloud provider and you reserve them ahead of the time, they're getting guaranteed a certain amount of revenue from you, and they're willing to give you a discount. And it could be a relatively good discount. And, there's 2 kinds of reserved instances. There's a standard reserved instance for the most part. Actually, there's a few kinds. And that's going to give you the highest savings, but you've got limited flexibility. There's also something called the convertible reserved instance, which gives you less savings, but you can change your instance type, operating system tenancy during the term. So with anything else, if you need the ability to control stuff, they charge you more. So think about that. So we talked about on-demand. Here's when on-demand is good. When you don't know. You're a brand new startup. You have no idea what your needs are. On-demand instance. A big business moves from their data center to their cloud, and they've got really good cloud architects. And those cloud architects know the systems utilization. They've done all the math, and they're going to the cloud. And they're not just certified. They understand business. They understand architecture. They get the concept. Go to the cloud. Reserve it for 3 years. Next, spot instance, or if you want to auto scale, that's going to be on-demand instances. But, that's a great thing. The next thing is something called the spot instance. A spot instance is maybe one of the most terrifying things you can think about, or a preemptible instance on other clouds, but in some cases it's really great. So these cloud providers have a whole lot of excess capacity. There was a movie, I think it was called Field of Dreams, where they said, build it and they will come. Well, that's generally the cloud provider's motto. Let's build it and hopefully someone will come. So they've got all this excess capacity lots of the time that's sitting around doing nothing. So you can purchase a spot instance, which basically says you agree to bid in an auction environment for a certain amount of compute time at a certain price. And as long as nobody's using it, it works. But then somebody bids a little more than you, and within 2 minutes you get shut down. So let's think about this. If you have a batch job to do that requires a huge amount of computer processing for maybe 12 hours, and you don't care if it starts and stops a few times, spot instances are the way to go. If this is your business website and you're in e-commerce and you're going to get shut down during the day, this is not the way to go. So I hope that makes sense. So next. Normal tenancy of one of these servers is as follows. You are shared with a whole bunch of other people on the same business. Now you have a top secret, super important thing. You don't want somebody to be on that same other server and have the potential for a hypervisor attack and get into your virtual machine. It's rare, but it can happen. But if you've got mission critical security, you may need to be on a different server than other people. And that's where you start getting into different types of tenancy. So we'll talk about a dedicated host. The dedicated hosts are realistically going to be in an environment if you need, say, compliance requirements, and you need to use a per socket or per core or per virtual machine software license. And you can think of it that way. So basically you can think of it as a system that's yours, like in a data center. Now, the alternative is a dedicated instance. And that's where you basically run all your virtual machines and only your virtual machines on the single hardware. So you've got host level isolation as well as hypervisor level isolation. So it's going to give you a lot more security should you need it. You can also reserve capacity. And you've got this concept of capacity reservations. And that will allow you to reserve capacity for one of your virtual machines in a specific availability zone for any duration, making sure you've got the capacity necessary when you need it without having a big long-term commitment. And there's this new concept of capacity blocks, and it's new for 2024, and it's specifically designed to reserve clusters of GPU instances if you need basically a workload that requires a lot of high-performance compute. I want to talk about that tenancy a little more. Probably see you could see questions on this on your exam, but it's really important to understand from a security perspective. Shared tenancy, multiple customers on your same virtual machine. So if you think about a hypervisor attack, that's how you could go from one virtual machine to another. With a dedicated instance, it is single tenant hardware. which means if I have my business and I have a dedicated instance, only my virtual machines are on that server. Now, here's the problem. I still don't know anything that's going on with that server. I have no visibility into it. I have no idea if that physical server is overused. All I get is access to my virtual machine, so I don't know that much. So I don't know the sockets on the servers. I can't see the cores. I can't get serial numbers of any. I get nothing. So good virtual option for increased security on the cloud. But what if I have a license for some custom software or enterprise software that's tied to the MAC address of my computer or the serial number of something in my computer, and it needs to see the hardware? Well, that's where I get a dedicated host. I've got full control over the hardware. I can see the underlying hardware. This is as close to I can get as data center performance level in the cloud because it's a bare metal server just like I would have. So keep that in the back of your mind. High regulatory compliance, complicated software management, this is your option. And guess where else this goes well? VMware had a really beautiful solution where you'd put your VMware servers on dedicated hosts on all your clouds. And that way, your people that were used to using VMware in the data center could use the same interface on the cloud, and it's basically they didn't have to use anything because all a cloud is somebody else's data center. There's also the concept of, say, Nutanix. Nutanix is a beautiful private cloud along with IBM's OpenStack, and you can put Nutanix Cloud directly in your data center. And with Nutanix, if you get some of these dedicated hosts that you can put in, say, AWS, Azure, and Google, your capacity could expand to any of these cloud providers, and you could use the Nutanix commands that you're used to and a business will be used to. So lots of good reasons for dedicated hosts. So how do we secure an EC2 instance? Well, there's going to be a lot that's actually going to be going into securing virtual machines. Far more than is actually covered here. But that kind of information would be covered in, say, a CISSP certification. Or, of course, we would teach it to our cloud architect students. But let's talk about doing it the way to get you to pass the exams. Because if I give you too much of this other stuff before you take the exam, you're not going to know how to answer the exam. Because if you know too much, these exams become a little harder. Because you have to figure out what they would do in the certification way versus what you might do in the real world. So I want to keep it to what's in this exam for this piece. So you can use a security group to keep unwanted traffic from getting into your system. So that's one of the ways you would do it. Remember from yesterday I said access control list, specifically network access control list on AWS, keep unwanted traffic out of a subnet? Well, with a virtual machine, you use a security group. And that basically is like a host-based firewall that says, allow port 443 traffic in for HTTPS and block everything else. So this might be what it might look like over here. You've got your virtual machine and you got your security group protecting it or limiting the traffic that could come in. So next, we'll talk about how to provide an EC2 instance and an IP address. So an EC2 instance can have multiple network interfaces. Just like any server can have multiple network cards in it. And anytime you've got more than one server in a network, for the most part, each interface, unless you're in a bridged environment, but in this case, each interface will need to have a unique VPC address space and a different subnet. You have 10 Ethernet cards in a server, 10 different subnets each card is generally on. That's why we need subnetting. And if you don't know how to subnet, my team, please drop a link to the last subnetting webinar we did. And actually, while we're at it, everybody needs to know BGP. So Chris or Tyrone or whoever's behind the scenes, drop a link to our most recent BGP workshop. That's in about 12 more hours of free networking training for you that you really do need. So when we deal with a virtual network card, we're going to get an IP address, which will give us a DNS name from AWS. And how do you access a virtual machine or an EC2 instance? Well, you can attach directly to the EC2 console. If you've got IP connectivity to it, maybe through your direct connection or your VPN, you will just SSH into your Linux machines. How do you access a Windows machine remotely? Well, you can't just SSH into it. You use the Remote Desktop Protocol, RDP, to remote control a Windows desktop. Of course, you can do some management of these systems at the software development kit. So I'm going to stop there because after this is containers, and boy, we can get into some topics there. So let me stop it and bring it to some questions. Who has questions? Can I explain more on Nutanix? What is it and what does it do? Excellent. Yeah. So the public cloud providers are renting you space in their data center. And public cloud providers have great data centers. They've got great practices. But generally speaking, it costs more to host your information in the cloud data center than it would your private. And here's the reason why. The cloud provider has to run the identical data centers that you do. So they need to buy the same stuff. Now, granted, the cloud providers get a bigger discount on the stuff than most businesses do, but they're also something that's called hyperscale, which means they need so much more management and overhead that things get bigger. Now you got your cloud providers, and some of them have 50 to 100,000 salespeople getting paid $200,000 to $300,000 a year in the sales and architects. So you might have, 40, 50,000 people doing that are just getting paid to do sales. Then the cloud providers have to do their marketing. So you can imagine you've got the same data center that you need to run, and then they need to pay a staff of, all the people to go sell it and market it. And then after that, they got to make money when they charge you for it. So that's why cloud computing generally costs more. Now, the next thing to understand is if it's next to me, it performs better. If it's 1,000 miles away, I've got latency to it. So the best performance we can ever get will be local. And the most control we ever get will be local. For example, in my private data center, I can make sure that the CEO's traffic goes first. The CFO and Chief Operating Officer next. My VP's traffic after that. My voice traffic right after that. My video traffic right after that. And then normal business traffic right after that, and anything else could be a worm or a virus. Deprioritize that. We can't do any of that on the cloud. So we have much more control in the data center, much more performance in the data center, and typically speaking, lower cost in the data center. But here's the problem with the data center. It takes a lot of work to manage this. You need really smart people with a lot of expertise to basically build and run your own cloud. So what Nutanix is, what OpenStack is, it is cloud software that you stick directly in your data center. So you install the cloud software. All your servers and storage effectively get pooled together in the identical way that Amazon or IBM or Cisco or anybody else's cloud would do it. You create a virtual machine. It moves it to any one of the servers that has capacity. It's got your virtual load balancers in it. So it gives you the ability to create your own private cloud. You want to run a function as a service like serverless computing, which runs on serverless. Instead of an Azure function, instead of a Lambda function, you run the function that's available on, say, Nutanix or OpenStack. So organizations get all the benefits of the lower cost and the higher performance for their main, and all the benefits like auto scaling, like they can have extra server capacity and their website could need more server capacity, and Nutanix or OpenStack will just give it as demand. So everything in the public cloud in your self-managed data center. And then you can still connect your Nutanix cloud or your OpenStack cloud to AWS, Azure, and Google and leverage their scalability and the agility benefits that you get on the cloud, because the cloud may cost more, but it's typically more agile. So this enables you to have the best of both worlds. Best performance with your data center and the ability to go out there and use all the other clouds for the things they provide. So this is a really great solution. Can I explain the difference between bare metal and dedicated machines? So here's bare metal, straight out of the box server. So when you're getting that dedicated bare metal server, you install your software on it. Want to run the system on bare metal without a hypervisor? because your application can't be run in a hypervised environment? You can. Want to put your VMware servers on bare metal? You can. Want to put your Nutanix or OpenStack stuff on there? You can. Want to put your managed Kubernetes like OpenShift on there? You can. Now, when you get more of the dedicated instance, these dedicated environments, what it means is only customer A's traffic is on server A, and only customer B's traffic is on server B, as opposed to the traditional tendency, which is everybody's anywhere on any server they want on a public cloud provider. That's a really good thought there, Anna. I hope that made sense. Any others? Okay, well, we will get back to the content. So, I need to know you're really awake for this because now we're getting into containers. And you know me, I don't want to just give you what's on a certification. I want to give you some knowledge too. So, I need to know you're awake. So, first, I want to tell everybody that if you have not gotten the 40 plus labs that we have for you to do, please go sign up for them. They're completely free. While you're at it, please get the free certifications guidebook. If you've not done it, to talk about which certifications can boost your career if you want to be a cloud architect or a solutions architect, for example. If you haven't liked the video, please do so. If you're having a good time anyway. And if you're not a subscriber, please subscribe and hit the bell to be notified of new videos to help you in your career. And please do check out the section, the description section of any of our videos. We've got lots of free stuff to help you in your career. So let's start talking about containerization. So what's a container? So to me, a container is a lightweight version of a virtual machine. And as I showed you the virtual machines before, you saw we had the server, we had the hypervisor, and I mentioned that in each virtual machine, we had a copy of the operating system, the application, and its dependencies. So I don't know how many of you are very familiar with the resources that an operating system takes, but I got to tell you, it takes a lot. We may have some operating systems that take 8 gigs of DRAM just to run it, and they can use a good CPU core or a half a CPU core just to run the operating system. So if we've got a server with a limited storage capacity, and we want 50 servers on something, and each one takes 8 gigs of DRAM just to run the operating system, well, you can see how much memory we're wasting, how much CPU resources we're wasting just for the operating system. So what if there was a better way? What if there was a way that we could leverage the operating system and the libraries that are provided and put multiple applications all on that single server and keep those applications that are on that server all isolated from each other? So we don't need multiple copies of the operating system, but what happened in one container wouldn't happen in another container. Wouldn't that be kind of cool? So that's what a container is. So a container will require much less memory and CPU resources than the virtual machine, which means instead of maybe having 50 virtual machines on a big server, well, it might be about have 300 containers on that same server. So think about less electric. And why are we concerned about electric? Because you have to understand that the electric creates heat. And these data centers get hot. And the amount of air conditioning these data centers take and power that it takes it. And, you know, we don't have enough electricity on the planet to power half of our stuff. So we got to be concerned about it. I can also tell you from lots of experience, cooling these data centers is ridiculous. And it takes so much power. The companies need to bring in extra power from the power companies just to run the air conditioners. And of course, you need backup air conditioners because if your air conditioners fail, your servers aren't going to be too happy. So think about that. So anytime we can do more with less, it saves us money, and we can then invest this money into new opportunities for the business. So understand that a container requires some operating systems from the library, which means a container that's designed to run on Mac OS, you can't stick on a Windows server or a Linux server because it doesn't have those operating system libraries. You cannot put a Windows-based container on a Linux host because it won't have the Windows libraries. You can put a Windows container on a Linux host. Now, Microsoft's pretty darn smart. That's why they're one of the most valuable companies in the world. I think they're the second most valuable company in the world. Here's what Microsoft did. They created something called the Windows subsystem for Linux, which is an Ubuntu Linux kernel, which they put into Windows 11. So now with Windows Server, you can actually run Windows containers and Linux containers. So that is the exception to that rule. So generally speaking, when we deal with containers, we need something to kind of orchestrate the containers and keep them going up and running. And we're going to have some options here, and we're going to talk about the reality of these options. If we were going to only be on AWS, which is 2% of the customers in the entire world that are only on one cloud at this point, of enterprise customers, I would tell you that Amazon has the most simple and beautiful and elegant solution in the world called Elastic Container Service. And that Elastic Container Service will orchestrate your containers. And if that's your case, it's very simple and elegant. Problem is, if you use Amazon's Elastic Container Service, and then your business changes, and you want to use more than one cloud, you're stuck in this proprietary container orchestration. So we will later talk about Kubernetes, which enables you to run in all clouds. But if you were just on AWS, if the business needed that particular use case, and that business wasn't concerned about vendor lock-in, and they weren't concerned about their future and the agility to move to other clouds, you could use Amazon Elastic Cloud Container Service, and it is very simple, and it is honestly very elegant. And it provides a fully managed container service for you, which is high availability, 99.99% available. It's deployed in a VPC, which means you can use access control lists and security groups for your network traffic. And it will orchestrate your containers in either virtual machines or in a serverless environment called Fargate, where you put your virtual machines in this serverless environment and it runs on their servers and they hide that from you. And that's, a level of abstraction you don't think about. So you don't have to think about managing servers and patching servers. So here's what it would typically look like. If we were to use this proprietary orchestration system, we would build our containers, we would deploy them, we'd provision them to where we're going to put them, and we isolate our containers, and we manage the application. By comparison, if we were going to use this Fargate thing, we would basically use this to the container, we'd build the container and just stick it on Fargate, which is going to be a managed container service, managed compute. Now, lots of time it's used with Fargate. Again, Fargate's going to be completely serverless, so there's nothing for you to think about. Generally speaking, with serverless, it gets real expensive when you use it, and it's cheaper if you don't use it, where virtual machines are the same price whether you use them or not, so you got to figure out what makes sense. And when you use a service like Fargate, you have no control, where you've got much more control if it's on a virtual machine, like an EC2 instance, so the architects will need to determine what's best for that business case. But if it was Fargate, it gets pretty simple. Here's what it would look like. You basically have the Elastic Container Service doing the orchestration, and Fargate itself will basically be where you put the containers, and then you pay for what you use. Here's the things to think about with ECS, or Elastic Container Service. It is fully managed, so you need a less sophisticated team to use it, which could potentially mean lower employee costs. It could be higher costs, but lower employee costs. It auto-scales, it load balances, much like Kubernetes, but it is a simple proprietary thing. You basically can set up task definitions, which means you're going to define tasks and which set of containers are going to run together on the same host. And you'll use some JSON formatted definitions. And you can use services to run or maintain a specific number of tasks. And that way you can ensure your application is always up and running. We can talk about cluster management. ECS will help you manage a cluster of either EC2 instances or Fargate containers running the system. And it will handle scheduling the containers and placement of the containers on your cluster. So you put it on a server that has it. space for it. The nice side of ECS, Elastic Container Service, is it integrates into AWS services because it's an AWS product. So it's pretty seamless with your identity and access management systems, your VPC, nice integration with, say, CloudWatch, your load balancers, even the container registry like Elastic Container Registry, which we will talk about at some point. And this is going to give you secure and scalable networking options with your VPC, at least with the security group anyway. So it's going to give you some very good deployment and rollback options. ECS, if you're going to do, say, a blue-green deployment or any kind of rolling update, you can use a container orchestration platform like this. Gives you the ability to roll back to previous versions if things don't work. It's got some networking options like bridge networking, host-based networking, and VPC networking. And that way, you can have containers that can also have their own IP addresses if they need to connect securely to an AWS resource. So how do you set up ECS? Pretty easy. You set up your environment. What you do is you create your cluster in the Management Console CLI or Software Development Kit. You choose whether you want to put your systems on EC2 instances or virtual machines to give you control of the underlying infrastructure. Or if you don't care about control, you give it to AWS Fargate and you've got some simplicity and elegance. Then you define your test tech definitions. You create your test definition that'll specify maybe the Docker image that you're going to use, the CPU, the memory requirements, the networking mode, and any other configuration details for your containers. And then you launch your services. You use the console or the CLI to create your services and launch them, and define the number of task instances you need. And if you're going to use more than one, configure your load balancing. You monitor it, you manage it, and as necessary, you scale it or you update it. So it is a pretty simple way to do things. Let's talk about some best practices with ECS. You're going to optimize your test definitions. You really want to carefully configure your resources, your CPU, your memory, for your tasks to be very efficient. You may want to use environmental variables and IAM roles to securely manage the configuration and permissions of your system. Maybe put in some good secure networking, Use VPC and security groups to isolate your traffic and resources. Ensure that your tasks are running in private subnets with controlled access to the internet, public internet especially. Monitor. You're not going to put anything out there and then not see what's going on. So monitor and log effectively. And look at those CloudWatch logs. Do something to aggregate them. And when possible, integrate it into the organization's DevOps or CI/CD pipelines. And that way, you can automate the deployment of new container updates. You can configure auto-scaling policies to deal with variable workloads. All right, that is Elastic Container Service. The next thing we're going to talk about is a little bit more complicated. And give me a hashtag, Kubernetes. And then I'll know that you're ready for this. Because I'm going to give you a little more on Kubernetes than, when I say a little more, I mean a whole heck of a lot more than you would actually get in an AWS Solutions Architect Professional or Associate certification. But it's important knowledge.
Hey, Mike, I got one question I want to do before we get into the good stuff. And then we'll just do this one question, and then we'll save the rest for
sure.
All right.
What kind of images can you run on ECS? Container images. So whatever the containers are that you guys have. But you have to understand that ECS is just orchestrating where the containers will be and their placement. All right, so Kubernetes, you strapped in? Did I see those hashtags, Kubernetes? Did they come in, Chris? I want to know everybody is awake. Okay, Alonzo Coleman gave me the first one. Adrian Flores, Kubernetes. All right, Miriam Flores, Kubernetes. Fantastic. Nate, Kubernetes. Jose Cruz, Kubernetes. And Moses. Excellent. So now we're going to have fun and talk about Kubernetes. Now I want you all to give it a thought for a second. And this is why we're going to talk about Kubernetes ahead of the Amazon proprietary Kubernetes things, or at least the Amazon managed Kubernetes things. If Kubernetes is orchestrating your containers, and you are on the AWS cloud, the Azure cloud, and the Google cloud, and you use, say, AWS's Kubernetes container system and AWS crashes, what happens to your container orchestration in Google and Azure? You got nothing. So after we talk about Kubernetes, tomorrow we'll give you the options that you can choose to or not. But if you have a standard managed Kubernetes thing like OpenShift from IBM and you have it in AWS, Azure, or Google, and one or two of your clouds go down, it doesn't matter. The other cloud will take over. You'll have auto scaling and you'll be in good shape. So Kubernetes is going to be really important in the multi-cloud world. Kubernetes is good in the data center. For the private cloud, it's good in the public cloud. And if you create your own clusters, it'll work anywhere. So let's talk Kubernetes. So Kubernetes, which you may hear of as K8, is an open source container orchestration platform. Kubernetes is designed to automate deploying, scaling, and operating. So if you think about what an architect does, the architect itself kind of orchestrates the team of people to design a solution to improve business performance. If you think about the conductor and the orchestra, they're basically orchestrating, okay, the flutist, you get up, you get quieter, the harpist, you do your thing, and they're guiding people with pace and tempo. Well, with Kubernetes, it's the same thing that we need to do. So it's orchestrating the container. So always remember that Kubernetes is a container orchestration problem. So when it comes to these types of plans, we typically have something called the control plane and a data plane or worker plane. So the control plane does the control. The work does it. So if you look at a network, you might understand that the network has routing protocols. That is the control plane. You may notice that routers have links. That is the forwarding plane. If you go to the AWS Management Console, that is the control plane for AWS. The server which you put your web server on is the worker plane or the data plane. So with AWS, or with Kubernetes, we're going to have a control plane, which is going to be called the master node. And we're going to have the worker plane called the worker node. So this is your high-level Kubernetes architecture. So now we'll talk about the various elements in Kubernetes. And they're plentiful. It's nowhere near as complicated as networking, but there's some meat to this. So that master node is going to be the most important part of the cluster because it's responsible for orchestration. And if that goes down, things will happen. So the master node hosts the control plane. So it's the orchestrator of the system. So if we have 3 containers and the master node were to go down, those 3 containers can still run. But if a container crashes, we're not going to start a new one. If we need the system to scale out because the containers need more capacity, it won't work. So that master node or that control plane is so critical that if you've got a multi-cloud Kubernetes environment, you're going to need some industrial Kubernetes that's going to run in all clouds versus a cloud proprietary one. Now, the worker nodes, this are the machines where the containers are, those virtual machines. And the containers applications are going to be pods, or where the pods run. So they are critical too. If you don't have anything controlling it, you've got nothing. If you don't have the computer or anything that can do the work, you still have nothing. So let's talk about the components of the master node. That control plane, the first component is going to be an API server. Why does the Kubernetes control plane need an API server? Well, that's going to be the front end of the Kubernetes control plane. It's going to be used by all other components of Kubernetes to interact with that cluster. It typically processes RESTful API requests. If you're familiar with RESTful APIs, it'll validate them and it'll update them with the corresponding objects in something called the etc data store. The etc is going to be a distributed reliable key value store that Kubernetes will use to store all the information, including its configuration data, state data, and metadata. Does that sound like a database to you? And the whole point here is to store the entire state of the cluster, and that's why it's another critical component. Now, we also need something called a controller manager. And the controller manager is going to run the controller processes that are going to regulate the controller. So the controller manager is going to watch the state of the API server. It's going to make adjustments to get it to the desired state. The controllers will include node controllers, replication controllers, endpoint controllers, and others. And then we're going to have the scheduler. And the scheduler is going to assign tasks to the pod. And its function is to ensure that the nodes are placed with sufficient resources, according to constraints, whether it be things like affinity or anti-infinity. So what's this kind of look like when it's put together? You can see this is a beautiful diagram, so you know Alonzo from my team joke because he makes beautiful charts here. So you can see in that master node, we've got the scheduler, we've got the kube controller, we've got the API server, and we've got that cloud controller module. And we talked about that etc.d, or that etcd. You can also see on the worker node, and we're going to talk about this soon, we'll have the kube proxy, kubelet, the container runtime, which is what's necessary to run the container, and of course we'll have the pods, which will have the containers. Now, generally speaking, this host kernel there is because the pods are going to be running on a virtual machine, and the kernel is going to be the kernel of that operating system. You know, that part of the operating system that manages memory, CPU resources, schedules tasks on the CPU, that kind of thing. So what's the flow? So the interaction flow is going to be, it's going to come in as an API request. Whether it's a user or an administrator or an automated system, it's going to make an API request to the API server. And that's going to happen anytime you need that needs to be create or modify or delete a Kubernetes object, whether it be a pod or a service or deployment. And you can see here, you know, the way that API request is going to come in and where it's going to hit the API server. The next part of the interaction flow is going to be related to state persistence. The API server is going to validate the requests, and it's going to persist a new state in that etcd. So, you know, you can look in this particular environment where it's going to persist it, and that way you can get access when needed. The third part of the interaction flow is going to be monitoring of the state. The controller manager is going to need to monitor the state of the cluster and work to make sure that it gets brought to the desired state of the objects that would be in that etcd. So you can see what's going on here. Not really sure what happened with my screen over here, but you can see, you know, the cloud provider's API. You can see the control plane. You can see where the nodes are, where things are being done. Or at least the next part of this is going to be task assignment. We're going to have this scheduler that's going to create new pods when appropriate, because we might need different resources. So, you know, you can see what that looks like here. And then, of course, we're going to have some node communication here. Each worker is going to have its kubelet, which is going to have to communicate with the API server to receive the state information. So, you know, we're going to have this communication flow between our nodes. And you can see in this diagram, you know, some of that communication and how it's actually working between the nodes. So now let's talk more about the worker nodes. If the master node was the control, the worker node's where the work's done. So Kubernetes worker nodes are typically speaking going to be virtual machines. Could you put it into some sort of a Fargate environment? Yes, you could. But typically speaking, you're going to put this in a virtual machine. So when it comes to Kubernetes, the worker nodes are where the pods are. And that's going to be the smallest deployment unit in Kubernetes. And each pod may have one or more containers in it. When it comes to networking, the worker nodes are going to get involved in all networking aspects of the pods. Communication between pods on the same node, communication between pods on different nodes, and any kind of external communication. Because think of it almost as like an end device. And if an end device is out there, whether it's a server or a container, it's still going to need to talk to the network and talk through the network. And we can talk about resource management. These worker nodes are going to manage the local resources, like the CPU, the DRAM, the storage, and then allocate them to the pods based upon the requests. And you're not going to go beyond the limits that you specify when you create these pods and their definitions, because you're going to give it a limit of CPU resources and DRAM resources. And then you could add more instances as needed, but you're going to specify what they have. And of course, these worker nodes are going to be like your end system, and they're going to collect logs and metrics from the pods and the containers. And there's tools here that you can use to kind of look through this and help you manage it. Things like FluentD or Prometheus. And there's plenty of others that can be used for monitoring and logging as well. Now, another component of the worker node is the kubelet. And the kubelet is going to be the agent that runs on each worker node. Its function is to ensure that the containers are running in a pod exactly as specified in the pod. So the kubelet's going to communicate with the API server to get the pod specifications, and it's going to ensure the desired state of our containerized applications. Next would be the kube proxy. So the kube proxy is going to be a network proxy that works on the worker node. It's going to maintain the network rules on the nodes, enabling the networking communication to the pods from inside and outside. And, kube proxy is going to manage IP routing, load balancing. So I always thought of the kube proxy as kind of like the networking. And of course, we have to have the container runtime. So when we have a container, it needs to run somewhere. So container runtime is going to be the software that's responsible for the containers. And examples, container runtime options could be things like Docker, Containerd. So you're having the orchestration control of this, but you got to have a runtime module to run your containers. And that's why we often have the interplay between Kubernetes and Docker together. Now, the Kubernetes worker nodes also have to interact with the master node. And that's where this API server communications come into place. The worker nodes are going to communicate with the API server on the master node. They'll get their state information, their updates that way. The scheduling needs to occur. The scheduling is going to be on the master node. And then it will assign work to worker nodes based upon resource availability or other constraints. And we have this concept of a control loop as well. And the kubelet on each worker node is going to be constantly interacting with the API server in order to ensure that the desired state of each pod is going to be maintained. Let's talk about the life cycle of a pod on a worker node. First thing that's going to happen, it's going to be scheduled. The scheduler is going to assign a pod to a specific worker node based upon resource requirements and policies. The API server will have a notification. The worker node will be notified of its pod assignment from kubelet. And the container runtime will instruct the container runtime to pull the necessary container images and start the containers. What I'm going to do is I'm actually going to show you a container runtime. I'll draw it out architecturally for you after this. And of course, the network setup. So the kube proxy, because it's the networking component, will set up the necessary network rules to allow communications from the pod. And of course, we're going to have the monitoring and management. So the kubelet will monitor the containers to ensure that they are healthy. And what they'll do is they'll report their status back to the API server. Now, I know I talked about it initially. I'll talk a little bit more about the kubelet. And the kubelet is going to be an agent that's going to run on each worker node. It's going to monitor the pod. It's going to watch over the pod, which is basically the smallest deployable unit in Kubernetes. And it's going to assign it to its node. It'll ensure that the containers inside these pods are going to be running healthy. So here in this particular environment, you can kind of see the way these things are sort of interacting here. And while I'm at it, let's let's draw out what this really is going to look like. So you get the concept of this container runtime. And I'll show you what you typically would see in a cloud computing environment here. So in this particular environment, we're going to have the physical server itself. And if it's in a cloud, you're going to have a hypervisor in most cases. Unless you buy a bare metal server. And then you're going to have your virtual machine. So let's make this a really big virtual machine. And I'm gonna make this a huge virtual machine instead of having multiple virtual machines. So let's say this VM has got 256 cores and 4 terabytes of DRAM. This thing is going to store a lot of containers. So that's your virtual machine. And then your virtual machine is going to have its operating system. So here this virtual machine is going to have its operating system. Let's say it's Red Hat Enterprise Linux. And then we need our container runtime module. And this typically is going to look something like Docker. Over here is going to be here. And then we'll have container A, and then we'll have another container, call it container B. And then we'll have the third container, which is, say, container C. And by doing this, you can see that all these containers are, for the most part, separated from each other. And we can put a lot of these containers on that same virtual machine. So I hope that kind of helped with the container runtime. So now let's talk about some other key components. We'll talk about a pod, a service. We'll talk about VM, namespace, and config and secret. So I previously mentioned the pod, but a little more because this stuff's a little icky and complicated. So I want to go over it a few times to make it sense. A pod is going to be the smallest and simplest Kubernetes object. Again, it represents that single instance of a running processor in your cluster. The pod will encapsulate our containers, and it typically will contain more than one container, or one or more containers. And usually maybe one, sometimes more, but they're going to be tightly coupled to share resources like storage and networking configuration. And the containers in the pod will have the same IP address, host name, and networking resources. So same IP address. So we'll have multiple pods with different IP addresses. A pod can typically share the same storage volume as well. Now let's think about lifecycle management. So Kubernetes is going to manage the lifecycle of the pod. So maybe we need 5. And it makes sure that we only have 5. Maybe we have 2 and it thinks we need more at a time and it will scale out for us. So what's a service? A service is going to be an abstraction that's going to define the logical set of pods and a policy for accessing the pods. So what's a service going to do? It's going to give us a stable IP address and a DNS name to access a set of pods. Because we need to be able to reach it. The service will provide load balancing. I've always thought of the Kubernetes service as a load balancer, and it will direct network traffic to all pods behind the service. Now let's talk about some other things and what does a service do. Let's talk about the cluster IP. That's going to expose the service on a cluster's internal IP address, an IP address that's going to only be accessible within the cluster. We're also going to have the concept of a node port. And that's going to expose the service on each node's IP address and as a static port. And that's going to be what makes it accessible from the outside. So it will also provide a service name to a DNS address. Kind of hope that sort of makes sense. Now, we also need to talk about a volume. So, what's a volume do? VIMs are going to provide storage that will persist beyond the life cycle of the containers. So when you mount a storage VM in a virtual machine, it's the same thing you're doing here. So if your container restarts, it's going to be able to access the same data. So let's talk about types of VIMs. We can have an empty directory, and that's going to be temporary storage when the pod is created and assigned to a node. We're going to have the host path, and that will mount a file or directory from the host path, from the host node's, say, file system to a pod. We will have a config map and a secret under a VM types, and that's going to provide configuration data and maybe sensitive information like passwords. And then we'll have the persistent VM and the persistent VM claim, and that's going to be a way to request and use storage resources that are not tied to the life cycle of the pod. Now, we have this concept of a namespace, and a namespace in Kubernetes is a way to divide our cluster resources between different users and applications. So what does a namespace do? It's going to help us organize and isolate resources like our pods, our services, our deployments, because each namespace is going to be like a virtual cluster in the main cluster. What else does the namespace do? Access control. We can apply identity and access management policies to the namespace, and even role-based access control, which we'll talk about when we get to the identity and access management section of this course. And it helps make sure that we don't have naming conflicts, because it'll allow resources with the same name to kind of exist in a different namespace. So it'll help figure us out for us. So let's also talk about config map. And what is config map in Kubernetes? It's going to be that object that enables you to store, say, non-configuration data in a key value pair. And the config map will help you with configuration management, because it'll store your configuration settings that your applications will use, whether it be configuration files, command line arguments, and environmental variables. It'll decouple your configuration, and that's basically to take your configuration settings and kind of decouple it from your application code. So it's going to make it a lot easier to manage and update your configurations when you need without recoding the application. I mentioned secrets. So the secret is where you keep your secret stuff, right? So your OAuth tokens, your SSH keys, your passwords. And you're going to use the secret in Kubernetes for sensitive data storage. This is going to give you that way to store and manage your sensitive data, because you don't want to make sure that it's exposed in application code or container images. And let's talk about access control. We can use that to reference the pods to access sensitive information securely. Let's talk about deployments. So in Kubernetes, we have the concept of a deployment. And the deployment is going to be used to manage replica sets. And this is going to ensure that a specific number of pods are going to be running at all times. So if we've got a pod that goes bad, we can add a new one. So rolling updates, rollbacks, that kind of thing. Let's address briefly replica sets. And that's going to be there to ensure that a specific number of pod replicas are running at any given time. You often use a replica set and it's often used by deployments, so you can orchestrate the pod creation, scaling, and deletion. And of course, a daemon set. A daemon is like a lightweight thing that runs in the background, and that's going to ensure that some of the nodes can run a copy of the pod and that all nodes are added to the cluster. And I'll briefly talk about a stateful set. And that's going to be managing the deployment and scaling of the pods. And it'll provide guarantees about the ordering and uniqueness of the pods. Think of it where maybe a stateful application like a database. And we'll talk a little bit about the cluster IP, which is going to be the default type. And this is going to expose the service on the cluster's internal IP address, meaning only accessible within the cluster. So let's talk about a load balancer, and that's going to be used to expose the service externally by using any kind of cloud provider's load balancer. Now, a little bit under networking, we can think of ingress, and ingress is going to manage external access to the service coming in. It's going to provide load balancing, SSL termination, and name-based virtual hosting. All right, so we did a basic overview of Kubernetes. That is about as quickly as we possibly could. So actually, while we're at it, I have the opportunity to just go through Amazon's Elastic Kubernetes service and its features, and then I will take questions, because I feel like it's going to be hard to go talk about Kubernetes now and then tomorrow talk about the Amazon proprietary features. So bear with me an extra few minutes. So in a multi-cloud environment, you're going to need a multi-cloud managed Kubernetes environment. Many organizations use IBM OpenStack because they can put it in AWS, Azure, Google, Alibaba's cloud, as many clouds as they want. And that way it's there, and if any cloud goes down, you don't care. If you were only going to be in Amazon, and you weren't concerned that if the Amazon cloud went down, your Kubernetes cluster couldn't have a control plane in your other clouds, you could use the Amazon EKS service. And it's going to automate the management and setup and availability of Kubernetes because it's a pre-made managed service. And that's going to bring with it more simplicity and elegance than Kubernetes, which we talked about, which is somewhat complex. Nowhere near as close to networking, but it's somewhat complex. And it's going to be integrated into every AWS service. So it'll work with your load balancers, your identity and access management systems, and CloudWatch. It's a high availability, high security control plane. So as long as AWS is up, for the most part, it will stay up. Of course, a hacking event, a major networking failure, a control plane failure will obviously take this down. And if this is running in AWS, it'll take down all your other cloud stuff from a control plane perspective. What's running will be there, and nothing else will be able to up, go down, or control. Same thing if you used Azure's Kubernetes service or Google's Kubernetes service. When you only have one point, it becomes a single point of failure. The cloud provider. So Amazon EKS makes it pretty easy to upgrade to different Kubernetes versions with minimal downtime because it's managed. It's going to scale great because it is a great Kubernetes service. Once you get past that architectural limitation of only working on one cloud with 98% of your organizations using multi-cloud, this in and of itself is a very great managed Kubernetes environment. And it's simple to use. You create the cluster in the management console. You specify the Kubernetes version you want and your VPC configuration. You configure your IAM roles. You provision your worker nodes and where you want them to be, usually on virtual machines. Tell the worker nodes to join the EKS cluster. And you deploy your Kubernetes application. And you monitor it and you scale it as necessary. So that's the Amazon proprietary one. Now, Amazon also has this concept of an EKS distro. And this is the distribution of the Elastic Kubernetes service. And this is a way that you can run your containerized applications in the data center the same way you would in AWS. It enables you to create Kubernetes clusters with the exact version used in Amazon. Main difference between EKS and EKS distro is that EKS is a fully managed Kubernetes service on AWS, whereas EKS distro is something you can download and install in any environment. So that's always an option for you. In this way, a user can deploy Kubernetes clusters that match their AWS ones without having anything to worry about. And in a hybrid cloud between just AWS and the data center, this could be a great environment. And that's really what it's designed for. And let's think of a hybrid environment. When your data center needs more capacity, additional nodes could be added on for AWS. EKS distro could be great in disaster recovery. You could use EKS to back up your data center. And if your data center goes down, AWS could take over the load. It can be deployed in lots of places. And then there's the concept of EKS anywhere. And that is going to simplify a customer's on-premise Kubernetes cluster management via default configurations and gives you the same kind of auto-scaling self-healing you get with Kubernetes. It's going to give a consistent and reliable cluster environment on-premise. And, it's going to be easier than a self-managed environment. It would reduce support cost, potentially, and it's open source with support from AWS. One second. Actually, let's finish with Elastic Container Registry because that's quick. The Elastic Container Registry is going to be a fully managed container image registry provided by AWS. So it's going to make it real easy for developers to store, manage, deploy their container images. And that way there's a good, secure place to put them. It's fully managed, so you don't have to think about setting up your own container registry and managing these types of things. It'll integrate with other services, so it makes it simple. It'll integrate with whether ECS is the proprietary one you're using, some form of EKS control plane, Fargate if you're not putting your systems on virtual machines. It supports into the AWS Identity Management Console because guess what? It's an AWS service. It provides encryption at rest, access to the key management system, designed to be highly available. And it's designed to simplify image management, provide lifecycle policies to automate the cleanup of unused images, helping to manage your storage costs. It can do some image scanning where it can look for vulnerabilities in your container images to help you identify and potentially remediate security issues. So let's bring it open for questions. Does anybody have any questions for us? What container runtime engine does KH use? I heard it does not use Docker anymore. You can use Docker, and it does have its own form, but many people use Docker. But, are you referring to EKS or are you referring to Kubernetes itself? EKS itself, the Amazon version, uses Containerd. And that's going to be a container runtime engine that's typically used instead of Docker. You can still run your Docker images on EKS. But you can also, by default, it's using Containerd. Containerd is rapidly becoming an industry standard runtime module that's going to manage the complete container lifecycle. So typically it's that. It's typically used because it also supports the Open Container Initiative, which means you can run your Docker images and your Containerd and your other container images with Containerd. What programming language would you use to communicate with engineers? Well, it all depends. So if you're an architect, you don't use any programming languages and you communicate to engineers in clear language. I need 10,000 virtual machines that each have 32 cores, 64 gigs of DRAM, and half terabyte hard drives with 2,000 IOPS. That's communication. So if you want to be a software developer, you will need a programming language. If you want to be a cloud engineer, you will need to learn certain programming languages. If you want to be what's the word I'm looking for? If you want to be a DevOps engineer, you will definitely need to know programming languages. But if you're a cloud architect or a solution architect, if you're a project manager, if you're a sales rep, if you're a manager, a leader, you probably won't need to know coding languages. So it's all really about what are you trying to do. How do you ensure security is implemented on Kubernetes? So first, remember, there's a lot more security you need than just Kubernetes. You will need to control your network access. You will need identity and access management systems. You will need encryption. You will need firewalls in the right places, IDS, IPS systems in the right place. And we can't pull Kubernetes security out of the full security posture. But if you're asking just Kubernetes security, we can use role-based access control. And role-based access control is a form of identity and access management where you group people into roles. So what do I mean by that? Let's say a company is like Amazon and they have 1.5 million employees. You could manually have people there and say, Mike gets this permission. Chris gets this permission. Mark gets this permission. And in order to do that for 1.5 million people, you're going to make a lot of manual errors and you're going to need a lot of people. Role-based access control is let's group our people into systems administrators. And every systems administrator gets the same permissions. Finance people all get the same permissions, and it scales. So that way you create a group of people, then you create the permissions, and then you assign users to that group. So that's going to be the way. So we're going to use role-based access control. We're going to enforce network policies to control the traffic between the pods. We're going to use secrets management to securely store our sensitive information. We are going to regularly update our Kubernetes environment to keep it up to date. We are going to work on good pod security policies. We will define security context and permissions for the pods. We will enable audit logging to track access and changes to the cluster. We will implement TLS security to make sure that the data is encrypted with TLS, the old SSL, but it's now been modified to TLS security. So those are some things we can do specific to Kubernetes, but we're still going to need all those other security things. How do you manage ephemeral containers and the applications running it? Well, typically, to manage ephemeral containers in an application, we can use Kubernetes jobs for short-lived containers. We can use a serverless function for like an event-driven or an ephemeral workload, like an Azure function or an AWS Lambda function. Typically speaking, we can use Kubernetes to handle the scaling or restarting the containers or managing the life cycle of ephemeral containers. You can bring in the next one, Chris. How do you scale Kubernetes in AWS compared to how do you scale them in virtual machines? The identical way you would do it, and we've done it since Kubernetes has been around. It doesn't change at all. Same Kubernetes control plane. It's a standard. Same worker data plane. So you don't. Except in the cloud, you could potentially use Fargate if you wanted to give up control. Any suggestions for freshers who's sick for interview and coming from a non-completely background? Absolutely. So, first, your background is meaningless. What you choose to learn is there. What's your goal career? That's the first thing. Because the first thing we need to do is give your goal career. If you can provide that, I can give you information. Because if you train to be an architect, you will not be prepared to be a cloud engineer. If you train to be a cloud engineer, you will not be prepared to be an architect. If you plan to be a lawyer, you will not be prepared to be an airplane pilot. So first we need to know. Then after we know your career, we have to define your career. Is it a planning career, like architecture or strategy consulting? It is a worker career, like engineering, where you're actually doing the work. Or is it more of a technician career, like cabling or a cloud admin type thing, where you're basically just configuring things without the depth of why you're configuring and what you're doing? So we need to first understand that. The second thing is get the right training. When I left internal medicine for tech, I got a lot of training. And, it was expensive, but that's how I did it, because I knew that every day I wasn't working, I wasn't earning. For example, and I've gotten lots of freshers, solutions architect and cloud architect jobs. But, the average cloud architect earns $1,000 a day. So when I started my career, I wasn't going to try and save, a couple of $1,000s to spend 9 months earning when I could have earned $20,000 a month. So kind of think about that in the back of your mind, getting the right training. But it doesn't matter. And you can get any job you want. And I'll give you examples of certain people we've gotten certain jobs for if you desire. But we have to know where you're from. Next side of it is really get some good interview training. I've hired people generally speaking, we need someone that can do the job. And this is what hiring managers look for. Mike, I want someone that can do the job. And I'm speaking of thousands. I need someone that communicates well. I need someone that's energetic, enthusiastic, and passionate about the work. I need someone that's willing to go above and beyond. I need someone that's emotionally intelligent. And I need someone that's a good team player. So When you're new and you can't compete with the others, you better get that stuff right, because that's how you get hired. Look, my first job was a senior engineer after leaving internal medicine. And 3 months later, I was the lead architect. And 6 months later, I was a senior network architect. And 2 years later, I was a principal architect. Why? Because I learned my job. So there's that. So if you tell me what job you want, I can guide you there. But without it, I don't know whether to send you to flight school or law school. And I'm not joking. These careers are that different from each other. What's the difference between a load balancer and ingress? Well, you bring in some really tough, good questions here. So a load balancer is going to distribute your incoming network traffic across multiple servers or virtual machines. Ingress in Kubernetes is going to manage all the external access to a service inside of the cluster, typically providing, say, some HTTP or HTTPS routing. So I typically think of a load balancer as general traffic distribution, and I think of ingress as managing and routing the traffic into a Kubernetes cluster. Testing perspective, which cloud certification will be perfected at intro level? Could you tell me what your goal is? Because the right intro level is dependent upon your goal. Generally speaking, a professional level certification, so after interviewing thousands of people, I can tell you that there's basically a 1 in 20 chance when someone has a professional certification, they know enough to do the job. And with an associate certification, basically a 3 in 100 chance that the person could potentially do the job. But I've hired people with 0 certifications many times because they were great. And there's going to be a point in your career where you're going to have to take the certifications off of your resume. In many cases, your management will want you to, because if you're going to move into an architecture role, a CEO isn't going to talk about being AWS certified, for example. An executive architect wouldn't be either. They'd be focusing on more. So what is your goal? What is your gold job? The gold job will determine your brand, what you need to progress, what you need to share. So if you can provide that, I can answer it. But without it, I can't give you any information. Which drug does the doctor prescribe for a medicated condition? Don't know what the condition is yet. Okay, so I will tell you that there is a completely free document on which that I'd love you to download. It's in the description of this video on the chat box, which will give you the information on which certifications would help you if your goal was to, say, be a cloud architect or a solutions architect.